Understanding all the problems from NeetCode 150 will allow you to become master at technical interviews. I can guarantee you that after this, you would be able to solve every single interview that you can ever find for all the top tier IT companies. And this is going to be the part 2 of a 3-part series for solving all NeetCode 150 problems. Part 1 can be found right over here. Now, once again, those who don't know, NeetCode 150 is an awesome list created by a YouTuber named NeetCode, and utmost respect to him for creating and sharing this list with us. In this video, we would be solving 50-ish more problems. So for 12 hours, we would be working together on understanding all the DSA concepts and different tips and tricks on how you can improve on your interview skills. Now, I am a big believer in free education, and that's why I have decided to put everything on YouTube. But the thing is, I have a request to make. I would really appreciate if you can support the channel, like, share, subscribe, and if you have financial means, please become a member, because it took me a lot of time, energy, and resource to create all of these video solutions and putting them together, and looking forward for your support so that it continues to motivate me and also help other people out there in the world. And now, before any delay, let's get started with the course. So the LeetCode problem we are going to solve is called binary tree right side of view. Now we can see that this one is the LeetCode medium problem and also an extremely well-liked problem on LeetCode. The problem statement is actually quite straightforward. We are given the root of a binary tree. Now we need to imagine that as if we are standing on the right side of the binary tree, and then we need to return the values that we see from the right side, and we need to return the top to bottom values. So let's try to understand this problem. Currently we have a binary tree over here. Now imagine yourself that as if you are standing on the right side of the binary tree. So from the right side of the binary tree, you can see only this portion of this given binary tree, which means currently you are only looking at these 4 nodes, and all of because this node is being blocked because of this one, and these 2 nodes are also being blocked because of this one. Okay, so in this case, what is your right side view or your right side vision of this tree? Well, first we need to return the answer in top to bottom manner. So first we are seeing node number 1, next we are seeing node number 3, next we are seeing node number 6, and lastly we are seeing node number 7. And this is what we need to return as part of the answer. Now let's first try to understand that what the answer looks like in each of these 3 different scenarios, so we have a clear understanding on what is being expected from our side. So if we take a look at this first tree, well, the answer is going to include, this is going to be the first node, this is going to be the second node, this node would be blocked, so we would not be able to see it, and then once again this node would also be blocked, so we will include this node. So these are the 3 nodes that we are dealing with. Okay, next in this particular scenario, we can see that we need to return the right side view. The thing is, hey, there is no node on the right side of the tree. So well, in that case, we can still see the left side of the node as well. So we are going to include this node, and we are also going to include this node in our answer. Okay, and in the lastly, this scenario is slightly tricky. So of course this node is going to be part of the answer, but then at this particular level, we will have to include this node. Once again, at this particular level, this one is the right child and this one is the left child, but still, because we are standing on the right side, we need to take the value that is closest to us on that particular level. So once again, this node, and then lastly, on this last level, we don't have any particular nodes, so we are going to use this node. Now in each of these 3 scenarios, we can see one very clear distinction in terms of answer. That is, we are seeing that at any given level, we will have to take one node from that particular level. We are going to select the node that is the last node in that particular level. That is the same case for this one, because this is one level, there is only one node, so this is the last node. Over here we have 2 nodes, but we are only going to consider the last node. Once again, we are only going to consider the last node over here as well. This one, there is no explanation needed. This one is slightly trickier example where we can, okay, so this one we understood why we take it. Amongst these 2 nodes, we are closest to this one, so we are taking it. Amongst these 2 nodes, even though these nodes are close to each other, we are once again closest to the right side node, so we are going to take it as part of the answer. And this one once again is still the last node at that particular level. So we are able to establish that for any particular binary tree, the right side of the view is simply going to be doing the level order traversal and finding that what is the last node at that particular level. So in either case, we simply have to do a level order traversal. Now level order traversal for trees typically refers as breadth first search. So we know how to do breadth first search. It's a very common and popular tree traversal techniques. If you don't know what breadth first search is, let me just quickly explain. We are at the root position. So what we are going to do is for root position, we are going to put it inside a queue. Now we know the property of a queue that it is a first in, first out type of scenario. For each level, we are going to iterate over all of the children that it has. And if it has the children, we are going to put them on the queue as well. And once again, repeatedly, we are going to keep on subsequently doing the same thing with their children as well. So logically, we would be iterating over in one particular level by level across the entire tree. And that is called breadth first search. So let's try to see our solution in action. So in this case, let me give values to these particular nodes. And we know that the answer in this case is going to be 1, 3, 6, and 7. But currently, let's say that this is our queue. Now in our queue, we are going to keep track of two things. Number one, that what is going to be the last element at any particular node. And number two, that for every single level, we will have to keep track of that at what level these particular nodes belong to. Okay. So we can very easily track that because every time we add a new child, we can just mark it as like a new level that we are adding inside the queue. And apart from that, we can simply move forward as it is. So currently the first value is going to be node number 1. For node number 1, because it has children, so we are going to add node number 2 and node number 3 inside our array as well. Inside our queue as well. Once again, for both node number 2 and 3, they also have the children of their own. So for node number 2, they have 4 and 5. So we are going to add 4 and 5. For node number 3, they have 6. So we are going to add 6. And lastly, we are going to have value number 7, that is the child of node number 6. So once again, let me just add one more entry over here, 7. So now we can see that I have color coded every single different level based on all the elements for that particular level. And in that particular color coded pattern, we need to find the last element. So this is basically going to be by default last element. So we are going to add this to our answer. Next, we have two values at this particular level. So we are going to pop this element out because we don't care. This is the last element. So once again, we are going to add that to our answer. Once again, we have 3 elements over here. We are going to pop each one of out, and the moment we reach to the last element, we are also going to mark it as the answer. And then this is also the last element at this particular level. So once again, we are going to mark it as the answer. And that's it. This is the whole solution. Now, at first glance, it looks complicated, but all we are doing is just doing the breadth first search in a common fashion and trying to find the answer. Now in this case, since we are standing on the right side of the binary tree, we are selecting the last element. But same can be said that if we are given a question where we need to find that what is going to be the left side view, where you are standing on the left side of the binary tree, same logic is going to apply. The only thing is now you are going to be dealing with the first entry that pops up inside of your queue for every single new level. And that is what you need to put it in the answer. So basically these are like two questions in just one question by just changing the direction of where you are standing. If you see time complexity in this case, this is going to be big O of n. If you see space complexity, this is also going to be big O of n because we are using an extra queue to keep track of all the elements that we have iterated so far. Overall, this is like a decent time and space complexity because this you have to go through this in any of your tree programs unless it's a binary tree and you're trying to search an element. So now let's quickly see the coding solution for this one. Okay, so this is the coding solution. First, we are going to initialize our new array list to store the answer, and we are going to mark it as result. We are also going to check for an edge case that if the given root is equal to null, we can simply return the result. If that is not the case, we are going to initialize our queue, and inside our queue, we are going to populate the very first element that is going to be the root node. Now we are going to iterate over the tree in the breadth first search manner by stating that while queue is not empty, do this. So first we are going to define that what is the current size of the given queue. then we are simply going to have a for loop to run over the given queue, where we are going to keep on polling elements at every single position, and we are going to mark the last node of the current level inside the result that we are going to populate. Okay, then we are going to check that for this particular given root value, do we have any left child and do we have any right child? If we do, add the left child and right child to the current queue as well, and this is going to iterate over the entire binary tree in breadth first search manner, and we would have our result array list populated as well. In the end, we can simply return results, and this is the whole solution. So let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions. Few things can be improved in terms of space complexity, but anyways, this is a good enough solution. I would be posting this in the GitHub repository that we have created. The problem statement is called count good nodes in a binary tree. We can see that this one is a relatively new problem, a medium problem, and also a very well-liked problem. On top of it, this has been asked at tons of different companies. So let's pay some attention that what the question is asking us to solve. Basically, we are given the root of a binary tree and we need to return the number of good nodes in a binary tree. The question is, what the heck is a good node? Well, a tree node is deemed good if in the path from root to that particular tree node X, there are no nodes with value greater than X. If that is the case, that node is a good node. So let's try to understand this with an example. Currently, we can see that there are 5 different nodes or 6 different nodes in this particular tree. Now we are being told we need to find the good nodes. The definition of a good node is that path from root to any particular node. If that particular node contains the maximum value, then it is deemed good node. So let's try to see what are the good nodes, starting with the root. Now root in itself is a good node because path from root to root is the biggest value. So we find one good node. Okay. Now let's consider value number 1. What is the path between root to value number 1? This path. Is 1 the largest number on this path? No, which means 1 is not a good node. Then let's consider the path 6. So for 6, the path is 5, then 1, and then 6. So in this case, 6 is the largest number from the direct path to the root, which means 6 is also a good node. So let's mark that. Once again, now we found everything we could. Let's try to move to next value number 5. So is 5 a good node? Yes, 5 is also a good node. Why? Because the definition of 5 is that from root to that particular X, there are no nodes with value greater than X. So in this case, the nodes we have is value number 5, 1 and 5. So there are no other nodes that has value greater than 5, which means 5 is still a good node. So we will also mark this as good. Then we will jump to value number 7. So once again, the direct path from 5 to 7 is this one. So in this case, 7 is the largest node. So 7 is also a good node. And next value is once again 7. So once again, even in this path 5, 7 and 7, there are no values greater than this 7 as well. So 7 is also a good node. So in this case, in total, we found 1, 2, 3, 4 and 5 good nodes amongst these 6 nodes. So we need to return 5 as the answer. And this is what the problem statement is asking us to solve. So now let's try to understand the logic on the solution we can build for this particular problem. The logic is quite straightforward, that we need to iterate over the given tree in some fashion, and we will have to keep track that around this iteration, what has been the largest value we have been able to find so far, keep track of it, and using that particular value, we are going to make some important judgment calls. So the logic we are going to do is that we will have to iterate the given tree in depth first search fashion. Why depth? Because we will have to keep track of the entire path from root to any particular node. So for that, we will have to go into the depth first search order. Now, what are the considerations? Number one thing is first we are going to check the root or at any given position, because first we are checking the root, then we are checking for its left entire subtree, and then right entire subtree. Same thing we are doing at every single level, that first we are checking that for this particular root whether it is the largest number. After understanding this, we are checking its left subtree and then right subtree. So basically we are doing the pre-order traversal in this case, and pre-order traversal is quite straightforward. The logic is root, then left, and then right subtree. So we are once again going to do a pre-order traversal, in this case in depth first search fashion. We are going to keep track that what has been the maximum value we have been able to find inside the current path. If the current node is equal to or greater than the maximum value we have been able to find, so in this case we are going to deem this node as a good node. So we also need a variable to store the good node as well. So let's assume that, okay, we are going to have our count variable to store all the good nodes we have been able to find so far, and this is the whole solution we need to create. So let's try to understand, or let's try to iterate over our given solution, and let's just arbitrarily give some values to these particular trees or these particular values. So in this case we can see that these are the different values. Now let's start with value number 3. 3 in itself is a good node because we are doing the depth first search pre-order traversal. We are going to take care of the root first. Okay, now we took care of this root. Now let's take care of the left child. So left child is once again 1. So once again, even at the left child position, we will have to follow this position of root, left and right. So once again, now left child in itself is a root. So we have value number 1. What has been the, and also we have our maximum value we have been able to find on the current path. So maximum value so far has been 3. This value is 1. So current node is not greater than maximum value, which means this is not a good node. Now we will need to check for the left pointer. So left pointer is once again 3. So 3 is same as the maximum value on this path we have been able to identify. So we are going to mark this 3 as the answer that we have been able to find so far. Now 3 is also going to be a good node. So we are going to add our count of good nodes. Now we are going to do a backtrack. Now for the backtracking, once again, we have a right node that we haven't checked. So we are going to take care of the right node as well. The value of the right node is 5. So currently at this particular position, the right node is actually greater than the maximum value we have been able to identify. So we are going to store, once again, count this 5 as a good node as well. Apart from doing that, we will also have to update the maximum value we have been able to identify. But this particular node does not have any subsequent child nodes of his own. So because it does not have any child node, there is no point in updating the value of the maximum node. But say for an example, if we did had one more child like this, where we need to check for the value of this node number 6, then this 5 would have been the maximum value we have been able to identify so far, but that is not the case. Once again, coming back, now we took care of 5 and we took care of 3. It does not have any children. We are going to do the backtrack. We already took care of 1, which means now we have to taken care of this entire left child. Once again, in our pre-order traversal, we took care of the root very first, then we took care of the left child. So this is the entire left child portion of this root. Now we need to take care of the right child. So once again, we are going to do the same thing. We are at position number 4. So we are going to first check that whether 4 is a good node or not. So in this path, the current maximum value we have been able to identify was value number 3. So 4 is a good node. But in this case, because we are checking for the subsequent children of 4, we will have to update the maximum value we have been able to identify along this path to value number 4. So this is the maximum value we have found so far. Next value is value number 2. So 2 is not is less than the maximum value we found. So 2 is not a good node. So in this case, we found in total 4 good nodes. So we are going to return 4 as the answer, and that's it. This is the whole solution that we need to return. Basically, we need to understand that why we need to use DFS in this case, because we are going in one particular direction. We will need to keep track of the maximum value at any given track. And we also have to do the pre-order traversal because we are following the principle of root, then left, and then right. And you can do this recursively or iteratively, it's up to you. We will see that in the coding. If we see time complexity, it's pretty straightforward. It's going to be big O of n because we are iterating over every single value. In terms of space complexity, if you use the recursion method, it will take big O of n. If you use iterative method, it would not take big O of n. And let's quickly see the coding solution for this one. Okay, so we are going to use a helper method called count good nodes to keep track of the good nodes we have been able to identify, and we are going to pass in the root value we found so far. Now this count good nodes is actually going to return an integer value that defines that how many number of good nodes we have been able to identify for this particular root node. Then we are in the initial input, we are just returning like the minimum value possible, because root in itself has to be greater than that. So root is going to be the first good node. Okay, now we are going to check, okay, that we are taking in as an input the tree node and the maximum node so far. We are checking for an edge case that if the given node is equal to null, we can simply return this 0. If that is not the case, we need to initialize our count to 0. Then we are going to check that if the given current node value is greater than the maximum value we have been able to identify. If that is the case, then we are going to update the counter to 1, and we are also going to update the maximum so far to the current node that we just found out. Once again, we are going to repeat the same process for the upcoming subsequent left child and for upcoming subsequent right child, and we are going to add the values of the left child and right child to our existing count value as well. So whatever count they come back with, we are going to add them to our existing count, and in the end, whatever the final count we found, we are going to return that, and that would be written as part of the answer for this one. So that's it. Let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster, which is pretty awesome, because this has to be some of the fastest code, because the runtime is also not 0 millisecond. So we are doing something really awesome over here. Once again, solution is posted on our GitHub repository, so feel free to go ahead and check it out. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do binary tree level order traversal lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Microsoft, Facebook, Bloomberg, Google, Apple, and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given the root of a binary tree. Now we need to return the level order traversal for this binary tree, and we need to return the nodes values. Now we are also told that we need to return them in left to right fashion and level by level. Basically we are given a binary tree over here. Now for any binary tree, basically we always have two things. We have a root node or a parent node, and that parent node has some children nodes. So, and furthermore, this children node can have children of their own as well. So every time a new set of nodes are being added at the bottom, essentially we can define a new level being created. So if we see this example over here, essentially this is level 1, this is level 2, and this is level 3. And we need to return the nodes level wise from left to right. So let's try to understand this with this example over here, where we are given 3 levels. So this is level 1. These two nodes, they are located at level 2, and this two nodes, they are located at level number 3. So in the answer, first of all, we are going to return this node 3, because this is the only node at this level. There are no other nodes. Now at the second level, we have two nodes 9 and 20, and we need to return them in the same sequence of 9 and 20. And in the third section, we have two nodes 15 and 7. First we'll return 15, and then we'll return 7, and that is the answer we are going to return in this case. Let's see that what would be different approaches to solve this problem. So when it comes to tree traversals, there are mainly two subcategories. First one is a depth first search, and second one is a breadth first search. Well, in the depth first search, we actually expand upon the depth of any given tree, and then we keep on iterating over all the nodes. While in the breadth first search, we actually visit the root node first and then visit its children, and then keep on repeating the same process. So in this portion, for depth first search, there are three further subcategories: in order, pre-order, and post order, which I'm going to show you first, and then I'll explain you how breadth first search work. And in this problem, actually we are going to use breadth first search to solve this problem. So during the in order traversal, basically first we visit the left side of the tree, then we visit the root node, and then we visit the right node. So first of all, for this root node, we will keep on expanding until the left node exists. So left node exists over here, and then left node again exists over here, which means this is the first node we are going to visit. So we start our visit traversal at 4. Now 4 does not have any more children, which means we can't go downwards anymore, which means now we go back to the root node. So root node for this 4 is actually 2, and then we again expand on the right side. For this 2, we still have right side 5 that we haven't visited, so we will do that. Now again we have visited all these 3 nodes, so now we are done with these. Now we again go back to the root node, which is 1, so we visit 1, and then again we repeat the same process, left, root and right. So again we go on the right side. So this is the strategy for in order traversal. Now for the pre-order traversal, basically we follow the principle of root, left and right node, and this is the way we visit the node. So first of all, we are going to visit the root node, which is 1 in this case. Then again we are going to visit the left node, which is 2. Then again we are going to visit the left node, which is 4. Then again we are going to visit the right node, which is 5. Again we come back, and now in this case we again go back to this root node, which is 3. Then again we go to the left, and then again we go to the right. So this is the strategy for using a pre-order traversal. Now for the post order traversal, basically we follow the principle of left node, right node and then root node. So first of all, we are going to visit up until left node exists. So this is the leftmost node, so we are going to visit that first. So we start our traversal at this position number 4. Then we visit the right node, which is 5, and then we visit the root node, which is 2 in this case. Now after this, we actually don't visit this node 1, because for this node 1 there exists a right subtree that we haven't visited. So we again go to the right side, and again this also has a left node, which is 6. So then we visit the node 6 in this case, then we visit the node 7, and then after visiting the 6 and 7, then we visit its root node, which is 3, and in the end, after visiting all the nodes, we visit the main root node, which is 1. And this is going to be the traversal strategy for the post order traversal. So when it comes to breadth first search, we actually expand upon its neighbors or its children for any given tree, rather than going in depth in any one particular direction. So if we see for this particular tree, the breadth first search traversal is going to look like this. So first of all, we are going to visit the root node, which is 1 in this case. Then we are going to visit its children. So its children are actually 2 and 3. So we are going to visit this node 2 and 3. Now for this left child, again it still has children of its own, so we are going to visit them first. So we are going to visit this node 4 and 5, and then for this node 3, it has children of its own as well, which is 6 and 7. Now in this case, we cannot further expand because this 4, 5, 6 and 7 does not have any children of their own. So we are done with the traversal. Basically we have iterated over all the nodes that were given. But if you see these nodes and the fashion we have visited them, it actually gives a very interesting perspective for the problem we are trying to solve. Well, first of all, we are visiting the node that is located at this position number 1. Then we visited its children, which are actually located at this level 2. So first we visited the level 1 node, then we visited all the nodes that are present at level 2. And then we visited all the nodes that were present at level 3. If we had any further nodes, then we would have visited them that were for the nodes that were located at this level number 4. So this breadth first search is actually a very good solution for the problem we are trying to solve, where we are trying to see that what would be the level order traversal for any given tree. Basically we are anyways iterating the nodes in particular levels. So all we will have to do is just simply make tuples of the levels that we are visiting and the nodes we are visiting at. So that is how we are going to optimally solve this problem. Now we are going to use the same tree that we have been using so far, and we are going to see that what would be the answer. So first of all, we will have to create an array list where we are going to store the answer. Now at any given position, whenever we start iterating over this tree and whenever we jump to a new level, we are going to create a new node inside our array list. So first of all, we are at this level 1, right? So now for this level 1, we are going to create a new node over here, which is this one. And for this level, because this node is located at level 1, we are actually going to create an entry over here. Now for this one, we are actually going to iterate over its children. We are going to call its children 2 and 3. Now because these are children of this node 1, they are actually going to be located at level which is whatever the level of this 1 is plus 1. So the level of this 1 is actually 1. So 1 plus 1 is going to be 2. So these nodes, they are actually going to be located at level 2. Now the moment we identified a new level, we are actually going to create a new node inside our array list. So over here we would have created this new node. Now in this new node, because we visited these values 2 and 3, we are going to actually add the value 2 and 3 over here. Now again we will have to further go down for this level 2 and 3. And remember that initially we only had this one node and we visited its children. Now again we have a node and we are visiting its children, and again we have a node and we are visiting its children. And suppose these had, if the new nodes, we would have visited their children as well. So basically we are doing the same work for different set of inputs, where initially this was a child but now this becomes a parent for these nodes. So we are basically doing recursion, nothing special in this. So now from this level 2, whenever we will call these left and right children, basically what we would have done is we would have increased whatever the value of level was for this value 2 plus 1. So this was located at level 2, which means these nodes, they are actually located at level 3. So now again we created a new level. So because we created a new level, we are going to create a new entry inside our array list, and then all the values located at this level, we are actually going to store them in this portion of our array list. So now first of all we are going to visit node 4. So we are going to add node 4 over here. Then from this 2 we are going to visit its right children, which is this node 5. So we are going to add 5 over here. Now we still have nodes that we haven't visited. So now we have this node 3. So we are going to first of all visit its left children, which is this node 6, and this is also located at level 3 because this 3 originally was located at level 2. So this is also because this is at level 3, we are adding it in the third portion or third placeholder inside our array list, and then in the end we are going to visit this node number 7 as well at the end. Now this does not have any further children, so we are good up until this point, and we can stop our traversal and return this new array list that we have created as the answer. So this is the approach we are suggesting. And if we see, we did the breadth first search traversal, and basically we did it recursively. Now we could have done it iteratively as well, nothing special in there. So you can discuss with your interviewer what is the strategy you want to use, and 9 out of 10 times your interviewer is going to ask you to do this problem recursively because it's lot less code. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present inside this given node. And if we see space complexity, well, basically we will have to create recursive, we will have to make recursive calls, and that takes some space, and that space is actually dependent on height of the given tree. So space complexity is actually going to be big O of h, where h is the height of the tree. Now first of all we are actually going to create a list of lists where we are going to store the answer, and we are going to declare it as a global variable because we are going to create a new method for our recursive call. So first of all, let me create this global variable called answer. Now we are going to create a new public method which is going to be acting as our recursive function, and it does not return anything. We are going to name it as order, and as an argument it is going to take any tree node and the level we are currently at. And now inside this method, first of all, what we are going to do is that whenever we are at any position or whenever we are creating a new node, basically we are going to add a new entry to our answer. After creating a new value for a new level, now all we will have to do is whatever this tree node is, based on its level value, we will have to add that value to our answer. Now after doing that, basically all we will have to do is for any single given node value, first of all we are going to check that whether it's left child and right child, if they exist or not. If they exist, basically we are going to call the same order method with this left child and right child, and we are going to increase the value of the levels. That is all we need to do for this order method. So now from this main method, first of all we are going to check for an edge case that if this given root is null. If this is null, we can simply return the answer. And if this given root is not null, basically we will have to call this order method with our root information and the current level that we are at. And now at the end, we simply have to return whatever the answer we get. Let's try to run this code. It seems like our solution is working as expected. Let's submit this code. And our code is actually pretty efficient compared to a lot of other solutions. And I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do lowest common ancestor of a binary search tree lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Facebook, Amazon, Apple, Google, Microsoft, Uber, Reddit and Twitter. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode easy problem, and basically first of all we are given the definition that what a lowest common ancestor means. The lowest common ancestor is defined between any two nodes P and Q, such as that the lowest node in given tree that has both P and Q as the descendants, where we allow a node to be a descendant of itself as well. We are given a binary search tree and we are also given two nodes in that binary search tree, and now we need to find the lowest common ancestor between those given two nodes. So let's try to understand this with this example. Basically we are given a binary search tree over here, and we are also given the value of P and Q to be 2 and 8. So subsequently if we see over here, 2 is located at this place and 8 is located at this place. So the most common element or the immediate common element that we can find is actually 6 in this case. So that's why in this case we are going to return 6 as the answer, because that is the lowest common ancestor between the node 2 and 8. If we take one more example in this case, so over here we are given this P is equal to 2 and Q is equal to 4. So P is located at this 2 and Q is actually located at this 4. Now if you see in this case, actually this 4 is a descendant of this 2. So that's a given fact. But we are, remember, we are also told that we allow a node to be a descendant of itself as well. So in this case, since this 2 and 4, so 4 is already a descendant of this 2 and 2 is already a descendant of its self. So in this case, we will have to return this 2 as the answer. And that is what is given over here. We are given one more example where we are given only two nodes for this given binary tree. So the binary tree looks like this 2 and 1, and in this case we are given the value of this P to be 2 and Q to be 1. So again we can see that in this case this 2 is already a descendant of itself and this 1 is actually a child of 2. So because of that, 1 is also a descendant of this 2. So in this case we will again return this 2 to be answer. Now I hope that this makes understanding the problem more easier, and now let's see that what is the approach we are going to solve this problem. Okay, first of all, I'm actually going to show you a bunch of different binary search trees, and for all of those binary search trees I have created some P and Q values, and we are going to see that what was the lowest common ancestor and why that was the lowest common ancestor. Right now we already know that important property of binary search tree, and that is that for any given root value, everything on the left subtree of that binary search tree is actually less than that, and everything on the right side of that binary search tree is greater than that. We already know this important property, and we are going to take it to our advantage based on this given root value or any root value and with subsequent P and Q values. So if we see over here in this case, the given value of P is actually 6, and if we start traversing through this binary search tree, immediately we would find the 6 to be present over here. So because we find the 6 to be present, there can only be one possibility, that this Q or whatever the value of Q, that would either be on the left side of the subtree or right side of the subtree, but we already find the value to be 6 over here. So immediately we can return 6 to be the lowest common ancestor, because anyways this value of Q is somewhere supposed to fall inside the remaining binary search tree, and in this case it is on the right side of the subtree. So we will return 6 as the answer. This makes sense, right? Now the next example, again we are given the same thing. We are given this value P to be 11 and Q to be 9. So we know that this P is over here and Q is over here. 11 is going to be answer, but let's go ahead with our algorithm. So first of all, we'll start iterating over this root. So the root value is actually 8. Now for this root value, we are going to compare it with the values of P and Q, right? In this case, the value of P and Q both are actually greater than this 8. So because both are greater than this 8, we know based on the property of binary search tree that they are meant to fall somewhere on the right side of this given binary search tree. So we will start iterating over the right side of the binary search tree to either find the values of P or Q, or if we can't find, we will try to find the lowest common ancestor. So when we start iterating over on the right side of the subtree, we will ignore this left side of the subtree. We don't care. Now this value is 11. This value is 11 is actually matches the value of this given P. So immediately whenever we find a match with either P or Q, we can return that to be the lowest common ancestor immediately, and in this case this is going to be the answer, because this 9 is meant to be somewhere below this binary search tree, and in this case it is immediately right here present, so we will return this 11 to be the answer, which is the lowest common ancestor. Let's take one more example which is very similar. So in this case this value is p is equal to 3 and q is equal to 1. Now again, based on our algorithm, we will start traversing over this binary search tree. Now the first value we traverse, whenever we compare its value with this p and q, immediately we find a match with this p to be over here. So because we find a match over here, do we really need to iterate over this given binary search tree? Well, the answer is no. Why? Because we know that this q value is somewhere going to be down below, and that is always going to be this descendant of this p. So again, we are going to return the values 3 as the lowest common ancestor. So far it makes sense that whenever either we identify the value of p and q, we can return that to be the lowest common ancestor immediately. But what happens if the case is a little bit different? So in this case, I have given the value of p to be 6 and q to be 9, right? Again, let's start with our algorithm. So we'll start iterating over this binary search tree. So first of all, this value is actually 5. So because this value is 5, we'll try to see that, okay, we will compare it with this value of p and q, right? So actually this 5 is less than p and less than q. Both p and q are greater than this root value. So immediately it is meant to fall somewhere on the right side of the subtree. So now we'll start iterating on the right side of the subtree. We'll ignore these two because we don't need them. Now again, this value is 7. So let's compare this 7 with this value of p and q. Well, if we compare this 7 is actually greater than this p, and this 7 is actually less than this q, where, right? So we can conclude this 7 actually falls somewhere in the middle, because for the 7 on one side 6 is meant to be, because 6 is less than 7, and somewhere on the other side 9 is meant to be, because 9 is greater than the 7, based on the property of a binary search tree. And if we utilize that to our maximum advantage, we can immediately determine that this 7 is the common point between this 6 and 9, where on one side 6 resides. So 6 resides on the left side over here, and 9 resides on the right side of the subtree. So on the right side of the subtree, this is where 9 resides. So we will return 7 to be the answer in this case. And this is the approach we are going to follow. So every single time for any given tree, we will start iterating over that tree, and we are going to compare its value with p and q. Based on that, we will decide that whether we go on the left side of the subtree or right side of the subtree. The moment we find a match between p and q, whatever the value we found, if we find that, we will return that to be the lowest common ancestor. If we don't find a match, and if we are in a situation where this value of p is on the left side of this any root value and q is on the right side of any root value, then immediately we can return that value to be the answer. And this is the approach we are going to take to solve this problem, and this is the optimal way to solve it. Now there are two ways to solve this problem. We can either solve it recursively or we can solve it iteratively. Now I like recursion better, but iterative method will also work as expected in this case. Now for the recursion, if we see the time and space complexity, the time complexity is actually going to be big O of n, because we will have to iterate over all the values in the worst case scenario. And for the space complexity, the space complexity is actually going to be big O of n as well, because we will have to maintain the runtime stack for this recursion method. Well, one good thing in iterative method is that for iterative method, the time complexity is still going to be big O of n, but for the space complexity, we can actually use a constant space complexity for the iterative approach. But in the coding, because I'm trying to improve my recursion, I will be showing you the recursive method. But just remember that iterative approach would be the better option in this case. So we are going to use the same method as our recursive method. And first of all, in this method as an input, we are given this root value, we are given the value of p and q. So first of all, because we don't need to deal with this tree node, we will actually have to deal with this integer value. So I'm going to initialize three variables called the parent value, p value and q value, and I'm going to assign the values based on this whatever the input we get. Now we will have to check that whether this parent value, if that is the common point between p and q, or either p and q falls on one side or other side of this binary tree. If that is the case, we will call our recursive method again. So first of all, we are going to check that if this p value and q value both are greater than this parent value. If that is the case, which means we will have to iterate on the right side of the subtree. So we are going to call the iterative method on the right side of the subtree. If that is not the case, we are going to check that whether this p value and q value both falls on the left side of this parent value. So again, we are going to do that. So if both p value and q value are less than the parent value, which means we will have to search the left side of the subtree. So we are going to do that. Okay, if that is not the case, which means that whatever this root value we are at, that is either p or q value, which means we can return root immediately. That's it. That should be working. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions in terms of time complexity. I already mentioned you that for the space complexity, this recursive solution is not the most optimal, but I want to practice recursion, so that's why I did that. You can find an iterative solution that works as well. And I would be posting this in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do validate binary search tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Bloomberg, Facebook, Uber, Google, Apple, ByteDance, Lyft, LinkedIn and Netflix. So that's why I am paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and one of the most liked tree problems on LeetCode. Basically, we are given the root of a binary tree and we need to determine that whether that given tree is a valid binary search tree or not. We are also given the definition that what a valid binary search tree is. Basically, for any given tree, if this root value or the node value, so if this is the value of the node, basically every single value that is present on the left of the node should be less than whatever this node value is, and every single value that is on the right side of the node should be greater than whatever this node value is. So if that is the case and that is true for the entire given tree, we can define it as a valid binary search tree. So let's take a couple of examples that are shown over here. So in the first example, well, basically the node value we have is 2. So in the left subtree we only have one value, that is 1, which is less than this 2, and on the right subtree we only have one value again, which is 3, which is greater than this node value 2. So in this case we can consider this to be a valid binary search tree, and in this case we will return true. But if we take a look at the second example, so in the second example we are given this root value as 5. So this node value is 5, that is okay. If we see on the left subtree we only have one child, and that is the value is 1. So this is again less than whatever the value we have for the node value. Now if we see on the right subtree, the value of this is actually 4. So 4 is again less than 5. So because this 4 is less than 5, and remember that we have the definition of valid binary search tree, that everything on the right subtree should be greater than whatever the node's value is. So in this case, this value is actually not greater than the value of this root node. So in this case, this is not an valid tree. So in this case, we will return false. And this is what we have to define basically. Now, based on the definition, we can define that what a valid binary search tree is. That for any particular given node, if its entire left subtree, if that is less than that node, and if its entire right subtree, if that is greater than that node, we can define that to be a valid binary search tree. Well, if that is the case, the first intuition that comes to our mind is that for any given node value, what we can do is we can check its left child and right child. If the left child is less than it and right child is greater than it, if that is the case, we will keep on repeating the same process for all the subsequent left child and right child with its root node, and in the end, if we reach to the end of this tree, we can return true immediately, saying that this is a valid binary search tree. Well, let's try to apply that same logic for this particular example. Basically, we are given this node 5. So this 3 is actually less than 5 and 8 is actually greater than 5. So in this case, this portion is actually valid. Now again, for this 3, this 1 is less than it and 4 is greater than it. Again, this portion is also valid, and same is true for this 8, 6 and 9 as well. So in this case, we can define this to be a valid binary search tree, and we can return true in this case, saying that this is a valid binary search tree. But the thing is, this solution is not the most optimal way to solve this problem, and let me quickly show you why. Because based on the same logic for this 5, this 3 and 8, again, okay, this is less than, this is greater than, so far this is valid. Again, for this 3, this is 1 and 4, so this is less than, greater than, again this is valid. But now for this 8, this is also 2 and 9, so this is less than, greater than, again this is valid. So all three portions are valid. By definition, we would treat this to be a valid binary search tree, and that would actually be a false positive. Why? Because remember that by the definition for this node, everything that is on the right side of this tree should actually be greater than this node 5, but in this case this 2 is actually less than this 5, and because of that particular case we will need to return false in this case. The thing is, based on our previous method we would have returned true. So let's see that what would be the actual optimal solution to solve this problem. So the idea for the optimal solution in this case is that we are actually going to do in-order traversal on the given binary tree to determine that whether it's a valid binary search tree or not. Well, if you want to learn more about different types of tree traversals, you can check out the video over here. Now let's get back to the question at the hand. So basically what the idea I'm suggesting is that if we do in-order traversal in any given tree, basically the idea for in-order traversal is that first of all we visit the left subtree, then we visit the node, and then we visit the right subtree. Also, this in-order traversal is a depth first search kind of a traversal where we are actually going in the depth first and then we are visiting the different nodes. So in this case, the traversal that we are going to do is that first of all we are going to go for the left subtree. So for this node, left node exists. Again for this node, left node exists. So first of all we are going to visit this left child. Then this child does not have any more children of its own. So now we are going to visit its node. So we are going to visit this node 3, and then again we are going to visit its right child, which is 4 in this case. After doing that, we are going to visit the node, and then we will keep on repeating the same process. So let's see that what is the path we are going to take for this in order traversal. Well, for this problem, basically the path we are going to take is that first of all, as mentioned, we are going to visit this node number 1. So first node is going to be 1, then we are going to visit node number 3, and then we are going to visit node number 4 in the fashion of left node, and then right sub node. Then we are going to visit the node. So we are going to visit node number 5. Now we are going to keep on iterating on the right subtree. So even on the right subtree, again we are going to follow this method of left node and right. So for this left subtree, now this becomes the root node or the node, and this also has a left subtree existing. So first of all we are going to visit this node number 6, then we are going to visit node number 8, and in the end we are going to visit this node number 9. So this is the in order traversal for this given binary tree. Now the thing is, if you see this traversal, basically everything is going in increasing order, and this whole thing is actually sorted. And this is the property of this in order traversal that we are going to make use of, and we are going to solve it optimally. The idea is for any given tree that we are presented with, we are going to do an in order traversal, and during the in order traversal, basically the only thing we have to keep track of that any given node that we are iterating, whether that node is actually greater than its previous node or not. If it is not greater than its previous node, immediately we can return false. So in this case, because this was a valid binary search tree, we were able to get an in order traversal that is completely in increasing order, and all the previous nodes, they are actually less in value compared to its next subsequent node, and this property is maintained throughout the entire journey. Now let's see one example where this is not the case. So in this example, we can clearly see that this node 2 is at the correct place, and this is not a valid binary search tree. So let's see the in order traversal over here. So in this case, the path is going to be, the next node we are going to visit is actually 2, and if we compare this node 2 to its previous value, the previous value is actually 5. 5 is actually greater than this 2, which should not be the case, and immediately at this point only we can conclude that this is an invalid binary search tree. We will return false immediately in this case, and that is the answer we are going to use. Now actually there are two ways to do in order traversal for any given binary search tree. There is an iterative way and there is a recursive way. If you know me, I like the recursion better, so I'm going to show you the recursive way in the coding, but it can be also done iteratively as well. And the tricky part in this problem is to identify that we need to solve this problem using in order traversal. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present. For the space complexity, we are using recursion, and we might have to store n characters in the worst case scenario. First of all, we are actually going to define a global variable called previous to store the value of the previous element. Now let me create a new in order method that would be our recursive method. So now I have created a new in order method that returns a boolean answer, and we are taking just a root value as the input. Now first of all, we are going to create the terminating case that if the given root is equal to null, we are going to return true. If that is not the case, first of all, for the in order traversal, we will have to call the leftmost function or leftmost value. So we are going to do that. So first of all, we are going to see that if the answer for the root dot left, if that is false, we will return false. If that is not the case, we will move on towards our next condition. Okay, so if we did not return false from our left side subtree traversal, then we are going to check our condition. So the condition we are going to check is that whether the current root value, if that is less than or equal to the previous value, if that is the case, which means that we have actually found an invalid binary search tree, so we can return false immediately. So if we don't return false by this point, which means the previous value was actually less than whatever the current root value we had, which is a good sign. So now what we are going to do is we are going to update the value of our previous variable. So that is going to be the current root value. And then after that, we are going to call the right side subtree as well. So we can simply return the in order for the right subtree. Now from our main method, all we will have to do is we will have to set up the value of the previous character. So initial value is going to be the null, and then we are going to call this in order method. Okay, seems like our solution is working as expected. Let's submit this code. And our submission runs pretty efficiently compared to a lot of other solutions, and that is because the code runs in 0 milliseconds. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do kth smallest element in binary search tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Uber, Amazon, Microsoft, Facebook, LinkedIn, Apple, Google and Bloomberg. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given the root of a binary search tree, and we are also given an integer called k. Now we need to return kth smallest value from all the given values inside any given binary tree. So let's try to understand this with a couple of examples that are presented over here. So this is a binary search tree we are given, and if you notice the important property of binary search tree, where for whatever the root node, everything on the left subtree is less than that root node, and everything on the right subtree is greater than that root node that is present for this BST. So that is the definition of binary search tree. I'm just making it clear. And now for this example, this is the binary search tree we are given, and we are also given the value of k to be 1, which means we need to return first smallest value. So in this case, the first smallest value or the smallest value is going to be this value 1, and this is what we need to return as the output. Let's take one more example. So in this case, again, we are given a binary search tree, and we are also given the value of k is equal to 3, which means we need to return third smallest value. If we see in this case, this 1 is actually the first smallest value, same way this 2 is the second smallest value, and same way this 3 is actually the third smallest value. So in this case, we will have to return this 3 as the answer. So I hope that you have understood the problem by now. Now let's see that what is going to be the optimal approach to solve this problem. Okay, suppose this is the binary search tree that we are given, and we are trying to find the kth smallest value at any given position. So the idea I'm suggesting is that for this particular binary search tree, if we make the sorted array of all the values and we sort them in increasing order, then whatever this array we have created that is already sorted, based on this, it becomes pretty easy for us to find the kth value. How? All we have to do is just look up in this array, and we will be able to find the value. Let me quickly show you what I mean. So for this particular binary search tree, if we see the sorted path where the first value is 1, then we have the value 3, then we have the value 4, and then we have 5, 8 and 9, and this is the sorted path that we have been able to generate. Now once we have this value, it becomes pretty easy for us to find any kth position. How? Suppose we are given k is equal to 2, we can immediately return second smallest value, which is the second value in this case, which is the value number 3. If we are given k is equal to 5, then we simply need to return this value number 8. If we are given k is equal to 3, we can simply return this value number 4. So now you get the idea that once we have this sorted path, it becomes pretty easy for us to find any kth position. So all we will have to work on is that from this given binary search tree, how can we actually create this sorted path? And if you know, or if you have followed my previous video, you know the answer. The answer is actually in order traversal. So let me quickly show you the optimal solution using in order traversal for this problem. Okay, so in order traversal actually a depth first search kind of a traversal, which means that first of all, on the left side of the subtree, we go to the leftmost position, then we visit its node or its root value, and then we visit its right subtree, and we keep on repeating the same process. So let's see that what is going to be the path in this case. So path in this case is, first of all, we are going to visit the leftmost element, which is 1. So we'll visit node number 1, then we will visit node number 3, then we will visit node number 4 based on following this left node and right more formula. After that, we will visit the node again, which is 5, and then we will be on the right side of the subtree. So again, on the right side of the subtree, we will have to follow the same path, left node and right. But in this case, since this right side of the subtree does not have any left children, so we won't be able to update or traverse any left value, but we would be able to traverse the node value. So again, we will travel the value 8, and then in the end we would traverse the value number 9. So in this case, this is the path we are able to generate from this given input binary search tree using this in order traversal. And if you see this path, this is actually increasing order, and this path is actually sorted, which is very good for us. So suppose we are given the k is equal to 3. So if kth value is 3, we can simply return 4 immediately. If we are given k is equal to 5, then again we can return this value number 8 immediately, as mentioned earlier. And this is the approach we'll have to take to solve this problem optimally. Now if you want to learn more about different kinds of tree traversal, check out my video over here. Now let's see the time and space complexity in this case. The time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree. And if we see space complexity, the space complexity is also going to be big O of n to accommodate our in order traversal. There are actually two ways to solve this problem. One is the recursive way and second one is the iterative way. Now, since you know me, I like the recursion better. And even in the coding, first of all, we are going to create our recursive method called in order, and that is going to return an array. So I have created the in order method that takes in a root value and also that takes in an array list. Now, first of all, we are going to check the terminating case. So if the given root is equal to null, we can simply return whatever the array value we have. Okay, if that is not the case, first of all, we are going to call the in order function again, and we are actually going to call for the left subtree. So we are going to call with the root dot left child, and we are also going to pass in the value of whatever the array we already received. Once that is done, we are also going to add whatever the node value we have. So we are going to add the value for that particular root, and in the end we are also going to call the in order method again for the right side of the subtree, because remember, for the in order we are actually following the method of left node and right. So with this time we are going to pass in the value of the right child, and we are also going to pass in the value of the whatever the array we have created. Now once this method runs, simply we need to return this array list that we have been creating. Okay, now from the main method, first of all, we are going to create a new array list called nums. In order to populate this, we are actually going to call our in order method, and we are going to pass in the value of the root, and we are also going to pass in the value of a new array list. Once that is done, all we will have to do is basically from this array list we simply have to return whatever the k minus 1th position element is, because remember this k is actually 1 index, meanwhile the array list we have been creating, that is 0 index. So that is one tricky thing that we will have to take care of. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions. It is also very efficient in terms of space complexity as well, and I will be posting this in the comments so you can check it out the solution from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do construct a binary tree from pre-order and in-order traversal lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Microsoft, Amazon, Bloomberg, Apple, Uber, ByteDance, Google, Facebook, and LinkedIn. So that's why I am paying my utmost attention. I hope you also enjoy the video. Now this is a very hated LeetCode problem, and let me show you why. This is from the solution tab of the LeetCode problem, where people have expressed their views very abruptly. Some people are saying why God, why? Some people are saying that it's time to leave for Himalayas. Some people are saying that if you get this question they do not want to hire you and things like that. There are many other comments. The thing is, we do not want to focus on the negativity. Let's try to see that what is the approach to solve this problem, and then we are going to see that how can we be able to solve this problem if we encounter this in any interview, because our aim is to get into FAANG, not just dream about it. Now this is a LeetCode medium problem, but in my opinion this should have been a LeetCode hard problem. Now let's try to understand the problem. Basically we are given two integer arrays called pre-order and in-order, and basically they are the pre-order traversal of a binary tree and in-order traversal of the binary tree. Now based on these two arrays that we are given, we need to construct and return the original binary tree. So let's try to understand this with an example. So over here we are given as an input, we are given two different arrays, pre-order array and in-order array. Now somehow if we iterate over this pre-order and in-order array, there is only one combination of binary tree we can make, and which is this one. So that is the example that is given over here. Now let's see that what is going to be the different approach to solve this problem. But before we do that, the important thing in this problem is to understand that what is a pre-order traversal, what is the in-order traversal, and how can we use their properties to our advantage. So first of all, I'm going to show you pre-order and in-order traversal, how it works. So first of all, we are going to learn about pre-order traversal, and basically pre-order is a DFS kind of traversal, which is depth first search. If you want to know more about different kinds of traversal, you can check out my video over here. Now let's focus on the pre-order traversal for now. So basically in pre-order traversal, first of all we visit the root node, then we visit its left subtree, and then we visit its right subtree, and we keep on doing that until the nodes exist. So let's see that for this given example, what is going to be the path that we are going to follow. So first of all, we are going to visit the root node. So in this case, the first node we are visiting is going to be node number 5. Then we are going to visit its left child. So left child in this case is 3. So again we are going to visit node number 3, and then again we are going to visit its left child, because remember it's root, left subtree and right subtree. So left subtree still exists over here, so we are going to visit node number 1. Now left subtree does not, nothing more exist in the left subtree, so now we will start visiting the right subtree. So we now will visit the node number 7. Now after visiting the node number 7, now there is nothing exist over here, so again we are going to go back to the root, because we still have to visit its right subtree. So when we start visiting the right subtree, again we are going to follow the formula for root, left and right. So root node in this case is going to be 8. So now we are going to visit node number 8. After that we are going to visit node number 6, and then we are going to visit node number 9, which is the right subtree, and this is going to be the traversal path that we are going to take. Now let's see that what would be the in order traversal in the same manner. So again, as mentioned, the in order is also a DFS kind of traversal, but in this case the methodology we follow is that first of all we visit the left node, then we visit the root node, and then we visit the right node. So for this given example, what we are going to do is, first of all we are going to go to the left node all the way possible. So left node in this case is 1. So first node we are going to visit is going to be node number 1. Now for now we can't go left anywhere, so now we are going to visit its root node. So root node is in this case is going to be 3, and then we are going to visit its right node. So right node in this case is going to be 7. After doing that, after visiting all 3 nodes, now we don't have any more nodes to travel on the left subtree. So now we are going to visit the root node as mentioned over here, because we have already taken care of this left part. So now we are going to visit node number 5. Now again we still have values that we need to visit on the right subtree. So again we are going to take on the same initiative. So now the first thing we are going to visit is going to be the leftmost element for this right subtree. So leftmost element in this case is 6. So we are going to visit the node number 6 over here. After that we are going to visit the root node, which is 8, and then in the end we are going to visit the node 9 over here, which is this one. So this is how in order traversal works. So after understanding both the values and both the different traversal mechanism, let's see that what would be the optimal solution and how we are going to approach that. Okay, suppose this is the binary tree that we are given that we need to iterate over, and we are given the pre-order and in-order traversal for both of them. So in this case, the pre-order traversal for this tree is going to be, and the in-order traversal in this case is going to be. Now once we have both the values, let's see that what is the approach we are going to take. So if you closely observe both of these values for pre-order and in-order traversal, they both have something to offer. The thing they have to offer is that this pre-order allows us to determine that what the root of any section of the tree is, and this in order allows us to determine that what is the left subtree and what is the right subtree of any given tree. How? Let me quickly show it to you. So if we see this pre-order traversal, The first value in this case is actually the root of the binary tree, which is 5 over here, which you can clearly see that the 5 is the root of the binary tree. So well, that is interesting information, but the thing is this alone is not helpful. If we see with this in order traversal for this 5, if we see the left side of this 5, there is only one entry over here, which is 3. And if we see in this tree, actually this 3 is the left subtree of this entire tree where the root is 5. Now if we see on the right side, the values are 6, 8 and 9, which is these 3 items, and this is actually the right subtree of this original given tree where the root value is 5. So now we actually have something meaningful that we can use. If we keep on repeating the same process, now for this pre-order traversal, again we see, okay, so the next value is 3. So 3 is already the left subtree. Now if we again break it from this in order traversal, for this in order traversal, we only have 3 value over here. We have nothing on the side, we have nothing on the right side, because the right side value is actually 5, which we have already identified that that is the root of this original value 3, which means we can determine over here that for this 3 it does not have any values on the left subchild and right subchild, because the very next value of this 3 is actually 5, which was already the root of this value 3. So now again we have some meaningful information. So far let's backtrack the information we have found so far. That let me create an answer value over here where we have already found that the first value is 5. The leftmost value, or the first left value or left subchild of this value number 5 is actually 3, and for this 3 it does not have any more children. So now we can add the values null over here. Okay, now we are done iterating up until this point, but we still have some more nodes that we need to iterate over. So based on this pre-order traversal, now the next node we have is 8. So now we know that the current root we are iterating over is actually 8. Okay, so we have this value 8. Now from this in order traversal, we actually have these 3 values where this 8 is actually in the middle, because remember this in order traversal allows us to determine that what is the left subtree and right subtree of any given root. So in this case, if the root is 8, then the left subtree is going to be the value 6 and the right subtree is going to be the value number 9. So we are going to use it to our advantage. Now for this value number 6, again we are going to try to see that what is on the left of 6 and right of 6, but in this case, since we don't have any more information for this value number 6, the left value is 5, which was the original root which we have already iterated over, and this next value is 8, which was the root of immediate root of this value number 6, which we have already iterated over. So now we can determine that for this 6 we don't have any other value, so which means that we have 2 null values. So again, now and same thing we can determine for this 9 as well, that for this 9 the leftmost value is actually 8 and in the right there is nothing over here, which means this 9 also does not have any more children. So now let's again backtrack based on the information we have found so far. So now on the right side, the value we got was 8, that was the root we iterated over, and we found that information based on the pre-order traversal. After finding this 8, now we started iterating over the left and right children of this 8. So left children was 6, so we iterated the value 6. Now the 6 did not had any more children, so we had the values null over here. And now then we had the value number 9, and 9 also did not have any more children, so now again we had the 2 more null values over here. And this is the actual binary tree that we were able to create based on this original given pre-order traversal and in-order traversal, and that is the solution that your interviewer is expecting, and that is what is needed for this problem as well. Now there are actually 2 ways to do this problem. There is an iterative way and there is a recursive way. If you know me, I love the recursive solution, so I'm going to opt for the recursive solution. Basically what we are going to do is, initially we are going to find the root value, and then we are going to find the left subtree and right subtree. Now again we are going to pick one value, so we are going to pick the left subtree. So now even for the left subtree we will have a root value and its left child and right child, and again we are going to keep on repeating the same process, and we will be continuing to building our answer, and same thing we are going to repeat for our right subtree as well. So basically we are taking a bigger problem and then dividing into a bunch of different smaller problems. I know this looks really messy, but you get the idea of what I'm trying to convey over here. And let's see the time and space complexity in this problem. So time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree, because we will have to iterate over both in order and pre-order traversal, and originally it's going to be 2n traversal. The thing is, generically we can write it to big O of n. If we see space complexity, Well, space complexity is also going to be big O of n, because recursively we might have to iterate over all the nodes, and it worst case scenario it could take big O of n space. This is a wonderful time and space complexity given that how complex this problem was, and based on the pre-order and in-order traversal we were actually able to build the solution for the binary tree. Now let's see the coding. So before we start coding, we will actually have to define that how we are going to use this pre-order and in-order array. Well, we are going to use this pre-order array to determine that what is the root value for any subsequent positions. And once we have the root value, we are actually going to use this in-order array to determine that what is the left subtree and right subtree for any given root. And once we have both the information, we are actually able to build our tree. Now the thing is, if you clearly understand that for this in-order array, we will have to look up at information in much broader fashion than compared to this pre-order array. So what we can do is, in order to iterate over this in order array, rather than iterating it just by considering this to be an array, we are actually going to create a hash map where we are going, which is going to allow us to iterate over this in order array pretty fast. And so let me define two global variables over here. First of all, once we have these two information, now from our main method, first of all we will have to iterate over this in order array, and then we will have to populate this in order index map that we just created. So let me quickly run a for loop. Now we have our hash map ready to go. Now we will have to create a separate method where we are going to call the recursion. So first of all, let me create a new public method. So now I have created a new method called array to tree that returns a tree node, and as an input I'm taking the pre-order array, the left portion and right portion, and now we are going to create this recursive method. Now before I do that, I will also have to initialize the values for this pre-order index and also for this in-order index map, so that I'm going to do it. Okay, now back to our recursive method. So for recursion, first of all, we will have to create a terminating case, and the terminating case in this case is going to be that if the value of left is greater than the value of right, if that is the case, we break out immediately and we will return null. If that is not the case, first of all, we will have to define our root value, and root value we are going to define from our pre-order array. So our root value is actually going to be the whatever this pre-order index value that we have, and then we are also going to increment the value of this pre-order index as well. So this is the root value, and after that we are going to increment the value of pre-order index. Now since we have our root value, we are actually going to create a new tree node called root, and for this root node we are going to assign the value that we received over here. Originally, the value of this pre-order index is 0, which means that the first value we are getting from this pre-order is the main root of the tree. Once we get that value, we will have to create the left subtree and right subtree. So we will have to call this array to tree method again, and we are going to populate the value for left and right child. So for the left child, we are again going to call this array to tree method. Inside the input, first of all, we are going to provide this pre-order array as we found as it is. Now for the left subtree, we are going to keep the value same for the left value, but for the right portion, the value is actually going to be different, and that is going to be different based on whatever this root value we had. So in this case, for the first value for this pre-order array, the root value is actually 3. So now for the left part, we already have the value, but for the right part, we are going to have to provide all the values that are present after this root node. So we are going to do that. So for that, now our in order index map is very helpful. Now we have both the information ready to us. Now we are going to call the right subtree in the same manner, but in this portion we are going to treat whatever the right variable we had already, but now we are going to change the left variable. So for the left variable we are actually going to use whatever the value we had for the root value, and we are going to do it +1, and as the right limit we are going to keep whatever the right limit we originally had. And after this recursion ends and after this function ends, we simply need to return the root variable. Okay, so now our recursive method is ready to go. Now all we will have to do is, from our main method we will have to call this recursive method that we just created. That should be it. So we are calling this pre-order method, but we are providing the pre-order array, and as the left position we are providing the value 0, as the rightmost position we are providing the value of whatever the pre-order length is -1, and that should do the trick. Now let's try to run this code. It seems like our solution is working as expected. Let's submit this code. And our code is pretty efficient compared to a lot of other solutions. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do binary tree maximum path sum lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, DoorDash, Facebook, Microsoft, Google, ByteDance, TikTok, Snapchat, Twitter, Apple, Uber and LinkedIn. So that's why I am paying my utmost attention. I hope you also enjoy the video. So despite being a hard problem, this is a very well liked problem on LeetCode. Basically, we are given the root of a binary tree and we need to return the maximum path sum for that particular non-empty path. So we will have to understand a couple of terminologies over here. We will have to understand that what a path sum is, and before we understand that, we will have to understand that what a path is. Lucky for us, we are given definition of both of them. So a path is a binary tree sequence of nodes where each pair of adjacent nodes in that particular sequence has an edge connecting them, and we are also told one very important thing, that any single node in that sequence can at most appear once. We are also given the note that it is not necessary that path has to go through the root of the node. Okay, so over here I have drawn a couple of different trees and I'm going to show you some examples of what a valid path is and what an invalid path is. So first of all, this is a valid path. And for that, we'll have to understand that why this path is a valid path, because all the three nodes that are connected in this particular path, they are adjacent to each other. They all have an edge connecting to them and they all appear at most once and nothing more than that. Now, this is also a valid path and this is also a valid path. This is also a valid path and this is also a valid path. Both paths are valid as well. And the path that looks like this is also a valid path, and the path that looks like this is also a valid path. Now let's see some examples of an invalid path. Suppose I start up my journey over here. I go up, I go down, I go to the left child, and then again I try to go to the right child. Again, this is an example of an invalid path because this node appears twice as well. Now we know many examples that what a valid path is. Now let's see that what the problem is actually asking us to solve. After understanding the definition of a path, we are going to understand the definition of a path sum. Basically, it is the sum of all the nodes that are present inside this given path. So that is actually quite simple to understand, and the problem is actually asking us to find the maximum path sum that we can make out of given binary tree. So now I have drawn three different trees to understand the maximum path sum for each one of them. So first of all, for this particular tree, the maximum path sum is going to be this path. And why? Because all the nodes are positive, and if we take the sum of these three nodes, it's actually going to be 5 plus 4 plus 9, which becomes 18. And this is what we need to return in the answer. If we take the second example, things are not as easy as the first one. Why? Because we are dealing with a negative value over here. So in this case, even if we try to do the same path that we had drawn over here, this won't work because the sum of this is actually going to be, which is not the most optimal path we can achieve. The most optimal path in this case is going to be this one, and the sum is actually going to be 5 plus 4 equals to 9. And in this case, we will have to return 9. So in this case, the maximum path actually is going to be this one between these three nodes. Why? Though there is a positive value over here, if we were to include this positive value, the path we would make would looks like this. And that would actually go through this root value, which has the value of negative 11, which actually brings the total path down or total sum down. So that is why it is not in our best interest to include this node, and that is why the maximum path in this case we can achieve is amongst these three nodes, where the sum is actually going to be 10 plus 8 plus 2 equals to 20, and that is what we need to return. Now, before we come up with the optimal solution, I'm going to show you a few different concepts with various examples. So first of all, we have an example of tree that looks like this, where in this case, all the nodes are positive, which means things are a little bit easy for us, and our aim is to find the maximum product sum we can achieve, right? So the idea is at any given portion, we have the root information. Now from this root information, what we are going to do is we are going to see that what this left subtree has to offer and what this right subtree has to offer, and then addition of all of them should give us our maximum product sum. So in this case, this left subtree does not have any more children. It only has one node, which means it can, the maximum value it can contribute towards the maximum path sum is going to be 5. So we have the value 3 already from this root. Then we gain this 5 from the maximum path sum, and then again we gain this 2 from this right subtree. So the total maximum path sum we can achieve is going to be 10, which is the answer in this case. And since all nodes were positive, it is in our favor to include all the nodes. So that is one way to do it, right? And this is a very simple example, so we are able to understand it quickly. Now let's try to see that what would be the approach in a little bit more difficult scenario. So suppose we are given a tree like this. In this case, we actually have a negative value. So if we apply the same logic over here, this left subchild has -5 to offer, this right subchild has +2 to offer, and this root value is actually 3. So maximum path sum based on the previous logic would actually become 0 if we just do sum of all the values. But that is not what we are going to do. We are also going to check at any given moment that whether the value that is being contributed, if that is less than 0 or not. If that is less than 0, immediately we are going to discard this value, which means that we are not going to consider this -5 to be part of this maximum product sum. And in this case, what we are going to do is we are going to do this 3 plus 2, because both values are positive. So in this case, the answer we are going to get is 5. So we gain one more important thing, that whenever we see minus values, we are going to ignore that from our maximum production because they don't add any more value over here. Now one more thing we need to consider. What if we have multiple nodes, and then what should be our approach in that case? Okay, suppose we are given an example like this. In this case, what should be our approach? Well, we want to find the maximum path sum. So again, we are going to repeat the same process. We are going to see that for this root node, what is this left subtree has to offer? It has to offer maximum 5 value. So we are good up until this point. For this right subtree, actually we will have to calculate that what is the maximum value it can offer. And how we can do it? We are actually going to take this root value, because that is going to be the part of this right subtree for sure. So we already have value as 8 over here. Now from this 8, we actually have two options to be included for our maximum path sum. We can either do 8-2 or we can do 8-1. So in this case, obvious choice is going to be 2, because this value 2 is actually greater than with this value 1. So in this case, we are going to ignore this 1 and we are going to keep this 2, which means that we can do 8 plus 2 to be 10. So in this case, we can determine that this actually has the value 10 to give towards maximum path sum. Now the question will come to your mind is that why in this case we only choose value 10 and why not we chose value 11? Well, what if under what circumstances can this value become 11? It can become 11 if we include all these three values to be part of this maximum path sum. But we already know that this goes through the root value, which means that if we were to include all these three values to make the value 11, it won't work, because then the path would look like this. It would go from 5 to 3. Okay, so far we are good. Then again through 8. Now from this 8, we cannot include both 1 and 2, because suppose we try to do it, we include this 1 and then we try to go back to 2, we come up at this 8 again, and we know that that cannot be part of a path sum. So that is why we only have the option to choose either 1 or 2. So that is the important detail over here. That is why for when we were calculating the maximum contribution this right subtree can make, we only had two options. Either we could do 8 plus 2 or we could do 8 plus 1, but not both of them. So just remember that. That is why I showed you this example. So in this case, the maximum contribution we can get from this right subtree is going to be 10. So now let's calculate the maximum path sum in this case. So the maximum path sum is going to be the root node is 3 plus this left subtree can contribute value 5 and plus this right subtree can contribute value 10. So the answer is going to be 18, and this is what we need to return in this case. So far we have understood, we had gained very good understanding of many different cases. Now let's consider one more case where the things become a little bit more interesting. And why it becomes interesting? Because so far we are under the impression that we have to take this root value as part of the answer. But what if that is not the case? What if we encounter some possibility where this root value does not need to be part of the main maximum path sum that we take? Then how do we approach that? So let me quickly show you an example for that as well. Okay, this is the last complicated example. Now in this case, we are again going to apply the same logic to find the maximum path sum, but we are going to do some interesting things. So first of all, we have this root value to be -3, right? Now we are going to see that what is the leftmost contribution it can get. It can get 3 as the contribution in this case. Now again, for this portion, we are going to see that what is the rightmost contribution it can get. The rightmost contribution it can get in this case is going to be this 8 plus 2. So 8 plus 2 is going to be 10 so far, right? Now if we see over here, actually this is not the most optimal way to approach this. Why? Because this path actually gives us the maximum path sum. So let's see that how can we actually determine that. Well, when we are traversing, we are actually going to have a variable called path to keep track of what is the current maximum value we have found so far, and whether do we need to include a new route. And new route in this case is going to be the condition where we actually refrain away or move away from the original route we were using, because if we were to use this route node, there is no way for us to use all of these three nodes. So that's why what we are going to do is, we are first of all going to see that if we use this current route, what is the maximum value we are gaining. So the maximum value we are gaining in this case is going to be 3, which is this one, plus 10, which is the contribution we can get from this right subtree. So 3 plus 10, and let me get rid of this maximum path sum for now. So 3 plus 10 plus whatever the root value. So root value in this case is -3, which is in this case the total value is going to be 10. But now when we are traversing, or when we were calculating the maximum contribution we can gain from this right subtree where the root node is actually 8, the value maximum we can gain from over here is actually going to be this value 8 plus it has the its left subtree is contributing value 1 and its right subtree is contributing value 2, so which both are positive values, and their total is actually 11. So this is 11 and this is 10. Then why are we so keen to keeping this root to be part of the optimal solution? We should not put it in the maximum path sum, and this is exactly what we are going to do. Then we are going to choose a new path, and this new path, the value is 11. So then we are going to have a maximum path sum variable where we are going to keep on updating the value, and we are going to update the value to be 11, and now it does not have any further no more nodes to check for, and then we are going to return this 11 to be the answer. And at any given moment, whenever we find that the new path we are getting that gives us better answer than whatever the previous answer we were getting, then we would update the new path and we will update the value of the path variable. So that is one tricky part that we have to understand in this question. And now let's see that after understanding all the concepts, now let's see that what would be the way to solve this problem. The idea is, let me clean this up a bit. Now I'm going to use the same example to quickly walk through this problem. So first of all, we are at this root position. What is the left contribution we can get, which is 2. The right contribution we can get, in this case it's going to be 10. We actually calculated all of them. Now the sum of these these three is actually going to be 10 only, but when we were calculating that, we had this path variable where we actually calculated the value of this to be 11, and we updated this path variable. And then we are going to have this maximum path value where we are going to keep track of the maximum path we have found so far, and in the end, because it does not have any more children, we are going to return the maximum path to be 11, and this is what the answer we need to return. So basically we are taking a bigger problem, and then we are dividing it into bunch of different parts. That for this root we are actually trying to calculate this left subtree and right subtree. Then again for this root value, we are again calculating this left subtree and right subtree, which means we are solving this problem recursively, and that is how we are going to approach it. And also let me show you the time and space complexity. So time complexity in this case is actually going to be big O of n. Why big O of n? Because at any given moment we will have to iterate over all the nodes that are present inside this given tree, and the space complexity is going to be big O of h, where h is the height of the tree. So first of all, we will need a separate method called max gain to calculate that what is the maximum value we are gaining. So for that, we are going to create a new method that takes in a node as an argument. We will also need a maximum sum value. So we are going to initialize it as global variable. We are going to assign it to the most negative value possible. So okay, now let's start implementing our max gain function. So first of all, we are going to have the terminating case that if the given node is equal to null, we will return 0. If that is not the case, we will need the values of left gain and right gain for any given tree node. So we are again going to call the recursive function for that. We are going to create a variable called price new path that we are actually going to calculate by using the node value plus whatever the sum of left gain and right gain is. Now that is done, we are actually going to calculate the max sum. We are going to compare it with whatever this new path we are calculating. And once that is done, basically all we will have to do is simply return the node value with whatever the maximum value is amongst this left gain or right gain. From this max path sum method, we will have to call this max gain function. So let's do that. After all the calculation, we are simply going to return whatever the max sum we are able to achieve. Okay, and now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our solution is actually pretty efficient and faster than a lot of other solutions. And I would be posting this in the comments so you can check it out from there. So today we are going to do serialize and deserialize binary tree LeetCode problem. And if we see some of the companies where I want to get a job who already asked this question, there are companies like Amazon, Microsoft, LinkedIn, Uber, Google, Facebook, DoorDash, TikTok, Apple, Snapchat, Splunk, and Goldman Sachs. So that's why I'm paying my utmost attention. I hope you also enjoy the video. Hello friends, the reason I have not been uploading in recent days is because I just had twin baby girls, and so yeah, that's the update. And now let's move on to the video. So LeetCode thinks that this is actually a hard problem, but in my opinion, this is not a hard problem. It's actually very creative problem. Basically, we need to serialize and deserialize the given binary tree. Now, first we'll have to understand that what does serialize and deserialize means. Well, serialization is the process of converting the given data structure, which is tree in this case, and we need to convert that into a sequence of bits so that it can be stored in some memory or file buffer, and then we can transmit it across any network. Now in this problem, basically we need to design an algorithm where we are actually serializing and deserializing a binary tree. So serializing means that first of all we are finding a way to convert the given binary tree in some sort of bits, and in this case we are told that we need to convert it in strings, so we are familiar with that. And then deserialize means that we are given this string and we need to write an algorithm to convert this string back to a binary tree. So we'll have to do both the things. And if you see this problem, this is actually very similar problem that we did earlier with strings. This is the solution of that problem, so go and check it out first. We are also given a clarification that we can be as creative as we can with the serialization and deserialization process. So we can have different way of serializing the tree and different way of deserializing the tree, as long as we maintain the tree data structure. So let's see that what is the approach I am suggesting, and you can also come up with your own creative approach. Well, basically in this problem, we are only given the root of a tree, and then somehow we will have to go over the entire tree and then traverse it, convert this given root and all of the entire tree into a string. And after we have converted it to string, we will have to find a way that suppose if we are given the string as the input, how can we convert from the string this binary tree as well? So we are doing both the processes. So the important thing in this case is that we will have to traverse over the given binary tree. There are mainly two strategies to traverse over the given binary tree, DFS and BFS, and I have explained this very carefully in the previous video. You can check it out over here. So basically in this video, what I'm suggesting is that we actually go with pre-order approach with using DFS to serialize and deserialize this given binary tree, and I will be showing you that what is the process we are following. So first of all, we are going to serialize this given tree, which means we are going to take this binary tree and we are going to convert it to a string. Now, as mentioned earlier, we are going to use the pre-order traversal for that. So if you are not familiar with the pre-order traversal, basically we visit the root node first, then we visit the left child of this root node, and then we visit the right child of this root node. And that is how we are going to end up creating the string from this given binary tree. So let's see that in action. So first of all, let's create a variable called s or string where we are going to store the string value. So first of all, we are going to visit the root node. The root node in this case is 1. So we are going to add an entry called 1 over here. Now we need to visit the left child of this root, and then we need to visit the right child of this root. Now remember, this is actually a DFS policy. So in the DFS, we go in the depth first. So first of all, we are going to visit the left child. So left child in this case is 2. So we are going to add an entry that 2 is the left child over here. And then again for this 2, because we still have left child left, so we are going to visit that. So for this 2, the left child in this case is actually 4. Now for this 4, we don't have any more left child and we don't have any more right child, which means that first we try to visit the left child. For this 4, there is no left child, so we enter a value called null over here. And then for this 4, again there is no right child, so again we add value null over here, saying that for this 4, the two left child and right child is actually a null value. Now after that, we still have nodes left that we haven't visited. So now for this node 2, we have this node 5 and it's right. So again we are going to enter the value 5 over here. After entering the value 5, we are again going to check the left child and right child for this 5. So left child in this case is null, and again right child is also null. So we will add 2 more entries, null, null again. And now we go back. So now we have visited all of these nodes, but the thing is we haven't visited the right portion of this original root node. So again we will have to iterate over the right subtree. So right subtree in this case is going to be 3. So we add 3 over here. Now for this 3, again we don't have any more children nodes, so again we add 2 null values. So this is the answer in this case that we have to return for this given tree, that this is the string value that represents this given binary tree. Now let's see that what would be the deserialization process. So now we are going to work upon the deserialization. So basically we are going to convert string into binary tree. So the idea is this is the string we generated from the serialization process. Now again because we are using pre-order traversal, we are actually going to apply the same logic. So we are going to treat the first node to be the root node, then the next node would be the left subchild of this root node, and the next node is going to be the right subchild of this root node, and we are going to keep on iterating this process in reverse order. So the idea is that first of all, okay, we identified this node. So this node is actually our root node. Okay, so root node is actually 1 in this case. Now again this 2 is actually the left child of this root node. So because this left child exists, the next node is again going to be the left child of this node 2. So again we are going to create a node 4 that is left child of this node. Now for this 4, the next 2 nodes are actually null. So because we encounter 2 null values, which means this 4 does not have any more children, so we can just ignore that. Okay, now we still have a node 5, which means that this 5 is actually the right child of this 2, because we have already visited the left subtree of this 2. So now because we are done with the left subtree, now we are visiting the right subtree. So we are going to create one more entry 5 over here as the right subtree. Again we have 2 more null values, which means that this right subtree is done. Now we don't have any more values. Okay, now we still have values, which means that this actually refers to a root node where we haven't visited the left and right subtree. Because remember that this is the left subtree we have visited for this 2, and this is the right subtree we have visited for this 2, but we haven't visited the right subtree for this original one. So now we are going to do that. So now we are going to add one more entry 3 over here, which is the right subtree of this original given one, and this 3 actually has null values, which means 3 does not have any more children. So we won't be adding any more entries over here, and we can just ignore that. Now we have reached the end of the string. So because we have reached the end of the string, we have created the binary tree that we are supposed to create, and we have completed the deserialization process, and we have converted the string into the binary tree. So this is the approach we are going to take. If we see the time and space complexity in this case, for the serialization process, the time complexity is actually going to be big O of n, because we have to iterate over n characters that are present, and the space complexity is also going to be big O of n, because we will have to create a string where we are storing all the n values. Now for the deserialization process, again the time and space complexity remains the same. Now we will have to create two methods for serialize and deserialization. So first of all, we are going to work upon serialize process. So I'm actually going to create a new public method that returns a string where recursively we can apply the pre-order traversal, and as an input it is going to take the root value, and we are also going to pass the string value. Now inside this recursive function, first of all we are going to find the terminating case. So if the given root is equal to null, then simply add the value to the string as null, If that is not the case, which means that root still has some value and it could have left subtree and right subtree. So now we are going to call the recursive function. So first of all, we are going to add the value to our string. Now we are going to call the left subtree and right subtree. So we are again going to call this recursive serialize method. Again, we are going to repeat the same process for the right subtree. Once this ends, we are simply going to return the string. Now from our main serialize method, all we have to do is just call this recursive serialize method and return whatever the answer we get. We are going to pass in root as an entry and we are going to pass in an empty string. So now we are done with our serialize method. Now let's work upon deserializing method. Now again, for the deserializing process, first of all, we will have to create a recursive method to iterate over this given string data, and then we are going to convert all the string values into binary tree. So we are passing a list of strings in this case for this recursive deserialize method. And now first of all, we are going to work upon the terminating case. If the given node is null, we can simply remove the value and then we can return null. Okay, if that is not the case, first of all, we are going to note the whatever the value of this current string is, we are going to treat it as a root node, and then we are going to call the left subtree and right subtree. So we are going to create a new tree node called root. So whatever the current value of this string is, we are going to treat it as a root node. Then after adding the root node, we are actually going to remove that value. Okay, now for the left value, we are again going to call this recursive deserialize method, and that should be it. After this ends, basically we should have a root variable, so we can simply return root. Now from this main method, first of all, we will have to create an array of string where we are actually splitting the string based on the comma that we initially created. After doing this, we are actually going to convert the string array into a list of strings. Now we will simply return whatever the answer we get by calling this recursive method. That should be it. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. So I will be trying to see other faster approaches and see I can make a future video on that. But so far you can find this code in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today actually we are going to learn about a new data structure, and we are actually going to learn to implement a trie or a prefix tree. And if we see some of the companies where I want to get a job, who already asked this question, there are companies like Amazon, Google, Twitter, Microsoft, Oracle, Apple, Facebook, Goldman Sachs, Uber and Bloomberg. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are going to implement a trie over here or a prefix tree. So first of all, in the problem statement, we are given the definition that what a trie is, and actually I'm going to show you very eloquently that what a trie is and how it works. But let's understand the definition first. Basically, a trie is a prefix tree, which is a tree data structure that is used to efficiently store and retrieve keys in a data set of strings. There are a bunch of different applications of this trie data structure, and I'm going to go over all the applications soon as well. Now, if we see that what is needed in this problem, basically we need to initialize a trie object first of all. Then we need to create three different methods which are mentioned over here. So first method is the insert method, which does not return anything, and basically we are only given the input as a string word, and we need to insert this word inside this new trie object that we are initializing. After doing that, we could be given a search method where again as an input we are given a string called word, and we need to return true or false, which means that whether if this word exists inside this trie object that we have created, we need to return true, otherwise we need to return false. And there is also one more method where again we are returning true or false, and the name of method is starts with, where we are actually given a string and the name of the string is prefix. But basically we need to check that whether this prefix actually exists as a part of any existing word inside this trie object, and if that is the case, we need to return true. If that is not the case, we need to return false. So here is an example that we are given. So suppose we are given as an input where actually first of all we are creating the try, we are inserting some word, we are searching for some words, we are doing the start with operation, and this is the explanation. So basically we initialize the try object as mentioned. Then first of all we insert the word apple. So okay, so currently apple exists over here. Now again we search for that whether apple exists or not, and because it exists we return true as the answer. Again we search for with the word app. But the thing is, remember, so far we have only inserted the word apple. App does not exist as a whole word, so that's why we return false. Again we search for starts with method for this word app, and remember, because this app is actually a prefix of this apple, so we return true in this case, and so on and so forth. We can do bunch of different operations. So this is what is needed. Now let's understand what a try is. Okay, so first of all, let's try to understand that what a trie actually is. Basically, a trie is a tree-like data structure, but it's a little bit different and a different variant of a tree. Now, if we know for any single tree, the basic properties are that every single tree has a root node. Now, this root node has some subsequent children nodes. There could be n number of different children, and those children can have some children of their own, and their links actually found some meaningful relationship. So that is what we are going to use to generate this trie, but we are actually going to generate this trie to store different string values per character. That is the important property, per character. So it makes us easier to understand or find different words or different strings, and there are n number of applications of a trie. Let's try to understand trie with some example. So first of all, as any different tree, we are actually going to have a root node, right? Now suppose for this root node, what we are trying to do is we are trying to add some different string value. So let's take a string value. Suppose the first string we are trying to add is actually the word FAANG. So if we take this word FAANG, first of all we will have to add the word F, because remember I already told you we are going to do it character by character. Then we will add A, N and G. We are going to add it in this sequence. So in order to do that, logically speaking, for this root is going to remain common. But the thing is, first word we will have to add is fan. But the thing is, first we will check that whether is there any children of this root node which is actually F. If that is the case, we are actually going to leverage that. But this does not have any children. So if this does not have any children, we are actually going to create a new children F. Now again, with this F, there is no children, that is A. So again we are going to create a new children, then again we are going to create a new children, and then we are going to add the values of N and G as well. After adding this, we have actually created a root inside this trie data structure which represents this word FAANG that we were originally trying to create. After creating that, we will have to find some way to identify that this FAANG word has actually ended. So what we are going to do is we are actually going to create a special character or a special node over here which we are going to denote as an end node, which defines that the word has actually ended over here, right? After doing that, let's try to add one more word. So suppose rather than FAANG, we are trying to add the character MAANG. So let's try to again add MAANG over here. Now for this MAANG, first of all we are going to check that whether this M exists as one of the children of this root node. So M is also no children, so first of all we are going to add M, and then we are going to add subsequent characters, and we are going to link them with this path. After that, in the end, we are actually going to add a special character and denote that the word has actually ended over here. So let's do a quick recap. Basically what we have done so far is we have actually created two separate branches where if we go depth first search diving in those branches, we would actually find those subsequent words in those particular branches. So it makes pretty efficient for us to identify any string and to see that whether it exists or not and predict that what the person is going to copy. Now suppose I'm trying to add the next word fan. Now for the adding this next word fan, what we are going to do is first of all we are going to check F exists or not. So F exists over here. So because F exists, we are actually going to leverage that. So now we are not going to add any entry over here. Again, this A also exists as one of the children of F. So again, we are not going to add any entry over here. Now this N. So N is not a children of this original A. So we are actually going to create an entry over here. So we will create an entry over here and we are actually going to name it as N. And now since this word ends over here, we are actually going to create this end node over here. So again, remember, if we go depth first search in this direction, we will actually be able to find this word fan, and that is the whole purpose of a trie. Now let's try to add one more word which is man. Sorry, MAA, ma. So if we try to add this word ma, So first M also exists over here, A also exists, and A also exists. So because these three exist, we are actually not going to break this link and create this end word over here, or we are not going to do that. Actually, we are going to keep this as it is, because this MAA is actually a prefix of this original word MAANG that we have already added to our trie, and that is why a trie is also called a prefix tree. So now the word makes sense, that why a trie is called a prefix tree. And basically this is what we are trying to implement. There are a bunch of different applications of a trie, and let's see some of the applications that are really cool in real life world. So before we start implementing the method, first of all, let's understand that what are different applications of a trie. So applications like autocomplete, where you type something and it automatically gets completed or understood by that particular product, that is implemented using trie. So features like Google Chrome, Amazon, where you type few words and then it automatically understands that what you are trying to do and automatically gives you the answer, that is implemented using that. All the spell checks or all the dictionary related mechanisms, they are also implemented using some versioning of a trie. Games like word search, word puzzle, wordle, they are also implemented using a versioning of a trie. And features like predictive text search or expected text search, that you type something, it automatically expects that what could be the next potential words. You see that in YouTube, Google all the time. They are also implemented using tries. So these are only few but very powerful applications of a trie, and there are hundreds of them. I haven't mentioned them. So that's why trie is important to understand. Now let's move back to our question and start implementing those three methods. So first method they are asking us to implement is an insert method, where we are not returning anything, but we are inserting different strings into our trie. So for this example, we are actually going to implement these 4 different types of strings into our trie, and we will see that what would be the logic behind it. Now, as mentioned earlier, that every trie actually has a root node. So again, with our trie, we are also going to have a root node. Now from this root node, the idea we are going to use is that whatever string we are trying to insert, first of all, we will check that whether the first word that we are trying to implement, or the first character we are trying to implement, if that is present as one of the children of the existing root node or not. If it is children of that particular root node, we would keep on branching for that particular child and keep on updating the number of characters that we are trying to implement. If it does not exist, we will actually create a new node or a new branch, and we will add that entire word into that branch. Now, as mentioned earlier, the moment we reach to the end of that particular node, we will actually have to create an end node to denote that this word actually ends over here. So let's start implementing what is being asked over here. So first we are trying to implement the word apple. So A does not exist as any of the children of this root node. Currently it has no children, so we will have to create a new node. So first we are going to create a new node for apple. Okay, so let me create a new node A, and then I will keep on appending all the remaining characters. And after adding all the word, because this word ends at this E, I am actually going to create a special node, and I'm going to denote it as an end node. So that is for us to understand that this word actually ends over here and we don't need to move any further. Okay, now next word we are trying to implement is G. And also remember one thing, I forgot to tell you that this root can have potential 26 different children, right? And this 26 different children can have 26 different children of their own. So the mechanism we are going to implement to find that whether a node contains any particular children or not is actually going to be used based on some key value mechanism. And because it's a key value mechanism, the whole operation of searching that whether any node or anything, if that is part of any children of that particular node or not, that is being done in constant time, so that it helps us understand, helps us to maintain the consistency and speed of our data structure. Now let's move back to adding the word Google to our trie. So for the word Google, we do not have any children that is starts with G. So we are also going to create a new node over here, or new branch over here, where first character is G, and then we will add all the remaining characters. As previously mentioned, at the end of the word we are going to create an end node. Okay, now things become a little bit interesting with this word Amazon. So for this word Amazon, when we start checking that whether this A is a children of this root node or not, we find that A is already a children. So we will keep on updating the value over here, that okay, we have already find a word or a character that is already a children, and then we will keep on moving to the next character. So first this A is already present, so we ignore that. Now next character we want to find is M. So for this M, we will try to see that whether this A contains any children that starts with M. But the thing is, currently this A only contains one children that starts with P and not M. So we will have to create a new branch over here. So let's create a new branch. So new branch starts with M, and then we will add all the remaining word characters over here. Okay, and now the next word we are trying to implement is amazing. For the amazing, okay, we already have a children of this root that starts with A, so we have taken care of this. M is also present as one of the children. Okay, now A is also present as one of the children of this M. Okay, so that is also good. Now this Z is also present over here. Now for this I is actually not present as one of the children of this Z. So we will actually create a new branch over here that starts with I, and then we will add this N and G over here, and in the end we will create, or we will add the end node over here. And now we have actually inserted these four characters as these four strings into our trie, and if you see, we can find each one of them by going in DFS motion in any particular branch. So first of all, this gives us the value Google, this gives us Apple, this gives us Amazon, and this gives us amazing. So that is how tries typically work. Now let's move on to the next method that is being asked. So for this search method for our try, we will be actually given a word as the input, and we will have to check that if that word exists inside our given try, we will have to return true. If it does not exist, we will have to return false. So let's start implementing the same method, and actually we are going to use the same try that we have created. Okay, so let's use the same try that we have created earlier, and we will try to see that whether these four strings do they exist inside this given try or not. So let's understand the logic behind it. Well, if the string exists, basically all we will have to do is, first of all, we will check that, okay, whether the first character, if that is the one of the children of this root node or not. If that is the children, we would keep on checking its children for this next subsequent words and try to complete this entire word. If we are able to complete this entire word without this try breaking or not able to find the children, if we reach to the end, we can conclude that this word exists. If we cannot come to the end, we will conclude that this node does not exist. So first of all, let's try to see in this example. So for the first word is A. So A exists over here as one of the children. So we will ignore this one. Now next word is M. M also exists, so we will again ignore this one. The next one is A, again this word exists. Now Z, I, N, G, they all exist in this particular fashion. So this word amazing exists inside this given try. So because it exists, we will return true as the answer in this case, right? Now let's try to search for this word good. Now for this word good, the first character is G. So first character is G present over here. So okay, we are good up until this point. Next character is O. O is also present. Again, O is also present. So we can ignore first three characters of this good. Now for this next O, we do not have a children that starts with value D. So because of that, we do not have any new branch over here that starts with D. So we can actually conclude that the word good does not exist in this case, and because it does not exist, we will return false over here. Okay, now let's try to search for the word Googler. So again, for this word Googler, okay, G also exists, O exists, G exists, L exists, and E exists. Okay, up until this point, all the words exist. But when we try to search for the next word, we actually encounter that, okay, this is the end node of our try or of our DFS search for this particular direction. So because it is the end word, we will actually return false over here, because this word has not been completely searched, because it does not exist inside our try, and we are actually able to do it pretty quickly and pretty efficiently. Okay, so now next word is app. So let's try to see that whether this word app exists inside our try or not. So first of all, we check for this word A. A exists over here. Then this word P. P also exists and P also exists, right? So we are up good up until this point, and our mind will say that, okay, because this word exists, we need to return true. But the thing is, that is not the case. The idea we are trying to do in this search method is that we are trying to see that whether the whole word that is given as the input exists as only a word inside this given try. But for this app, if we try to see the next node is actually the SL and E. So there are still some characters that exist inside this given DFS path that we are traversing, and the next node is actually not the end node. So because the next node is not the end node and there are still some more nodes that exist, this app is actually a prefix of original word apple, but not the whole word as it is. So that's why in this case we need to return false as well. And this is the important thing that is differentiating between this method, search method, and the next method we are going to implement. Now if we see the time and space complexity, in this case the time complexity for this method is actually going to be big O of n, where n is the number of characters that are present that we are trying to search in any given word. If we see space complexity, for the space complexity we are actually not using any additional space, so that is going to be the constant space complexity for this case, which is pretty efficient in my opinion. So now let's understand our starts with method, and we are also going to use the same try that we have created before, right? And we are going to see that whether the words that starts with these characters, are they present inside our given try or not. So again, this is very similar to the search method, where we are going to iterate over word by word or character by character for any given word, and we will see that whether that is present inside our try or not. If that is present, we can return true. If that is not present, we will return false. So let's see that in action. So first of all, we have this character A. So A is already one of the children of this root node. So okay, we are good up until this point. Then we have M. M is also a children over here, and then we have A. So A is also a children of this one. So we can conclude that because this word ended, we do not have any more things to search for, and all of the characters, they were present inside this given try. We would actually return true. In this case, they are saying that the word that starts with AMA is actually present as one of the children or one of the branches of this try. Now let's try to search for this word APK. So A exists and P exists, but the thing is, for this P we do not have any children that starts with K. So because of that, this K is not present. We can actually return false in this case, saying that we do not have a word that starts with APK as the prefix inside our try. And remember, because we are searching through prefix, that is why this is also called prefix tree. So yeah, mind blown, right? Mine as well. Now let's try to search the word good. Well, there is Google, but there is not good. But the thing is, Google is pretty good. Yeah, so that's why it's one of my dream companies. But let's try to search that. So okay, this is GOO. So GOO is present over here, but this D is not present as one of the children of this O. So because of that, we will also return false in this case. Okay, now we have this word apple. So apple is actually the entire word that is present over here. And if you look at it, we do have a word that starts with the word apple, even though it ends at apple. But the thing is, also it starts with apple, right? So, and the name of the method is actually starts with. So why should not we return true in this case? So this will also become true, that okay, word that starts with apple is present inside our given try. And that is the logic we are going to use to implement the starts with method. Again, very similar to the search method, just a little bit different variations. Now if we try to see the time and space complexity, in this case the time complexity is also going to be big O of n. That is where n is the number of characters that are presented inside any word that we are trying to search. If we see space complexity, the space complexity is also going to be big O of 1, or constant space complexity, because we are not storing anything in our text stack. This problem is asking us to implement insert, search, and starts with method. But before implementing these three methods, first of all, we'll have to define that what a try node is. This is only a try class. So I would be creating a separate class called try node. Now in this try node class, first of all, let's go over some basic methods that we are going to use that will enable us to do a lot of things. First of all, we have defined a finite number of cases R, which is 26, because any single node can only have up to 26 distinct children, because each children represents a character inside the alphabet. Now every single try node has a certain set of links, and links are defined by the children of that particular node. We also created some more methods, so let's go over them. So one method is contains key method, where we pass in a character and we get the answer that whether any particular link or any particular node does that contain that particular character as one of its children or not. And we can get the answer in a constant time complexity, because remember, we are using array indexing, and the maximum possibility of indexing can be 26, and we can get the answer immediately. Same, we have a method get, where we provide the character and we get the answer that whatever the value of that particular character is inside any of the children of any try node. We also have a method put, where we provide the value of a character and the node we are trying to put it as, And we also have set end and is end method. That is to define that whenever we run out of words that we need to put in any single try block or any single try branch, the last node is going to be is end node, and we will mark its value to be true. So now let's start implementing the try node. So first of all, we will have to create a try node root. So let's do that. Now since we have our root node, first of all, for this public try method, we are going to initialize the root. After doing that, first of all, let's start working on our insert method. So for our insert method, we are going to have a root node. Now we are going to iterate over the given input word. We will define that what is the current character we are at. Now first of all, we will have to check that whether the given node we have, if that contains that particular key or not. So if the given node does not contain that key, we will actually have to create a new entry over here. So we will use our node.put method, and inside that we are going to pass in the value of the current character, and we are going to pass in the we are going to create a new try node for that, and then we are going to update the node's value. And once this loop ends, basically the last node we are at, we will have to set its value to be the end node. So we are going to mark its value to be the set end value, and which would basically, so it defines that this is the last node. Before we work on the search and starts with method, remember both search and starts with method, they are pretty similar to each other. So we are actually going to create a supporting method called search prefix. Once again, we are going to initialize the node to be the root node, and now we are going to iterate over the given word. So now we are going to check that if the current node, does it contains the given character or not. If it contains the given character, we can actually set the value of node. If it is not present, we simply need to return null, and that's it. And if we somehow reach to the end of this loop, we can simply return whatever the node we are at. Now from this our search method, basically what we are going to do is, first of all, we are going to initialize our try node, and we are going to pass in the value of the word. Now we simply have to return that whether the current node we get in the return, and if it is not null and it is end, we can simply return true. And same thing we are going to do for our starts with method. So again, for our starts with method, we are again going to call the search prefix method, and basically all we will have to check that whatever the return value we get, if that is not equal to null, if that is not equal to null, we can simply return true, and that should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code, and our code runs pretty efficiently compared to a lot of other solutions. And it is also very much efficient in terms of space complexity. The thing is, I was not able to come up with this solution on my own. I actually had to use a lot from the solution tab, so I just want to make it clear. So yeah, everyone has to go through it, and I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do design, add and search words data structure lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Google, Microsoft, Apple, Facebook, ByteDance, Twitter, Uber and Lyft. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and as the name suggests that we are actually designing a data structure where for this data structure we have to support that we can add new words to this data structure, and if given any string we can actually find the previously added words or strings as well. So we are being asked to implement the word dictionary class. Now in the word dictionary class, first of all, we'll need to initialize the word dictionary object, and then we need to create two different methods. First method is add word method that takes in a string word as an input. Which being done, it adds the word to our data structure that we can use to match it later. And then there is a boolean method called search, where again we provide a string word as an input, and that returns true or false if that word has been previously added or not. We are also given one more condition, that for the search method there could be dots provided as inputs, where we can conclude dot to be any letter. So if we are given the word something like bad, that is already being added, and then we are asked to search for the word using b dot d, actually these two words we can consider same, because this dot we can consider it to be a. So let's try to understand this with an example. Over here we are given a bunch of different add word, and search word mechanisms, and this is the explanation provided. So basically, first of all, we initialize the object word dictionary. Now for that, first we add the word bad, dad, mad. We add all these three words. Now first of all, we search using pad. So pad is not present, so we return false. Then bad is present because we have previously added it. Then we are also given a word which is dot ad. So this dot can actually mean anything, and if we see, we already have a word like bad and dad, that both, and even mad, that all three of them, they actually match with this string, so we can return true in this case as well. And we are also given one more search criteria where we are only given b dot dot, which means for these two dots we can conclude any other word, and since we already have a word bad added, we can conclude these two to be similar, and we need to return true in this case. So before we start the solution, first let's understand that what a trie is. If you want to check the full explanation, you can check out my previous video over here. Now let's move back over here. So basically a trie is actually a form of a tree, whereas any given tree, it has a root node. Now this root node can have many subsequent children, and each children can have some children of their own, and based on that we actually use trie to search, store, and iterate over different strings. And for any given strings we actually use it character by character to store distinct values inside this given trie, and based on per character we actually store it in a manner where it becomes pretty fast for us to find that whether any particular parent node contains some character as one of its children or not, and then we iterate in some particular fashion, in DFS fashion, to find any words. So suppose these four are the strings we are trying to add. So let's initialize our trie data structure. So first of all, we are actually going to have a root variable. Now for this root variable, we are going to store all of these values one by one. So first let's store the value hello. As mentioned that for any given string, we are actually going to go character by character. So first of all, we are going to take the character h, and we are going to see that does this root node has a child that is actually starts with h. It does not. So we are actually going to create a new node over here, and this node starts with h. Now we are going to add all the values of subsequent characters because they don't exist. So I'm going to add append e, l, l, o, and after adding all of these values, actually we are going to have an end variable that denotes that this word has actually ended over here. So far if we iterate in this direction in this given trie, we can actually form the word hello, and when we reach to this o, we will actually encounter a special node that denotes that this is actually the end node, and if that whenever we identify that, we can conclude the word has actually ended. Now let's add this word hi. So if we want to add word hi, basically first of all we will check that whether this h exists or not. So h already exists as one of the children of this root, so we do not need to create a separate branch for this one. But the thing is, for this particular h, I does not exist as one of its children, so we are actually going to create a new branch over here, I, and we are going to denote that this represents this word h, and then because this word ends over here, we are actually going to denote an end node over here. Let's add one more word, that is pop. So if we want to add pop, again p does not exist, so we are going to add, or we are going to create a new branch, and we are going to add all of these values, and we are going to add the end node. Now this next word is pond. So again we are going to use the same methodology. So p and o exist as the children, so first two characters we are done with. Now from here we will have to create a new branch, so we will do that, and after that we will add our end branch, and this is the logic we are going to use to implement our insert or add method to add different strings inside our word implement data structure. And this is the logic we are going to use, that first of all we are going to check that any character exists as the children of the root or not. If it exists, we are going to leverage that particular branch. If it does not exist, we are going to create a new branch, and then we will keep on making separations, and based on that things becomes pretty easy for us to find different words. Okay, so for our search method, suppose this is the trie that we have actually created, and these are the words we have added. Let me quickly go over them. So first word is pen, If you look at this direction, we have the word pen, then we have the pot. So P is common, so then there is a branch out and we get the word pot as well. Same, we have cat, cars and bed in the similar sequence, and these are the words we are trying to search. So couple of words are just regular words. Then I have added some examples with the dots in it, so because they are more complicated ones, so we can understand that. So let's quickly start to go over and see that what would be our search policy for this given try that we have created. So for this character pot, first letter is P. So from this root we are going to see that does there a children that contains the character P, and yes, we have a child that contains the character P. So based on that, we will keep on iterating in that direction. So next character is O, so we have O as well, and the next character is T, so we have T as well. Now we don't care about this end node, because as long as we are able to generate the word that we were given, we are good up until this point. So over here we will actually return true to be the answer, that yes, this word is present inside the try that we have created. Second word is pots. So again, for the pots, we up until this pot we are going to go in the same direction, but this S is not present as one of the children of this pot, and because we encounter an end node over here, so we can drop out immediately and we can return false in this case, that yeah, we don't have any character that matches the word pots. Now this is a little bit interesting example. So for this .ar, the policy we are going to use is that whenever we encounter a dot to be a character, we will actually have to iterate over every single possible route using this dot to be the character and see that can we make this AR to be part of that sequence or not. So let's quickly do that, and let me clean this up a bit. For this .ar, the strategy we are going to use is, for this particular dot, we are going to consider it that every single child of this root can be used over here, and then we will try to see that whether is there any place where second character is actually A. So first we go down this path. Okay, so P, we consider P as dot, right? Then we check that, okay, this is E and this is not A, so we cannot go on this path. Okay, now we backtrack. Now we keep this P to be dot. Now again we try to repeat the same process. This is A and this is O. So again, this is not the path we are going to choose. That is going to lead us to this answer. We come back. Now, okay, we are at this position. Again, we check this child. So this child is actually C. We consider C to be the dot. Okay. Now from the C, the next character is actually A, and all over here the next character is also A. So that is good sign for us. So now we can continue in that direction. So now from this A, we will try to see that is there a child that is actually R, and yes, from this A we also have a child that is R. And since we reach to the end of this word, we can return true in this case, that yes, this .ar is present inside this try that we created. Okay, so yeah, that's a wonderful news. Now let's focus on the next example. So next example is .t. So for the .t, actually we will have to branch out even more. So for this second .t, what we are going to do is, again we are going to repeat the same strategy. We will have to go over every single child that is possible. So first we will consider this P to be the first dot. So this dot is this P. Okay, now from this P we will also consider two child to be separate dots. So for both the childs, okay, this is going to be the first dot. So we are good up until this point, but this value is actually not T, this is N. So we will have to backtrack. From this E, we do not have any child, so we will again backtrack and we will come back to this P to be one dot. Now from this P, we still have one more root that we haven't considered. So we will consider this O to be the second dot. And from this O, we actually have the last character T present. And that matches this string .t. So if we go down this path, we will be able to generate this word, and that's why we will also return true in this case as well. And the same thing we are going to repeat for this .ey strategy. So for this .ey, what we are going to do is, first of all, we are going to consider this to be the dot. We will see, okay, this is E, so that is good, but this is not Y, so again we cannot go down this path. Again, this is dot, this is not the path, this is not the path, this is not the path. So this .ey is actually not present inside this entire try block that we have created. So over here we will return false, but before returning false, we will actually check every single possible route to see that whether we can find a match or not. Okay, so that is how we are actually going to implement the search mechanism. Basically, the only tricky part is to take care of the dot values. Apart from that, it's pretty simple. Now let's talk about time and space complexity. So for the add function, the time complexity is actually going to be big O of n, that depending on the number of characters that are presented inside the input. And also for the space complexity, it's also going to be big O of n, depending on the size of the input. For the search mechanism, things become a little bit tricky. Over here, the time complexity is actually going to be big O of 26 times n. Why 26 times n? Because remember, for any given dot, there can be 26 child of any particular root element that we might have to iterate over, and again, in the bottom we might have to keep on repeating the same process, right? So basically, the maximum time and space complexity we might have to go over is going to be n times 26, but since 26 is a finite number, we can also consider this to be big O of n only. Okay, and for the space complexity, it's also going to be the same. It's going to be big O of 26 to the power of n. So for this problem, we are being asked to implement three things: word dictionary, add word, and search method. The thing is, before that, we will actually have to define a trie node. So I'm going to create a separate class for to defining a trie node, where every single trie node has a different set of children, and we can easily quickly look up those children because we are actually using hash map to define them. Okay, now from our main method, first of all, we are going to create a new trie node. So now to implement our word dictionary, first of all, we are actually going to create an instance of this trie. Now for this add word method, first of all, we'll have to create a node. So we are going to create a trie node. We are going to run a for loop across the given word. If the current node, if that does not contain any children with this character, then we will have to create a new entry inside our node. And if the entry exists for this given character, we are actually going to go to the next element, and in the end we are going to define node.word to be true. So before we start our search method, we are actually going to create a helper method called search in node, that is going to take the input word and the trie node as the input, and that is going to help us to iterate over the given trie node. So first of all, we are going to create a for loop to iterate over this given word, and inside this given word we are going to iterate over character by character. So I'm also going to create a new character variable. So first of all, we are going to check that if the given node or does its children contains this word or not. If it does not contain, then we are going to check that whether the given character is dot or not, and if that is the dot, then we might have to iterate over all the subsequent characters of this node. Once we determine that the children does not contain this character ch, we are going to check that whether the ch is actually a dot or not. If that is dot, then we are going to run a for loop across all the children for every single character value, and then we are going to define a new trie node called child, and basically we are going to call this search in node method iteratively for the next character in that particular word, because remember, we are already eliminating the dot character and providing its child as the trie node, and we will keep on repeating this, we will keep on iterating this process, and we are going to return true. If that is not the case, and if this given ch character is not a dot, then in that case we can return false immediately. Somehow this ch is actually a child of this node. If that is the case, then we simply need to iterate over the next value inside this given node, and in the end we simply need to return that whether the node.word is present or not. And remember, we are storing this node.word value inside our this add word method as well. So the moment we identify a matching word, it would return true, otherwise it would return false. Now from this our search method, all we will have to do is we simply need to call the recursive search in node method that we have created, and as the input we are going to provide the value of the word, and we are also going to initialize a new trie node, or we are also going to provide the trie node that we initialized earlier, and that's it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. Okay, seems like our solution worked as expected. It was not the fastest solution in terms of time complexity, but in terms of space complexity, it was pretty efficient. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do word search to lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Uber, Microsoft, Google, Snapchat, Facebook, Apple, Twitter, TikTok, Bloomberg, Spotify, Twitch and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is the LeetCode hard problem, and basically we are given an m cross n matrix of characters. Now, and we are also given a different list of string called words. Now we need to return all the words that are present on the given board. We are also given one more thing, that each word must be constructed from the letters that are adjacent to each other. So, and we are also given the definition that what adjacent cells are. Basically, any cells that are horizontally or vertically neighboring to each other, we can consider them to be a part of the consecutive sequence series, and we can use them to create words. So let's try to understand this with an example over here. Over here we are given a 4 cross 4 matrix, and for this matrix we are told that these are the list of words. We need to check that whether they are present inside this given matrix or not. So if we try to just look at this example, basically we can see that this first word oath is actually present over here, where O, A, T and H, they are creating or forming this word, and if you see, they are all sequentially adjacent cells to each other. So that's why we can use them to form this words and see whether it's present or not. So in the answer, first of all, we are going to add the word oath as one of the answer. Then if we look at the answer, we can also find this word eat to be present. So E, A, T, that is present in this manner. And again, though this is on the left side, this is not the conventional way to write it, but still based on the adjacent cells, we can actually form this word eat, and that's why this eat is also going to be part of the answer. So we will add eat in the answer as well. Now for this two, PEA, P and rain, these two are not present inside this given matrix, so we will not include them in the answer, and this is the answer we will have to return. So basically it is one kind of a word search game or word search puzzle. So that is why the name is word search 2, and this is the little bit of advanced version. So first we will see that what is going to be like a basic, very trivial approach, and then we will try to improvise using a different set of data structures. Okay, so most basic idea we are going to have is that we will start iterating over all of the characters that are present inside this m cross n matrix, and then for every single character we are going to see that whether that matches with any of the starting words or not. If we find a potential match, then we will try to find the subsequent character and the neighbors of that particular character to see if we are able to generate any exact word or not. And the moment we do that, we will actually put it in a new variable called answer, and that is how we will be able to generate our answer. So let's try to see this in action. So first character in this case is X. So X matches with this character over here in the given set of words. So next we will have to see that whether any neighbor of X is actually Y or not. Neighbor of X is actually H and A. We do not find Y over here. So because we do not find Y over here, this X does not lead to anywhere. So we can mark this as visited. That does not lead to any answer. Next character is H. So H matches with this first character, and then we will have to see that whether B exists as one of the neighbors of H, and B also exists as one of the neighbors of H, and then the subsequent character O also exists as one of the neighbors of B. So in this case, this HBO is actually a complete word we are able to make based on subsequent characters that are present adjacent to each other inside this given matrix. And because of that, we are going to create a new variable called the answer, and in the answer we are going to add the value HBO over here. Now we will start iterating over this A. So again, A is the starting point over here, and next character B and C, we are able to generate this pair using sequentially iterating over. And if we see over here, we can also generate this ABC in this fashion. Now this character is Y. So again, Y is not part of starting character of any other word, so we cannot do anything about this. Next character is again C, that we have already visited, so we don't need to visit this. And next character is Z. Z again is not the starting point of any of these characters. So in this case, this is the answer we are going to have, and we can return this one. This solution works as expected. There are no issues with this one. But if you just see, we only have a 3 by 3 matrix, and for every single character in the worst case scenario, we might have to iterate over every single word and check that whether it matches the starting word or not. We can maybe simplify using a hash map, but the thing is, this is still going to lead to a very bad solution. In terms of time complexity, this is going to be disaster, because for every single character we might have to iterate over every single word that there is, and once we find a match, then we will have to iterate over all the neighbors of that particular character as well. So that leads to nowhere. So let's try to see that where we can find a better time complexity, and the solution to achieve a better time complexity is actually using a new data structure called Trie. Now I have already extensively worked on Trie, and you can find all of those solutions over here. Check out this video if you want to learn that what a Trie is and what are its applications. Now let's see that how we are going to use Trie in this case to improve our performance. Okay, so the previous example we see, basically what we are doing is we were iterating over every single character, and then we were trying to see that whether that character matches the first element or not, and sequentially we will have to check every single word that was present. And if we find a potential match, then we will have to check all the neighbors to see if the next consecutive element is present or not. And that was the major reason that why we were having a disastrous time complexity. So in order to improve that, if we can find some way to eliminate this checking procedure, that for every single character we might have to look up all the elements or all the words that are present, because imagine if there are million words present, we might have to check million times, and then that is going to be very disastrous. The idea we are going to use is that whatever the words that we are given, we are actually going to convert these into a Trie, and because we are converting them into a Trie, for any character, searching that whether it is the starting point of any word or not becomes pretty easy for us, and we can actually do it in nearly constant time. Because in the Trie it is very fast and efficient to find that whether any word exists or not, and if it exists, it is very easy for us to iterate over that particular word or not. So first of all, let me quickly create a Trie block based on these three words. The Trie block is going to look like this. So based on the words that we were previously given, we actually created a Trie block. And now using this Trie block, we are going to make things pretty easy for ourselves. Basically, we are going to iterate over in the same fashion for the given matrix, but this time all we will have to see is to look up in this Trie that whether the current character, if that is any children of this given root node or not, and if that is the case, we will keep on iterating. So first we find this character to be E. E is not part of any children, so we can ignore that. Next one is F. F is actually part of a children. So okay, now we have found F to be part of the children. Now we will have to see that what is the next character in this Trie block. So this next character is A. So we will have to see that whether any neighbors of this F is actually A or not. So we will have to check on three sides, and we find a match over here that this is A. Okay, now again next character is A. Again this neighbor is actually A. Okay, now this character is N. So again neighbor of this A is N present over here, and again the next character is G. So G is also present over here, and since we have reached to the end node inside our Trie, because of that we can conclude that the whole word was actually present inside this given matrix, and we can return true in this case, and we will add it to our answer list. So inside the answer list, the first word we are going to add is FAANG, that is present inside this given matrix. So see how easy it is for us to find these things. And okay, now the next character is R. R is not children of any of these root nodes. Next one is T. T is also not a children. L is not a children. These are all visited. Now this G. G is actually a children. So now it becomes easy. Now we will have to start iterating over. Okay, so we are at this position G. Now the next element is O. The next element is O, and O is also a neighbor over here. Okay, so which is good. Now the next element is O. Again, O is a neighbor over here. So which is good. Now this next element is G. G is also a neighbor of this O, right? So we are good up until this point. Now we have to find this L. Now, if we look at this G, we do not find L to be a neighbor of this G. So because of that, we will actually have to roll back, and we cannot move forward with this path. So now we would have visited this G, and that did not lead us to anywhere. So again, we will start with our routine procedure. Okay, now this next character is O. O is not starting point of anything. T is also not starting point of anything. G is we have already used it. Now this is again G. So again, G is the starting point of this one. Next character is O. O is present over here. Next character is O. O is also neighbor of this one. Next character is G. G is neighbor of this one. Next character is L. L is neighbor of this one. And next character is E. E is the first character. And because we reached to the end character over here, we can conclude that Google is also present inside this given matrix, and we will add it to our answer. So we will add one other entry called Google. Okay, and now next, again this character is L, so L does not lead to any children of this root node, and F does not lead to any children of this root node. So in the answer we are going to return this FAANG and Google to be the answer, and this would be the most optimal way to solve this problem. Remember, because we used a try block, things becomes much more faster for us, and we can immediately look up that whether any single character that leads to an answer or not. Okay, now let's do the tricky part. We will have to do the time and space complexity analysis. So for the time complexity analysis, it's actually a little bit tricky. The first thing that is a given fact is that we will have to iterate over every single character that is present inside this given m cross n matrix. So that's a given fact. Suppose that the total number of cells that are present are actually m. So now, okay, we already know that is whatever the time complexity is going to be the factor of m. Now for this particular m, imagine that for any particular character, what is the maximum work we will have to do in the worst case scenario? Well, the maximum work we will have to do in the worst case scenario is that any particular character, suppose this F matches this character that is present. Now, whenever we find a potential match, we will have to look for the next element in all three directions of that particular word. So suppose this O was a potential match, we will have to iterate over all four directions in any given case. So for any single cell, we might have to iterate over in the all four directions, and for all four directions, the number of traversal that we will have to do for each one of them would depend on the next three or the next remaining three characters. Because remember, for this Google, suppose we find a match, this O to be a match. Now the moment we find this O to be a match, again we find this O to be a match. So now because we find this to be a match, we do not have to look for this particular element, we will have to look at the remaining three positions. So then we will have to, for any single character, we will have to look in the four directions, and for all the subsequent elements, we will have to look in the remaining three directions, and that we will have to do depending on the length of that particular word. So for the remaining three elements, we will have to iterate over to the length of that. So that's why 3 to the power of L minus 1. And why minus 1? Because for this first character, we are actually looking in the worst case scenario in all four directions, and for all the subsequent length parameters. So suppose for this particular FAANG, for this F, we might have to look in four directions, and for this A, we only have to look in the remaining three directions because one adjacent cell is already F, so that we do not have to look at. So this is going to be the time complexity. So if I write the final time complexity, it's actually going to be big O of m into 4 times 3 to the power of L minus 1, and that is the final time complexity. This is a very difficult time complexity analysis. So yeah, it gives you an idea that why this problem is pretty popular. If we see space complexity, that is pretty simple. Space complexity depends on the total number of words that are present. So suppose we sum that up to big O of n, where m is the total number of characters that are present in the initial word list. So after doing this time and space complexity analysis, now let's move on to the coding. Before we implement our solution, we are actually going to create our class Trie node. In the class solution, we are going to define a couple of global variables. Now inside the find words method, first of all, we are going to initialize our try block, and we are going to add all the words to our try block. After creating the try node, now we are going to start working on backtracking, starting with each cell in the board. So first of all, let's create the board variable. And now we are going to initialize a couple of loops to iterate over this full board matrix. So now for every single position inside this given matrix, we are going to check that whether that is actually any of the children of this root try node that we have created. And if that is the case, then we will create a helper method called backtracking, where we are going to iterate over all the adjacent cells of that particular row and column position, and also that particular entire DFS traversal for that particular branch inside our try node. After this loop ends, basically we should have populated our answer inside this answer variable that we have created. So we can simply return that. And now let's create our backtracking method. So this is going to be our recursive method. First of all, we are going to define a couple of variables. First of all, we are going to check that whether the current node is actually a word or not. If that is a word, we can immediately add it to our result. Okay, if that is not the case, we will have to start doing our traversal. So how we are going to do our traversal? Remember, whatever the current row and column is, we cannot use the same word again. So we are actually going to mark this as hash in a way for us to identify that that is the node we have already visited. Now for any given row and column, we will have to iterate over all of its neighbors. So we are going to use couple of variables to our advantage. Now with the help of row and column offset, it becomes pretty easy for us to iterate over all the neighbors of any given node. So now we are going to run a for loop and we are going to iterate over all the neighbors of given row and column position. First we check that whether our new row and new column, if they are going out of bounds or not. That is the case, we just simply ignore that. Otherwise, if we are at the correct neighbor, we need to check that whether that neighbor is actually subsequent character that we have already stored in our trie or not. And if that is the case, we are going to call our backtracking method again. Now after our exploration ends, basically we will have to put back this hash to its original position, and that should be it. There is one more optimization we can do, and that is to incrementally remove the leaf nodes, which means that whenever we identify that the current node's children, if that is empty, then basically we can just remove that from our parent. That should be it. Let's try to run this code. We will also have to update the value of the node in the else condition. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently. I will be posting this in the comments so you can check it out from there. Thank you. So the LeetCode problem we are going to solve is called kth largest element in a stream. Now we can see that this one is a LeetCode easy problem and also an extremely well-liked problem on LeetCode. The problem statement is quite straightforward. We need to design a class where we can find kth largest element inside a stream, and we are told that we need to find the kth largest element in terms of sorted order number, not the kth distinct element. This is just to avoid confusion. Now let's see the requirements for kth largest class. Basically we need to implement two methods. First method is kth largest method, where as an input we are given an integer k and we are also given an integer array called nums. Now amongst these integer array nums, we need to return that whatever the kth largest element is. So suppose the given k is equal to 3, we need to return that what is the third largest element inside this array. Second one is an add method, where we are continuously adding value to a continuous stream, and in that continuous stream we are able to represent or return the kth largest element in that continuous stream. So with every new value being added, we can determine that this is the largest element inside the current k array. So for both the case, let's try to understand this with an example. Suppose this is the array we are given as an input, and we are being told that k is equal to 3. We need to find the largest element. Okay, so logically we can see that over here the largest element is 7, second largest element is 6, and third largest element is 5. So in this case we need to return 5 as the answer, that this is the largest element. Now say for the same example, this we took care of the kth largest element method, the first method. Now for the second method, the add method, basically let's say that we are given k is equal to 3. Okay, and this is a continuous stream. So first we add value number 1. Currently we don't have any large value. Then we add value number 2, and then we add value number 5. Now so far, what is the third largest value inside this continuous stream? So the answer is going to be 1. Then we decide to add value number 4. So once again, what is the third largest stream currently? So third largest value would be value number 2. So we will need to return 2. Let's say we add value number 3. So currently what is the third largest stream? So in this case, the third largest element so far amongst these 5 elements is value number 3. So we need to return this. So basically in both the cases, we need to find that for any particular given input, what is the kth largest element. Now for this add method, you would say that, hey, we need to check for every single time. So how can we do that? The idea would be to design a data structure where at every given moment we should be able to quickly identify that, hey, currently by adding this value to this particular data structure, the kth largest value is going to be either 1 or 2 or 3, depending on the number of elements that are currently present inside our existing stream. So let's try to see that how we can actually solve this problem. Okay, so if we see the brute force solution for this problem, brute force solution is actually quite straightforward. Let's say for given input array, we can simply start iterating over every single value in order to find the maximum value we found so far. Then we can repeat the same process to find the second maximum value, and then we can find the third process to find the third maximum value, and that would basically yield us the result of, let's say, if we are given k is equal to 3. This approach is very slow. Basically it yields in big of n square time complexity, so we definitely don't want to do that. So that is one option. Second option in this case is, let's say that for the same given input, if somehow we decide that we can actually sort this given input, then it becomes very easy for us to find any kth largest element. So let's say in this case, the sorted array is going to look like just all the values from 1 to 7. And in this case, the kth largest element, let's say our k is equal to 3, which means we need to pick the bottom third value in the answer, and we can simply return this one. So the sorting solution would work fine, but the thing is, in order to create like from this non-sorted array to sorted array, it's gonna take n log n time. So but this is still a much bigger improvement compared to our brute force approach, and this is actually what we are going to take into account in order to solve the problem. But the thing is, not only we need to create like a data structure where we can store the sorted value and find or calculate the result, but for our add method, because we need to continuously check for any particular existing value that is being added into the stream, that what the kth largest element is. So for every single time doing the sorting would not make much sense. Rather, with addition of every single value, we need to keep track of all the largest values that we currently have so far. And for that, what I'm suggesting is that we actually use a very popular data structure called heap that is specifically designed to store or identify kth largest or kth smallest element. The approach I'm suggesting is that for this particular heap, we actually create a min heap of the size k. Okay, and what does min heap means is that it stores the values in like the minimum order in its sequence. So let's say currently in our array we have values like 2 and 4 and then 1, something like this one. So this is currently not sorted, but if we try to put these values inside the min heap, it is going to store values as 1 and then 2 and then 4. So basically we will have sorted values that are being stored, and adding every single new value inside the min heap only takes logarithmic time, so log n time. So the idea would be that if we just have a min heap of size k, that is number one scenario, and number two condition is that whenever we find a value that is actually greater than the current value we have, then we are going to pop this value out, and then whichever value x we found, we are going to push this value inside our array, and this should allow us to find the kth largest element very quickly. Let's try to see the solution I'm suggesting in action, and then it would make much more sense. So currently this is our given input array. We are trying to find the third largest element. So what I'm suggesting is to create a min heap of size 3. Okay, currently this min heap is empty. Now we have value number 4, so we simply add value number 4. Then we have value number 5. So remember, because this is a min heap, if there is like the low value, it needs to be at the very beginning. Okay, so then we add value number 5. Once again we have value number 1. So currently value number 1 is actually smaller than both 4 and 5. So we will min heap automatically would readjust itself, and we would have values 1, 4 and 5 stored in this manner. once again, okay, so now let's say if up until only this point we want to find out that what is the kth largest element, all we need to do is just simply check that what is the very first element present inside the min heap, and that is going to be the kth largest element. So not only this min heap is going to allow us to calculate the kth largest element for given input array, it can seek subsequently applied in order to use for our add method as well. And that's why this one data structure is going to solve both of our problems. So now currently the kth, let me just put down the answer over here. Okay, that currently the minimum value is 1, so that we can find, and this answer is for the add method. And at the same time we will find this answer over here for the kth largest as a, okay, that will come when we reach to the end of this given input. Now once again we have value number 2. So currently 2 is actually greater than the very first value inside our min heap, which means 2 should be our should be in our min heap, and we are going to pop the smallest value inside the min heap. So now currently we have values 2, 4 and 5. Once again the answer is going to be 2, because this is the third largest element we found so far in this stream. Next we have value number 6. So the moment we want to add value number 6, which means 2 is definitely clearly smaller than value number 6, which means 6 needs to be added. But with addition of 6, 4 and 5 also needs to be readjusted. So now 4, 5 and 6. So far up until this point, the third largest element is going to be value number 4. Okay, once again now next element we need to add is value number 3, but currently 3 is actually smaller than the current value we have inside the min heap, which means we don't need to do anything. We can just simply skip over 3 as it would not be part of the solution. Next is value number 7. So for value number 7, once again we will have to do the readjustment. So 4 would be kicked out and 5 and 6 would be adjusted to have 5, 6 and 7. Currently our inside the stream the value is going to be 5, and the answer is also going to be 5. That 5 is the third smallest element, or sorry, third largest element inside the given array. So just by simply using min heap of size k and then having the logic that if the value we are trying to add, if that value is actually greater than the current very first element inside the heap, we will need to kick this element out and insert this value inside the heap. Then the solution would work perfectly fine. If we see time and space complexity, in this case the time complexity is going to be big O of n log n, because for every single element we will have to enter it into inside the heap. So that's why the time complexity is n log n. If we see space complexity, it is going to be big O of k, where k is the the kth element we are trying to find, because we are initializing a new min heap of size k. And for those who don't know, min heap also means a priority queue. So that's the logic right there. So first of all, we are going to initialize our priority queue and integer k, a couple of private variables to store them. Then we are going to have our kth largest method, where we are going to store the values of k and also initiate a new min heap instance with the size k. Then for every single element that is currently present inside the nums, we will need to add that value inside our nums array. So for that, rather than doing anything else, we can just simply use the add method. And now let's quickly also see the add method, where we first check that if the current min heap size is less than k, then we are simply going to add the value inside the min heap. If that is not the case, then we are going to check that if the given current value is greater than the current very first or smallest value we have inside the min heap, then we will have to kick that value out, and then we will have to add the new value we are currently at inside the min heap. In the end, we simply need to do a peek operation, or the very first element that is present inside the min heap, and that is going to be the kth largest element for us. And that's it basically. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions, which is pretty good. It is excellent in terms of space complexity as well. And once again, the coding solution is present on our GitHub repository, so you can go and check it out from there. Thank you. So the LeetCode problem we are going to do is called last stone weight. Now, in my opinion, this is one of the most awesome problem I've seen. We can see that this one is an easy problem and also a very well-liked problem. The problem statement is that we are given an array integer of stones that defines the weight of every single stone that is currently present. Okay. Now we are playing a game with these stones. Now during the each turn, we choose the heaviest two stones. So this is the important part. We choose the heaviest two stones and then smash them together. Now the question is, there can be two possibilities. One possibility is that either for two stones X and Y, either both are of same weight or both are of different weight, which means one is heavier than the other. If both are of same weight, then both stones get destroyed. Okay, because we are smashing them together, both stones get destroyed. If that is not the case, and if we realize that one stone is heavier than the other, then the stone with lesser weight gets completely destroyed, and the stone with higher weight has a new weight that is like a y minus x. So whatever the difference between weight is between two weights, and then we are going to keep on repeatedly going to do the same process until the end of the game, where there is only one single stone left, and then we are going to see that what is the weight of that particular stone, and that's why the name is last stone weight. Now let's try to understand this with an example so it would make more sense. Currently we are given an array where every single value represents the weight of stones at that particular position. What are we being told? That we need to find the two heaviest stone during every single iteration. So currently two heaviest stones are going to be 8 and 7. So currently 8 and 7 are not equal to each other, which means when these two stones get smashed, this 7 is going to completely be destroyed, and this stone 8 is actually going to be only of size 1, because we will have to do 8 minus 7. Okay, following this particular condition. So once again, if we do that, currently we have this 7 gets completely destroyed, and we have this element number 8 that is now being turned into element number or stone weight size 1. So now the new array we have is values 2, 4, 1, 1 and 1 and 3. Once again, we are going to repeat the same process. So find the two heaviest stones that are 4 and 3. Once again, both are not same. So once again, if 4 and 3 gets collided, we are going to left with one stone that weighs 1 kilogram, and this stone number 3 is going to get destroyed. So the new array we are going to get is going to look like this, where the values are 2, 1, 1, 1, 1. Okay, so once again in this case, now this 2 and 1 are both are the stones, so they both are going to be crashed against each other. So if we do that, once again this stone will get completely destroyed. This one only becomes of weight 1. So new value is going to be 1 amongst these two, and then these 3 ones we already had. Okay, so now once again we are going to repeat the same process. Now two heavy stones are both contains the same weight. If the weight is same, both gets destroyed. So in the next iteration we are only left with two stones, 1 and 1. And once again, if we try to smash these two stones together, both will also get destroyed. So we will not have any stones left in this case, so we will need to return 0. Now let's say in the same condition, let's take one more example where we try to have some weight inside the stone. So let's say the values are, now in this case currently the two heavy stones are this 8 and 6. If both gets smashed, then we will have values with 2, 3 and 4. 6 will get destroyed. So once again the two heavy stones are 3 and 4. So once again, if both get smashed, then this 3 is going to be destroyed, and we are going to be left with values 2 and 1. If these two get smashed together, then this 1 is going to get destroyed, and last stone will only be left with size 1, and this is what we need to return as the answer. So basically this is what the problem statement is asking us to solve. The brute force approach is actually going to be quite straightforward, where at every single iteration we will first have to find the two heaviest stones. Once we find the two heaviest stones, then doing all the remaining work is not that much complicated. Then we can simply find the difference between them, and then once again create a new array, and then once again try to repeat the same process until we are only left with just one stone or no stones at all. So brute force approach would yield us the correct result, but the issue is For every single time, if we have to find the two heaviest stones for each of the remaining array, basically we are going to be doing big of n square work just to find the two heaviest stones. And once we do that, solving this problem is very simple and very easy to do. So the question we will have to focus on is that how can we improve upon the scenario where finding the two heaviest stone becomes very convenient for us at every single iteration. And for that, the idea is whatever the given input array is, we will actually try to create a priority queue or a heap where we are going to store all the values, and we are going to set up this heap to be of max heap type. So max heap means that whenever you try to add the values inside the heap, it is going to store the maximum element first and then smaller elements later, which means it is going to store all the values inside the descending order. Okay, this is the whole concept of max heap. So that's what we are going to use in this problem. And let me quickly show you that using max heap, this problem becomes really easy to solve. The idea is that first, currently we are simply going to iterate over every single values and start putting them one by one inside the max heap. If we do that, we will get a sort of I would say a value that is sorted in decreasing order. So very first element is going to be value number 7, and then we will have value number 6, and once again then we will have all the subsequent values in the same decreasing order. And this is the input we currently have. So once after finding this input, in order to find our x and y values, we simply need to poll these two values in. And after polling these two values, all we need to do is find that if they are of same size, then destroy both of them and move forward. If they are not of the same size, find that what is the delta between them, and whatever the difference is, try to put that back inside the max heap. Keep on repeating the same process until we are only left with just one element. And let's try to see the solution I'm proposing in action. So once again, in this case, currently this is our max heap, and currently these are the two largest elements, 7 and 6. We will try to pop them out, and we find that the difference is going to be 1. Okay, so currently this 7 and 6 has been popped out, and we have element number 1 that needs to be added. So in order to add element number 1, it will be added in the back side of the heap. So we will I will not draw a new heap. I will just keep on adding 1 values. Okay, and these are just empty shells, so don't just ignore them. Now once again, during the next iteration, we are going to find the two heaviest elements, that are 4 and 3. Once again, the difference is going to be 1. So once again, now we no longer have values 4 and 3 inside the heap, and we are just going to add one more element, 1, at the end of the heap. Next two heavy elements are 2 and 2. So because both are same, so we are simply going to ignore them and not add any other values. Now the two heavy elements inside the given heap are 1 and 1. Once again, both are same, so we are going to delete both of them and don't do anything. And lastly, there is only going to be one stone left that is going to be of size 1, and this is what we need to return as the answer. So you realize that after storing all of this information inside a heap, that is a self-balancing data structure that automatically sorts itself with new elements being added, how easy this problem becomes. So once we implement the heap, this problem is very simple, and we know that insertion inside the heap takes log n time, and we will have to do it for n given input. So it's going to take n log n to store all the values and complete this problem. So this is going to be the time complexity. If we see space complexity, that is going to be big O of n, because we will have to create a new heap to store all of these values. So there is no other way to move around that, but still this is a very good time and space complexity. Now let's try to quickly see the coding solution for this one. Okay, so first of all, we are going to initialize our max heap, and this is how we actually initialize it using the priority queue. And in the comparator class, we are mentioning that only the maximum element has to be at the beginning of the heap. Then we are going to add all the values inside our max heap, and then we are going to continuously remove and smash the two heaviest objects until we are only left with just one element. And for that, we find our y as the very first element inside the heap. We find our x as the second element inside the heap. We simply have a condition that if x is not equal to y, then we are going to add the element that is the difference of weight between y and x elements back inside the heap, and keep on repeating the same process while the size of the heap is greater than 1. and the moment we reach to the end, we are simply going to check that if the heap is empty, we are going to return 0. If the heap is not empty, we are going to poll the last remaining element inside the heap as the answer, and that is going to be the heavy last remaining stone weight of our original input of stones that we were given. So now let's try to run the code. Seems like our solution is working as expected. Let's submit this code. And our code runs 98% faster than all the other solutions. That in itself suggests that we are doing something really good and really right. So once again, this coding solution is present inside our GitHub repository. You can go and check it out from there. Thank you. So the LeetCode problem we are going to solve today is called k closest points to origin. Now we can see that this one is a LeetCode medium problem and also a very well-liked problem on LeetCode. The problem statement is quite straightforward. We are given an array of points that represents points on an XY plane or a graph. And we are also given an integer k. Now we need to return the k closest point to the origin. Now we are also given that what is the mathematical equation to point the distance between any two points, and that is the Euclidean distance formula. So that is x1 minus x2 square plus y1 minus y2 square and square root of the whole thing. So we need to say that, okay, say for an example, if this is the input we are given, we can see that there are a bunch of different points presented to us. Now I have plotted these points on this graph, and we need to return the k closest point to the origin. So origin is going to be this point 0 0. So origin point is always going to be 0 0, and we need to use the Euclidean formula. So let's say that we are given k is equal to 2. So we need to return that what is the second closest point to the origin. So we can see that in this case, this is going to be the first closest point to the origin, and the second closest point is going to be this one. So we need to return this value 2 and 1 as the answer, as this is the second closest point to the origin. Now in order to calculate the distance between any two points, let's say that we want to calculate this distance between this 1 point and 0 0 point. So the mathematical equation is going to be 0 minus the whatever the x square is, that is x minus 1. So 0 minus minus 1 and the square of this one plus, once again we will take y1 minus y2. So 0 minus this one is 1, so 0 minus 1 and the square of whole thing, and then we are going to do the square root of this whole thing. So that is going to give us this distance. That since in this case we are given k is equal to 2, we need to find the second closest element in order to, and return that as the answer. So in this case the answer is going to be 2 and 1 that we need to return. So that's it. This is the whole thing that what the problem is asking us to solve. So brute force approach is actually quite straightforward. In the brute force approach, what we can do is we can simply start calculating all of these distances that are currently given to us. And then after calculating all of these distances, we will have some random values, because for sure we are not going to get exact values, because we don't know which one is the closest, which one is the farthest. Let's say we find some random values, like let's say that this one is 3, this one is 2, this one is 1. I'm just giving some arbitrary values, okay? So something like these. Then once again amongst these values, we will have to find that what is the second closest value. So once again for that we will have to iterate over the given array and find the second closest value. In order to do that, it can still take big of n square time in the worst case scenario. So we will have to do something better. So here now for the optimal solution, I have just put down like every single point denoted as a number, and for that number I have calculated that what is going to be the distance from the origin point for that particular value, and I have marked all of these values over here. Now say for an example, just for understanding's per sake, we will try to now understand that this one as if it does not contain a square root. Okay, this is just going to help us understand that what the solution is look like and how we can use max heap in this case to solve the problem. The idea is that we are going to create a max heap of size k, and inside the max heap we will always try to first add the value inside the max heap, and the moment we realize that the size is actually greater than k, then we will have to poll the lastly added element outside of the max heap. Okay, we are only going to store the k values. So in this case we are trying to find the second closest point to the origin, so k is equal to 2. So let's say let's quickly initialize our max heap, and inside the max heap currently we don't have anything. Now in the max heap we are only going to store two elements. Okay, I'm just adding one more element over here, because this is we will put down the buffer value to see if we exceed the size of the max heap. If we exceed, we are going to pop this element out. Okay, so now let's try to populate our max heap with the theory we just mentioned. So first we have value number 7, so we are going to put value number 7. Then we have once again value number 7, so we are going to put value number 7. Once again we have value number 2, so once again we will have to adjust the input. So it's going to be 7 and then 7 and then 2, but we exceeded our place because we only want to store two elements. So we are going to kick the 7 out and we are going to leave this as it is. Then we have value number 5, so once again this needs to be readjusted. So values are going to be 7 and then 5 and then 2, but once again we exceeded the number of inputs, so we will have to kick the 7 out. Now we only have value number 5 and 2. Once again we have value number 6, so 6 would come over here because this is a max heap. So we are following the property of descending order coming to the first, so the maximum value is going to be stored at the very top. And then once again we will have to kick the 6 out because we only wants to keep k is equal to two elements. Lastly we have value number 3, so once again first we will do the readjustment. So values are going to be 5, 3 and 2, but once again this 5 is excess, so this will also be kicked out. And then we are now done with all the values, and now we only have these two values inside our max heap. And the very first element inside the max heap has to be the kth closest element to the origin, and which we can see because this is the endpoint and the distance is square root of 3, and we can see that this is actually the second closest point to the origin after this one. So this is what we need to return as the answer, and this is the whole solution. So basically the important portion in this one is that first this problem looks complicated because we are dealing with like XY graphs, and I know many people after high school haven't even dealt with this one, plus you might have forgot about the Euclidean distance equation. But don't worry, these are all just the constant matter. So all we need to do is, number one, we are going to iterate over the given input, and we are going to find that what has been the Euclidean distance from every single point to the origin using a simple mathematical formula, that is x1 minus x2 square plus y1 minus y2 square and the square root of the whole thing. Okay, after doing this one, we simply need to initialize our max heap to the values or size of k, and we are simply going to do the operation that we just mentioned. In the end we can simply do max heap dot peak operation, and that is going to provide us the kth closest point to the origin, and that's it. This is the whole solution. So now if we see time and space complexity, in this case time complexity is actually going to be big O of n log n, because it takes log n time to enter values inside the heap, and we will have to do this n times. Plus we will also have to spend some time calculating the distance from the origin to that particular point, but that is going to be constant effort that needs to be done for n values. So we can simply ignore this one because it is no longer relevant, because we already have a higher time complexity component. Space complexity, once again we will have to create an extra heap, so that is going to be big O of k. So now let's try to see the coding solution for this one. So the coding solution is actually quite straightforward. We are first of all going to initialize our max heap, and inside the max heap we are going to store the values based on the distance from the origin to that particular element, and that is going to be done based on using the Euclidean distance formula from the origin. And once we have those values sorted, then all we need to do is just simply add those values inside our heap. Now inside the heap we will first add the value, then we will check that if the size of heap exceeds the value of k, we are going to poll the very last element we entered inside the heap, and that's it. Now in the end we simply need to collect the kth closest point from the heap. So for that we can simply create a result array, a 2D array, and we can simply run from I to the k, and we will try to find the element, and then we will poll it inside the result, and then we can simply return that as part of the result. So this is the whole solution. Now let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared in terms of time complexity and extremely good in terms of space complexity. So once again, the solution is present in our GitHub repository. So if you want, you can go ahead and check it out from there. Thank you. So the LeetCode problem we are going to solve today is called kth largest element inside an array. And we can see that this one is a LeetCode medium problem, also extremely well-liked problem. Now, in my personal opinion, this should have been an easy problem, but anyways, they have put it as medium. So let be it. We are given an integer array nums, and we are also given an integer k. Basically, we need to return the kth largest element that is currently present inside the array. Now let's try to understand this with an example. Suppose this is the input we are given. We can see that there are a bunch of different random values present at the random location. Now let's say for this problem we are given k is equal to 3, which means we will have to find the third largest value that is currently present inside the given array. Now we can see that the largest element is 7, so that is the first largest element, 6 is the second largest element, and 4 would be the third largest element. So in this case we will have to return 4 as the answer as the third largest element. Now let's try to find that what are the different approaches we can take to solve this problem. First approach comes to our mind is a brute force approach, where the idea is quite straightforward. We simply iterate over the given input array simply one by one, and in order to find the maximum value, then once again we iterate over in order to find the second maximum value, and we iterate over the third time to find the third maximum value until we reach to the kth maximum element, and we return that this value as the answer. Obviously you can see that we are doing a lot of repeated work with the brute force approach, and the time complexity is going to be big of n multiplied by k, so that is not a good approach. Let's try to find the second solution. Now second solution is quite straightforward, that for this given input, if we somehow sort this given input, then finding the kth element is very easy, because then we will know that after sorting this, the largest element is going to be for the first one, and then we will have values stored something like this one, where we can easily find that which is the third largest element in just like that. So sorting will take big O of n log n time, and then finding this element will only take big O of k time, or just like this would be instantaneous because it's an array. Okay, so overall this is a good approach, works fine, but the issue is we are explicitly told that we need to solve this problem without sorting. So let's try to see that how can we actually solve it without sorting. For that we actually have two options. First option is that we find the most optimal way to solve this problem, that is using a priority queue or a heap. That is one way. And second option is that whether we use a quick select algorithm. So let me know in the comments if you want to see the quick select approach. I can also make a video on that in the future, but in this time we are simply going to use a heap. The idea is we need to find the kth largest element. So we are actually going to store a min heap, where we are going to store all the values in a min heap fashion, which means in a ascending order. Okay, so the very first element inside the min heap is going to be the smallest, and then all the other values are going to be larger than that. Next thing is we are going to have this min heap of size k. So we are only going to store k values at one time. And third thing is that in this particular min heap, we are going to have a condition that, let's say if a new value we are trying to add, if that value is x, if that value is greater than the very first value we currently have present inside the min heap, then we are going to kick this value from the min heap out and try to put x inside the min heap. So min heap once again is going to maintain its sorting property, and it is going to keep all the values inside the min heap or ascending fashion. So let's try to see the solution in action. So let's initialize our min heap. So currently the given k is equal to 3. So the size of the min heap is only going to be 3. Very first element is value number 4. The second element is 2. So once again we are going to store the values inside the ascending fashion. So 2 and 4. Next element is 6. So 6 would be added over here. Okay. Next value we are trying to add is value number 1. So once again 1 is a smaller value. So if one value is smaller than current minimum heap, then we don't need to do anything. We can simply skip over. Why? Because we know that in this particular fashion, the third largest element is actually going to be the very first element inside the heap, and that is still going to remain 2. So we don't need to add value number 1, and we can simply skip over. Now we are at value number 7. So 7 is greater than the very first value inside the min heap, so we will have to kick this value out, and then we will have to put 7 in. But 7 would not be put in the place of 2. Once again we will do the operation of self adjusting the min heap, so values are going to be 4, 6 and 7. Once again, after adding 7, we have value number 3. So once again 3 is actually smaller than value number 4, so we don't need to add 3. Once again we have value number 2. 2 is once again smaller than value number 4, which means we don't need to add 2 as well. So after the end of iterating over the entire array, the very first element inside the min heap has to be the kth largest element, which we can see over here that this 4 is the third largest element inside our array, and that's it. So this is how easy it is to solve this problem using a min heap, and we can simply come up to the solution very quickly, very easily, without any delays. So let's try to calculate the time and space complexity in this case. The time complexity is going to be that we will have to iterate over every single element, and for that we will have to insert the values inside the min heap or do some sort of checking. So for n times we will have to do log n work. So it's still going to be the n log n time. It's still same as sorting, but the thing is, rather than sorting, we are using a priority queue to take care of the values inside the priority fashion, inside the min heap fashion. If we see space complexity in this case, space complexity is going to be big O of k, where k is the size of the given kth element we are trying to find, because we are initializing a new min heap to store the value. So it makes absolutely good sense to store this one. So we can see that this one is a really good time and space complexity to solve this problem. And once again, as a general rule of thumb, whenever you find any question where you want to find kth smallest element or kth largest element or kth biggest element, something like this, whenever you see kth, try to see that if you can use a heap to solve this problem, and almost 99% of the time you should be able to solve this problem. Okay, so now let's quickly see the coding solution for this one. So this is the coding solution. We can see that this is very simple and short coding solution. Basically, we first of all initialize our priority queue or min heap, and then we have a for loop to iterate over the given input nums that is provided to us, where we are simply going to add these values inside the min heap one by one. Then we are going to check for a condition that if the size of min heap is greater than k, then we need to poll the very first element that is present inside the min heap, and that's it basically. So in the end, we should have a min heap that only contains the kth largest element at the very first position, that we are going to do a peek operation and return. And let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code. So our code runs faster than a lot of other solutions, and this is a really good approach. So I would be posting this solution inside our GitHub repository. So now we are going to do one of my favorite problems on LeetCode, that is called task scheduler. We can see that this one is a medium problem and also a very well liked problem. Now I just have one request for you. I really want you to pay utmost attention to this particular problem, because if you can understand to solve this problem, there are a lot of important LeetCode concepts that would enshrine in your brain. So please, please, please pay utmost attention. Now let's get started with the question. Basically, we are given an array of CPU tasks, and each task is represented by a letter somewhere between A to Z. Then we are also given a cooling time n. Now we are told that each cycle or interval allows the completion of one task. Okay, that's fine. And then we are told that tasks can be completed in any order, but there is one small constraint regarding this interval n that we are given, and that is that identical task must be separated by at least n intervals due to cooling time. Okay, so let's try to understand what it just mentioned with some examples, and basically we need to return the minimum number of intervals required to complete all the tasks. So let's try to understand this with an example. In this case, we can see that we are given 3 tasks that we need to complete. First task is A, second one is B, and third one is once again A. We are also given the cooling down period of 2. Now, how does this cooling down period affect our task is that identical task must be separated by n intervals. So let's assume that during the first window, we start to complete task A. Okay, so we got rid of this task. Once again, we got rid of this task as well, task B. Now the thing is, we only have one task remaining that we need to complete. But if we try to complete task A over here, and if we see the difference between this interval and this interval, then we can see that the difference is only going to be 1. But the thing is, it has to be separated at least by 2, because that is what the cooling period is. Because once again, I'm repeating, both A and A are identical tasks. We are told that identical task must be separated by at least n intervals, and in this case is 2, which means 2 identical tasks has to be separated by 2 intervals. Currently we only have it separated by 1 interval, so we will actually have to add one more interval over here where we are not going to do anything. So this would be an idle period where we are just going to stay idle just to complete that one more interval. And now we have 1 and 1, 2 intervals completed after we completed task A, and then once again we can complete the remaining task A. So totally we need to return the minimum number of intervals required to complete all tasks, and in this case we can see that we took 1, 2, then this idle third, and then this completing A4. So in total we took 4 intervals to complete this task. Let's try to understand this with a couple of more examples. Next example is, once again we are given n is equal to 2. Now in this case we have 3 identical tasks. We have 3 A's and 1 B. So one logical solution would be, we can start with task A. Once again we go to task B. Now we know that the cooling period is 2, which means we cannot use a task A once again. We will have to stay idle. So we got rid of this one. Okay, now once again we can do task A. But after completing task A, once again the next task we need to do is once again task A, for which we have to have 2 idle cycles. So since there are no other tasks remaining, we are going to remain idle for 2 more cycles, and then we are going to complete task A. So if we calculate in this case, we need in total 7 intervals to complete every single task in this input. And same way in this approach, we would actually need in total 8 intervals. How? Because we are given 3 A's and 3 B's. So logically we can do task A, then we can do task B, and then we cannot do task A or B once again. So we will do an idle scenario. Once again we would do A, once again we would do B, and once again we would do idle, and once again we would do A, and once again we would do B, and then we don't need to stay idle because we completed all these 6 of the tasks. So that's what the problem is asking us to solve. I know understanding this problem is quite tricky. Now, first let's try to understand the brute force approach. Now, logically, the most simplest brute force approach would be to try out every single possible permutations and combinations. So we start with task A. Then once again, we try to find that what is the next task that is not A. Once again, we identify task B. Once again, we mark task B. Once again, we try to identify that is there any other task that we can do that is not A nor B within this 2 window period. We cannot find anything. So then we decide to go idle. Once again, we repeat the same process, and once again, we keep on finding the next task. So this is a very slow approach, and we are doing lot of repeated work just to do this one. Because number one, we are not sure that how many number of total tasks are available. Number two, we are not sure that what is the frequency of every single task. So we cannot know that during any particular interval cycle how many number of tasks we can accommodate. That is one huge problem with this brute force approach, and this problem is what we are going to solve and exploit it in order to make this algorithm much faster. So let's try to understand that what is the optimal solution I am suggesting. But for optimal solution, first we will have to build up some logical understanding on how we can improve our solution. Okay, So for that, once again, let's take our favorite example where we are given 3 A's and 3 B's, and once again we are given our n is equal to 2. Logically, most efficient matter for us to solve this problem would be that in any particular given input, first we need to find out that what is the character that occurs most number of times, and we always have to start with that character in order to complete it in the fastest manner possible. So logically, in this case, both A and B occurs 3 times. So what I'm suggesting is that first approach we can take, first smart approach is that we can actually take an entire input, run it through some sort of like array or hash map and create a frequency map. And in this frequency map, we are going to make sure that every single time any particular character, how many times it appears. That is number one thing. Next, we will need to learn that what is the maximum time any particular value repeats, and then we will need to store the values in the decreasing order. So once again, we will need to find some way to sort this frequency map. So for that, one of the very good approach we can take is that we can actually create a heap where inside the heap we can store the information that how many times any particular character appears, and we can actually store its information. So let me just make this slightly different, and we are going to have B appear 2 times. Okay, so now it makes sense that A is 3 times and B is 2 times. Okay, now one more logic I'm suggesting is that we actually take understanding of this scenario, that what is this n represents. So basically this n simply represents that how many number of computations we can do back to back on separate characters during any particular interval size. But the interval size has to be n plus 1. Why n plus 1? Because remember, we want, let's go back to our very first example. Now let's try to understand this logically. First, let's say we add value number A. Okay, then we add value number B. Okay, now how many more operations we can do where we can basically either there can be 2 options. Number one option is that maybe we have some other value that is not A and not B that we can add over here. That is one option. If that is not the case, another option is that instead of adding this another value, we will need to add an idle value over here. And then the whole cycle of once again reaching out to character number A would reset, because then we would have covered the 2 destination from this our original value A that we were looking at, which means that in order, depending on the value of n, we would actually have to consider the scenario of n plus 1 as part of one cycle, because in one cycle we can only take unique characters during that one cycle, and if we have less unique characters than this one cycle, then we will have to use idle cases. So which means if we have unique characters, we can simply reduce the values of those unique characters. So in this case, we got rid of this 1A and then 1B. So we are basically reducing the values. Let's say if this one was C, then we could have just reduced C, but we don't have C. So we still have A. So which means repeated characters would only be decreased by 1 during one n plus 1 cycle. And if we have unique characters, we will try to fit as many unique characters as we can inside this n plus 1 cycle. So this is the second improvement we are trying to do of applying n plus 1 cycles. So let's understood that number one, we already know that we created our hash map. We created our frequency map. Then we created a heap to store the frequencies that are coming in. And next we are going to be marking the scenarios based on n plus 1 cycles. Now these are the 3 improvements. Now I'm suggesting 4th improvement, and that's why I'm telling you that this problem is such a mind-blowing problem, because you are making improvements after improvements after improvements in order to make the efficient algorithm, and that's why you are learning a lot of new things. So that's why I'm paying my utmost attention. Coming back to the question, so understand in this case that so far we are keen on understanding that how many number of A's are present and how many number of B's are present and how many number of C's are present. The thing is, apart from storing this value inside the frequency map, we don't have any other information that we need to utilize this for. All we can do is that we are already tracking the values based on the cycles. We already have a heap to store the values in sorted order. Now, instead of storing these characters, why don't we just store the frequencies? Because in the end, we simply need to return that what are the total number of intervals we are going to need. So in the heap, we can actually store the frequencies. The idea is we are going to be traveling in the cycle by manner. So cycle in this case is this is 2. So there is going to be cycle of 3s. Okay. And we know that how many number of unique characters are present inside this given input, because inside the heap we only have 2 distinct frequencies. So that's why there are only 2 unique characters present. So this becomes our way to understanding that there are only 2 unique characters. We know that in one cycle we can only iterate over just unique characters and reduce their frequencies. For rest of the time we will have to put the idle slots. And what I'm suggesting is that we initially start our heap this way. Then we are going to run in the cycles of 3s. With every single cycle, we are going to pop the elements out of the heap to make sure that whether heap is empty or not. If heap is empty, if there are no values inside the heap, then we will simply add idle values till we make n+1. So why do we even make idle values? We know that after removing all the elements of the heap, basically for this cycle, we still have some elements that for which we haven't calculated the frequency. And if there exists some frequency, which means the entire n+1 has to be part of the answer. And then we simply have to reduce the frequency by 1 and once again repeat the same process. So this is the whole solution I'm suggesting. Now let me quickly show you the optimal approach. Let's walk through the optimal approach and then we will see the coding solution. So if we see the optimal approach now, it is going to make much more sense. Once again, let's take our example and we have 3 A's and 2 B's and we have n is equal to 2. Okay. Logically, we have our heap. So currently inside the heap, we only have values 3 and 2. That is the frequency map. And notice that this frequency map is actually sorted based on the ascending order property. Then once again, for n is equal to 2, which means we are going to do the cycles of value 3. Okay. So let's try to do the first cycle of value 3. During the first cycle of value 3, we are going to pop one element, this 3, out of our heap. Currently we have, and we are creating a temporary list to store the value of heap, and then we are going to reduce it out of the temporary loop. Okay. So currently this is 3. We popped one element out. Currently this is 2. Once again, we popped both the elements out and we realize that currently our heap is completely empty. There are no values inside the heap. So if heap is empty, then we need to check that what was the value that we took out from the temporary loop. We took out the values 3 and 2, which means we will have to reduce these values, and reducing these values are going to be 2 and 1, which means the temporary list is not 0. So in this case, because temporary list is not 0 and our heap is empty, we know that during the first cycle, we will have to do 3 intervals. So we are going to mark 3 that we have completed so far. So we are going to have a variable called interval where we are going to store the values. So far we have completed 3 variables. Once again, notice that inside the temporary list, we first had values 3 and 2, but we reduced the frequency by 1. After reducing the frequency, once again, we are going to populate this value 2 and 1 once again back into the heap. Once again, we are going to run the operation. So once again, in our temporary list, we are going to have values 2 and then value 1 coming in. And we are also going to have a heap becoming empty. Now heap is empty. We try to reduce the frequency. So reduced frequency is going to be 1 and 0. Now after reducing the frequency, we realize that there are still some values present, which means this entire interval we are also going to consider. So it is going to be 3 plus 3 so far. After this, once again, we realize that this value is 0. So 0 value we kick out from the temporary list. We put the value back inside the heap. So currently heap only contains value number 1. Okay, so now after containing value number 1, we will try to pop value number 1 out. Currently heap is empty, but we are not going to add 3 so far because this might be the last character, which is the case because in the temporary list we identify that there is only 1. If we do like a reduce operation minus minus, then this becomes 0, which means temporary list does not have any value and heap only had 1 value. So we are simply going to add that value that we take out from the heap or take out from the temporary list. So in this case, we need to make minimum 7 intervals to complete each of these cases. And let's try to walk through these 7 intervals. So of course, our given n is equal to 2. So first we are going to do operation A, once again operation B, and then we will have to do idle operation. Once again, we are going to do operation A, operation B, and our idle operation. So now, so far we have taken out 2 A's and 2 B's, and in the end we simply have our operation A we need to do. So total we need to do 7 intervals in order to complete this problem. And this is the solution. I know I went over a lot of things, but I hope that this made sense, that what I was explaining. If we see time and space complexity in this case, well, time complexity contains a lot of steps. So number one step is we need to build frequency map. That takes big O of n time. Plus we will need to iterate, we will need to generate the heap. So that takes big O of n log n time. Then we will have to run our while loop iteratively till we reach out, till we complete every single cycle. That is once again going to take big O of n, and then we will have to subsequently do the total number of intervals that we are going to be able to make. And that can, in the worst case scenario, it can be big O of n square. So in total, we can say that our time complexity is still going to be big O of n square, but this is much more efficient approach compared to our brute force that would have yielded us big O of n cube time complexity. So that was going to be horrendous. If we see space complexity, well, we are using frequency map and we are also using heap and plus temporary array list. So basically we are using big O of n extra space, and this is still, in my opinion, a good enough time and space complexity. So here is the coding solution. First thing we are going to do is, for given input task, we are going to run across and create a new frequency hash map where we are going to store the frequency for every single task or every single character. Once we have frequencies, we are going to build our max heap based on the frequency. So we are going to initialize our priority queue to store the integer values of the frequency sizes, and we are going to add all of these values from our frequency map, and they would automatically be sorted in descending order. Next thing is we will need to process every single task. So initially we are going to have our variable time set up as 0. Then we are going to have a condition that while our given heap is not empty, we will need to do the following. So first thing is that we will need to initialize our temporary list that we mentioned that we will have to create. Then we are going to run a for loop from I is equal to 0 to I is less than n plus 1, which means this is going to be one of our cycles. So this is going to be our cycle logic where we are simply checking that we are going to check if the max heap is not empty. We are going to keep on polling every single value out from the temporary list to the temporary array list, and we will keep on repeatedly doing it until our given max heap is either empty or we complete the n plus 1 cycles. In either case, we will have to add n plus 1 items depending on this. Then we will have to reduce the values from the frequencies. So because we are popping values out from our temporary from our heap, which means currently they are stored inside our temporary array list. So we are going to reduce the frequency and keep on checking that if the frequency is greater than 0, we are simply going to add that value to our max heap. If the value is equal to 0, then we are not going to add it to our max heap. Next thing is we will need to update the time, and the time update is going to be quite straightforward, that if the given max heap is equal to empty, then we simply need to update the size by n plus 1. If that is not the case, then we will need to update the size or update the time based on the temporary variable size we had, which means that was the additional values we found inside our temporary array list that got popped out of heap. And in the end, we simply need to return the time, and this should provide us all the intervals we had. So this was a brilliant question, a brilliant solution. Now let's try to run the code. Okay, seems like our solution is working beautifully. Let's try to submit this code. And our code runs pretty fast in terms of time and space complexity. Once again, the coding solution is available in our GitHub repository, and the link of the GitHub repository is in the description. So feel free to check it out from there. Thank you. So now the problem I'm going to solve can be asked in three different ways in three different interviews. It can be a data structure and algorithm type of LeetCode problem. It can be a system design problem, and it can also be asked in low level design problem. So I'm going to do my best to explain in as much detail as possible. I hope you pay utmost attention to this particular problem. So the problem we are going to solve is called design Twitter, and we all know what Twitter is. This one is a LeetCode medium problem and also a very well-liked problem. Let's try to understand the problem statement. Basically, we need to design a simplified version of Twitter where users can post tweets, follow and unfollow other users, and it is able to see the 10 most recent tweets in the user's newsfeed. So the Twitter class we need to create, we should be able to initialize the Twitter object. Then we need to create these four methods. First method is post tweets, where we are providing in the user ID and tweet ID that composes a new tweet with a new tweet ID by the user. Then we need to create a linked list type of structure for get news feed, where depending on the user ID we provide, it retrieves the 10 most recent tweet IDs in the user's news feed. Now for this 10 most recent tweet IDs, we are given some logic that each item in the news feed must be posted by the users who the user followed by the users themselves. Okay, so you should only be able to see the tweets that of the people that you are currently following. That's basically what it's trying to say. And this is the important part, that the tweets must be ordered from the most recent to the least recent. The latest one should come in first in your feed. So you need to maintain that timely order. And then we are being asked to create two simple methods, that is follow and unfollow, where you provide the IDs of follower and followee. And basically followers should start following with the follow method, and they should stop following with the unfollow method. So let's try to think and document all the things that we need to create. Okay, number one thing is we need to create a Twitter class. Now in this particular Twitter class, we need to generate four methods. Now logically, first let's start thinking about each one of them one by one. So let's take the small problems first, because if you can't solve the hard part, solve the easy part first. Now for the following and unfollowing logic, basically we have two sets of users. So let's say that I am currently a user. Okay, now I am as a user, my name is Parth, and that's it. Now there are a bunch of different users just like me that I'm currently following, and they also have their own white buckets of being users, and they might also follow me back. Some might do, some might not, and they may also be following bunch of different more users as well. So one logical conclusion would be that we want to make sure that the moment I provide you that any particular user, let's say Parth, and then I provide another user, let's say John Cena. So I should be able to see immediately that whether Parth follows John Cena or not. And I would like to do this in the quickest manner possible. So the only way to do that is that if for any particular user, I create some sort of hashing solution like a hash set or a hash map, where I provide the information of every single user that this particular user Parth is currently following. And in this hash set, then it becomes very easy for me to find that whether any particular user ID is being followed by this username Parth. If that is the case, then I can quickly add and remove those entries. So that way I should be able to tackle both follow and unfollow methods, because then it becomes pretty simple for us to identify that. But in order to accomplish that, we will have to first take in few accounts or few considerations. Number one thing is how we are going to configure our user details, like what are the items we should be putting in inside the user class. And for each user, because we are trying to create like a separate hash set, so how should that work? So we also have to think about that. We are trying to fix it using the users, and for every single user having a hash set of all the people that particular user follows. So for that, what I'm suggesting is that we first of all create a separate user class, and in this particular user class, that number one, we have the user ID, and then we also provide two methods. First one is a follow method and second one is an unfollow method, where both the things this follow and unfollow method does is exactly to look up inside the hash set for that particular user and identify that whether there is a connection or not. In order to do that, we also need to have a hash set where we are going to store the values of all the users that are currently this user is following. That's it. So this is what our user class should look like, because we are taking care of the IDs and we are also taking care of follow and unfollow method. Now, after tackling the issue of follow and unfollow, we need to also understand the logic of post tweets and get newsfeed. So now the next lesser complicated portion is post tweets. So now once again, now let me deviate slight bit of side from the users and also go into the issue of Twitter or tweets. So for any particular tweet, what are the different items a tweet needs? So number one thing a tweet has to consider is basically what you are trying to tweet, right? Of course. So in this case, we are being told that we are just posting an integer associated with that tweet. So basically a tweet ID. We are only going to be posting the tweet ID on what information is there, and that is sufficient. Okay, so every single tweet is going to have a tweet ID that we have to take care of. Next thing is, remember, when we are trying to generate the news feed, we need to provide the top 10 most recent news or most recent tweets. In order to do that, we have to identify that for these top 10 news feeds, based on the time, we need to have some way to keep track of the timestamp that this tweet has been tweeted. So for any particular tweet, we will also have to keep track of the timestamp, that at what time did we created that tweet. That is numbers. Second thing we have to identify. Third thing is we have to associate that what was the user who created this tweet. So in order to do that, we can actually have the tweet ID, or we can have a post method basically on the user class, where we can simply create a tweet, and this post method should call this tweet method or this tweet class, where we are simply providing all the information we have in order to create a new tweet, and that's it. So now this tweet also has an access to the user ID, and this user ID and this tweet ID becomes our connection points to separate the tweets depending on per user basis. Because remember, when we get to the level of generating the news feed, we will have to generate the news feed based on the people I am currently following who have tweeted. So I need the information of the user, and I also need the information of the tweet, and I also need the information of time. So combination of these three attributes should take place into my tweet class as well. And next thing is for our tweet, typically tweets are generally stored in like a linked list sort of fashion, because even for the generate news feed, we have to create the linked list. So the ideal scenario is that even for any particular user that is currently generating a tweet, we also provide a link to call to the next tweet that this user also has made. So when we get to the coding portion, this thing would make much more sense on how we are configuring this user account and this tweet account. Now let me come back. Okay, now and also let me do a quick recap. So far we have created the users class, and we have also created a tweet class. In the users class, we are storing all the necessary information that we need for the user. So things like user ID, and then things like tweet that this user makes, and then what the hash set to store the information of all the people that this particular user is currently following. We also have the tweet table, where in the tweet we have the tweet ID. We also have the user ID, because we need to know that for any particular tweet what user was associated with that. And anyways, we are also having a post method that deals with the tweet class we have on our side. Remember, there needs to be a connection in this case. Okay, so that's why it needs to make sense. Once again, coming back for our tweet class, and also this is also going to be a time bound event, so we are also going to store time for each one of this one. Now coming back to our main Twitter class. Okay, we already took care of follow, and we already took care of unfollow methods. We also took care of how we are going to post tweet method. So basically, if we see the structure of the post tweet method in the original question description, we are simply providing the user ID, and we are also providing the tweet ID that this particular user is posting. Same thing, what we can do is, even for our post tweet method, we can simply provide in the values of the tweet ID and the user ID, and we can associate all of these things together. Now comes the tricky part, and the tricky part is that last thing is we need to be able to generate the news feed. Okay, so in order to generate the news feed, what we will have to do? So let's first try to understand logically what is being asked us to solve. We need to provide the top 10 or the most recent 10 tweets that were being made by all the people who I currently follow. Okay, so all the people who are followed by me. Okay, now this makes sense. Now let's try to visualize it. Currently I am the user, and for this particular user path I'm trying to generate the newsfeed. This path is currently following 10 different people, and all of these 10 different people, they are also users on their own. Now these 10 people, whenever they tweet something, they would have a tweet associated with their user ID. Okay, and that association can be linked through the combination of user ID class and the post class, because remember, even in the user ID class we are actually calling a method to create tweets, and we can actually store those tweets inside the user ID. So user ID knows that for any particular user ID, what are the different tweets that user has made. And let's say that some users just made one tweet, some user made bunch of different tweets, and then some user made few more tweets, something like this. So now we can go to any particular user, that is option number 1. Through this user we can find all the people I'm currently following, that is second step. Through finding all the people I'm following, I need to find all the tweets that they have made, that is the third step. After fetching, so let's say I identify that so far all the people I follow, they have in total made 50 different tweets. Now amongst these 50 tweets, I want to find that what has been the top 10, or let me use most recent 10 tweets that has been generated. So in order to find the recent 10 tweets, the logic is quite simple. I take all of these 50 tweets, I create a heap. Now we all know the concept of heap or a priority queue. Now inside this heap or a priority queue, I store the values based on the time they arrived in. So the value that came in at, let's say, time 1 second, and the value that came in, let's say, at time 3 second. So the 3 second should come in before 1 second. And this process can be easily maintained and manipulated by a heap, because it's a comparator type of data structure where you can compare between any two values and store the values in some sort of sorted format. So in this case, the sorting is going to be done based on the time that it came in, and it is actually going to be in the descending order. So the value that came in at the latest time should be at the beginning, and the value that came in later should be towards the end of the heap. And then once I have entered all of these 50 values inside my heap, then in order to generate the news feed, I simply have to fetch, or I simply have to poll the top 10 values, and that should be able to generate the entire tweet. So now I have some sort of rough way and idea to solve all these 4 methods. Remember, once again, let's try to reiterate, and the reason I'm doing this repetitively again and again is because this question is extremely important, and I really want you to understand the whole logic and the whole thought process, because we are using a great number of combination of data structures to achieve what we want. Okay, so for the unfollow and follow method, we are currently simply using the combination of that for any particular user is associated with a hash set of all the people that currently user is following, and then we can very easily follow and unfollow people around. Okay, in order to post tweets, we are simply relying on the concept or the connection between a user and a tweet, and we are combining everything based on the user ID and tweet ID. And even in the tweet, we are also associating the time associated with that particular tweet, so we can very easily put it inside the hash map. And the last thing is, in order to generate the news feed, we are working with a heap, and we are also working with iterating over any particular user. And for that user, we are going across all the people that this user is currently following, and after finding that information, going to those followers and trying to find all the tweets that they have made, put those tweets inside our priority queue or a heap, and then only fetch or poll top 10 out of this particular heap, and that should give us the generated news feed in a linked list fashion. But we still are missing one key portion. How would, in order to do these operations, how would we know that for any particular user, what are all the users associated with that, or how for user ID, what is the user ID class, and then what is the information being followed? So we need some sort of mapping structure over here as well. And for that, what we are going to do is we will first of all have to create a hash map, where inside the hash map we know that this is a key value based data structure. So as part of the key, we are going to have a user ID, and as part of its value, it is going to point to that particular user class or the user object that we have created. And once being connected to that particular user, then we should be able to find associated people that are being followed by that particular user, and the tweets that are being made by that user. And by going to those followers, we can also find their tweets and all of those things. So we are in total, we are actually using like 5-6 different data structures. We are using a hash map, we are using a hash set, we are using priority queue, we are using what do we call linked list, and we are using like all sorts of practices to make everything work together. So this is a brilliant question in my opinion. This question can help you in a lot of different ways, and that's why I spent so much time explaining all of these different concepts and different scenarios. I hope you've understood my explanation. If you still face some issues, just write it down in the comment, and I will be more than happy to answer your questions. But now I think it's time that we start seeing the coding solution for this, and it would start making more sense that why did we do what we did. Okay. Okay, so this is our Twitter class, and we first of all initialize a static timestamp, initialize the value at 0, and then we are simply going to update the value by 1, so we can keep track of the time. Now let's try to understand how does our user class looks like. As specified, we are going to have an ID for any particular user. We are also going to have a hash set where we are going to store all the people that are currently being followed by this particular user ID. And we are also going to make a reference to the tweet or the tweet class. Now let's see that for this particular user, we are also initializing a constructor where we are simply providing the value of ID, and we are also creating a new hash set for any particular user. Plus we are also adding the value of this particular user in the hash set, because a user should follow themselves. So that's a simple value. And then as a head of the tweet, or the very first element inside our tweet linked list, we are simply marking the value as null. Okay. Now for the follow method, we are simply adding the value to the hash set, this follow hash set that we have created. For the unfollow method, if the value does exist, we are simply removing that value from the hash set. So follow and unfollow are pretty simple from the point of view of our user class. And then we are also making one more method called post, where we are providing the ID, and we are creating a new instance or of a new tweet associated with this new ID that is being provided. And then we are marking the new tweet that we just created as the head of the new tweet. So we are this is just an intermediate step, but basically the tweet head is going to be the new tweet that we just created. Now let's talk about the second class, that was our tweet class that we talked about. Number one, we are going to have our tweet ID, or just like ID for this. Then we are going to be dealing with the timestamp, And since this is a linked list type of structure, we are also going to have one more node pointing to the next tweet in line. We are also going to have a constructor where we simply provide the ID of the tweet, and then we are going to add the value. We are also going to update the timestamp, and we are also going to point the next value to the null. Notice that we are already pointing to the tweet method using the user class that we have created. So we should be able to tweet for any particular user. Now we have both of our classes ready. Now we are going to generate a user map where we are going to have an integer ID as part of the key, and we are going to have associated user as part of its associated value. And now we are going to be working on our Twitter class. So first of all, we are going to initialize our initializing our hash map that we just created, and then we will start implementing all the methods that we talked about one by one. So first method is post tweet method, where we simply have a user ID and we simply have a tweet ID. So first thing we are doing is we are going to check that if in our user map, do we have this user ID as part of one of the users that we have created. If we don't have it, then we are first going to create a new user. After creating a new user, we are going to put that value inside the user hash map that we have created. And let's say that, so now we do have an existing user, and in either case, if we have, whether we have an existing user or not, we would create an existing user. Once that is done, for that existing user, we will try to find its information, and then we would call the post method inside the user that we have created. That is this method I'm talking about, where we are creating a new tweet. Okay, so this is how the post tweet method is going to work. Next logic is that we need to retrieve 10 most recent tweets in the user's news feed. So this is a complicated task. For that, number one thing we are going to do is have a linked list where we are going to be storing the news feed. We are going to check that if for this particular user ID, if we don't have it as part of the user ID, we can simply return a blank news feed. If that is not the case, we will first have to create a new hash set to store the information of all the users that are being followed by our user ID that is provided as part of the input. So we find that information. We also create a new heap or a priority queue where we are going to store the information based on the timing. So the value with higher timing would come in before, and the value with lower timing should stay on the backend side. Once we have all the data structures ready, then we are going to first of all go through every single users that we are currently following for this particular user ID, and iterating over each one of them, we will get all the tweets that they have created. So we are going to go over the tweet linked list that they have created, and if the given tweet is not null, we are going to add those values to our tweets. So now we have tweets being populated, and once we have those, then we are simply going to initialize a counter. On top of it, we are simply going to check that while the count is less than 10, we are going to go over all the tweets. We are going to add all of those tweets to the news feed that we have created, and we are going to be updating the counter. And how we are going to be able to do that? Because remember, inside our tweet heap that we have created, all the values are sorted in chronological order based on the most recent timestamp. And then once we simply check that if we find that whether count is 10, then we can simply get out of the loop if that is not the case. And if the tweet.next is not equal to null, we will simply add that value to our tweet heap as well. And that's it. In the end, we can simply return the newsfeed. So we took care of the two most complicated problems, and then working on the follow and unfollow method is quite simple and straightforward. For follow method, we are first of all going to check that if the person who is trying to follow someone else, does that person exist or not? If that person does not exist, we will create them. Same way, if the person we are trying to follow, if they also does not exist inside our hash map, we would create them. And once they both exist inside our hash map, we are simply going to call the follow method for our user, and we are going to have like follower and followee setup. Same way, in the reverse order, we would simply call the unfollow method, and then that user would no longer be followed. And that's it. That is the whole solution. I know it looks complicated that we have to create a user class, and then we have to create a tweet class, and then we have to create a Twitter class, and then we will have to generate all of these 4 methods. But if you try to think it from the perspective of like regular logic, that if you are the developer of Twitter and you are trying to improve the system, or you are trying to implement it, how would you do that? So then you would gain much more beautiful insights from this problem. So let's try to run this code. Okay, seems like our solution is working beautifully. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions in terms of time complexity. It is also excellent in terms of space complexity as well. Once again, this solution is present inside at our GitHub repository. So the link is in the description. Feel free to go and check out that GitHub repository. I know it is going to be really helpful. And let me know in the comments if you find this question interesting. Did I explain it well? Did I messed up? Or whatever your thoughts are. Okay, thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. So the LeetCode problem we are going to solve today is called find medium from a data stream. It is a very nice problem. And if we see some of the popular companies where I want to get a job who have already asked this question, there are companies like Amazon, Apple, Uber, Adobe, Bloomberg, Google, Spotify, Microsoft, Facebook, Nvidia, ByteDance, LinkedIn, and bunch of more. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also a very well-liked problem. Basically, we need to find the median from an incoming data stream. Now, in this problem, basically we are being asked to implement the median finder class. Now in this median finder class, we need to implement these 3 methods, where the first method is the median finder method by itself. Second one is a void add number, which means that if this method is being called, it will add an integer called nums from the data stream to our data structure. And third one is the find the median, that we need to basically find the median. Now let's come back to the problem statement. First, we are given the definition that what a median is. Median is the middle value in an ordered integer list. Now this is the tricky part. We are being asked to find the median from an ordered integer list, which means that the input, whatever the input comes, let's say the input comes like 11, 3, 5, something like that, we still need to find the median as if the input was 3, 5 and 11. So this is the tricky part. Like most of the people would not realize that the wording ordered integer is there, and then they will get confused. So now we have get that sorted. Now we need to see that what is the definition of the median is. Basically median is the middle value, and if the size of list is even, then which means there is no middle value. In that case, we need to find the median as the average of 2 middle values. And we are given some examples, but we are going to see this in much broader examples. So first let's try to understand this with some existing example. Suppose we are given a stream that looks like this: 1, 2, 5, 11, 15, 16, something like this. What would be the median in this case? Well, if we go based on the definition currently, well, this stream is actually an even stream, which means that there is no exactly one middle value. We are currently seeing 2 middle values in this case. And also notice that for this whole thing, I actually set it in ordered motion already. So we are going step by step. So first, this is an ordered list, that is an even list, and it has 2 middle values. So in this case, the median is going to be the average of these 2 values. So which turns out to be 5 plus 11, 16 divided by 2. So the answer is going to be 8 in this case. So second, again, let's suppose that once again the list is ordered list. So 1, 2, 5, 8 and 9. In this case, we are dealing with odd numbers. Now for these odd numbers, the middle value is quite obviously clear, and that is going to be value number 5. And again, the ordered property is still maintained in this example as well. So in this case, the answer is going to be simply value number 5. Now let's take one notch a little bit more complicated. What would be the median in this case? Since this is odd number, we know that we need to find the middle value, but in this case this is not in order. So first we will have to put this in order. So that is going to be 1, 3, 5, 8 and 15, and in this case, now since it is easy to calculate the middle value, it is going to be 5. So this would be another scenario. Now with these examples, you at least got one broader idea that how to deal with the median finder class, like when we need for where we need to first of all create a method to find the median. Second, we need to create a method to add the median, and third, we need an object of this median finder class. So basically we need to focus on these two items the most. Now the most important part in this one is first we will have to see that what would be the actual problem is going to look like. So actual problem is going to look something like this, where there can be multiple options. So first, let's say that it selects and the option is that you need to find the median. But currently if we see our list or our input data stream, let's just mark this as input data stream. Currently in our input data stream there are no values, which means if we call out this find median function, basically it is going to return 0. So this time, or return null value, actually not 0. So let's say that this returns the value null. Okay, now again we are calling add number method. So if we call add number method and we say that okay, add number 5. So in this case, currently in our data stream there is only one value, that is 5. Now we call add number method again and we add value number 6. So now our data stream has value number 6. Once again we call the add number method and we add value number 2. So in this case, currently our data stream has value number 2. And then if we call the find median method, which means we will have to find the median. Now in this case, ideally this find median method should give us the answer according to all of these examples we saw. So basically first for this data stream, it's 5, 6, 2. So we are going to put it in the ordered list, that is going to be 2, 5 and 6. And the answer in this case needs to be returned as value number 5. So 5 is what we would return over here for the find median. Now again, there can be bunch of more operations to be performed same way. So let's say that again we add a number and this time we add the number 11. So our data stream is going to have value number 11. Now if we want to find the median, then again there would be an additional bit of changes. So it would be like this would be our sorted data stream, and the median is going to be 5.5, and this is what we will return. So basically it will keep on changing. Now our job is to do this in the most efficient manner. Okay, now in this array list, what we are going to do is from whenever our main method, whenever we see add number method being called, we are going to simply push one number down this data structure. So let's say we got numbers coming in as 6, 8, 2, 1, 5. Okay, this is the sequence of numbers that came in, and then we encountered the find median method. Now again, since this is a brute force approach, we are going to take this step by step in the very preliminary fashion. So first thing that we would do is that we need to find the median of this array list, but currently this array list is not sorted. So because this is not sorted, we are going to simply sort this. Now sorting an array or array list, actually there are a bunch of different ways, but typically this can be achieved in n log n time if we use something like quick sort or merge sort, but we are not even going to bother implementing those quick sort or merge sort. What we are simply going to do is call collection.sort method. So if we call collections.sort method in any programming language, basically it sorts the given array for us in n log n time. So after that, we are going to have a sorted array, and the sorted array is going to look something like this. It's going to be 1, 2, 5, 6, 8, and this sorted portion took us n log n time. Okay, now for this 1, 2, now finding the median, it becomes quite simple, because we know that for array fetching takes big O of 1 time, and also putting the value takes big O of 1 time. We already know the size of the array, so in this case the array size is going to be 5. So because array size is 5, we know this is odd number, and since this is odd number, we need to find the middle value. So middle value has to be located at position number 3, or if we see in the array, it has to be sorted array, and the index value has to be 2. So because this is 0, 1 and 2, and whatever the value is located over here, we are going to simply return that, and that is going to be our answer. So let's break down how does our brute force solution compare to everything we have done so far. So it actually seems to do justification, because if we see in this case, the finding median is being done through two processes. First process is that we are sorting the given input, and second process is that we are actually finding the median by doing the average depending on the odd or even value. Now this case is a constant operation, so this can be done in big O of 1 time, but the sorting is actually a little bit tricky, and this takes n log n time. So overall the finding median is going to be done in n log n time, and adding number is actually quite quick, so that is being done in big O of 1 time. So if we see the total time complexity in this case, the total time complexity for this brute force approach can be considered as n log n, and that is not so bad, but we want to do it in much faster manner. So we will have to strive for something that where we can store or where we can save in terms of time complexity. Well, optimal solution is actually comprised of couple of different components, and what those components are, first we will have to find the room that where we can actually save in terms of time complexity. So we are currently taking care of finding median by using first sorting the given input, and second one is finding the actual median. Now this portion is quite easy, so we can ignore this one. This portion is the trickiest. And why this is the trickiest? Because we actually have an incoming data stream that is generating bunch of different random numbers, and we are taking these random numbers and creating them in a beautiful sorted list, and this sorted list is then being used to find the median depending on the middle values. Now since we already know that the input that is coming in at one at a time, so if the input is already coming at one at a time, why can't we design a structure that automatically sorts itself, and we are not going to need to care about the sorting property? So we already took care of one portion of it. And what would be that automated sorting mechanism data structure is? Well, you already know it. It is actually called a heap or a priority queue, where depending on the how you configure it or how you set up, you can actually configure it to have in either in increasing order or decreasing order. So no matter the sequence of numbers that are coming in at random, eventually this is always going to be in the sorted manner. So if it is always going to be in a sorted manner, then it becomes very easy for us to basically find the median, because we already know that how to find the median from a sorted property. Now there are a couple of tricky parts over here, and first let's break those down. Currently we have already decided that we are going to use heap. Now what are the trade-offs with heap? Well, the first trade-off is that if we want to insert any data, basically the insertion takes big O of log n time, right? So that is adjustable because it is maintaining the sorting property. So how it does it is that let's say that you have this initial heap that is being created, and currently this heap is empty. Now you have this one incoming value 15 coming in. So 15 comes in. So it currently, because there are no values, it puts 15 as it is. Now let's say that there is one more value coming in, and that is value number 16. So now for this value number 16, heap is not just going to append it anywhere in the sequence. It is going to see that, okay, let's assume that this is actually a min heap, which means that the topmost value has to be the minimum value, and all the other values would be greater than that. So in our min heap, basically we need to make sure that the first value remains the smallest and everything is sorted in increasing order. So in this case, because of this is a min heap, it is going to put 16 over here and 16 is going to stored over here. Now suppose we have another value coming in, and that is value number 5. Now this value number 5 is actually lesser than 16 and 15 both. So in this case, it is actually going to find a proper bucket or a proper place for 5 to be stored, and that is that it is going to do using the binary search. And we all know that binary search takes log n time, so that is why first it is going to do the binary search to calculate that where to put this 5. It calculates that okay, currently the 5 is the lowest or the minimum value, so that is why it is going to put 5 at the beginning, and it is going to take care of all the other values. So basically our heap is going to look like 5, 15 and 16. And because of this property, there is this log n time penalty that we have to pay. But this log n is actually much better than n log n because we are only doing it once. So that is the trade-off. Now I hope I was able to explain you that how does a heap work. Once we have that sorted, now let's see that will this make any improvement to our problem? Well, of course, it is going to make significant improvements to our problem. Currently, let's assume we are using a min heap. Again, using the same example, let's say that we have our data stream. Now in our data stream, assume that we have all the values coming in at random. So the random values that are coming in at the moment are going to be, let's say 1, 15, 3, 8, 9, 11, 13. Okay, these are the random values came in, but we have a heap and we have a min heap, which means it is going to take care of all the values in the sorted manner. So sorted manner is going to be, now in this case, since we have 7 digits or 7 values stored inside our heap, which means that this is odd number. So because this is odd number, we need to find the middle value. Now this is the tricky part. We know that with array, it was actually easy to fetch any value from the middle because we were able to do it in big O of 1 time constant time. But that is not the case with the heap. So fetching the middle value, it is actually going to take big O of n divided by 2 time because we are doing it sequentially 1 by 1 to reach to the middle point. So in that case, since it is taking that much time, can we do some improvements to actually find the median quicker? So now we know that what is the issue with the typical ordered list. Basically inside the ordered list, despite having all the values properly set up using the heap, it will still take us time to reach to the middle pointer, and we want to basically make this process much faster. So how do we do that? Well, one simple conclusion is that breaking this heap into 2 portions. And how do we break this heap into 2 portions is that first we are going to have a max heap. Now what does a max heap means? Max heap is going to be this portion of the given existing list. And if we notice one property in this portion is that every single element at the end of this heap is always going to be the maximum value compared to all of its peers. And this is the only value we care. Same way we would have another partition being made inside our heap, and that is going to be this remaining portion. Now inside this remaining portion, we can actually call this min heap. And why we are calling it min heap? Because the only value that is of concern to us is this middle pointer. We don't care about all of these values. We only care about this value because this is going to be the minimum value compared to all of its peers. And if, for an example, if the current heap size, or if let's say that max heap and min heap, we will try to make them exact equal in terms of the number of elements that are currently present. So let's say that in our current data stream, if the values are even, basically in that case, max heap and min heap, they are going to have even values. And in our data stream, if the values are odd, then in our case, our max heap is going to have one more value compared to our min heap, and that's it. So if the values are even, or if min heap and max heap are same in the size, then the median value is going to be the combination of, or the average of, this max and min heap. And if it is odd, basically we simply need to return this max heap value or the max element. Confused? Don't be. Let me show it to you with an example. Suppose this is our current order, current data stream. What would be the ordered list? First, let's just try to understand. So median in this case, again, that is quite easy to find. The median is going to be this value number 3, that is the middle value. And why we came up with this value number 3? Because once again, this is the total number of elements are in the odd number, so that is why it is easy to find the median. Now let's see that how would my approach work. So first, let me quickly create a max heap and a min heap. So I'm just first giving you the end result, that how they are going to look like, and then we will go step by step on how to implement that. Okay, so end result is going to be that this max heap is going to have all the values that are greater than the very first element inside the max heap. So max heap is going to look something like this: 3, 2 and 1. Actually it's going to be 1, 2, 3, but I'm giving you more general idea so that visually it is more interesting that the very first element is the element that we are looking for. So in this case, this is going to be that. And if we see it with the original list, basically we are taking care of these first 3 values. Same goes with the min heap. What are going to be the values? So the values are going to be simply 4 and 5. Why? Because the very first element is going to be the minimum value compared to all the other values. Now again, going back to our equation of the values being equal or one value being higher than the other. So in this case, currently if we see the number of values in our, okay, this MH is not the best abbreviation, in our max heap. Okay, max heap and min heap. So currently in our max heap the number of elements are 3, in our min heap the number of elements are 2. Because max heap has one greater element, the whatever the value of max heap is, or the whatever the value of the very first character in the max heap is going to be our median. And in this case, if we were to find the median, we can simply return the answer as 3. Now let's see that how step by step we are going to maintain this property. So first we have our max heap, and then we also have our min heap. Now the property inside the max heap is that the very first value has to be the biggest value compared to all the other values, and the min heap is that the very first value is going to be the smallest value. And also there are one more property, that every single value inside the max heap is always going to be less than or equal to the min heap, nothing more than that. So first we are going to enter the value inside the max heap, and that is this very first value 52. So first we add 52 over here. Currently min heap does not have anything, we took care of this value. Now the second value is value number 2. First we are going to check the size difference between max heap and min heap. And what the size difference is going to tell us is that whether the value should be added to max heap or min heap. So if we were to add this value number 2 to max heap, then the size difference between max heap and min heap is going to be value 2. So because this is greater than 1, we cannot have them, which means we will have to push one value to the min heap. But the question is which value, and that is the interesting part. So we know the property that every single value in the min heap has to be greater than max heap because of this one. So if we enter value number 2 in the min heap, will it make sense? No, absolutely not. Which means first we will have to push the maximum value that is currently present inside our max heap to the min heap. So the first we are going to have value number 52 being pushed over here, and then we are going to have this value number 2 being pushed to our max heap. I hope this makes sense. If not, try to rewatch the video for this portion and you will understand what I exactly said. So now we already took care of value number 2 as well. And also remember, because we have both the values at the same time, if we want to find the median, it becomes quite easy. We can do it in just constant time at any given moment. Because let's say I tell you that after these two values, there is a find median command. You can do it quite easily. You can just say that, okay, 52 plus 2, 54 divided by 2, I think it's going to be 27, and 27 is the answer. You can find it quite obviously. So that is why this approach is very fast. Now again, going back to our example, now this value number 3 we need to push in. Currently both of the min heap and max heap, the sizes are same, which means the value has to be entered into the max heap, because max heap can have one more value than the min heap. So 3 we know we have to push it into the max heap. Now what is the property of the max heap? That very first element in the max heap has to be the greatest element or the biggest element compared to all the other values. So in this case, because 2 is the small element, we are going to adjust our max heap. So first element is going to be 3 and second element is going to be 2. Now we took care of this value number 3 as well. Now we have this value number 5 to take care of. Again, 5 has to be added to the min heap. So if should we add 5 directly to the min heap, or should we add it to the max heap? We are going to check the very first or the biggest element inside the max heap. The biggest element of the max heap is lesser than the value of that we are trying to enter, which means 5 can easily enter our min heap. So since we are entering 5 into the min heap, we also want to maintain a property inside the min heap that the very first element inside the min heap is always going to be smaller, which means 52 we will have to move on the side and value number 5 we will have to put together, because up until this point, even if you see that what are the elements, so the original elements were 52, 2, 3 and 5. If you just want to put them in a single ordered list, the value is going to look like 2, 3, 5 and 52. And we are only concerned with these two values 3 and 5, and which we are able to make sure or use using this min heap and max heap. So that's why we are going to get rid of all of this. This was just for explanation purposes, but you get the idea that what we are trying to do. Now once again we have the value number 11 that we are trying to enter. So for this value number 11, it has to go to the max heap. What is the property of the max heap? That the very first value has to be the biggest value. So currently the value is 3, so because 3 is smaller, so 11 will go over here in the middle in the very first value. So we are going to get rid of these two, and the value is going to be 11, 3 and 2. And currently what is going to be the median value? The median value is going to be value number 11, the biggest value of our max heap. But question is, can 11 stay there? Of course not. Why not? Because every single element inside the max heap has to be smaller than every single element in the min heap, and currently we have value number 5 that is actually smaller, that is residing in the min heap, so that should not happen. So once again we will have to first before adding 11 over here, first we will have to add value number 5 over here, and then since the size differences between max heap and min heap is greater than 1, so 11 would rather going there, it would enter over here, and in this case the values are going to look like that 11 and 52. Okay, now we have the very final element 7 that we need to enter. So where should 7 go? Again, this already has one element greater, so we know for sure that 7 has to go to min heap. But 7 we are going to compare 7 with the very first element. So 7 is greater than 5, which means 7 can easily go into our min heap. And since 7 is the smallest element, we will have to make adjustments before we enter 7 over here. So the values are going to be 7, 11 and 52. So in the end, we are going to have our two min heap and max heap. So max heap is going to look like 5, 3 and 2. And the min heap is going to look like 7, 11 and 52. And now if we are being asked to calculate the median, it is quite obvious. We are just going to do addition of 7 plus 5. So our value is going to be 12 divided by 2. And the answer is going to be 6. And this is the beauty of heap. And this is why this problem is a hard problem, but also very popular problem. Let's calculate the time and space complexity. So again, for the time complexity, first we need to find that for the max heap and min heap. So insertion takes log n time, and essentially we are going to be inserting values in the max heap, min heap, sometimes from max heap to min heap and sometimes from min heap to max heap. But in either case, we are going to be achieving that in log n time. So essentially we are doing log n 4 times, and then for the one time we also have to enter the value from the data stream to one of the heap. So essentially we are actually doing the log n operation 5 times. So if you want to be very specific, you can mention 5 log n to be the exact time complexity. And plus, in order to find the median, this operation is actually constant. So that is being done in big O of 1 time. So this is a very good time complexity. Now let's calculate the space complexity. So space complexity is basically going to be big O of n, where n is the number of values that are currently present inside the incoming data stream. So here is the coding solution. First of all, we are creating our class called median finder, where we have our two priority set. First one is a priority queue named low, that is our max heap, and second one is our min heap. Now we need to create a method to add number. Basically, to add number, we are first of all adding it to the max heap. Then we are balancing the both the heaps, and then we are checking that if they both are maintaining the proper sizes or not. If not, we would pop the element and move it to the other heap. And in the end, it becomes quite easy to find the median, and that is essentially you just check the size. If the sizes are equal, then you do the average of both the lowest and the highest value and divide it by 2. Otherwise, you take the value from the max heap and return it as the answer. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs decently efficiently, and I would be posting this solution in my GitHub. So this is my GitHub repository, and you can find bunch of different solutions over here, and it is going to be quite useful. Good luck. So the LeetCode problem we are going to do today is called subsets, and we can see that this one is a medium problem and also a very well-liked problem on LeetCode. The statement is quite straightforward, that we are given an integer array called nums, and we need to return all the possible subsets of this given array. So possible subsets means every single possible values or combination of values you can make out of the given array. So let's say that we are given an input element like this, and we are trying to determine that what are all the possible subsets that we are going to be able to make. So we know that for any given n value, we can make 2 to the power n subsets. So in this case, we should be able to make 4 different subsets. Let's understand that what these subsets are going to be. So first subset is going to be quite obvious, that is going to be an empty array, nothing more than that. And because that is a subset of this by default, because if we remove both of these values, still we have an empty array which we are able to generate using this. Next way, we can also generate values just 1. Same way we can also generate value just 2, and same way we can also generate value 1 and 2. So logically, using this logic, we should be able to try to understand that what is the way we can approach this question. And what I am suggesting is that this is nothing more than a decision making algorithm, where at every given step you are making the decision on whether you are going to include that element in your answer or you are not going to include that element in your answer, and based on that you should be able to come up with these 4 answers. So let me try to explain you my approach using this example, and then we will try to understand this for a bunch of different other examples. Let's say that currently we are given these two elements as part of the input. Now in order to generate the very first subset, we have 2 options, and let's say that we are also iterating over this given input array in this fashion. So the moment we iterate over this input array 1, the very first option we have is that we should we include this 1 in our answer, or should we not include 1 in our answer. So let's generate those subsets. So if we don't include 1, we come up with an empty list. If we decide to include 1, then also we are going to be able to generate a subset like this 1. Same way, next we have the option that after this 1, now the next element in the loop is 2. So once again we have the same option, that whether we should include this 2 in the answer or we should not include this 2 in the answer. So let's say that if we decide to include this 2 in the answer, then we are going to be dealing with values 1 and 2. Then once again we still have one more option, that is because remember we are trying to build the subsets, so with every single value we iterate to the next, we are also going to calculate the possibility by removing the previous value. So let's say that we decide to remove this 1 completely, then also we still have one more option, that should we include this value number 2 inside the answer or not. So once again we will have one more subset like this, and then we have reached to the end of our loop, so we don't have any more options. So this logic gives us the correct answer of all the number of subsets that we can make, where what we did is at every given step we check that whether including that value or not including that value would result in some sort of subset, marking those subset in our answer array list we are going to create. And this answer array list is going to be list of list, because it's this array is also going to contain bunch of different array values, and where we are storing the value of every single result that we are calculating. So once again, let me try to go and explain this for a broader scenario, the solution I'm proposing, and then it should make you absolutely clear on what is the approach we are suggesting. Basically, at every single step, we are going to make a decision to whether to include that element or not, and every single answer we generate, it is one of the subsets. So let's say at this very first position, we have two options, whether to include one as the part of the answer or not to include one. So let's see both possibilities. If we don't include one, we have an empty list. If we include one, we have one value, that is value number one. Let's say we decide to go down the path of including value one. Once again, we have two possibilities, whether to include value 2 or whether not to include value 2. If we decide to include value 2, we are going to have 1 and 2. If we don't include value 2 and go to the next element, we are going to have value 1 and 3. And that's it. Now these are all the elements we have, so we won't be able to go any further, but we still have a decision to make, which is over here, that after this 1 2, do we need to include 3 or not include 3? So let's include 3. So that is going to be this decision 1 2 3. If we don't include 3, then it is just 1 and 2. That's it. Now once again, now we took care of all the possibilities with value number 1. Now let's try to work on value number 2. So once again, we have the possibility of including 2 or not including 2. We already calculated if we don't include 2, then it is going to be an empty list. So let's include 2 now. So by doing that, we are going to have one decision tree like 2. Now at this 2, once again we have two possibilities, include 3 or not to include 3. So let's decide to include 3. Then we are going to have value 1, 2 and 3, and that's it. If we don't include 3, we already calculated that possibility over here. And last one is value number 3. So once again, for this value number 3, we have two possibilities, whether to include this 1 and 2. We already calculated all of these by including 1 and including 2. If we don't include 1 and 2, then we only have one possibility, that is to have value number 3, and that's it. So these are at every single decision that we are able to generate, we are able to see that what are the values being generated by those decisions, and all of these are actually the answers or the subsets that we need to record, and that's it. This is the crux of the entire problem and the whole solution. So we can see that we are being able to generate in total these 8 values, and these 8 values are actually the answer we are looking for. Now let's try to think about that how did we generated this answer. The logic is quite simple. We do this recursively and using backtracking. And how do we do backtracking and recursively? Let's understand this with, first of all, what is the recursive pattern. So we know for recursion we need two items. First one is a base case and second one is a recursive function. So base case is quite obvious, that whether we have executed all the possibilities or we completed every single elements. So both of these base cases works perfectly fine, because at every step we would be able to generate an answer. So this is our recursive function, that whether we exhausted all the possibilities or we don't have any more elements that we need to traverse over. Now, what is the recursive function? It is also quite obvious that as long as any particular elements exist, then once again record both possibilities of including that value and not including that value as part of the answer. After doing that, once again do a recursive call back to the same function in order to check that if you include that value, then also what are the remaining values persisted. Call back the recursive function with those values. Once again, if you don't include that value, what are all the remaining values persisted? Once again do a callback operation, and if there are no other values left, then basically just do a return call. So this recursion would be able to generate the answer. Now why do we need to do a backtracking? And that is also quite obvious, because what we are doing is that we are building a decision tree. So let's say that we are given this values 1 2 and 3. So once again, we first check all the possibilities for this value number 1. So we check their value number 1, then we check value for 1 2 and 1 3, and once again we check for value 1 2 and 3. And after, at this moment, we will once again have to go back and see that did we miss out any particular element or any particular possibility that we did not check. So far we did not, we checked all the possibility over here, we checked all the possibility over here. Once again we do a rollback, once again we check, did we check all the possibilities? Yes, we did. So once again we do a backtracking and go to the next element and once again repeat the same operation. And that's why backtracking is the backbone of this problem that allows us to solve this problem flawlessly and pretty smoothly. So this is how we are going to be able to use solve this problem using backtracking and recursion, and this is, these two typically go in hand. Whenever you try to solve some problem using backtracking, most likely doing it recursively would make much more sense. We already know what is going to be the time complexity in this case. That is going to be big O of n multiplied by 2 to the power of n, because that is all the possibilities we will have to check. Now let's quickly see the coding solution. So coding solution is quite straightforward. First of all, we have our subsets class where we are receiving a nums as part of the input. Then we are generating a list of array list to store our result. And then we are going to call our recursive method that we have created, that is called generate subsets. Now we are passing in the current index, the starting index. Then we are passing in the nums array, and we are also passing in a variable to store our result. And also we are passing in a new array list or the current array list that we are going to be creating, that we would be adding at every single subset iteration. Now let's see our helper method. So first of all, the moment we enter inside our subset, we are first of all going to add whatever the current array list that we have been able to generate it so far as part of our result as a new instance of the array list. And then we are going to have a for loop that is going to simply iterate over every single index position inside our nums array, where we are going to check for the following. First of all, we are going to add the current value as part of the current iteration that we are building, which would be added into the array list or into the result in the next iteration of the recursive call. Then once again, after adding the current value, we are once again going to call the current value as part of the result, as part of the recursive call, and this is our recursive function. And after that, once that is done, we are going to be removing the current element in the next iteration. Why? Because let's say we are dealing with 5 elements, then at every given instance we need to remove one element after we are done iterating every single possibility at that value. So this is that step, and that's it. So by the end of this array, every single value should be populated inside our result array list that we have been able to create it. And at the end of this recursive call is done, we are simply going to return that value. So let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions. And also it is excellent in terms of memory utilization as well. So once again, the solution of this code is available on our GitHub repository. So you can go and check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important lead code problem, and I have provided the introduction of what are the things to expect from this video. We are going to solve the combination sum problem, and first of all I'll be showing that what are the top companies that have recently asked this question from LeetCode Premium. We'll understand the problem statement, we'll also find the optimal solution, and we will also determine that what would be the intuition behind it. We will create an example and we'll walk through it, and at the end I'm going to write a Java code. I'm going to explain it thoroughly, that how we come up to it, and also we would be explaining the time and space complexity. So first of all, these are the top companies that have asked this problem recently, and if we see from past 6 months to a year, it's eBay, Google, Goldman Sachs, and these companies. And pretty recently, Amazon has asked this question 20 times in its interviews. Facebook has asked this question 18 times in its interviews. So I highly suggest you to take a look at this problem, understand it completely, and then practice it as much as you can. This is a medium problem, and we are given a distinct integer called candidates, and we are also given a target integer, and we need to return all the unique combinations of candidates where we can reach up to the target value. Now this is a little bit tricky part to find all the unique combinations for this target candidate, because let's try to understand this with an example. So over here we are given the candidates as 2, 3, 6 and 7, and we need to reach the value number 7. So we can clearly see that 7 is already present over here, so we can return this one. The thing is, we need to return all the unique combinations. So one unique combination is 7, second unique combination, and also one more thing, we can use the same number from the candidate unlimited times. So if we apply this theory, then we can find another value that can reach to the sum of 7, and that would be 2 plus 2 plus 3. If we do that, this also sums up to 7. So we need to return a list where the two values are 2, 2 and 3, and the second element is just 7, and this would be our solution for this given problem. Okay, let's try to understand this problem with a custom example. And it is really important to create your own custom examples, because it shows that you have the ability to think outside of the box, and you can create test cases on your own. It is a really important skill to have for any engineer, and especially FAANG engineers. So we are given 3 candidates, 2, 5 and 6, and we need to see that what are all the combinations we can get out of these candidates to achieve the target value 8. Now just by looking at it, we know that the two combinations we can create is 2, 2, 2, 2. This is one combination, and the second combination we can create is 2, 6, and this would be our answer. The thing is, let's see that what would be the most basic solution we can come up with, and what would be the intuition behind it, and based on that we would be able to create an algorithm that would solve this problem. So initially we are at this position 0. Now at this position 0 we have 3 possibilities from which direction we can go. We can either go to this value number 2, we can go to the value number 5, or we can go to the value number 6, because these are the 3 candidates that we are given. And also we should not forget that the target value we want to achieve is 8. Okay, so keeping this in mind, we need to go and pick a side where we need to go further, and keep going. So again, let's just go on one direction for all the cases we can. So over here we are at 2. Now remember that we can use same element infinite times, which means that there can be one possibility as 2, 2. Of course, there can also be one possibility as 2, 2, 2. Of course, the thing is, notice that we need to put a constraint for the number of decisions we are making, and the constraint is that if at any point the direction where we are fetching all the candidates, if the sum of those can either be less than target, they can either be equal to target, or they can be greater than target. These are the 3 possibilities we can have. If it is less than target, which means that there is still room for us to find the potential combination, which means we can keep further going on that direction. If we are already at value number 8, or whatever target we are, we can directly put this value in the result. But if we and which means that we have found the combination, so there is no point in going further after we have already found the combination, because all the elements, they are only going to add up to whatever combination we have, which means that we won't be able to find another combination with the same numbers that were used to achieve this equal to. And the third option is that the value could be greater than 8. If it is greater than 8, why are we keep on going or to do more iterations and putting more strain in our computer? There is no point in doing it, because we could have infinite options, and if we do it, this would be like the best way to deplete the resources of our company. So we don't want to do that. So now, since we have kept these things in our mind, now let's see that how can we use them over here. So far the sum we have found up until this point is only 2. But the thing is, over here we have 2 candidates, and the sum we have found so far is 4, which is still less than 8. This is 6, again still less than 8. Now over here we can have one more possibility as 2 2 2 and 2, and if we do the sum of this, this is 8, which means that this is actually equal to whatever the target value we had. So we can add this to our result combination. We would have that we have already find one value in our result, and we will just add it as 2 2 2 2. This is one combination that we have found so far. The thing is, we are not done yet because we still have other candidates that we need to look at, and we need to check the possibilities. The thing is, we have concluded at least one thing so far, and that thing is we can't go further down on this path because all the values would be greater than 8, and which is not what we want. So the only way we can go is actually we can go back and see that have we missed out on any combination. So over here, the next possibility we can get is we have already used 2 as our candidate for this value 2 2 2. So the next possibility we can have over here is it could be 2 2 2 and 5, or it can be 2 2 2 and 6. So let's do sum of all the combinations. So some of these combinations would be 11, and some of these combinations would be 12. Notice that both are actually greater than the value of our target, which means that we can't go further down at any of these positions, and we have exhausted all the possibilities up until this point. So since we have already exhausted the possibilities up until this point, the only way we can go is we can go back. At this position 2, we have exhausted all the possibilities that can have. One, we found the answer, and the other two we found that it cannot be part of the combination, which means that we have already exhausted all the possibilities for this value 2 to 2 as well, which means that we can't go down, but we can go up. So over here, have we exhausted all the possibilities so far? No, there are still room, there are still other possibilities that we can check. So let's do that. So one possibility we can have over here is 2 2 2, which we already checked. The next possibility could be 2 2 5, and the next possibility would be 2 2 6. So sum of these values is actually 9, and sum of these values is actually 10. Again, both are greater than whatever the target value we had, which means that we cannot go down. So we will go back. We went back. Over here we check that we went through all the possibilities, which means that we are done over here. So we can't go down any further on this path, but we can go up. So if we go up, we ask ourselves a question that have we explored all the possibilities at this position? No. The possibilities we could have is 2 5 2 6. So let's take this value first. So at 2 5, the current sum we have is 7. 7 is less than whatever value we have as our target, which means that we still have possibilities. The possibilities we can have is 2 5 5 or 2 5 6. Notice that over here we only had two possibilities where we can calculate it from. We did not had the possibility of 2 2 5. Why? Because we already calculated it for this portion over here. Remember, in the previous iteration we already calculated for this scenario, which also shows one very important property, and their property is that out of our candidates, whatever the candidates we are given, if we are at any particular position or any combination of positions, so whatever value we have as last, we can only use that multiple times, or we can use the values that come after it. We cannot go backwards because we have already exhausted those possibilities in an iteration before this, as I showed you earlier, that this we have already explored over here, and this 2 to the 5 2 5 we are exploring at this position 2, which means that the only combinations we can make up after this point is either 2 5 5 5 something blah blah blah, or 2 5 6 6 6 something like this, but we can't make like 2 2 2 5 because we already checked that over here. So, and this is a very important property that we are going to use. Okay, at this point the sum we can have is 12, which is greater than 8, so we can terminate over here. We can't go down any further. And over here the sum would be 13. Again we can terminate over here. We can't go down, which means we have to go back. So we come back at 2 5. We say that okay, we have explored all the possibilities over here. We go back to value number 2. Now the thing is, at value number 2, have we explored all the possibilities? No, there is still one possibility pending, which is 2 6. So at 2 6, this value, the sum would be 8. Again, this is really critical because we have found a pair that equals to whatever target value we had, which means that we will add this combination to our result list. So over here we will add another entry 2 6, and after adding this, we have explored all the possibilities after this point, which means that we would go back. Now at this position 2, we have explored all the possibilities it could have, and because we have explored it, we will again go back to our 0th position. The thing is, we are still at 0th position, so can we stop now? No, we can't stop because we still have a whole lot of possibilities that we haven't touched so far. Because remember, over here we still have this 5 and 6 pending. So let's see that what could be the possibilities over here. Now at 5, again we can only have two possibilities. As explained earlier, we could have either 5 5 or we could have 5 6. So let's do the sum of these values. So 5 5, the sum is actually 10, and 5 6, the sum is 11. Both are greater than 8, which means that we can terminate over here. So that concludes that at this position 5 we ran out of the possibilities. We went up. At this position we are done. So again we go back. At 0th position. We check that do we have any other options where we can explore, and yes, currently we are at value number 6. So 6 is again less than our target 8, so we can go further from 6. The thing is, at 6 we can only do 6 6. We can't do any other combination because those we have already checked so far, which means that 6 6, the value is 12. So 12 is already greater than 8, which means that we can't go further from this, which means we can't go further. We go back. At 6 we see that have we explored all the possibilities? Yes, we have explored all the possibilities, which means again we go back to this position 0. So at this position 0, we check that now have we explored all the possibilities? Yes, initially we check all the possibilities for the value 2, again we check for value 5, and again we check for value number 6, which means that even at 0th position we are done. So our base case has satisfied. Now whatever we have stored in our result result list so far, we can simply return this, and this would be our final solution. And this is actually the optimal solution that we can achieve. Notice over here that we are doing lot of repetitive work. At any position we were calculating the different possibilities we can have. We are picking a possibility, we are exploring in that direction, depth first search. We kept on exploring. Once we found a terminating case, we would go back to a point where we can still explore for more possibilities. Over here again we would further go down to additional possibilities. We would find a terminating case. Again we would come back, and eventually we would come back to the 0th position from where we started, and after the calculation we will return our result. So this, where at any point we are coming back from where we originally started. This is actually called backtracking. This is a really important concept in computer programming, and I just showed you that how can we use it, and that is why, because this concept is really important, it has a lot of very practical applications, and that's why you see that why all those big companies like Google, Facebook, Amazon, Goldman Sachs, they were interested in asking this question to their candidates, because they want to know that are you familiarized with very important things that are really critical, and can you go down that path. And yeah, so since we have found our optimal solution, I did not mention explicitly that I was showing you the optimal solution, but the thing is, I told you that this is the intuition behind it. And once we knew the intuition, we just need to find a way to implement it in computer programming. The way to implement this, you must have guessed it correctly, that we were doing so much repetitive work again and again, and we were using it somewhere, and we had some terminating conditions that either if the value is equal to or greater than our target, we would terminate, which means that we were using recursion at its best over here. So yeah, this is basically our solution. So let's calculate the time and space complexity. That time complexity for this one would be big O of n to the power t. Now first let's determine that what this n and t means. N is actually the number of candidates and the least value for this one, and t is actually the total amount. Because imagine that what could be the longest sequence we can have at any given position. Well, suppose our target value is 8 and our candidate is 1, which means that we would do 1 plus 1 plus 1 up until 8 times till we get the value 8, which means that we need to go in one direction 8 times, and at any position we can have multiple options or we can make multiple decisions, and from further down we can go ahead, which means that we need to do this work n to the power t times until we find the solution. So that's why this is the time complexity. So first of all, we'll create our result list, and now we'll create a list to store the current combination. Okay, now we'll create a backtrack method, and in this would be our recursive method. So initially we are going to provide the target result combination 0 as the starting point and the candidates array, and after whatever the result we get back from that recursive call, we simply need to return whatever we find in this result list. So let's create the recursion method. Okay, so first of all we are going to create the terminating cases. So if target is equal to 0, which means that we have find a combination that sums up to the target value, so we can just simply return it to we can simply add the combination to our result. If this is not the case, we need to return we need to check that whether the target is less than 0, which means that we have already surpassed our target and we need to break, so we can just return null. If both cases are not true, which means we still need to look for our combination. So we'll start by checking in our combination from the position start, and we'll go until we still have candidates. Now inside the loop, first of all we will add whatever candidate we are currently looking for in our combination list. Okay, after that we can do our recursive call, and as a target we will have target minus whatever candidate value we found. and start would be ith position. And I think that would be it. Yeah, one more thing, we will have to remove the entry from our combination list because we will be doing backtracking when we move towards the next value. And I think this would be it. Let's try to run the code. This should have worked, but I don't know why it's not working, so we'll just enter the value manually. Oh, it should be candidates. Okay, our solution seems to be working. Let's try to submit the code. And yeah, our solution works perfectly fine, and I would be posting. Now the LeetCode problem we are going to solve is called permutations, and we can see that this one is a medium problem and also an extremely well-like problem. The statement is quite straightforward, that we are given an integer array called nums of distinct integers, and we need to return all the possible permutations that we can make. And for good thing for us is that we can return answer in any order. So first let's try to understand this with few examples. Let's say that in the input we are only given one element, then we can only generate just one permutation. So this is what we need to return. But if we are given more than one element, let's say 1 and 2, then we can actually generate two permutations in this case. First permutation is going to be the same value as it is. In the second permutation, we are going to have the values being flipped around between 2 and 1. So these two are the permutations that we need to return. Let's take one more example. Suppose in the input we are given the values 1, 2 and 3. Then we can basically calculate that we should be able to make 6 permutations in this case. Why? Because for any particular given numbers, you can make n factorial permutation. So in this case we are given 3 elements, so 3 elements is going to be 1 multiplied by 2 multiplied by 3, as in 3 factorial. So in this case the answer is going to be 6. Now let's see that what are all these 6 elements are going to be. Well, so these are all the 6 permutations we can make. Now logically this is nothing more than a decision making element or decision making algorithm, because over here we can see that if we have to make permutation of this element, let's say that I have 3 blocks where I can fill in values. Now let's say for some reason I decide to put 3 in the first block, then I know that I still have 2 values where I need to fill out something, but the thing is I can only fill out between this value 1 and 2, not this value 3. So once again I can repeat the same process, and let's say randomly I decide to pick value number 1. So now for this last element I only have just one possibility, and that is to fill in this value number 2. And this, the moment it reaches to the length of this previous one, we can determine that this is one of the permutation that we can store as part of the answer. Now after storing this, we need to check that whether keeping this 3 over here at the beginning, are we leaving out or being done with all the permutations? No, there are still possibility of permutations left. Let's say that we decide to eliminate this value number 2 over here and this value number 1 over here. Now once again, keeping this 3 on this place, once again we have the option that instead of selecting 1, we can actually select 2 over here, then we will have 1 over here, and this would be a new permutation. So visually this is very simple to understand that how does this function, but the thing is implementing this is slightly tricky. So what I'm suggesting is that we actually use the same algorithm that we just saw, but we apply it using the logic and possibility and concept of backtracking. Plus on top of it, after using the backtracking, I also suggest that we use a recursive approach to recursively recall the same function with different inputs. And why am I suggesting this is because number one, we already know that we are repeating the same process. All we are doing it is that the input we are given, we are picking one value in, we are marking that particular value with one of the values, and for that let's say that over here we have 1. So once again now we have two possibilities. First possibility is that on this place, for the second place, we can fill in the value 2 or we can fill in the value 3. Once again, let's say if we decide to fill in value number 2, then we are only left with just one possibility for this last element, that is this value number 3. And this whole path defines one of the permutations. So this we will be able to mark as the answer, and then if we decide to go down this path, once again the values are going to be 1, 3 and 2. So this is going to be our second permutations, and once again we can mark this answer as well. So now let's say that what are the things we need to solve this problem and how we are actually going to be doing that. I just explained that we are going to be using backtracking plus recursion. So let's say that what do we need for our backtracking function? The idea is quite straightforward, that we will keep on going in one direction until we reach to the length of the given input. Once we reach to the length of the given input, we will mark that entire path in as part of the one of the answers, and we would put it into our list of lists that we have created to store our answers or results. Once doing that, the idea is to once again do a backtrack, and after doing the backtrack, once again see that what is the potentially different path that we could have taken, and once again once we reach to the answer, we basically store that answer. Now there are two critical parts in this case that we will have to consider. Number one thing is that we will need to know at some point that what are the values we have already calculated and what are the values we have not calculated so far. So what I'm suggesting is that let's say you decide to put 1 over here, then I would need some sort of way for my computer to tell me that this 1 is already part of the function. So for that I'm suggesting to use a used array, or like array named use, and the moment we add any particular value inside the current consideration for our recursive function, we are going to mark this used function as true or false. So this would be my used array of boolean values, and currently I would mark that this is true, which means I'm currently considering 1. Then once again, let's say that now I know that through my used array I only have 2 more possibilities left because this 1 has already been filled. So for the next element, I'm going to consider this value number 2, and once again I'm going to mark this value 2 as being used as one of the decisions. After doing that, once again I'm going to mark this value 3, and then I'm going to mark this 3 as being used. But the thing is, because I reached to the end of the list, so the moment I reach to the end of the list, I can mark this answer 1, 2 and 3. And after marking this answer, I can actually go back, and I can go back in time with my recursive function and say that over here, instead of using 2, now I have decided to take another path where I'm going to be considering 3 as part of the input. And in order to do this one, I will need to constantly update this used array. That is number one thing. Second thing is, in order to calculate this path, I will also need to have a current array or array list to store this path as well, that these are the values we are currently iterating. And the moment we identify that we have reached a new answer, then for the next iteration of the recursive call, I simply need to regenerate the entirely new array. So I know my solution might confuse you a bit, but let me just give you this with like using 2 examples. So let's first quickly take the example of simple 1 and 2 values. Okay, the logic is that we are going to have a recursive function that is going to store. So for the recursive function I did not explain, but basically for the recursive function we need 2 items. So we need a base case, and we need that what is going to be our recursive call. Base case is quite straightforward, that the moment we identify that our given current n or the current length of the given input is equal to the original n of nums, then we have found the correct path. In this case, we would mark the current path inside the answer, and after marking that, we would basically return. So this is going to be our base case. Now for our recursive function, the idea is quite straightforward, that we are going to pick one element right now, and through that one element we are going to be marking the used array for that particular element to be true, and then we are going to call the recursive function once again with the remaining portion, because we still haven't identified all the values. Once we identify all the possibilities and we receive an answer back, then we are going to eliminate the last element we had inside our recursive function to be turned out to be false, and keep on repeating that in order to calculate other possibilities. So let's first see for this example. The idea is that first of all over here I have 2 possibility. Let's say I mark number 1 element as being used, and I have a current list where I'm going to store that what is the current path I'm taking. Okay, I took 1. Now I'm once again going to call for the next element. So now I call for the next element, that is obvious choice 2. So I mark 2, and now I know that my length of this current has reached to the n. So I'm going to mark this as part of the answer 1 and 2. After doing this, once again I'm going to do a backtrack call. During the backtrack call, I'm going to mark this 1 as not being used and 2 as not being used, and then I'm going to be iterating over this given input in this fashion. So I already took care of this element, and now I'm going to start taking care of this element. So now I have my 2 as being used. Now I have my new current instance being created where I'm starting the path from 2, and I'm going to go down to the next path. So I only have one possibility, that is to add value number 1. So I'm going to add value number 1 over here, mark 1 as being used, and because this n is correct, so once again mark the another answer as 2 1, and now I have my answer that I was looking for. So after this, I realized that in my existing loop I already be done through all the elements inside the given input. So which means now whatever I have in the answer, I can simply return that. So now if you want, you can directly go to the coding approach if you already understood what I meant. If you didn't understood, then let me also do the same iteration for this path as well, and once again repeat the same procedure. So logic is, we are going to be iterating over every single element one by one. That is number one thing. Next thing is we are going to have our current list or the current values we are iterating over, and we are going to have our used array where we are going to be storing that which are the elements we have already used so far in the current iteration, and we are going to be updating the values one by one. So let's say that in the current path I add value number 1, so I'm starting the path from value number 1. After 1, I decide to add value number 2 as an input. So once again I do that, and after this 2, I add value number 3. So the moment I add value number 3, my length is equivalent. So I'm going to store the answer 1 2 3. After storing this, now once again I do a recursive call. So I basically break out, so which means I will have to remove the last element I added. Still keeping 1, I still have one more possibility that I haven't tested. So once again I'm going to mark 3 as being visited. So now I'm going to take one more path, and by the way, this is going to be a new instance where currently the nodes I have visited are 1 and 3, and next time I'm going to be visiting the value 2 because that element is left over here. So once again I'm going to be marking 2, and I'm going to have one more possibility 1 3 and 2. Once again now I do a backtrack. So backtracking would make sure that I took care of 3 over here, I took care of 2 over here, and all of these things are done. So now my used array is being backtracked to all the way to the beginning. So now once again I'm going to repeating the same process, but now this time with value number 2, and keep on doing this recursively until we reach to this very last element 3, where we have all of the 6 possibilities calculated, and this is the whole solution. So now let's quickly see the coding solution, and that would make much more sense. Now first thing we are going to do is that we are going to create a new array list which is going to store our results. So now you can see that this one is an array list that stores different array list inside. Then we are going to initialize our used boolean array in order to keep track of that what are the current elements we have already used. And then we are going to have a helper method called backtrack, where as an input we are providing our result that we have calculated so far. Then we are going to have a new instance of an array list where we are going to be storing the current elements we are iterating over. Next, we are going to be passing in the given input nums, and lastly we are going to be passing in the new array used array that we have created. Now first we are going to be checking for the base case, that if the current size is equal to the length of the original given array, then we are going to add the results of the current array list inside the new instance of a new array list, and we are going to be doing a simple return. If that is not the case, then we have our for loop that we need to iterate over. So very first thing we are doing is that we are starting from the 0 and iterating I until we reach to the end of the array. Then we are first of all checking that if the given I value is not used, then we are going to be adding that value inside the current path that we are iterating over. So we added that. Then we are going to be marking that particular element as true inside our used array. And after that, we are going to be calling our backtrack for method recursively, where once again, we are simply providing the results that we have calculated so far, the current path, which now contains a newly added element, and the nums input, and the used array that now contains that the current element is being used. And that's it. Basically, this should ensure that all the work gets through, and the moment the list size is correct, then we would start adding those values inside the result. But the thing is, after the backtrack call, we will also have to remove the lastly used elements. So we are going to be doing that, and we are also going to be removing that value, the very last value that we had in our current list. So we are always updating that in order to calculate new possibilities. And this is the whole solution. Now I know it's hard to visualize, but coding is very small, and also you can understand that how to generate it on a pen and paper. So you can just work around with different examples and it would make sense to you. Now let me quickly run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs super fast compared to all the other solutions, which means this is an excellent approach. Now I know using an extra used array might hamper with our space complexity, but this is still a much faster result. So now I will be posting the solution in our GitHub repository, so you can check it out from there. Thank you. Now we are going to be solving the problem subsets 2. Now this is very similar to our original subsets problem, but there is a slight difference. Now we can see that this one is a medium problem and also a very well-like problem. The problem statement is that we are once again given an integer array nums that may contain duplicates. So we need to return all the possible subsets. Plus we are told that the set must not contain duplicate subsets. So there is only just one tiny bit of difference. Now let's first understand that what does a different subset means. So let's say that we are given an input array like this, then the number of subsets it can contain is going to be 2 to the power of n. So where n is the given number of elements. So in this case we have 2 elements, so we can expect that 2 to the power 2, which means 4 subsets we should be able to create. And these 4 subsets are going to be an empty list, a subset only containing value number 1, a subset only containing value number 2, and a subset containing value number 1 and 2. That's it. So this is the whole solution. But the thing is, I know we just solved this problem in like our subsets problem, so if you want you can check it out from there. The thing is, in this case, the only difference is that let's say that we are given a value like this where the input may contain duplicates. Then this changes our equation a bit, because in this case we need to only return the unique subsets. So in this case, if we want to create the number of subsets, definitely we can create 2 to the power of n subsets. The issue is that we can create a subset, we can create like an empty subset, then we can create a subset with just one. But once again, if we try to create a subset with this 2, let's say, then we can also create a subset like this 2. And if we were to put both of these in the answer, then there would be duplicated entries. So we only need to just pick one. So that is number one thing. There can be one more duplicate in this case, and that duplicate could be that we can create a subset like this, value 1 and 2. And we can also create a subset like this where value is 1 and 2. So if such kind of situation occurs, then we need to take care of that scenario. So basically making sure that whenever we have duplicated entries, we just have to keep them aside or not consider them for the current part of the subsets. Now we all know that what was the strategy we used in order to calculate the subsets. Let's say that we only have just 2 values given and we are trying to generate the subsets. Logic is quite straightforward. We are going to be using the backtracking. On top of it, we are going to be using recursion. Now what is going to be logic for our backtracking? That while after calculating every single path for every possible subset, then we are going to be doing a backtracking and once again repeating the same operation. What do I mean by that? Let me just explain. So first of all, we are at the empty list position. Now over here we have the possibility to include this value 1 or not to include this value 1. Same way we have the possibility to include this value 2 or not to include this value 2. Let's say that we decide that we are not going to include both of these 1 and 2. So in this case, we can create a subset like this, like an empty list, and we will mark this as part of the answer. So let's say that this blue line indicates that we already marked it as the answer. Now, once again, after marking this answer, we still somehow needs to go back and revert our operation. So in the previous choice, we decided that we are not going to select this value number 1, but now let's say that we do decide to go ahead to select this value number 1. So once again, we can create a subset where we are only selecting the value number 1. So once again, this is also part of the answer. So I'm marking it with a blue line. But after doing this, once again, we will have to do a backtrack and see all the possibility. So we already exhausted all the possibility of selecting one and not selecting one. But the thing is, we haven't exhausted all the possibility of selecting 2 and not selecting 2 along with this one. So let's say that along with this one, we have the possibility that whether we select 2 or not select 2. So we not selecting 2, we already calculated. But now we are calculating one more possibility where we are selecting 2. So we have values like 1 and 2. Okay. After doing this, we can do a backtrack. We check all the possibility at 1. Once again, we check everything so far. The thing is, we haven't checked the possibility of only considering 2. So once again, we are simply going to be considering 2, and this is going to be our backtracking mechanism. On top of it, this is also going to be our recursive function that I just explained, where for the recursion we need 2 items. We need a base case and we need a recursive function. So for the base case, it's quite straightforward that whenever we create or we make any single decision, we simply add it to the answer, and this is our base case. After this, for the recursion, we go back to the next recursive call with that selected value or not selected value, and once again repeat the same process for the next upcoming remaining elements inside the array. So this already makes sense. We already do this. But the only issue in this case is that we simply don't want to consider, let's say that we are given values 1, 2 and 2. So now in this case, once I'm making the decision, let's say I put down the empty array, then I put down a list with 1, right? Now at this 1, I have 2 possibilities. First possibility is that I'm going to be considering this 2, and second possibility is I'm not going to be considering this 2. So let's say I decide to consider this 2. Then I should be able to create an input array like this, or like a new subset like this. Once again, let's say that I go to and let's, for a simplicity, let's assume that this value is currently 3, okay, not 2. So if this value is 3, then I create one possibility where I'm considering 2. I can also create one more possibility where I'm not considering 2, which means there can be a subset like this 1, 3. But in this case, rather than this value being 3, this value is also 2. So it's the same value. So if I try to do this possibility in this case, then I'm just stuck. I'm left with only this value. So what I can simply do is that I can take the given input. Let's say the given input array is like this, but it right now it is already sorted, but it is possible that this may not be sorted. We could have given values like this. So once again, if we want to do the solution, what I'm suggesting is that whatever values we are given, we simply sort those values. So let's say we get a nice looking values like this. After sorting, all we simply do is we check that at any given moment, whenever we calculated a possibility with this 2, now we are trying to calculate another possibility. We just check that the current element we are considering for the possibility, if that element is same as the previous element, then we just don't consider that possibility. That's it. This is the whole solution. So now what would happen in this case? We will have an empty list. We will have value with 1. Now we will have one more subset with 1, 2. Now after this 1, 2, we still have 2 possibility whether to include this 2 or not to include 2. So let's say that we decide to include 2. So then we still have one more subset like this. So we also consider that. After this one, we are doing our backtracking by removing the last element added. We do the backtrack. We don't need to calculate this one because we already know that it's the same element. We go back to 1. We check all the possibilities with this 1. So now we are at this position number 2. So we decide to include 2 only. This is a new subset. We add it to the answer. Now after at this 2, we have the option that whether do we need to add this value or not to add this value. So this value is quite straightforward. It's 2, 2. It's a new subset. So we haven't calculated that. So we can simply add this one. Now after calculating this, once again we do a backtrack. Now at this backtracking location, now our time is to move to the next element and not consider this one. But once again, while making a decision for this one, we check that whether it matches the previous element. Yes, it matches the previous element. If it matches the previous element, what is the point of considering this for the subset? So we are not going to do that. And that's it. This is the whole solution. And if you see the coded approach, it would make much more sense. Plus you already know that how does the calculating subsets work, because we already saw that in the past, that the whole explanation and the whole 9 yards. I just re-explained the whole thing, and I also explained that why we are adding this tiny logic to our already beautiful solution. Now let's quickly see the coding approach. So very first thing we are doing is creating a new array list where we are going to be storing the results. Then we are simply sorting the given input array. And then we are calling our backtrack recursive helper method where we are passing in the new result, where we are going to be storing the array list of lists. And we are passing in the new instance of the array list to store the current list that we are iterating over. Then we are going to be passing in the given input nums, and we are also going to be passing in the starting index where we are looking at. So initially we are starting from the index 0, so we are just going to pass in 0. Now let's see our helper recursive method. First thing we are doing is whatever value we have in the current list, we are adding it into the answer. So during the very first call, we are adding just an empty list into the answer as well. Next, we are running a for loop from the start to the end of the given array. Plus, we are just checking for a very simple condition that if the given input I is greater than start and the current element is equal to the previous element, if this is the case, we simply continue. If this is not the case, then we simply add the value to our current array list. Then once again we call our recursive function. After the call comes back from the recursive function, we remove the very last element added inside the current array list, and then we repeat the same process until we are done with the entire for loop. And this should populate our results completely. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs beautifully, faster than all the other solutions, and also best in terms of space complexity. So once again, the solution is present at our GitHub repository, so feel free to go ahead and check it out. Till then, thank you. Now we are going to be doing an awesome LeetCode problem that is called combination sum 2. This is the subsequent question to our original combination sum problem with some slight tweaks. Now we can see that this one is a LeetCode medium problem, but in my opinion, this can be categorized as hard problem sometimes as well, because combination sum in itself is slightly tricky to understand. And we can see that this one is a very popular LeetCode problem, also being asked at tons of companies. Basically, we are given a collection of numbers called candidates, and we are given a target number. Now we need to find all the unique combinations in the given input array such that the sum of those values is equivalent to the target value. There can be more than one results, so we need to consider all of them. Now we are told that each number in candidates may only be used once in the combination, and we need to make sure that the given solution set must not contain any duplicate combinations. Okay, so now let's first try to understand this with an example. We are given this candidate array and we are given the target value to be 5. Now next thing is that we need to generate the unique sets. Now let's see that what are all the combinations that can generate this value 5. We can see that we have value 4 and we have value 1. So 4 and 1 is a combination that can sum up to value number 5. So that this can be one of the potential answers. Next one is we have value 2, 1 and 2. So once again we can generate value like this, and this can also be an answer. Next value is that we can do 3 to 2. This is also one of the subset that can generate the answer. But now there is one problem over here. We also have this 3 that we can utilize with this 2 to once again generate the target value 5. The thing is that value is also going to be 3 2, which we have already entered in our result. So we should not be reusing the same set in our results, because we need to make sure that this answer becomes unique. So if we, by considering these elements, we can only generate these 3 values or these 3 sets that combination to the total value 5. So we need to understand that this is how we need to solve the problem. So now let's try to see that what could be the potential solution over here. Now, the logically, the very first thing that it would make sense for us to do is that instead of treating all of these weird values side by side randomly, it would make much more sense to, number one, sort the given input array. Why am I suggesting to sorting the given input array? That has two reasons. Number one reason is that let's say that we have some values like, let's say 10 and 15 and then so on and so forth, like 100 other values, okay? And we are given the target value to be 5. So the moment we reach to a value 10, then why do we even have to check possibility for all of these 100 values if we have already sorted the results? We know that all the values sum is always going to be greater than 5, which means it is going to be shortening the reach we will have to search for. That is a good benefit. Second benefit is that it will allow us to handle the duplicates in a more elegant manner. So what I'm suggesting is that let's say that in this case, we have the values 1, 2, 2, 3 and 4. This is the input we are given. Now, what we are doing is that logically it's very simple. We are just simply making decisions. And what is the decision we are making? We are iterating over the very first element. Okay, so let's say that we are currently passing through value number 1. We know that the target has to be 5. But our current sum that we have made so far is just value number 1. So we will need to add some more subsequent values. So let's say we decide to add value number 2 down this current path. So now the sum is 3, still less than 5. So once again, we decide to add value number 2. So after adding this value, our sum becomes 5. So the moment our sum becomes 5, whatever the values we were currently having as part of our path, this is one of the potential answers. So let's mark this as part of the answer. Okay, that we currently have found one of the combination 1 to 2 as part of the answer. After doing this, there is still more possibility that we could have some other value that we might have missed on. So we will have to backtrack and once again see for other possible answers. So let's say that we do a backtrack at this position number 2. And once again, now the problem comes because this next element is already 2 and we just did a backtrack. But the thing is, we already considered this 2. So now we will have to consider value number 3. Okay, so let's say if we try to do this one, this current sum becomes 6. So the moment current sum becomes 6, we know that this is no longer a viable solution, which means we will have to do a backtrack because this solution is leading to a value greater than 5. And once again, we will have to repeat the operation for all the other remaining possibilities. So we remove value number 2. So once again, now with this value number 1, there might be some other solution with 1 and 3 that we could make. So we try to add value number 3. After this value number 3, the current value is 4. After 4, we add value number 4 over here. So doing this also brings our sum greater than 5, which means we will have to do a backtrack. We do a backtrack and we get rid of this value number 3. Now at this value number 1, we still have possibility to check for value number 4. There is still one more decision we haven't made. So let's say we do this one. The sum of this is actually 5, which means we found another set that corresponds to our correct result and our correct instinct. So we are going to mark this as part of the answer as well. Now, once again, we know that we took care of all the things we could using this value number 1. So now we are simply going to go to the next element and not even consider 1 because we ran through all the possibilities we could with value number 1. So we don't have to worry about it. Now at this value number 2, let's say, let me just clean this up a bit. Now we are making a new decision tree, a new decision path where we have 2. Once again, we go to the next element, that is once again 2. After doing this, we go to the next element, that is 3. So now this sum in total becomes 7. So 7 is greater than 5. If 7 is greater than 5, going down this path 2 does not make sense. So we are going to ignore that. Ignoring this, we are going to be going with 3. So we are at this juncture and we found that current sum is 5, which means this is one more potential answer that we will have to record. So let's mark this one. Okay, marking this, we are not done yet because we may still find another results, we don't know. So we go to this next element 2 to 4, but this also leads to result number 6, which means we calculated all the possibility at this current 2 as being the very first element where we are calculating. Now the thing is, next element is also value number 2, and we can see that with previous element 2 we already calculated all the possibilities. So if we had a target value, let's say instead of over here instead of 5, if we had a target value 4, we would have a potential value 2 that is being generated by this 2 already. So we don't have to do anything over here. And also if we try to go down this path, let's say that we ignore my advice for now, and we say that currently we took care of this one, we took care of this 2, this 2 is still valid and legitimate. So now we have this value number 2. Once again we go down to the path, so we find value number 3 as the next potential match, and this matches. So should I add it to the answer? No. Why should I add it? Because I already calculated this one. So what I'm suggesting is that once we have the sorted list, we simply check that for any particular element that we are trying to iterate over in the recursive manner using our backtrack function and recursive function, we first check that whether if it is the same element as the previous element. If that is the case, we already calculated all the possibilities and added to our answer, so we can simply ignore that. So now we are all going to be ignoring this 3 as well. Now we are left with this element number 3. So let's try to make possibilities with this 3, and we are just going in one direction. We are not going in the opposite direction because we calculated all the possibilities. So with this 3, the only possibility we have is to add value number 4. The sum is going to be 7, so greater than 4, which means this leads to no result. So we already calculated all the possibility as 3 as well. Now next is the only element 4. Once again, if we calculate the possibility, there is only going to be just element number 4, which is not 5, so we cannot put it in the answer. After this, we are done with all the elements in our input, and this is the answer we need to return. So now let's do a quick recap. What we did, we calculated that what was the backtracking function, and we also calculated that what is going to be a recursive approach. For a recursive approach, we need two items. We need a base case and we need a recursive call or recursive function. We know that what is going to be our backtracking logic, that at every possibility, the moment we either reach to the target value is equal to 5 or target being greater than 5, in either case we are if it is 5, we are going to be adding it to the answer. If it is greater than 5, then we are going to be going to the very previous element that we were iterating over and remove that from our current list and follow along with the remaining possibilities. That is option number 1. For our recursive, the logic is quite straightforward. Base case is going to be that the total sum of the current elements that we are iterating over, it's either 5 or greater than 5. If it is equal to 5, we add it to the answer. If it is greater than 5, then we can simply just move forward or jump to the next element. And for the recursive function, we are simply going to go in a normal fashion by adding the current value and removing the current value from the given input array, and just making a recursive call by adding a new value that is next inside our given array. So if we see the coding solution, it would make much more sense, and this is, in my opinion, a very beautiful solution. So I hope you understood what I was trying to explain. Now let's quickly see the coding solution for this one. So here is the coding solution. First of all, we are generating our result where we are going to be storing the list of array list. Then we are sorting the given candidates array. Plus we are going to have our backtrack recursive method where we are going to be doing backtracking and also making recursive calls. And so now let's understand our backtrack method. So first we are passing in the result list that we just created. We are also maintaining a current list. We are also maintaining the candidates array that we are iterating over. On top of it, we have provided our target and we have provided our start values. Okay. Very first thing we are doing is checking that if the given target is equal to 0, then we are going to be adding the current list inside our result, and we are simply going to do a return from our current recursive call. If that is not the case, we will run our for loop where we are simply going to iterate over all the values that are currently present inside the candidate. Very first thing we are doing is skipping the duplicates. So we are checking that if the current candidate is same as the previous candidate, we can simply ignore that value. Next, we are also doing an early termination if the sum becomes negative, because at every given moment, the moment we see a new ith value, we subtract that ith value from the given current target element, and the moment we realize that this is going into the negative, we are simply doing a break operation. Now if that is not the case, we add the current value to our current array list that we are maintaining. Then we once again make a recursive call with the current value, which contains one more value right now, and we provide the target minus candidate psi because we are subtracting the value from the target that we need to achieve, and we update it with the next element inside our for loop, and that's it. Now once we get a result back from our backtrack, we simply remove the very last element, and we once again do the same operation for other possibilities that we are yet to calculate. So this approach should work. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions, which is pretty good. So once again, I would be posting this solution in our GitHub repository, so you can go and check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do word search lead code problem, and if we see the number of companies where I want to work at who have already asked this question, there are companies like Amazon, Twitter, Microsoft, Uber, Bloomberg, Facebook, TikTok, Snapchat, Google, Apple, Samsung, Roblox, Goldman Sachs, ByteDance, and eBay. So these are really popular companies, and this problem is really popular because it has very real life applications. We have all played games like crosswords and Wordle on our phones and on the newspapers and different kinds of stuff. So that is where this problem is associated with, and we are going to see that how to solve this one. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given an m cross n grid of characters called board, and we are also given a string called word. Now we need to see that if this word can be created based on whatever the number of characters we are given on this board, and if it does, we need to return true, else we need to return false. Also, we are given a note that the word can be constructed from letters sequentially adjacent cells, where adjacent cells are either horizontally or vertically neighboring. And we are also told that same letter cell may not be used more than once in order to create that word. So let's try to understand this with an example. Over here we are given this big board, and on this big board we are told that we need to find the word A, B, C, C, E, D. So if we see over here on these marked values, so this starts with the word A, the neighboring word is B, the neighboring word is C. Again, we are told that we can horizontally or vertically see the words. So if we go vertically downwards, we see another C, and then we find another E, and at the end we find D, which is also adjacent to E, which is this letter, and this is basically part of this given board. So in this case we can return true. Now suppose if this word if we were not able to construct this word, we would not return true and we would return false. So let's see that what would be the optimal approach to solve this problem. Well, we have actually solved similar problems like this in the past using DFS and backtracking, and this is what we are going to do for this problem as well. Let me quickly show you how. Okay, so suppose this is the custom example we are given, and we need to find the word spider to see that whether it exists on this given board or not. And the idea is actually quite simple. What we are going to do is, first of all, we are going to take the first character inside this word, which is S, and we are going to iterate over this matrix until we find this first character. The moment we find the first character from whatever the place is, then we will keep on trying to find the next letter, the next words inside this word, to see if it exists in the neighboring node or the neighboring cell of the board inside this given matrix. And if somehow we are able to reach to the end of this word, we can return true. If we don't reach the end of the word and we actually reach the end of the matrix, we can return false. So the idea is actually quite simple, and there are just few tweaks we will have to use in between. So first we will start iterating over this matrix, trying to find this word number S. Now this is not S, this is not S. Over here we find the first value as S. So because this is the first value as S, now we will have to try to see that whether this P exists or not in the neighboring node of this S. We can clearly see that P exists. But before doing that, what we are going to do is we are actually going to mark this node as visited. So one way to do is to use some visited hash set and store all the values, but that is just causing strain on and to have an extra memory usage. Rather than doing that, we are going to actually modify this input and we are going to mark it something like hash or something, which is an invalid value and it can never be there. So which means at any point we encounter that this value is hash, we don't need to go back to that place. Now we will start iterating over the neighbors of this s. So neighbors of s can be these three places. If we try to look at these three places and we are looking for the alphabet p, so p is present over here, which means that so far we have found s and p. Now we will update our value to I and we will try to look for I in this p's neighbor. Also we will mark this node p as like hash, so we don't come back to this place again. Now this p has only two neighbors because this neighbor s has already been visited because its value is hash, so we can't do anything about it. Now we are looking for this letter I and we find the letter I over here, which means again we will mark this as hash. We will update the value of word we are looking for. The word we are looking for now is D. We'll try to find the neighbors of I and in the neighbors of I, okay, we don't find anything over here. This is not D and this has already been visited, which is hash, which means that there is no neighbor of I that contains this value D, which means that now we haven't found the word so far and we still have matrix to go to that we haven't visited so far, which means that now we will backtrack from this I to the position we were originally at, which means that from this I we came from P, from this to this P we actually came from S, and now we can say that okay, even in this S it does not lead to us to find this word, and then we will again proceed with our search. So again we are trying to find this letter S again and not the D because we did not find anything in the route, which means that now okay, this P is not S, this I is not S, this T is not S. So we are good so far. Now at this position we find a letter S, which means that okay, this S has been found. Now in the neighbor of this particular cell we will have to find the letter P, and we are going to mark this S as hash as a way to identify that this has been visited. Now what are the neighbors of S? These four are neighbors of S, and the one value we can find where the P exists is this one. So again we will repeat the same process. We will mark this as a hash. We'll try to find the word I we will find over here. So again we will mark this as a hash and we will try to find D in the neighbor of this I. So we find D over here. So again we will mark this as hash. We will go update the word we are looking for, and now we will try to search for E inside this these neighbors, and we can find it over here. Again mark this and then try to find this R. So R we actually find in the neighbor of this one, and this is the correct R, which means that now we are able to reach to the end of this word list, and we can return true in this case, saying that okay, this actually exists inside this given board, and we will be good. So this solution works perfectly fine. Let's see the time and space complexity with this one. So for the time complexity, actually the time complexity is a little bit tricky to find. Why? Because the time complexity is actually big O of n, which is the number of cells. So for every single cell we will have to iterate at least once. So n is given, but then we will have to repeat the same process for 3 times to the length of L in the worst case scenario. Why 3 times to the length of L? Because notice that at any single position, suppose we were at this position number D, and we need to see that okay, whether the next value E exists or not. So we need to check 3 places, not this one, because this already has the value hash, which means we won't check this one. But in theory we might have to check at all 3 places, and imagine if all 3 of them had the value E, we might have to explore the paths on all 3 of them in order to find the next value R. So that is why at every single position N we actually have 3 different options to see that whether this word exists or not, and this L is actually length of the given word. So that is why this is the time complexity. In terms of space complexity, we actually need to store the value inside our space until the time we reach to this entire word. So it would be big O of L, where L is the length of the word that is given. And this time and space complexity works perfectly fine, and I hope this solution makes sense to you. Let me quickly show you that what would be the coding for this one. So for this word search problem, we will actually have to create a backtrack public method that will call itself, and recursively we will try to achieve its answer. So there are some variables that we will need in both in this boolean exist method and also in the new backtrack method that we are trying to create. So let me define some variables that are global and that we can use in both the methods. And the variables we are going to create is to store the value of this board, and we will also need the row and column size of this given board character array. Now we have these, we will assign values to all these three variables from these given input endpoints. Once we have this, we will have to iterate over this board character array. So we are going to assign two for loops, and for both the for loops we are going to have the I and j value iterate up until the point of this rows and columns, and inside this for loop we will call our backtrack method. Now inside this for loop we are going to call our backtrack method, and we are going to have backtrack method return a boolean reply either true or false. And inside the backtrack method we are actually going to pass in the values of the current row position, current column position, word we are trying to find, and the index value we are currently at. So for the index value we would initially start with the position 0 and we would increment it every single time inside our backtrack method. And if at any case this returns true, we can simply return true in this case. And somehow if we are able to complete this loop and get out of it without returning true, which means word does not exist, so we can return false. Once this is done, now we will create our public boolean method called backtrack. Now first of all we will check that what is the condition where we will need to return true. So if at any point we identify that the index value is actually greater than or equal to word length, which means that we have already found that the current word already exists inside our given character array, so we can return true in this case. So now we will try to find the terminating conditions, and inside the terminating conditions first of all we will check that whether the row and column position are they going out of bounds or not. If they are going out of bounds we can return false immediately. If that is not the case, we will try to see that the current value we are looking at inside our board, if that value is not in sync with whatever the index value of the word we are looking for. If that is not the case, we can also return false immediately. So if any of these conditions are true, we can return false immediately. None of these conditions are true, which means that the current index value actually matches the value of that row and column position inside the board, and now we will have to iterate over the neighbors of this current row and column value inside the board. So in order to iterate over the values of the row and column, we are actually going to have two arrays called row direction and column direction, and that will help us navigate all the neighbors of any particular cell. Also, before moving to the next element, we are going to mark the current row and column position to have a value called hash, so we avoid checking the same element twice. Okay, once this is done, we will also have a boolean variable called return, and initially we are going to initialize its value to false, because basically we are going to call the backtrack function for all the four neighbors of the current cell. So for that we will keep track of this ret variable, and we are going to run a loop to iterate over all the directions, and we will add the values of these row direction and column direction to subsequent row and column positions inside this recursive call to our backtrack function. We will also update the value of the index, because we can determine that we have already find the word inside the previous index, and that's why we are calling the next index value to be searched inside the neighbors of any given row and column position. And also at any point, if we identify that the answer of this return function is actually, or this return variable is actually true, we can break out of that particular element immediately, and we don't have to check all the other neighbors. So we will put that condition as well. Once that is done, basically we are done with the checking part. Now the only thing we need to do is we will have to update the value of the row and column position to whatever the value that was originally there, and in the end we can simply return whatever the answer we got for this ret function. This is pretty much it for both our backtrack method and also our main method, and this should be able to solve our problem. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code, and our solution works as expected. And I would be posting this in the comments so you can check it out, the solution from there. So the LeetCode problem we are going to solve now is called palindrome partitioning. We can see that this one is a medium problem, but in my opinion, this should have been a hard problem. We can see that this is a very well-like problem. Now let's understand that what is being asked us to do. We are given a string S and we need to partition this string S such that every single substring of that particular partition becomes a palindrome, and we need to return all possible palindrome partitionings of S. So it sounds a little bit awkward, but let's try to understand this with an example. First, let's understand that suppose we are given a string S such that the values are A, B, C. So we can see that in this case, if we have to partition string, there are a bunch of different options. We can have a partition that is completely like this, or we can do a partition like A, B, and C, or we can do a partition like A and B, C, something like this one, right? There are a bunch of different ways for us to partition any given string. But the thing is, in this case, we need to find partitions such that every single partition becomes a palindrome. Now we all know that what is the definition of a palindrome. Suppose we are given a value like this ABA. In this case, this ABA is a complete palindrome. Why? Because if we write it from left to right or right to left, in both the cases, the answer is just going to be ABA. So same way, this let's say if this is the input we are given, and if we have to partition it in such a manner that every single substring of that partition becomes a palindrome, we only have one possibility. That possibility is if we partition it by using just individual characters, because an individual character in itself is a palindrome. Because let's say if we only have one value, you can read it from left to right or right to left. In both the cases, we are going to be left with the same value. So this is the only answer we need to return in this case. But let's say that we may have been given some other options. Let's say that our given string S is equal to values such as A, then A and B. Okay. Let's say our given string S is equal to values A and B. So now in this case, we will have two options in order to generate the partition. First partition is going to be quite straightforward, that is taking on individual characters because they are palindrome and their own, and combination of these characters actually form in such a manner that every single character is a palindrome in itself. But we can make one more distinction or one more answer in this case, where if we create a partition of these two values A as one partition and we create another partition of this individual character B, then also this becomes a valid partition of the substring such that every single portion of the partition actually forms a palindrome, because this AA is a palindrome and this B is a palindrome in itself. So this is what the problem statement is actually asking us to solve. Now let's try to understand some logic on how we can actually solve this problem. Well, if we just have to solve it using pen and paper, what is going to be the first logic you are going to apply? Well, the very first logic is that we will start iterating over this given string character by character, comparing every single character with the previous characters that we have been able to find so far, to determine that whether using the combination of previous characters are we able to generate palindrome or not. If we are able to generate a palindrome, we would mark it as one of the partition and then we will keep on moving forward. So let's try to understand the approach I'm suggesting. Let's say over here we start iterating over at this very first element A. Now for this very first element A, the moment we come to this element A, we have two choices. One choice is that A in itself could be a palindrome. So we mark A as a palindrome, And same way, there could be another possibility that we may find some value where this A could be potentially part of some future palindrome that we are yet to discover. So let's leave this possibility open for us for the moment. Okay. Now, if we decide to create a partition based on A, then once again, we have the option to move forward with a single A or the next element. So let's say that once again, we decide to move in with a single A and create another partition, which this is the first partition and this is the second partition. Okay. And once again, we move to the another value. And for this next value, we encounter value B. So once again, we create a partition in its own. Now the thing is, when we reach to this B, we realize that now we have reached to the end of our array. So far, all the values we find inside or all the partitions we did for our given string S, all of these values are palindromes, because let's say that in order to determine that whether any particular string is a palindrome or not, we are actually going to create a method that checks that if the given string is a valid palindrome or not. Okay. And this string is quite straightforward. They are the values of itself. So we know that all of these values are correct palindromes, and we are also storing some current array list where we are keeping track of all the current values that we are iterating over one by one. So we realize that this is the correct sequence of partition that generates a palindrome. So we are going to mark this option inside as part of our answer. After marking this, we are not done yet, because once again, I mentioned that there could be some potential ways or some potential other paths that we are able to generate, which could lead us to more palindromes that we are yet to discover. So once again, let's try to apply that same logic in this case. So now, once again, we already explored this path. Okay. Now what we are going to do is we will do a backtrack operation once again to the very first character to make sure that maybe we did not miss out some palindromes that we could have found. So let's say that we, instead of just creating a single value partition, from this single value, we actually decide to do a partition of two values. So creating a partition of two values would give us value AA. Once again, we check that if is this a valid palindrome or not, and yes, this is a valid palindrome. So we are good to continue to the next element. For some reason, if we identified that this was not a correct palindrome, let's say for some reason that this value given is X, so then this AX is not a correct palindrome. If this is not a correct palindrome, then it does not make sense for us to continue down this path of partitioning. So then we would choose a different path where after this AX, we would actually include B in our decision making as well. But there is no need to do that. So let's leave it as it is right now. So after leaving it as it is, okay, so we created another partition at this moment AA. The answer is valid, legitimate. So we are keeping it as it is. After keeping this as it is, now we decide to go to make another partition, that is this value B. So once again, we create a single partition of just one value B. This is also a palindrome. And with this B, we reach to the end of our list. So after reaching to the end of our list, we are also going to be marking this sequence that we found as part of the answer as well. Now let's try to clean this up a bit. And now once again, we are yet to explore more possibilities that we haven't found. So we will also try to do this one. Now for the more, initially we took down a possibility where we are only partitioning the string based on just one value. Then we partitioned the string by using values A, and then also it worked out. Now we are going to partition the string based on considering all three values. So let's say that we just create a partition that is A, and B. This is definitely not a palindrome, plus we reach to the end of our list. So now we are done with our search with starting all the possibilities from this current value A. Now we are yet to identify more possible palindromes that we are yet to identify. So let's say that in the very first beginning, when we made this partition, now we will continue down this path, but previously we went down this path that was this answer over here. Now we will try to choose a different path, and in this different path, what we are going to do is with this A, now we are going to pass the baton on to the next element, and now we will say that, hey, next element, if you want to do or try some partitions, let's check those. So once again, from this A, we can create another partition like AB. But Definitely, this partition is not a palindrome. So if this is not a palindrome, then it does not make sense for us to continue down this path. And anyways, we are running out of elements in this case. But let's say if we had some more elements over here, let's say some more element like say C. So do you think it would make sense for us to create a partition such that A, B and next element to C check like this? No, because we already know that this is not a palindromic substring. So why even bother checking? So then in that case, our logical step would be to include C as part of one of the possibilities as well. But once again, this is also not palindrome. So now we can be done with this. So this is the simplest approach we can take to solve this problem. Now we all know that what we did. We use the backtracking option to basically go through all the possibilities that we can in order to generate or find sufficient answer. Now let's try to understand that what has to be the logic of our backtracking function. This is going to be a simple function that takes the current partition that we are dealing with, and based on the partition from the input string, it is going to have a starting index for the next partition that we are going to check with. And with the starting index of the next value, we should be able to understand that are we at the end of our string or not, and whether we can conclude the current partition to be over or not. On top of it, with every single value, we are going to check for any particular substring that we are generating, that whether that is a palindrome or not. And in order to do that, in order to accomplish all of this, we will actually use recursion. Now for recursion, we know that we have two items that we need. First one is a base case and second one is a recursive function. Base case is quite straightforward, that if I previously mentioned that we are going to have a variable called start to keep track of the next index. That would be the starting point of the next sequence of palindromes. Let's say that we created a subsequence like this, AA as one of the palindrome, then start index would be living over here with value number 2, as that is the logical starting position. So we are going to check that if for the current list we come to a place where the starting index is the length of the given string, then we are going to be marking that current index as part of the answer and returning or coming back through our recursion. So we identified our base case. For the recursive function, we will have to do two things. First thing is that for every single new partition we make, we will have to check that whether this one is a valid palindrome or not. If let's say that is a valid palindrome, then it would make sense for us to call the recursive function once again with the next value in line and creating the current partition as it is. Now I know it sounds confusing, but if you just understand that or try to walk over the solution that I presented, then it would make absolutely beautiful sense to you that what I'm suggesting. And on top of it, for the recursive function, we are also going to be updating the current index value that we are iterating over. Let's say that we iterated over AA. So then we will have a recursive function starting with value number B. And once again, we will try to repeat the same process. Combination of all of this should give us the answer. But thing is, this is not just enough. Once we receive a call back, and we will have to check for other possibilities, where first we check for the possibility of A only, then we may have to check for the possibility of AA. So in order to do that, we will have to do a backtrack. And for the backtrack, the simplest thing is to remove the very last element we added inside our current array or current array list, and once again repeat the same operation. So basically combination of backtracking and recursion is the way to move forward in this case. Now let's try to calculate the time and space complexity. Well, time complexity is difficult and tricky to calculate in this case because we don't know that how many number of potential partitions we can make. So at the end of the day, this is simply a decision making algorithm. And in the decision making algorithm, at every given step, let's say that we created a partition like this A. Now we will have to check whether to include this A or not to include this A as part of the partition. So at every given step, we are checking for whether to make that decision or not to make that decision. So basically we have 2 to the power of n possibilities, where n is the number of characters given. And for every single character we will have to repeat the same operation. So it's going to be n multiplied by 2 to the power of n possibility, and that's why this is a very expensive operation. And if you go through the LeetCode problem, we are only given like up to from 1 to 16 as part of the range of n for the length of the string, because they also realize that they don't want to put much load on the LeetCode servers. So now let's try to quickly see the coding solution for this one. Okay, so the very first thing we are doing is that we are generating a new result array list that is going to store different array list inside it to store our answers. Then we are going to have our backtrack method where we are passing in first of all the result array list we created. Then we are also passing in the current list we are iterating over, passing in the given string that we are given as the input, and we are passing in the starting value of the next pointer that we should consider for the partitioning. This is the starting pointer that I just mentioned. Okay, now first of all, let's see in our recursive function, we are going to have our base case where we are first checking that if the starting value is the length of the given string, which means we are actually reached to the end of the string, so we can add the current result we are iterating over inside our result array list, and we can simply do a return call from the iterative stack. And now let's check our recursive case or recursive function. So for that we are basically iterating over from the starting index till the end of this list, and we are updating the value. And here I mentioned starting and ending pointer. This is just simply so that we can check that the given palindrome or the given sequence of element partition we are iterating over, if that is a substring or not, we can simply make that call. So first thing we are going to check is that if the given current substring, is it a palindrome or not. For that we have created is palindrome method where we are doing nothing but we are simply iterating over from both ends, like starting pointer and ending pointer. If at any given moment we identify that there is a mismatch, we simply return false. If that is not the case and we complete the whole iteration, then we can simply return true, saying that this current substring is a palindrome. Okay, after determining that the current set of partition is a palindrome, we are going to add that substring to our current list that we are maintaining. And once again, we are going to recursively make call with the same values except the next index position that we will have to iterate over, and that is going to be our end plus 1. You can also define this end instead of end to be I as well. I just put in end for it so that it becomes better readable for our is palindrome method. And once we get a result back from our backtrack method, we are simply eliminating the last value we inserted inside our current list, because we still have to explore more possibilities. And this is our backtrack function basically. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to 98% of all the other solutions, which is exceptionally good. Once again, the solution of this code is presented on our GitHub repository, so you can go and check it out from there. Thank you. Hello friends, hope you are having a fantastic day today. So in this video, we are going to do a very popular LeetCode problem that is going to be pretty nostalgic for a lot of people. So without any delay, let's get started. The title of this problem is called letter combination of a phone number, and now many of the iPhone users won't know it, but in the past phone actually did used to look like this, where if you have to type any messages, you will need to do it according to the keys that are present over here with the corresponding numbers. And people were so good that they were able to do it without even looking at it. But anyways, now coming back to the question, this is a LeetCode medium problem and also an extremely well-liked problem on LeetCode. Also has been asked at tons of popular companies. So let's see that what does the problem statement ask us to do. Basically, we are given a string containing digits from 2 to 9, because notice that in this problem, we are only given the characters from A to Z present between the letters 2 to 9. Now, inclusive, now we need to return all the possible letter combinations based on the given digit numbers, and that it can be represented. For our convenience, we can return them in any order. So let's try to understand this with couple of examples. Suppose we are given as an input just character number 4. So how many characters does this character number 4 can represent? Well, only 3 characters. So if we have to return this, the answer is going to be G, H and I as the answer that we need to return. But let's assume that instead of that, we are given the input as like 4 and 6. Then what should be the answer? So we know that 4 can represent G, H and I, and 6 can represent M, N and O. So the answer is going to be the combination of both of this GHI and MNO. So the answer would look something like, where you can see that currently we have 9 entries and they are combination of all the characters from these two entities, and that's what we need to return. So this is the whole problem statement. So let's try to see that what is the approach we can take to solve this problem. Now, number one thing is that currently we are only given characters between 2 to 9 as an input and nothing else. So first thing we need to do is that we will have to create a mapping so that based on any given input location, we can actually identify that if the character 2 is given, we know that it can only have the possibility of storing ABC. Same way, if character number 9 is given, then it only has the possibility to store 4 characters W, X, Y and Z. And same way, we can store this in any such fashion so that this lookup needs to happen in big O of one time. So we actually have two options to do that. Number one option is that we can actually create a hash map, and inside the hash map we can store all the entities, and based on the key we can mark as the digits, and their subsequent values we can mark all of the entries. So that is option number one. This will yield in big O of one time complexity whenever we have to do the lookup. Second option is, since we know for sure that we are only dealing with characters between 2 to 9, nothing more, we can also create an array, and inside the array, based on the index positions, we can store the values. So let's assume that because in the array we have values like 0, 1 and then 2 and all, so on and so forth. So for 0 and 1 we can store as an empty strings, because anyways they are not going to be part of our inputs, and starting from position number 2 we can start storing values as A, B, C and stuff like that. Now this is only for our convenience purposes, so that we can quickly look up what element we are trying to find. Now this is the pre-work that needs to be done in the solution so that we can do it in the efficient manner. Now let's see that what is going to be the optimal approach to solve this problem. Suppose as an input we are given the characters 2 and 3 that we need to return. Now we know that 2 is represented by ABC and 3 has been represented by DEF. That we actually take this given input 2 and 3, then we break this input based on all the digits it currently has. So first we get the digit 2. For digit 2, whatever the characters that it can represent, we create 3 decisions trees based on that. So currently it can represent A, B and C. So we create 3 separate decisions tree. And now, since this is not the answer, because we need to return the combination or the potential combinations that can be there. So this is just a part of the answer that we have created so far. But now we will have to complete the combination portion. So in order to do that, the number one thing we will need to do is to keep track that how many number of characters are currently present, or how many number of digits are present and how many are pending. So now 3 is pending. So we will append 3 with each of these decisions trees, and we know that 3 is currently represented by these 3 values. So once again, for each one of them, we are going to have 3 separate decisions tree being made. Notice that currently at this very first location 2, we only had 1 entry per character inside our representation. But the thing is, in the input we were given 2, 3, 23, which means we were dealing with 2 character letter. But in the problem, we are only at half of the step, where we only have just 2, which means after creating this possibility, we still have to wait to add the values to the answer until we find this path where now the index position matches the total number of inputs that we are given. The moment this condition matches, we will need to add it to our answer list. So because over here we only had one characters, but now we had two characters, and even in the input we were dealing with two characters. We are going to add DA or AD in the answer. Same way AE is going to be part of the answer. Same way AF is going to be part of the answer. And the good thing about this is because this is same operation being done multiple times, so we can actually keep on doing this. The moment we find out that this is one of the potential pair that we have already added to our answer, we can actually backtrack to see if A still has any more values that it needs to add to the answer. And yes, AE still needs to be added. So we will add AE. Once again, we will backtrack to A, and once again this AF needs to be added. So we will do that. Once again, we would backtrack to 2. Now we have completed all the path with A. So we will repeat the same process with B. And this is the whole answer we need to return. Now I know what I just explained might have confused you a bit. So that's why when we do go into the coding section, I will explain the whole thing in much more clarity. But this is the whole approach. Basically, we are simply using recursion and backtracking to solve this problem, because repeatedly we are doing the same operation. And we know that for this we need to have an terminating case. So terminating case would be that the moment we identify that one path or one combination contains the same number of characters as the number of input that is given or the index values, then we need to add it to the answer and once again do the backtrack, keep on repeating the same process until we have exhausted all the possibility, and whatever the answer we found, we need to return that. Okay, so what is going to be the time and space complexity in this case? The time complexity is only going to be the number of potential combinations that can be made, which means the number of characters that are given. So let's assume that this currently has 3 times 3, 6 characters. So whatever the value is, so we need to do square of the number of given input for every single digit. So in total, it is going to be the number of combinations that are currently present. That is going to be the time complexity. For the space complexity, because we will have to create another array that contains all the mapping from the characters 2 to 9, we will have to store that. But that is going to be limited in scope. So instead of calling this as big O of n, we can actually treat it as big O of 1, because the space complexity is not going to change. So now let's see the coding solution. Okay, so first of all, we are going to initialize our string array, where we are going to mark first couple of entries as blank, and then we are going to mark all the values. So this is going to allow us to iterate over all the digits to the letters. And then let's start our code actually for the problem statement for this method letter combination, where we need to return a list of strings as the answer. So first we are going to initialize a combination string that we are going to return as the answer, and this is going to be the blank array list so far. Now first we are going to check for an edge case, that if the given number of digits is equal to null or digit.length is equal to 0, then we simply need to return combinations. If that is not the case, we are going to call our backtrack method, and we are number one thing, we are passing this list that we have created. We are also passing the input digits that we have received. We are passing an empty string that is going to be considered as the current combination that we have so far, and we are passing in 0 as the current index values that we have processed so far. Okay, now let's see this backtrack method. How does it work? So number one thing we are checking is that if this given current index location, if that is equal to the digit length, which means we have an answer that we need to add to our current combination. So we are going to add all the answer that we have found in the current combination to our combinations array list that we have created. If that is not the case, we are first of all going to differentiate the letters for every single index position. So let's say in the input we are given value number 2, then we would have ABC as the letters passed on. And then we are going to run a for loop across every single letter. But now this time we are recursively going to call back the method backtrack. We are passing in the same combination, same digits, but for the current combination, we have added the current combination plus the current letter we are working on. On top of it, we have also updated the number of increased value, index value. So if in the previous iteration, if we would have passed in value number 2, in the next iteration, we would have passed in value number 3. And that's how we will be able to start storing all the combinations in the current combination array string that we have created. And this is it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. and our code runs pretty efficiently compared to a lot of other solutions, which is awesome. By the way, you can always find this coding solution in the GitHub repository we have, and the link is in the description, so you can check it out from there. Thank you. Okay, so now we will attempt to do a very scary question that is called N queens. Now, in my opinion, this is one of the most toughest and most interesting problem I have seen. Basically, this one is a LeetCode hard problem, and very justifiably. It is also an extremely well-liked problem, and let's understand the statement. The N queen puzzle is a problem of placing N queens on an N cross N chessboard. So if we are given, let's say, 4 by 4 chessboard, we will have to place 4 different queens. Now we know that every single queen can iterate in 3 directions. Let's say that if I decide to place a queen over here, then this queen can control these squares, and these squares, because queens iterate in all 3 directions. So based on considering a formation such that I am able to place 4 different queens, and without these queens intersecting with each other on a given n cross n board, and I will have to make sure that I populate all the n queens. Now let's see that what else is being asked for this problem statement. That we are being told that we are given an integer n that defines that what is going to be the size of the board we are dealing with. Now we need to return all the distinct solutions to the n queens puzzles, and good thing for us that we can return the answer in any order. Now there is also one more just a quick note, that each solution contains a distinct board configuration on a place where the queens can be placed. Let's say that if I decide to place a queen over here, then next queen might be placed somewhere over here, because I need to avoid hits by this queen. So there can be one solution or 2 solutions or 3 solutions, no matter how many solutions are there, where I can place all 4 queens on this 4 cross 4 board. I will have to put all of those solutions inside the answer. Next thing is, we are being told that where we are placing the queen, we will mark it as cube, and where we are not placing a queen, we will just mark it with a dot. So let's first try to understand this problem with this given example of a 4 cross 4 board. The idea is we are trying to place 4 different queens on this board, and we will have to explore all the possibilities we could in order to generate the answer. Now this is going to be a very long video, so I'm just warning you beforehand. I don't want to take any shortcuts, and I want to make sure that I understand this problem and you understand this problem. So now let's get started. Basically, let's start one by one. Let's say that I put the first queen naively on this very first location. If I do that, which means essentially I am eliminating all of these squares for any other queen to pursue and use it as for their configuration. Let's say I put this queen. Now in order to put the second queen, I have 2 options. So let's say randomly I just pick this option. Okay, so once again, after picking this option, also these squares are now being controlled by this queen. Next thing is, if I want to put another queen, there is no place for me to put the third queen, because this entire row has been covered because I put this queen over here. So let's try to revert that. Let me try to put this queen somewhere else. Okay, so let's say if I don't put this queen over here, then all of these squares would become empty. And once again, let me just try to put this queen on the second position and then try to see. So let's say if I put this queen over here, once again these squares gets controlled by this given queen, and now I only have one option in order to put the third queen. So I can put third queen over here, but that controls this option, which means once again I cannot put 4 queens over here. So once again I will have to go back, I exhausted all the possibilities for the second row, which means I still have to exhaust more possibilities at the first row by changing the position of this queen. So let's try to do that operation. For that I will have to clear the board and basically do a backtrack operation. Let's do that. And now I'm trying to place queen over here. Now which are the squares being controlled? Let me just quickly mark each one of these to make sure that I don't create any confusions. Now for the second row, I only have one possibility where I can place my queen. So let me do that, and let me also mark all the items that are being impacted by this queen. Okay, Now for the third row, I only have one option. So let me also place one queen over here and once again exhaust all the possibilities. And now for the fourth row, I only have one choice where I can place the queen, and that is this empty square. So now we can see in this case that we are able to place all four queens on a 4x4 grid. So this is one of the potential solution. So we will actually have to mark this entire solution and place it inside our answer array. So the thing is, let's say that we create a list that is going to store all the answers. How we are going to take the snapshot of this is that we are actually going to create an array that is going to represent every single row for this given entire section, and for each of the row we are going to mark it as this, that we are going to store string values, where for the first two elements we don't have a queen, so we are going to mark them by dots, and then we do have a queen, so we are going to mark it by queen, and then we are once again going to mark it by dot. Once again we are going to do the same process, so queen and then dot dot dot. Once again for the next element repeat the same process, so basically 3 dots and then a queen. And for the last one we are going to have dot queen and dot dot, so dot queen and dot dot. Okay, and so this becomes one of our answers. The thing is, this is not the whole answer. We could still have more potential answers. So let's say we explored one possibility. Let's try to explore another possibility. And remember, once again, we are doing the backtrack operation, going back to the very initial call. We already exhausted these two possibilities for the position of queen. So let's try to explore more paths. Let's say if queen is over here, then once again let's repeat the same operation. We are going to eliminate all the squares being controlled by this queen. The option is to place it over here. Once again eliminate all the options. Once again we can place a queen over here, and for the last one we can place a queen on this position. So once again this becomes another one of distinct answer, because notice the positioning of queens are different compared to our previous answer. So once again we are going to note this entire answer. Now don't worry, I will not put you through the painful process of going through the whole thing. Let's say that I just paste this answer over here as part of the next array list inside our answer, where we are going to return the list of array list. Okay, and now let's say we try to explore the very last option for the queens. Once again for the very last option we are going to be placing the queen over here. If we try to do this one, basically this solution would not work, because we would not be able to find appropriate queen positions in order to fill it out. So notice that in this case once again we filled out all these four possibilities because we placed a queen over here. If we don't do that, if we decide to place a queen over here, then once again we are eventually going to fill out all of these possibilities. So these are the only two distinct ways through which we can place all four queens on this 4x4 grid, and this is what we will have to return as part of the answer. So this is what is being asked us to solve. Now the thing is, let's see how we can actually solve this problem. So notice at the very beginning when I selected a queen over here, immediately I did not started rejecting this option. Basically what we can do is that at every single position we have two options to make, that whether we can place a queen over there or we can not place a queen over there. Now we will have to explore both the possibilities, and in this case we will proceed in column by column area. So we will try to put the queen on the first column. Based on that we will it will determine the position of the second column, and then third column, and then fourth column. So initially the idea is going to be that for the very first column on the leftmost portion or the very first value, we will try to place queen. And let's say that after placing this queen, our logic would be that we will have to find an empty space in this particular section where the squares are not being hampered by this queen. We can completely ignore this entire column the moment we place queen at one of the position. So our jumping is going to be based on column by column level, and at every single column for all the n values we will have to determine that whether it is a sufficient place to place a queen. And the moment we find the very first opportunistic moment where we can actually place the queen, once again we are going to repeat the same operation for the next subsequent column, and once again we will try to find an appropriate cell where we can actually place the queen. So there could be two options. One option is that let's say that we are able to identify some place where if we just take a look at this example, basically in this example, if I place a queen over here, we exhaust all the possibilities. Now there are no place for us to place a queen, which means immediately it should come to our brain and also in our program that placing queen over here is not a good idea. That is option number one. Option number two is that placing queen over here is not a good idea. So we are going to do the backtrack operation, and after backtracking we will first try to remediate our this mistake, and we would, instead of placing queen, we would place at the second possible place, and once again try to repeat the same operation. But eventually this will also not yield us the correct result, and eventually we would keep on backtracking to our very first decision. And through the very first decision we would try to make sure that, okay, instead of placing the queen over here, let's try to explore other possibility, and then this would lead us to our correct result. So that is number one thing on we can understand that how we are actually able to find the answer. The logic is quite straightforward. We are simply going to do a recursive backtracking call in order to determine that whether the given path is a correct sensible path or not. But this is not as simple as it sounds, because there are a lot of computation and a lot of things we will have to understand and break down for our program to that how it is going to work. So let's quickly understand first that what is going to be the recursion we need to do in this case to complete the problem. Well, we know that for recursion we need two items. Number one item is that a base case, and second item is that we need a appropriate recursive function. Base case in this case is quite straightforward. The moment on the C4th column we find an appropriate location for the queen, we know that we already crossed all of these columns, and then we reach to the column 4 where we are able to find an empty slot for a queen to be put in. So which means this has to be the complete correct path that we are able to generate in order to fill the answer, and that is exactly what we are going to be storing as part of our base case. So what we will do is, number one, we will need some way to keep track of all the paths that we have taken so far, because by doing that we are doing two things. Number one thing is that when we do reach to that happy path scenario for our base case, we can actually add the path that we have stored for so long for the positions of queen as part of the one of the values for the answer. So that is number one thing. Number two thing is that using this path, let's say at some moment we decide that we cannot go further anyway, then once again we can just say that this path does not yield to the correct result. If it does not yield to the correct result, we can simply do a backtrack operation, and through the backtrack operation we will try to explore other paths. So just same way we saw over here that this queue location was not working out, so we tried to see for this queue location. Once again that didn't work out, so once again we updated from our queue location this one to this one, and then we try to identify that whether this is the correct path or not. So we made some judgment calls through our recursive function on what are the things we are trying to achieve. Basically, don't get confused. We are just doing exactly the same thing that I showed you on throughout the entire graph. The only difference is we are trying to do it recursively, and we are trying to follow both the things, that what is going to be the base case where we need to break out of the recursion and store the value to the answer. If we are not able to do that, then we will also have to do the recursion using the current path we are choosing in order to solve the problem. Now there are also few more things that we will have to understand. First thing is that at every given moment, whenever we are checking for potential candidates, we will have to understand that whether this path we are taking, if that is the correct path or not. Because let's say that in this case I place a queen over here, which means I am eliminating these elements that can ever be used for the potential queen. So now when I am at the column 2, I once again going to check all of these positions one by one, and in order to check that whether they are good candidates or bad candidates for my queen to be placed over here, I will need some method to basically do a validation that whether I can place my queen on this square or not. And the only way I can check is that is to check my current path that I have currently iterated over and see that this particular cell, has it being impacted by any of the queens that I have previously placed. And by doing that, we can actually make sure and find the potentially good values for our queen. So let's say that we identified potentially good values for our queen. So we did this operation for this first column. Then once again, we repeated the same operation for this next column. Once again, we are going to repeat the same operation for this third column. So logically, we are just redoing the same thing that we have done in the past, but for the different input. And that's where the second requirement for our recursion comes into the place, because remember, recursion needs two items. First one is a base case and second one is a recursive function. So as part of the recursive function, whenever we are moving to the new column, we are simply updating the value of the column, plus we are also updating the value of where we have stored the queen in the previous value inside our current path. So this will allow us to do the backtrack and also allow us to move to the next value inside the logical iteration of our recursion. On top of it, that's why this is a hard problem, because there are a lot of on top of it that you will have to understand. At every given moment, once we reach to the very end, in the current path, we are not keeping track of all the items of the board. We are just simply keeping track of the position of queen that we have placed so far in each of the columns. So once again, we will have to have a method where we are actually generating the board based on the positioning of the queen. So remember that ugly board that we are seeing, like that contains dot q dot dot, then once again like dot 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 q, and this type of like Morse code type of structure. We will also need a method to generate this as well. And this is the solution. Basically, this is the optimal solution in order to solve this problem. We are using backtracking, we are using recursion. For recursion, we have a base case, we have a recursive function, we are keeping track of the current path we are at. We need to have a method to check that whether the given path is valid or not, to place the queen based on the previous queens we have placed. Plus we will need a method to generate the board that we need to generate in order to solve the problem. And in the end, we need to store everything in an answer, where in the answer we are actually storing the bunch of different arrays as part of the array. So it's going to be an array list that contains multiple array list. And if we try to calculate time and space complexity in this case, well, it's really difficult to calculate the time complexity, but let's try to understand the time complexity logic in this case. If you can understand this, then your logic to solve time complexity is going to be pretty beautiful. Logic is quite straightforward, that for every single column we are iterating over all of these values, and we are doing it for each of the columns, which means basically we are in the worst case scenario, we are iterating over each one of the elements. So basically and the number of elements we know are n to the power 2, and at every single element we have two choices to make, whether to include that element or not to include that element, which means we are actually doing 2 to the power of n multiplied by n, or 2 to the power of n square work for this one. And we will have to repeat the same operation for each of the columns, because remember that in column 1 there are 4 possibilities that can lead us to different paths, which means we will have to calculate this for each one of them. So we will also have to do this operation n times. So time complexity is horrendously bad, and that's why if you read the problem statement on LeetCode, we are only being told that the value of n can only be between 1 and 9, nothing more than that. We are dealing with a very small number of finite solutions, because if you try to do this with million values, we need quantum computers in order to solve this problem. Okay, now let's quickly see the coding solution, and I hope my solution made sense to you. Okay, so the very first thing we are doing is that we only have value n that we need to return. So first of all, we are creating a blank board of n cross n size, and we are marking all the values as initially as dots, because we don't have any queens placed at the moment. We are also initializing a new array list of list called result, where we are going to be storing all the result, and then we are going to be calling our backtrack method. This backtrack method is going to do the backtracking and also recursive function for us. In the input, we are providing the new board that we just created, plus the starting index of the very first value that we need to iterate over, and the result array list that we have just created in order to store all the answers. Now let's understand our backtrack method. So very first thing we are doing is, this is our base case, that if the current length of our column is equal to the length of the board, which means we have placed the queens correctly on all 4 columns or all n columns. So the correct current path or the current version of board is is suitable enough for us to place it into the result. But the thing is, we are not directly placing it into the result. We are actually calling a construct method to construct the board we want in the subsequent manner. And first, let's just see the construct method. Okay, so in the construct method, we are just passing in the board. On top of it, we are checking that what are all the current positions of the queen that we currently have, and we are just adding those values as part of the queue. Apart from that, we are not doing anything else, and we are simply returning that to the result. Okay, next thing is, so let's say we add the appropriate result over here. Then we have our for loop, which allows us to iterate over all the values inside our given input, where we are starting the value from 0. We are going until the length of the board, and we are just doing I plus plus. Very beginning, for every single board position, we are checking that is it a valid place where I can place my queen. And this is valid method is doing nothing but checking that based on the previous paths that we have calculated, whether we have any particular queue or any particular queen placed before, that is either in the row of that particular queue, in the column of that particular queue, or in the diagonal of that particular queue. If that is the case, we simply need to return false, that this is not a valid position where we can store our queen. If none of these cases are true, then only we will return true, saying that yes, this is a valid place where we can actually place our queen. So once we find a valid place, we update the position of our board to mark that value as q or queen. And then once again, so this is what this we are updating the current path. And then once again, we are going to be calling our current recursive method with the new recursive call, where we already updated the current path of the board. And we also call in with the next index position or the next column we will have to iterate over, and we will keep on repeating the same process. Once we receive a call back from our board, we will also have to explore other paths that we haven't explored so far. And that's where this recursive call comes in, where remember, first we are marking this current position as q, but next we are marking this current position as a dot, that this is no longer a q, and we are exploring other paths. And this is the whole solution. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 87% faster than all the other solutions, which is pretty good, comparing that how difficult question this one has been. Also in terms of memory usage, our code is pretty good, and in terms of like much better than a lot of the other solutions. Once again, the solution of this code is present on our GitHub repository. I highly urge you to go and check it out and try to solve this problem. If you can solve this problem, I don't think any backtracking problem would be a cause of concern for you. Okay, thank you. Hello friends, the problem we are going to do today is one of the most versatile, most asked question in the history of LeetCode questions. Like if you just look at the sheer numbers of the amount this question has been asked and the range of companies this question has been asked, it's just mind-boggling. Whatever your dream company might be in the entire world, and if they do good technical interviews, they must have asked this question probably at least 2, 3, 5, 10 times to their candidates. If I only had 10 minutes to prepare for a technical interview, I'm going to choose this question at the top of my choice. Like just look at the companies over here, like Amazon, Microsoft, Bloomberg, Facebook, Google, LinkedIn, Oracle, Apple, ByteDance, which is basically TikTok, DoorDash, Yahoo, Paytm, Walmart, Tesla, Samsung. So I doubt that there are any companies left that didn't ask this question. And the question we are going to do today is number of islands, and I'm going to pay my utmost attention to this problem. Now in the input problem, we are given a grid of m cross n as a 2D binary matrix, and in this particular grid we are all the cells are filled with either values of 1 or value of 0, and whatever the value that represents as value of 1 actually represents land in the real life, and all the values that are marked as 0 is actually water. And we need to find that what are the total number of islands inside this particular grid. Now based on the definition, we know that suppose if we have some sort of body of land, something like this, and if it is entirely covered by body of water, we can say that this particular body of land is actually an island, and that is what we are trying to find in this given problem. Now we are also told one more thing, that at the edges of this particular grid, like all of these values, this is also water, which means that suppose we are given an input like this, where all of these values are zeros, and we only have just one single one over here. This we can also conclude as an island, because on these three sides of the island is already water, and on the outside is also water, because we are told that everything on the outside is also water. So just keep this in mind, that if we find some place at the edge of the grid, we still consider it to be surrounded by water if all the other side inside the grid is also water. And our aim is to find that what is the maximum number of islands that are present inside the given grid. Now this problem is actually pretty simple. Like if we just see over here, like in this particular input, if we try to find for this example one, that how many number of islands there exist, actually there only exists just one island, and that is this one. Because notice this, that these all ones are actually able to be connect with each other because they're adjacent to each other. If for any particular cell, suppose this is marked as 1 and this is a part of land, and any cell adjacent to this cell is also marked as 1, we can say that both of these are a common part of land, because there does not exist anything in between. They are right adjacent to each other, and this is what we are given over here. So in this example, we can only find one island. Now if we take the second example, we can see that there are actually more than one islands. So this is the first island that we can find. This one is by itself, and if we see all four sides of it, this is 0, this is 0, this is 0, and this is 0. So this is also an island, and these two ones, they are also an island. So in this example, we actually have three distinct islands. Okay, suppose we are given a custom example like this, and I have mentioned in my previous videos that it is really important to come up with your own custom examples, because it shows that you can think on your own and you can create test cases on your own. It's a really important skill for any computer engineer to have. Now suppose this is the grid that we are given, and this blue line indicates the body of water we have outside of our original grid. So this is just for understanding purposes. I'm just going to get rid of it now, so it does not become an issue, and I can explain the problem better. So we know that there is water outside. Now the most basic approach is that we start traversing through the entire grid in some manner. Like there are bunch of different ways to traverse through the given grid, and we try to see that at any moment if we find one, which means that so far we have find a body of land. Now since we have found this one, we need to see that what are the different islands we can create, and we can create bunch of different islands if all the values are connected with one. Like no matter how many number of values are connected with any single one, we would mark all of them as just one island, as long as they are connected with each other. And basically what we are doing is we are trying to find separate set of ones. Understand what I'm saying? I will repeat, we are trying to find separate set of ones. So in this example, if we just see that how many different sets we can find, Like we can find this one set of 1, we can find this another set of ones, and we can find this third set of ones, and over here we only have one individual element, but still that is a set on its own. Like even if we only have just 1 acre of land, it's still a piece of land which we can consider as island. So that is what we are trying to find. And let me just revert back. Okay, so now we know that what we are trying to find. The most basic approach is we start traversing through the given input array, and we start traversing. Okay, suppose we traverse the first row, we don't find anything. Okay, now again we start traversing over here, we don't find anything. Now at this point we find that okay, there exists an element 1 over here. The moment we find that there exists an element 1 over here, we are going to call our function, and basically what that function is going to do is it is going to iterate over all the adjacent cells, and it is going to keep on iterating till we exhaust all the ones that are connected with this one. So till we exhaust all the sets that are associated with this particular one. So let me just go back a bit, and this is the approach we are going to take. That initially, currently we came to this particular item, we find that okay, there exists a 1 over here. Now because there exists a 1, we need to find all the ones that are connected with this one. So what we are going to do is we are going to mark this coordinate, and once we have this coordinate location, first of all we are going to increase the number of islands we have. Like initially the number of islands we have is 0. Now because we find at least a single one, which means that we have found at least one island, so we will update the number of islands we have. Now since we have already updated the number of islands, and we already have coordinates for this one, first of all we will mark this one as 0. So let's mark this one as 0. Okay, and now from this coordinate we will try to find all of its neighbors to see that there exist any adjacent ones. So over here we find that okay, this one is also 1 and this one is also 1. So we are going to repeat the same process, and remember, we are not going to update our islands in this case because we are still connected with whatever the previous value we had found before. So we are still in the same set of 1 that we were dealing with, so there is no point in updating that, but we have to exhaust all the ones that are connected with this original one we had found before. So we will check over here. Okay, this is 1, so because this is 1, we will will change its value to 0, because it now it becomes part of this original set we had. Now again we are from here we are going to repeat the same process. Okay, we don't find any ones from this point, so we are good. But remember, over here we didn't exhaust all the possibilities from our original coordinate, so we still have to do some work. So again we will come back, we will find 1 over here, which means we will have to turn it to 0. So we will convert this 1 to 0 as well, and now from this particular position we will try to repeat the same process. So we will check all of its neighbors, and all of its neighbors in this scenario are now 0, which means we are good. Like we have at least exhausted some possibility, and we have at least found one set of island. Okay, now we will again repeat with our process, and notice that I convert all these 3 values to zeros because we already found an island over here. And now we will repeat the same process. So again we will start traversing our matrix, and over here we encounter the 1 again, which means now we have encountered a new set of island. So we will update the value in our islands, we will update this to 2. Again we are going to repeat the same process. So first of all we will update this one to 0, and now this is 0, we still have to check its neighbors. We find an adjacent neighbor, again we flip it to 0 first, and again we go to the next element, again we flip it to 0, and now we won't find any more neighbors that are basically 1, which means that again we will start traversing. So we keep on traversing over and over and over, and we don't find any ones. But now we are at this point, again we find a 1, we update our island. So our number of island becomes 3, and now we need to find all the neighbors that are present in this particular island, and we set up all of those values to 0. So these values are set up to 0, and now we check that okay, no neighbor actually has a value of 1, which means we have exhausted all the possibilities of number of neighbors that could be a part of the island. And now again we repeat the same process, and now we find this one, and this is the last element. So again we increase the number of islands that we have found to 4, and we set this up to 0. And now because we have exhausted all the possibility and we reach to the end of the grid, we can simply return whatever the value we find in the number of islands, and that would be our solution. Suppose we were given an input with all the zeros, like over here we wouldn't have found any island, and we can simply return 0 in that case as well. But this is like a very basic approach, and the approach we took in this scenario is actually depth first search to find the set of ones that are adjacent to each other. Like we could have used BFS as well, but I mentioned earlier, like I'm trying to learn graph theory, and first I'm going to master DFS, then I will start working on the BFS. So that's why I decided to choose the approach of depth first search in this scenario. Okay, and the time complexity in this case would be actually big O of m cross n time complexity, because that is in we have to iterate over entire grid that is given. And the space complexity would also be big O of m cross n in the worst case scenario. Suppose that we are given a grid where all the values are just ones, which means that for any single element we will have to iterate over all the entire grid, and that could be the worst time in space complexity. First, we'll create two parameters, row and column, to calculate the current row and column values for the given grid. Okay, and we'll also create a variable called island, and initially we will set it up to value 0, and we would update this every time we encounter 1 inside the given matrix. And inside the loop we will have a condition that if the current I and jth position inside the grid is actually equal to 1, then only we are going to call our DFS function. So first we'll do island, we'll increase the value of islands, and now we'll call our DFS function. In the DFS we are going to provide the ith position, the jth position, and we'll also provide the grid that we are working on. And once this loop ends, like we should have all the set of separate ones, and we should have all the values of the total number of islands. So we can simply return the number of islands we have found. Okay, now we need to create the logic to implement this DFS function. So first we'll create a function. Inside the function we will need the values for the row and column again for the entire grid. So we'll just name them new row, and this would be grid's length, and we will also create a parameter called new column. This would be the first position's length. And this is basically the same as finding the row and column we found over here, but we need to use it, so I'm just giving different names. We'll also create a 2D array of called directions. This would make our lives easier and allow us to iterate over all the adjacent values of any current position, and we are going to initialize it with default values. We have this established. First we will put a condition that if the current row and column are they out of bounds or not. We will also put an additional condition that if the current value we are at inside the grid, if that is already 0 or not, because if that is already 0, we won't have to do anything. So if any of these conditions satisfy, we can simply break out of the DFS function, and this would be our terminating case. If this is not true, first of all we will update the current position we are at inside the grid, and we will enter the value as 0, because remember we have already updated the islands. And now we will just run a for loop and iterate over all the 4 directions. So that will allow us to go over all the neighboring candidates of this row and column that we have. And now we are simply going to call DFS on row plus direction of 0 and column plus direction of 1, and we'll also provide the value of grid as well. And yeah, I guess this should be our logic, and we can try to run this code. Okay, looks like we messed something up. Oh, okay, seems like our solution is working. Let's try to submit the code. Seems like our solution is also working, but it's not the most efficient solution, and I'll try to make my solution better, because maybe there is some other way we can solve this problem, and if I find out, I'll probably make a video on that sometime in the future. Meanwhile, let me know in the comments if you have any thoughts regarding this problem. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Graph problems have always been a big no-no for me. I have always been afraid of graph problems, but the thing is now I have decided to take them heads on, and today we are going to start doing more graph videos. So this is the first of many graph problems to come. And this question has been really popular with Facebook recently. It's been asked 44 times, which is a huge number. Also, key other companies like Amazon, Google, Bloomberg, Microsoft, Twitter, they are also asking this question. But the thing is, Facebook for some reason has been really interested. So I highly urge you to go and check this video if Facebook is one of your dream companies to join. Okay, this is the LeetCode medium problem, and we are given a reference node in a connected undirected graph. So first let's understand the meaning of these two values. Suppose we are given a graph like this. Notice that there are only 4 nodes, and from any single node we can reach to all the other nodes in the given graph, which means that this is a connected graph. So this is what connected means. And undirected graph means, suppose we are given a graph like this, and we establish that A is B's neighbor, which means that we can traverse from A to B, and also we can traverse from B to A. So there is no restriction regarding the direction of any edge between 2 nodes. So we are given a reference point to that, and we need to return a deep copy of the graph. So what does a deep copy of the graph means? That suppose we are given a graph like this. So we need to return a graph like this, where if you see the values of the nodes, they are all the same. But the thing is, we are not using the exact same nodes. We are using different nodes with same node values, which means that this would be a legitimate case where we can consider this as a deep copy of this original input. The thing is, if we create a graph like this, over here we are using the same node to represent over here, which means that we are not creating a copy of this original graph. We are just referencing this point to whatever value we had over here. So this is not what we want to give. And also, if we create some graph like this, if we see the values of the nodes, the values remains the same. But the thing is, the ordering is different, that in terms of neighbor selection and how they are perceived, they are different. So this is also a false case. We need to return a copy of this exact same input, just with the nodes that are copied from this one. So at the beginning, the most basic idea we are going to have is that okay, we are given an input, we are given a reference point, we know that the input graph is connected, which means that there are no loose ends that we have to worry about. So why don't we just traverse through the given input graph? At every single node we start creating a copy of it, we start creating the same sort of neighbor connections that we have in the original graph, and then just try to return the new graph. That would be a perfectly good logical rational person would think, and that would be a good entry point to start our solution. But the thing is, we are going to see that with that approach, what would be the issue, how can we remediate that issue, and what would be the final solution. So let's start. So first of all, suppose in this given input we start at this one position, so we create a new node 1. Okay, now from this one we can go to any neighbor, we can go to 2 or we can go to 4. Let's say that we go clockwise, so we go to 2. So we create a new neighbor over here called 2. Again from this 2 we go to 3, and over here, keeping the same logic, we create a new node. Now notice one thing, that initially we created a clone over here, we went to its neighbor. Again we created a clone over here, we went to its neighbor. Again we created a clone over here, we will go to its neighbor. So basically we are doing the same problem again and again for different kinds of input. So that should immediately click in your mind that this we are going to solve recursively. So just keep this in mind, that this is a very good way to use the recursive approach. And now at this 3, again we go to its neighbor, so we'll create an edge and we'll create a new node 4 for this one. So from this 4, again we go to its neighbor, again we go over here. But the issue with this approach is that for this our recursion to end, we need to have a terminating case. But in this scenario we are not terminating it anyhow, because the thing is, the graph is connected. We are terminating in a scenario where if the graph is empty, we return something empty or something like that. But the thing is, over here again, when we come back to this 1, we are still going to see that okay, this is 1, we need to create the clone of it. We will create a clone of it again over here, which means that we are going to overwrite whatever value we have, which would be the same value. Again we would go to 2, we would again create another clone, again we would go to 3, again we would create another clone, again 4, again another clone. So basically we are going to end up inside the loop again and again infinitely. This is almost like Infinity War. Thanos is gonna snap his fingers, something like that, because we are completely destroying our computers resources, our company's resources, because it's an infinite loop. It's never gonna stop. So, and the reason it's never gonna stop is because we are doing the repetitive work again and again and again, and that is the issue. So somehow we need to resolve the issue. So how we are going to resolve the issue? Well, basically the idea is simple. If at any point, suppose we create an additional data structure, in that additional data structure we keep track of whatever the value we have traversed already or we have cloned already. If we know that, which means that initially when we start, we are going to check in that new data structure first that hey, this element, have I cloned it already? If I have cloned it already, I would skip over, I would go to next element. If I haven't cloned it already, I would create a new clone of it, and then I will put the same entry in the hash map first before I go to the next element. So that way, when after this first circle comes and when I come back to the same position, I would know that okay, I have already calculated this one, which means that I don't need to calculate it again and I can skip over it. First of all, let's see that what kind of additional data structure we are going to create, where we can immediately find that whether we have visited any particular element or not, which means that we are going to do a lot of searching. Hence we will need a data structure that is very quick and efficient in terms of finding the any element, that whether it contains that element or not. And the answer is pretty simple. If that kind of scenario happens, we need to use hash map or hash stat or something with the hashing. We cannot use the linked list over here. It would work fine, but it's going to add that much more additional time strain or on our system. So make sure that you justify your reasoning. I mean, in the interviews, people are not typically going to ask that why did you use hash map? This is a given. But the thing is that thinking should be clear in your mind that why you are using it. And in most of the graph problems, typically hash map is being used. Now inside this hash map, we are going to store two values. So as a key, we are going to store a node, and as a value, we are also going to store the node. But the thing is, as the key, we are going to store this input node, and as the value, we are going to store the cloned node that we will create. So let's see that what should be the algorithm for our solution and how we are going to approach it. So initially we start at this position 1. Now at this position 1, first of all, we check that whether we have this entry inside our hash map or not. Okay, we don't have the entry inside the hash map because we can find it in constant time. If the entry does not exist, we first of all create a clone node. Okay, clone node has been created. Now after creating the clone node, immediately before even we check for the neighbors of this one, immediately we are going to add an entry inside the clone node. So the value would be the cloned value that we have created, and the key would be the original input we are given. Now this is done. Now we are going to check for this one's neighbor. So one, let's say we end up at this neighbor number 2. So again, for this neighbor number 2, first of all, we are going to check that whether neighbor number 2 exists in this hash map or not. It does not exist, so we will create a clone. Now the clone has been created. First we will add the value to the hash map, and after adding the value, we would again go again recursively do find for the 2's neighbors. So in this case, the 2's neighbor would be 3. So we will create first we will check that whether 3 exists in the hash map. 3 does not exist, so we create the node, and then we create this one. Now again we check for the value number 4. 4 does not exist, so again we create an entry inside the hash map. We provide the key value, and then we create the clone node 4 again. Now for the 4th, we again check for its neighbor. So 4's neighbor, one neighbor is 1, which we already have it in hash map, which means that now we can ignore this case because we have already dealt with 1. Now second neighbor for 4 is 3, which already exists in the hash map, which means we can be dealt with it. We go back, 2 is already done, 1 is already done, which means that now we are running out of neighbors to track from inside the given original input. And we know that the original input is completely connected graph, which means that there is at no point there is a possibility that there exists some value 5 over here that is part of this graph, but it is not provided using this connection, because all the elements are connected, which means that this would be our final clone graph that we need to return. So after the loop ends and the recursive termination cases trigger, we can simply return whatever the clone graphs we have found, because from any single location we are able to guarantee to reach all the other elements. And once that is done, essentially we are done. So this is a very effective solution. Basically all we are doing is just we are traversing over the given graph, and during the traversal we are doing something. So in this case we are cloning it. We are using the hash map to keep track of whatever the visited elements that we have been through, and this solution is pretty efficient. It's not the most difficult problem in the world, but the thing is, I am very bad at graph problems. So and I have always been scared of graph problems, but the thing is, now I have decided to spend more time on graph problems, because if you want to join Facebook, you can't even think about not doing graph problems. Okay, so today is first of many problems to come. If we see the time and space complexity, the time complexity in this case would be big O of V plus E, where V is the vertices and E are the number of edges, because notice that over here we are only doing this much work, we are not doing any additional work. So that's pretty simple. And in terms of space complexity, it would actually be big O of V in terms of number of vertices, because over here we had 4 vertices, and in the hash map we created 4 entries. So whatever the number of vertices we are provided, we are going to use that, and that would be our space complexity. So this solution is actually pretty efficient. We are using depth first search to solve this problem, but even we can solve it with using breadth first search. So it makes no difference in terms of time complexity. The thing is, I just did this using depth first search. Next one I'm going to use breadth first search maybe. So first of all, we are going to create a new hash map, and we are going to name it visited to keep track of whether we have already visited the node or not. Now inside the method, first of all we are going to check that if the given node is null, which means that we can return the node. Okay, and also we are going to check that if if we have already visited the existing node, then we are simply going to return whatever the value we have stored inside the visited hash map. Okay, if this is not the case, first of all we are going to create a clone node. So let's just name it clone node. And inside the clone node we are going to give it the value of whatever the node value that we currently have, and we are going to assign a new array list. We are going to add the new clone node to the visited node. We are going to run a for loop for all the neighbors of existing node. So inside the loop, we are going to iterate over the neighbors of the existing node, and we are going to create the clone nodes for that. And inside the current clone node, we are going to put the neighbor as an array list. So, and over here we are going to make the recursive call with the neighbor. After this loop ends, we are simply going to return the clone node. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit the code. Okay, our solution works, and it works pretty efficiently. There is still room to make a lot of improvisation, as we can see that our solution is not the most efficient. But the thing is, I'm really bad at graphs. So it took me a lot of time to make this video because I need to understand very thoroughly by myself first before I can create the video. But soon I'm going to do a lot of graph videos. So so my video quality is gonna improve, and also my coding is gonna improve. So hope for the best, and let me know in the comments what do you think about the video. And yeah, see you next time. Thank you. So the LeetCode problem we are going to solve now is called maximum area of islands, and we can see that this one is a medium problem and also a very well-liked problem. The statement is quite straightforward. We are given an m cross n binary matrix named grid. Now for this particular grid, we are given bunch of different ones and bunch of different zeros. Now we are being told that ones represents an island and zero represents just water. Okay, then we need to return the maximum area of an island that we can make inside the grid, and if there are no islands that we can form, we need to return 0. Plus we are being told that every single cell with value 1 is the island, and if there are bunch of different ones connected with each other, then we need to basically do the addition of all of those cells, and then we can consider them as one entire block of an island. So let's try to understand this with an example. Here is an m cross n grid we are given, and we can see that there are bunch of different zeros and bunch of different ones. Now some ones are isolated, so this is just an island in its own, and we can see that the area of this particular island is going to be value number 1 because it is only connected with just one island by itself. But if we take a look at some other islands, we can see that they actually form bunch of different ones that are adjacent to each other amongst all 4 horizontal values, and that increases the area of those particular islands. So we will have this island that is of size 4, same way this island of size 5, and so on and so forth. Now we need to return the island that contains the maximum value. So in this case, this island chain or this connection of ones are actually total area of 6. So in this case, we will need to return the maximum area of islands as 6 as the answer. So this is what we need to return. Now let's try to understand that what are the different logic we can take to solve this problem. Now we know it's a very straightforward problem. The idea is that we are going to iterate in one single direction from the starting point, and the moment we identify that there exists some island or value number 1, then we need to iterate over every single possible neighbor of this particular one. And the moment we exhaust all the possibilities by exploring every single neighbor, we can determine that that has been the current area that we have been able to find. Plus we will also need to keep track that what is the maximum island chain we have been able to identify it so far. So let's try to understand the most common basic approach to solve this problem. Let's say that we start iterating from this very first cell in sequence, in just regular sequence. So we say that this is water, this is water, so there is no area we can find. We come to this node, this value is 1. So the moment we identify 1, we will have to take a look in all 4 directions to see if there are any possible island chains that we can make. Since in this case there are no island chains we can form, we can say that the area of the current value we have been able to identify so far is 1, and so far we have only found one island with area 1, so the maximum area we found so far is also 1. After doing this, we will have to mark this one as being visited because we have already visited this node. And why are we marking it visited? I'll just explain it to you later. So let's say that we mark this one as visited as well. Okay, that this one has already been taken care of. We iterate again, nothing, we don't find anything. Once again we find one more one over here, which means we will have to do the iteration for our current updation right now. So once again we start looking in all 4 directions. The moment we go to this direction, we find one more one. So once again for this particular one, we will have to repeat the same operation, look in all 4 directions. And here the problem may arise. Let's say that we look in this direction and this direction, and then we decide to look up into this direction. So this is also a neighbor of 1, and we can also by mistakenly calculate this one once again, so as part of the island, which means we may stay inside an infinite loop. And that's why, in order to prevent that issue, the moment any particular value that we have visited, we are just going to mark that that value has been visited, so we don't recount those values again. So let's say that we count this value, then we go into this direction, and so far we have visited all of these 4 ones, and the current area so far we found is 4, which means maximum area also needs to be updated. So we are going to update the maximum area once again. Now we start our iteration in the similar fashion. These are all zeros, so nothing to do with this. Once again, this one would have been 1, but since we already visited this one, there is no point in redoing the same operation. So we are just going to go and ignore this case completely, and once again we are going to ignore all of these cases. Once again we identified 1 1, so far the area is going to be 4. We cancel out all of these 4 nodes as well, and we keep on repeating the same operation until we find the maximum area, which we would find when we get to this particular one as value number 6, and this is what we need to return in this case. So the moment I was explaining this solution, it should completely come to your head that this is actually a graph problem, where this given m cross n grid is actually the matrix we are given that represents a graph. It's an adjacency matrix, and for this adjacency matrix, all we need to do is we will have to find that what are all the connected components for any particular graph, and the cluster of the connected components, whichever has the highest value, we simply need to return that as part of the answer or as part of the area we have been able to calculate so far. Now we know with any particular graph problem, the most important thing is that how we are going to iterate over the graph. So we know that iterating over an m cross n grid is quite straightforward. We simply need to run 2 for loops to iterate over that. The moment we identify any particular one, then we will have to explore in all 4 directions and iterate over the entire set of directions where whichever the value is 1, and we will have to keep on repeating the same operation. So logically, all we are doing is a depth first search whenever we identify any particular one that exists. We can also do a BFS, but DFS in my opinion would make much more sense in this case because we need to go in any particular direction. It won't change the result, but I just like to use DFS for this particular type of case. Then in order to complete the DFS and not run into the issue of recounting the same value, we will have to keep track of all the visited nodes. For that, we have 2 options. One option is that we can try to manipulate the existing input But let's say that your interviewer is very picky and he or she does not want you to play around with originally given input. So instead of playing around with originally given input, you can also create a m cross n matrix and just mark all the values by 0, whichever the ones that you have visited so far. So that way also you can just keep track of all the nodes that you have visited, and you are only going to do a DFS on unvisited nodes. So that's it. That is the whole solution. And on top of it, for the entire duration, you are going to keep track of the current area that you have found so far and the maximum area that you have been able to find so far. And combination of this would actually solve this problem quite simply, quite easily. Let's try to understand the time and space complexity in this case. Time complexity is simply going to be big O of m cross n, because we will have to iterate over every single cell, and even for our DFS operation we are going to mark those nodes as visited. In terms of space complexity, because we are using an extra space to store all the visited nodes, it is also going to be big O of m multiplied by n, or nodes multiplied by edges. So in this case, overall this is a very good time and space complexity. Once you understand that this one is actually a graph problem, it becomes very simple to solve and also move forward. So now let's quickly see the coding solution for this one. So the coding solution is quite straightforward. We are given our max area of island that we need to find, and we are given the grid as part of the input. First thing we are going to do is to check that if the given grid is equal to null, then we are simply going to return 0. It's an edge case. Then we are going to initialize a variable called max area, and initially the value is going to be 0. Then we are going to iterate over every single value that is currently present inside our grid using two loops, I and j. And for every single value, first thing we are going to check is that if the given grid position, if that is equal to 1, then we will start calculating the area of this current one that we have been able to identify so far, and we will have to iterate over in all 4 directions, and that's where we are using the DFS method. Next thing, for every single one that we have been able to identify so far, it could be possible that that particular value could be the maximum area we have been able to identify so far. So we are going to compare the maximum area we have so far and the new area or the current area we just found for this particular through this DFS call. Now let's understand this DFS call and how does it work. In the input, we are providing the grid that we are working with. We are also providing the current I and jth position. Very first thing we are checking is that if the given grid is going out of bounds, in either one of these cases, we are simply going to return 0, or if the given grid position I and j that we are working with, if that is also 0, then also we can return 0. If that is not the case, we are going to mark this cell as visited. Now in this case, I'm not using an extra hash set. I'm just using the same grid to update the call. But if your interviewer asks you that you cannot change the given input, then you might need to create a new instance of new m cross n matrix and repeat the same operation. Then we are going to add value of area by 1, and then we are going to make 4 different calls in all 4 directions, and we are going to do the plus and equal to operation for the area, which means for every single one that we are being able to identify in each of these 4 areas, we are going to add that value to our existing area, and we are simply returning the area in the end. So this is our helper method, where recursively we are using the DFS operation and we are updating the area of the current area we have been able to identify it so far. In the end, we simply need to return the max area we have been able to identify so far once this for loop call ends. So now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs 100% faster than all the other solutions, which is exceptionally good. So once again, the solution is present in our GitHub repository, so feel free to go ahead and check it out. Thank you. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important LeetCode problem, Pacific Atlantic water flow. And as you can see that this problem hasn't been asked in too many companies. The thing is, the companies where this problem has been asked are really one of the most important companies in the world. Google, Amazon, Uber, Microsoft, Facebook, Apple, ByteDance, which is a parent company of TikTok, Bloomberg. So you can understand the scale that why this problem is important and what kind of companies ask this problem. And the thing is, main intention for understanding this problem is to not to understand the actual problem, but rather the approach behind the solution, because that can become a base foundation for too many other problems. There is a lot of information in this problem statement, but if we try to comprehend this using the picture, it's really simple to understand. So I'm just going to go over that. Essentially, we are given a grid like this, and we are told that this is actually an island on somewhere in the ocean. But the thing is, it is at the cross junction between Pacific Ocean and Atlantic Ocean. And the way it represents is that this top and this left edges, they are actually Pacific Oceans, and this bottom and this right edges, they are Atlantic Ocean. So this, and the second information we are given is that all of these coordinates inside the given island represents the height of that particular area. And why the height is important? Because we are told that on this particular island, on this particular grid, there happens to be a lot of rain, which means that rain falls, and we know the property of water that it gets transferred from higher height to lower height. We are also told that that rain at any particular cell can can go to four directions. It can go to top, right, bottom, or left, which means it cannot go diagonal in any scenario. And the condition that if it can traverse from one cell to another cell is that if the height at any particular given cell, if it's greater than or equal to the cell we are trying to reach, then the water can travel to that cell. Which means, suppose we take this cell for an example, the height for this cell is 4, which means if the rain falls on this cell, we can conclude that the rainwater will go to cell 3. It will also go to cell 1 and cell 2, but it would not go to this cell 5 because the height at cell 5 is greater than cell 4, which means that this is cell 4 and this is cell 5. So water can't travel like this. Now, the interesting part for this question is that we need to understand that what are the cells in the given grid that can travel where if the rainwater falls, it can travel to both Atlantic Ocean and also Pacific Ocean. So let me clean this up a bit. Suppose we consider this cell number 5, and if rainwater falls in the cell number 5, let's see that can it reach Atlantic and Pacific. Like, we know it can reach, but in this cell adjacent to the cell number 5, the height is 3, which means water can go over here. From this 3, the water can go to this 1, and because this is at the edge of Atlantic, of course water can go to Atlantic Ocean from here. Now from this cell number 5, we know that water can also go on this side because the height is 4, and from this 4 the water can go because the height is 2, which is less than 4. And from this is at the edge, which means that at any point, whatever the height over here is, like 1, 2, whatever value, all of that can go to Pacific Ocean. So we can conclude that water from this cell number 5 can reach to both Atlantic and Pacific Ocean. Let's take another example. Suppose we take an example of this value number 4. So we know that from this cell we cannot go over here, we cannot go to 5, but we can go to 2, and from 2 we can go to Atlantic. So that concludes one option. Now let's try to see that can we go to Pacific Ocean. So first, if we try to go on top, okay, we can go over here because this is 3, but from 3 we cannot go to the top because this is 4. So we can't go Pacific in this direction. If we try to go over here, we can reach to this 1. We cannot go to this 7, which means that from this 4 we can go to Atlantic Ocean, but we cannot go to Pacific Ocean. So we wouldn't include this in our intersections. For every single cell, we are going to check that whether it can reach to both Pacific and Atlantic Ocean. If it can reach, we will just maintain a list or some sort that will take care of all the cells that we are able to reach to both the oceans, and we would keep on adding them in this list. So first we'll start with this first element. We know that it can reach to Pacific Ocean, but it won't be able to reach Atlantic Ocean because height over on both these cases are greater. So we wouldn't include this. We would go to next one. So over this, this again can reach to Pacific, but it cannot reach to Atlantic because it will traverse in these two directions, but it won't be able to go any further over here and over here. Same happens for this one, and basically this solution would work. We would find our answer. Eventually our list would be filled out. Suppose we are at this location 5. So we know that this is at the exact intersection of both the oceans, and it can clearly go to the rainwater can clearly go to Pacific and both Atlantic. So we would add this particular location in our list, and eventually the list will be filled out. But the thing is, the issue with this approach is that in terms of time complexity, we are actually doing a lot of repetitive work, because for every single cell we are checking all the possibilities, and we might end up doing, in the worst case scenario, big O of. So suppose this is M and these are N cells. So we can say that the time complexity would be big O of M multiplied by N squared, because for every single cell we will have to iterate over all the other cells, and this is not a very good time complexity. There exists a better approach. So in order to solve this problem, we are actually going to use a different approach, and the approach we are using is actually, if mountain cannot come to Muhammad, Muhammad will have to come to mountain. And what I'm trying to say is, suppose that rather than checking at any particular cell that whether it can reach both Atlantic and Pacific Ocean, we create two separate grids. So suppose we create a grid and another grid, so two separate matrix of Boolean values that has the same size of whatever the input size we are given. And at any particular location, we just name that okay, this matrix consists the data of all the cells that can actually reach the Pacific Ocean, and this matrix contains all the data of all the cells that can actually reach to the Atlantic Ocean. And once we have these two matrices defined, the moment we find that, okay, so over here we know that this particular element 3, this can reach to Pacific Ocean. So over here, suppose this value corresponds to this 3, so we will set the value as true over here. And same goes on this side, that suppose we find out that this particular element at position 4 can reach to Atlantic Ocean via this way. So whatever the corresponding value we have over here, we will set that value as true, and eventually we will have the entire matrices filled out. And once we have those, all we need to do is just intersect both of them and find the common elements between both of these matrix, and that would be our final list of matrix that contains all the cells that can reach to both Pacific and Atlantic Ocean, and this would be our solution. Well, this solution actually works pretty fine, it's pretty efficient, and all we need to do is we need to figure out that how we are going to generate these two matrix and what are all the different logic we are going to take. Let's take the most basic approach. I'll be showing you an example that suppose we want to reach to Pacific Ocean, how can we fill out that matrix. Now, what is the most basic thing we know about Pacific Ocean? Well, we know that for this particular island, all the cells that are present in this row and all the cells that are present in this column, they are actually at the edge of the island. Also, they are at the very adjacent to Pacific Ocean, which means all the water in these positions can actually reach to Pacific Ocean in all the cases. So in our matrix, whatever matrix we have, we can basically define all the elements these positions as true, because we know that they can reach to Pacific Ocean. Now, previously at any particular location, we were actually trying to go outwards to see if water can reach to adjacent cell or not. But rather than going outwards, why don't we come inwards from the cells we already know that can reach to Pacific Ocean? So over here, these cells we already know that they can reach to Pacific Ocean. So if we check that whatever the cells that are adjacent to these cells, from this particular cell that can reach to Pacific Ocean, can we reach to these adjacent cells or not? and the moment we find that okay, we can reach to some adjacent cells that we haven't already visited, so we can set that as true. Suppose the value over here is 3 and we know that this is able to reach to Pacific Ocean, and suppose the value adjacent to this one is actually 6. So we know that since the height difference, there is a height difference, and over here we need to check the reverse height difference. Previously in this approach we were actually checking that whether the height we are currently at and the height, the adjacent cell is actually the height is lesser than whatever the current height we have. Over here we are coming inwards, so we will check that whatever the next cell is that we haven't checked, whether its height is greater than whatever the height we currently are at. So in this case this is 3, this is 6, which means that okay, from this cell we can come to this cell, and over here we know that we are coming to this cell from this particular cell that is already able to reach to Pacific Ocean. So over here we can directly mark this one as true, and we won't have to do lot of calculation over here because we already know that this cell is true and we are reaching to this cell via this cell, and this would be a very good solution. And this is how we can actually fill out this entire matrix or like all the remaining portion in big O of m cross n times in just single traversal, because we are not, for any particular cell we are not going to check the whole thing, we are only going to check the cell that is exactly adjacent to it. Suppose we are at this particular cell and we know that this cell can reach to Pacific Ocean, we have already set this value as true. Okay, now we do calculations like this, and suppose before we come over here from this route we have already calculated this and we know that this is already true, that this can already reach Pacific Ocean, and we are at this position and we are checking this again. So first we will already find that whether the value for this particular element has been calculated already or not. If it has been calculated, we don't need to do repetitive work and we can just simply skip over it. That way we can also make some runtime adjustments that would be more efficient on our case. Okay, now we need to find a way to somehow create the matrix that stores the information of all the cells that can reach to Pacific Ocean and also to Atlantic Ocean. In order to do that, at first I thought that we are going to use dynamic programming over here, and the reason I thought is because first of all we are defining a set of all the cases that can reach to Pacific Ocean, so this becomes our base case. Once we have our base case defined, we are essentially going in all the directions to see that if we can reach to next cells, and suppose in this case we are able to reach to this cell from over here due to the height difference, so we will mark this as true, and again from over here we will again do the same thing, and we will, so basically at any point we are using whatever the calculation we have calculated before to generate the next results. So that's a very clear indication that we need to use dynamic programming over here. But it turns out that I was not able to solve it efficiently. I was still missing out in a lot of test cases. So apparently dynamic programming is not the way to go, but I still urge that if anyone can solve it using dynamic programming, I would be more than happy to understand your approach. So second thing I tried to do is okay, in order to solve this we need to iterate over the entire matrix, and in order to iterate over the entire 2D matrix we have basically two methods. We can use either breadth first search or we can use depth first search to iterate over all of the elements and do some calculation. Now I'm new to graph theory and I need to first of all perfect myself on depth first search before I move towards solving the problems using breadth first search. So I chose the approach of taking depth first search, but it can also be solved using breadth first search without any issues. And we know that in order for us to complete this program using depth first search, we need to use recursion over here, and of course we can use recursion because notice that at every single position, so over here first of all we define that this can reach to Pacific Ocean. Now we move on all the directions and over here we find the height difference, so again we know that this can reach to Pacific Ocean because this can reach to this cell, so we mark this as true, and then again we repeat the same process that we have just did, and again we would mark this as true, and again we would repeat the same process. So essentially we are doing the same sort of work but for different inputs, and that's a very clear indication that we need to use depth first search using recursion. And let's move on towards coding now. First of all, we are going to check the condition that if the given input is actually an empty matrix, then we just need to return null. Okay, if that's not the case, let's create two parameters to store the value of row and column. Now we'll create two Boolean matrix to see to store the value of cells that can reach to Pacific and Atlantic Ocean, and we are going to name that Pacific reachable and Atlantic reachable. And we are going to create both of them to the size of whatever the initial heights matrix we are given. Now we will run a for loop on the for both the matrix to be filled out. In order to fill both the matrix, we are going to create a DFS method, and inside the DFS method we are going to provide the row and column location, and we are also going to provide Pacific and Atlantic matrix. So first we'll do it for Pacific matrix, and we are also going to provide the input heights that we are given. We are again going to call the same function for the Atlantic. We'll iterate using column as well. Now before we calculate the result, first let's create the method. Now inside the DFS method, we will have to iterate over for any particular cell. We will have to iterate over all four of its adjacent cells. So we'll just create a 2D array called directions, and we are going to use it to iterate over all the adjacent or neighboring cells. So we are at this DFS location, which means that we already know that this row and this column pair is already able to reach to subsequent whatever reachable matrix that we are trying to calculate. So which means that we will set that value as true. Now we will start iterating over the neighbors of whatever the current cell we are at, and we are going to create the new row and new column. Now we will have to check that if this new row and new column, are they out of bounds or not. If that's the case, we just ignore that and we continue. We also check that if we have if the new row and column cell if we have that value calculated before, we can also just ignore that case. Okay, if both the cases are not true, we will check that if the height difference of the previous cell and new cell is in our favor or not, which means if the heights for the new row and new column if that is greater than or equal to whatever the previous height was. If that is true, we will need to call the DFS function again with the new row and new column. And this would be our logic for this DFS method, because we are eliminating all the cases and we are also calling the recursive function based on the height difference. So after these four entries run, we should have both of our Pacific reachable and Atlantic reachable matrices filled out, and now it's just a matter of finding the common elements between them. So first of all, let's create a list of lists to store our result, and we'll just name it as result. Just going to iterate over the entire array row and column wise, and we are only going to check that if both the values are true in both the Atlantic and Pacific Ocean cells. So if both are true, we can add it to our list. So uh, After this loop runs, we simply need to return whatever the result we found, and that should be our solution. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code. Okay, our solution also works. It is accepted by LeetCode, but the thing is it's not the most efficient solution. So let's see that if we can do some modifications. And one modification I can think of is rather than calling this DFS system right here and checking this condition all the time, what if we revert the condition, and if this condition is satisfied, we can just return it, and we can just continue before. So that's why loop breaks more times before. And if all of these conditions are not true, then only we will call our DFS function. Let's try to run the code. Okay, the code is working. Let's try to submit the code. Okay, we see some improvement in our code, and now it's a little bit faster than what our previous result was. So I'll be posting this code in the solution. You can check it out from there, from the comments, and let me know how do you like the video. Thank you. So the LeetCode problem we are going to solve now is called surrounded regions. We can see that this one is a LeetCode medium problem and also very well like problem. Now the statement is quite straightforward, that we are given an m cross n matrix named board that contains bunch of different x's and bunch of different zeros. Now we need to capture all the regions that are four directionally surrounded by x. And if a region is captured, then we need to flip all the zeros into that particular region into the axis that is a surrounded region. So let's try to understand what they are trying to ask. We are given in this example an m cross n board where we can see that there are bunch of different x values and bunch of different zero values. Now in this case, what is the definition of any particular zero region to be surrounded? A region is surrounded if in all four directions it is connected by some sort of x in each one of them. If that is the case, we can determine that this particular region is surrounded. Now notice one important thing. We are not concerned with its immediate neighbor, but even if the neighbor of the neighbor is still a value x, then we can determine that that particular value is still surrounded by x's. So the moment we identify a surrounded region, all we need to do is convert all the zeros into x's, which means we can see that this node is surrounded by 4 x's in these four directions. Same way with this particular zero, it is surrounded by these 4 x's, and same way for this particular zero, it is surrounded by these 4 x's. So logically, all of these would be converted into the x's, which we can see over here. But for this particular region, it is only surrounded by x in 3 different directions, not 4. So we are not going to flip this 0 into x. We are going to leave it as it is. And then we need to return this state of the m cross n grid as part of the answer. So let's try to see that what is the simplest logic we can use to solve this problem. Now let me give you one example of bunch of different zero potential values in all of these different grids. Let's say for this particular grid, if we have any single value 0, then that value has to be not surrounded region. Why? Because currently this particular value is located over here. Even if in all the other directions we have access, then also we would never be able to get a 4 directional pattern where this region becomes a surrounded region. So in the answer, we are always going to have a scenario where this 0 is going to remain 0. Same way for this 3 by 3 grid, let's say that if we have any particular 0 present over here, and let's say that all the other values are currently x's, then we can very easily determine that this 0 is actually surrounded by x's in all 4 directions. So in the answer, when we try to create, basically this 0 has to be flipped into x. That is true. But let's say instead of doing that, instead of this being 0 in this middle portion, let's say if we have 0 located at any of these edges, any of these, okay? I'm not saying all of them are zeros. Let's say any one of this is a zero, and let's say that all the other values are x's. So I'm currently marking these by a bunch of different x's. This region would never be surrounded. That's a given fact. Why it would never be surrounded? Because there is always going to be one or two directions where it is located on the edge, which means there can never be an x planted over here. So if the node is in the middle, then it has the possibility of being a surrounded region. But if we identify 0 at any particular edge, then that 0 is always going to be a not surrounded region. So it does not needs to be changed. That is what I'm trying to explain. Now let's try to see one more example in this case. Let's say if we have any particular these 4 zeros placed like this and all the other values are x's. In this case, all of these zeros has to be converted into the x's because all of this becomes a surrounded region. But for some example, if we have any particular zero located over here, we already established that this does not needs to be changed. That is number one thing. Second thing is that not only this does not needs to be changed. Let's say that if there are any particular other zeros connected with this value, then also they are also going to be not surrounded regions. Once again, I repeat, if there are any particular zeros that are connected with this edge, then we can determine that this is also going to be not a surrounded region, and we are going to exploit this property to its fullest. Because remember, in this case, particular this zero is actually always going to have one more zero located over here, which means it can never be four directionally challenged by another zero. And this is what we are going to use to solve this problem. What we are simply going to do is that we are going to treat this as a graph problem. Not only a graph problem, we are also going to treat it as a graph traversal problem where we need to do the depth first search. At any given moment we identify a value that is currently 0. The thing is, we are not just going to blindly start looking for zeros in all of these particular grids. That it makes no sense. If there is any particular 0 in the middle, it might be possible that there might be x's in all four directions that could prevent it from becoming a not surrounded region. What we are going to do is we will try to only traverse into the edges of this particular matrix, and for each of the edges we will try to find that if there exists any particular 0, then we are going to start doing the DFS, and all the values that we identified through this iteration, we are just going to mark those numbers that they are always going to be four directionally not surrounded regions, and all the other regions or all the other values we can simply mark them by x. So let's try to understand this with an example that I'm trying to show you. Let's say that in this case we are currently given that these two nodes are currently zeros, and let's say that this is connected with this 0, and let's say that this one is not connected with anyone else, and then we have this 0 connected like this, and all the other values are currently x values. So logically, the algorithm I'm proposing is that we start iterating over this m cross n grid in first of all the edges. So let's say that these four are the edges, and then we once again identify this edge and this edge, and then this edge and this edge. So we found a one edge that contains a value 0. The moment we identify one edge that contains the value 0, first of all we are going to mark this one as a special 0. So let's say that I'm keeping track of all the zeros that I have been able to identify so far, and let's say that this one is a special character that contains a 0 at the edge. Then we are going to do the DFS operation in all four directions to find all the connected zeros. But we can see that this one does not have any connected zeros. So we are just going to say that this is the only 0 we find, and then continue with our iteration. Once again, we are at this position. This is also x. Once again, we identified one more 0. So the moment we identify one more 0, we are going to mark it as a special character, and then we are going to start doing the DFS operation in all four directions. This one is an x, so we don't do anything. This one is an x, so we don't do anything. But this one is not an x, so this one is also a 0, and a 0 that has been found by reaching a 0 that was present in the edge. So once again, we are also going to mark this as a special character, and then now from now on we cannot move ahead anywhere forward, so we cannot do anything. On top of it, For our DFS operation, we will have to keep track of all the visited nodes. So we are also going to mark all the visited nodes as well. So it's just simply for our convenience. And that's it. So once again, we don't find any more access. So then we simply say that we iterated all the edges. We did the DFS on whenever we found a 0 at the edge, and we marked those nodes. And apart from these nodes, everything else should be converted into the x's, which means this node has to be converted into an x, and that's it. This is the state of m cross n that we need to return of all the zeros that are not surrounded, and all the surrounded regions are being converted into the x's. So that's it. This is the whole solution. If we try to understand the time and space complexity, in this case time complexity is going to be big O of m cross n, because we will have to iterate over every single nodes, and this is an example of adjacency matrix kind of representation for the graph. Space complexity, well, this is debatable. If you have to create a new snapshot, then you might have to use m cross n space. If you can modify this current existing node just by changing this character from something else from 0, maybe something like a hash or something, then also we can use the same pattern or same logic. So it's up to you how you want to approach that, or how your interviewer wants to do that. It can be a common space complexity, or if you are not allowed to change the input, then it is going to be big O of n cross n space complexity. So now let's try to see the coding solution for this one. So the coding solution is quite straightforward. We need to solve the given board, and first we are going to check for the edge case, that if the given board is equal to null, we can simply return. If that is not the case, we are going to define our m and our n. Then we are going to start iterating over the boundary and start marking all the zeros that we find on the boundary as like a temporary character or a temporary variable. So let's say that we run 2 loops. We have this if condition that if the given node is equal to 0 or m cross m minus 1, and j is equal to 0 or n minus 1, which means we are checking for the edge nodes. On top of it, we are also checking that if the given board position marks the value as 0. If that is the case, then we are going to call our DFS method. In the DFS method, we are checking that all the surrounded regions that we need to find. So this is our DFS method, where we are first of all checking that if the given node is equal to null, or we exhausted all the possibilities, we can simply return. If that is not the case, we are going to mark that particular value as a temporary character t, stating that this has been visited, and we are going to run the DFS operation in all 4 directions repetitively, which means we are only going to be left with temporary values that are currently visited by us after this DFS operation, that are connected with the zeros that are located at the edge. Then once that is done, we simply need to check and capture all the surrounded regions. So for that, we can simply iterate over the given input array and check that if the given input board position is equal to 0, which means it is not t, then we are going to simply mark it as x. If that is not the case, and if that value is t, which means it is not a surrounded region, so we are going to mark it as 0. And that's it. This is the whole solution. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code is exceptionally faster compared to all the other solutions, which is great to see. And once again, you can find the solution on my GitHub repository. Link is in the description. Thank you. Hello friends, hope you are having a fantastic day. So now we are going to do an awesome LeetCode problem called rotting oranges. We can see that this one is a medium problem and also an extremely well-liked problem. The statement is quite straightforward. We are given an m cross n grid where each cell have one of these 3 values. First value is 0, that represents that there is an empty cell, which means there are no values over here. Second potential value can be 1, which represents that there exists a fresh orange on that particular cell in the m cross n grid. And next value is 2, which represents that there could be a rotten orange or a bad orange placed in that particular cell. Now there comes the interesting part, that with every single minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. So after every single minute iteration, we will start finding more and more rotten oranges, and they would keep on growing. Now we need to return the minimum number of minutes that must elapse until no cell has fresh oranges. That is number one thing that we are being asked. If that is the case, we need to return the minimum number of minutes. And if it is impossible to rotten every single oranges, then we need to return -1 as part of the answer. So let's try to understand this awesome LeetCode problem. Okay, so suppose this is one of the example input that we are given. Now notice that the values are 2, 1 and 0 given in different sections of this 3 by 3 cell. Now we know that value number 2 refers to a bad orange. So I have denoted that as like B over here in this grid, and 1 refers as normal orange. So I have just marked O or like 0 that represents a fresh orange. Okay, don't confuse this with like value 0, because value 0 I have left it as empty because there are no oranges or nothing on that particular place. So now let's focus on our input. Now the way we are given this problem, this is a bad orange. Now let's say that this is the current starting position. So at minute number 0, this is currently what is happening right now. But we know that after every single minute, all the oranges that are adjacent in 4 direction to this bad orange will start getting bad. So after 1 minute passes, we are going to have 2 more oranges that have gone bad, and that are these 2 oranges. So we can mark them as bad oranges, and all the other oranges that we have are going to remain as it is. This happens during the first minute. During the second minute, once again more oranges are going to get bad. So since this orange is right adjacent to this one, this will go bad, and this orange will go bad in the next minute. So these 2 oranges will go bad. So if we mark the number of bad oranges, it is going to keep on increasing in this fashion, and now we are only left with 2 fresh oranges. And during the third minute, basically we are also going to have this orange go bad, because notice that this is directly adjacent to this orange. So during the third minute, this orange will also go bad, and all the other oranges we already have, they are bad. And during the fourth minute, basically because in the third minute this orange is fresh, but during the fourth minute this orange will also go bad, and now we don't have any fresh oranges. So we can say that after 4 minutes, basically every single oranges that could go bad, they have all gone bad. So in this case, we need to return 4 as the answer. Now let's say for the same example, we are basically given one more scenario. Let's see that what would happen in this case. Well, we know that during the first minute, the adjacent orange is going to get bad. So now we are going to be left with 2 bad oranges and few other good oranges. During the next iteration, once again the same thing is going to happen, and now in this next iteration, basically this orange is going to go bad. So then we are going to be left with these 3 bad oranges and then these 3 good oranges. During the next minute, once again same thing is going to happen, and basically we are going to be left with this orange as becoming bad orange as well, and all the other oranges would remain good. And during the next iteration, basically this orange will also go bad. But notice one thing, that despite every single orange being bad, we do not have any particular way for this particular orange to go bad, which means no matter how many iterations we take, even if all the oranges went bad, this orange will still remain fresh. So in this case, because we cannot have every single orange becoming rotten, we need to return -1 as the answer. So this is what is being asked us to solve in this problem. Now I know this problem looks really interesting and really important in terms of many different aspects. So first let's try to start breaking the problem down and start understanding different things on what we can do to solve this problem. Let's say that in this problem we are given oranges like this and all the other cells are simply empty. Logically, what is the most simple thing we are going to do? Well, we need this is the initial position, so we are going to have a value called minute, and in this particular minute we are going to mark that all the minutes that has elapsed so far. So during the 0th minute, this is the position. So during the first minute, what is going to happen? We are going to start noticing that this orange will go bad. Okay, then during the second minute, this orange will go bad. during the third minute this orange, and during the fourth minute this orange will go bad. So this case, it's going to take 4 minutes for every single orange to get rotten. So the thing is, we can visualize it very quickly and very easily, but how can we implement this programmatically? So that's where few important concepts come into the place that let me start describing. Number one concept is that basically for every single position we will have to understand that what is the rotten or bad orange, and then we will have to start iterating from that particular element. So far we were lucky that the very first element was actually a rotten element, but let's say in the same scenario, instead of this being rotten, what if this was a rotten orange? Once again, the answer would still be 4 minutes, but in this case we would have iterated over all of these cells before finding this rotten cell, before we start branching out. So that is number one thing, that we need to first of all find that what is a rotten orange. Okay, that is number one thing. Next thing is, the moment we find the rotten orange, what we do is we start branching out. But the question is, are we branching out in the depth first manner or a breadth first manner? Well, logically in this case we are actually iterating in the breadth first search manner, because for every single node that we iterate over, we try to iterate all of its neighbors before visiting before visiting their neighbors. And let me give you a very simple example for that. Let's say in this example, during the very first iteration we simply visit this neighbor. Okay, so we are going to mark this as a bad orange. But in the next iteration, rather than going in one particular direction, we are going to branching out in two directions and marking both of these as bad apples. And then after exhausting all the neighbors of this particular orange, then only we will start exploring more neighbors of these remaining oranges. So this is also another important point to be understood. Okay, that we will actually have to use breadth first search in this case to solve this problem. Okay, we took care of two items. Now let's try to understand that how we are going to keep track of the number of minutes. Well, logically the answer is quite straightforward, that whenever we have to make any single new BFS call, we are going to keep track or keep incrementing the number of minutes that we will have to make. So this would be our minute counter that we are always going to update with every single new BFS call we make. Now we know that in order to use a breadth first search, we will have to use a queue, and logic is quite straightforward, that first of all we are going to iterate over all the oranges that we are given and try to find all the bad oranges we have. In this case we only have one bad orange, but it could be possible that we may be given multiple bad oranges. So let's say that we are only given just one bad orange, so we are going to put this bad orange in the queue, and with every single iteration we are going to branch out in all four directions from this bad orange. The moment we identified a good orange, we are going to mark that also as a bad orange and push it down the queue in order to be processed in the next iteration, and that next iteration will happen during the next minute. So this is the second important logic that we will have to understand, that how we are going to be processing the queue. Now comes the interesting question, that how would we know that we have actually isolated or completed every single oranges that we could, and whether we need to return the minutes or do we need to return -1. So for that, during the first time when we are actually iterating over to find all the bad oranges and pushing them on the queue, at the same time we are also going to have a counter that stores the number of good oranges we have. And what we are going to doing is that, let's say in this case we realize that we have 4 good oranges. Now every single time we add one value to the B, we are going to reduce one element from the good oranges. We are going to be doing the breadth first search as long as we are able to reach some oranges, and then once we get out of our loop, we will try to check that, hey, do we still have any more good oranges? So in this case we would not have any good oranges, so we can simply say that we did not find any good oranges, so we can return the minutes. If we do find some good oranges, then we need to return -1. That's it. This is the whole problem and this is the whole solution. Now I know that we can use queue plus we can use recursion to complete the BFS call. Also, for this given m cross n grid, we are actually treating it as an adjacency matrix for our graph kind of problem, and every single node we are treating it, every single node that contains the value of either a bad orange or an orange as a node, and connection or the neighbors of each other are being treated as sort of like edge between them. If we see time and space complexity, in this case time complexity is going to be simply big O of v multiplied by e, vertices multiplied by edges. And for the space complexity, well, since we are not using much space except storing a queue, the space complexity would be directly dependent on the number of bad oranges or number of total oranges present, because in the worst case we might have all the oranges that might go rotten. So this is the whole time and space complexity. Now let's quickly see the coding solution, so my solution would make much more sense over there. So the very first thing we are doing is to check that if the given grid is equal to null, we can simply return -1. If that is not the case, we are going to define the values of m and end. Then we are going to initialize a count called fresh count. This is to store the fresh oranges that we have at the beginning of the queue. And then we are going to start our queue where we are going to be storing all the rotten oranges that we found so far. Now, the first thing is count the fresh oranges, and we are also going to push down all the rotten oranges down to this queue. So we simply use two for loops to iterate over all the values, and we are going to be counting that what are all the fresh oranges we found. And if we identified that the value is 2, which means that particular cell position is a position of a rotten orange. Okay, so now that's good. Now the very first thing we are going to check is for the edge case, that if there are no fresh oranges, we can simply return 0, that during the 0th minute all the oranges are rotten. If that is not the case, we are going to initialize a variable called minutes with the starting position 0, and we are going to have direction array to iterate over all 4 neighboring directions for any particular cell. So these are nothing special, just the 0 and 1 combinations of adjacent cells, and that we can simply add to the current I and j positions. Now we start our BFS operation, where we first check that if the given queue, we are going to iterate until the given queue is not empty. First thing we are going to check is the size of the given queue. Then we are going to check that for any particular given I position, while it is less than the size of the queue, we are going to first of all pop one element out, marking it as rotten, and then we are going to be iterating in all 4 directions. So notice that with the by using the direction variable, we are actually going to calculate the x and y positions of all the adjacent cells. Then we check that are we going out of bounds. If we are not going out of bounds, then we are going to be turning the fresh oranges into the rotten, and we are going to be reducing the count of the fresh oranges that we found so far. On top of it, we are also going to be updating the rotten queue and adding those values inside our queue as well. Lastly, we are going to be updating the minute variable for every single new breadth first search operation that we make, because this is the increment timer for every single level of BFS. Now, in the end, we simply have to check that if the given fresh count is equal to 0, we are going to return minutes. If that is not the case, we are going to be returning -1. That's it. Now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs extremely fast, and it beats 99.99% of every single solution, which is pretty great, pretty awesome. Once again, you can see the coding solution on our GitHub repository, so feel free to go ahead and check it out. Thank you. So the LeetCode problem we are going to solve now is called walls and gates. We can see that this UI looks slightly bit different than our typical LeetCode problems, and that is because this is actually a very popular LeetCode premium problem. So that's why I took this screenshot from a website called leetcode.ca. So whoever is operating that, thank you so much. Now let's understand the problem statement. We are given an m cross n 2D grid that is initialized with 3 possible values. First possible value is -1. So -1 defines that there is a wall or an obstacle that we cannot cross over. Next value is 0. 0 defines that there is a gate. And third value is an INF. So INF is a very large number basically. And if we are given this very large number, that defines that the given room is empty. So basically we are given three distinct values. One value defines that on that particular cell position, there could be a wall, or it could be a gate, or it could be an empty room. So for the rest of this problem, let's just try to use only these three values, so it would make sense for us to understand. Okay, now we need to fill each empty room, so each cell that contains the value E, with the distance to its nearest gate. So this is the gate that we are given. We need to calculate the distance from every single empty room to its subsequent nearest gate, and if it is impossible to reach a gate, then it should be filled with an infinite value, or which means like an empty room. So let's try to understand this with an example. Basically we are going to be given a grid like this that contains three different values, infinity, -1 and 0, but the thing is I have presented them slightly nicely over here. So let's try to understand and figure out that what does this problem statement is actually asking us to solve. So we can see that there are a bunch of different empty rooms that are currently given to us, and we are only given two different gates that these empty rooms can try to reach to. Plus for some empty rooms we actually have walls that are coming in between, so we will have to ignore those walls and try to figure out that what is the best way to reach to those particular gates. So let's just create an empty like empty m cross n grid, and we will try to fill out these values. So we can see that for this very first position, this one is an empty room. So what are the closest gate to this empty room? One closest gate is located over here. If we calculate the distance, this is actually 3 cells away. So in this case, one option is that we can fill value 3 over here, or if we have to calculate the distance between second gate, it looks like this is very close. This feels like that this is only 2 steps away, but that is not the real case. Why? Because there is a wall in between, so we cannot cross the wall. So if we have to reach to this particular gate, we will have to go down this path and then this path and then this path. So that actually makes the total distance as 4. But the thing is we need to calculate the shortest distance. So over here, shortest distance to the gate is going to be value number 3. Same way, shortest distance over here is actually going to be this gate, that is this value number 2. Shortest distance over here is once again this gate, and that is this value number 1. Now this value is already gate, so we can define it as 0, or let me just mark it as gate for our understanding. Now at this particular position, the closest gate is actually this one, and this is only 2 steps away, so we can actually mark value 2 over here. Same way, this is only 1 step away through this gate. Same way, this is also 1 step away through this gate. Same way, this is 2 and this is 3, and this one is actually 4 steps away from the gate, and that path is actually going to be this one. So this is going to be 4. For all the other ones, the walls are always going to remain the walls, so we can simply mark the walls as it is, and the gate is going to be as gate, and this is what we need to return as part of the answer. Now for some reason, let's try to understand that suppose this value is also a wall. Let's say that over here, let's say that this value is also a wall, okay, just for the understanding purpose. So then now at this position we have no way to reach to a gate, because both adjacent doors contains a wall. So in this case we are still going to make put this as an infinite value, or mark it as an empty cell. So just for our understandings okay, so let's break down the problem in subtask, and we will try to calculate the result. Number one thing we need to check is that distance of any particular cell from the gate. This is the number one thing. Second condition we have is that if there is a wall, we cannot cross, so we cannot go to the wall. We should not consider. If there is an empty room, we will try to find that how many steps it take from empty room to reach to the gate, or from gate to reach to the empty room. So now what the approach I'm suggesting is that if we try to calculate at every single gate that every single empty room, that where is the closest gate, and if we try to find this one, this problem can get like slightly more expensive. Why? Because remember that at this gate location we will have to do like either a BFS operation or a DFS operation, and we need to keep on iterating over of every single possible neighbors in order to calculate that where does the nearest gate lies, and it could take potentially big O of like m cross n times for every single grid in order to find both the gates in the worst case scenario. So this problem can become like m cross n multiplied by m cross n. That is going to be very expensive problem. So rather than finding out the from like distance from empty room and searching for the gates, it would make much more sense that from any particular gate we can start iterating over and branching out in like different traversal fashion and try to find the empty rooms. And for each traversal that we make, we simply have to do one iteration, because we know that it is one step further from the gate in order to reach to that particular empty room. So what the approach I'm suggesting is that first of all we simply iterate over the given input array and try, or sorry, given input matrix, and try to mark all the positions that contains gate. We identified that this contains gate. Now from this gate we start traversing in all the possible directions until we exhaust every single possibility of finding an empty room for the from any particular gate. That is option, that is number one thing. Second thing is that we also take care or take into the consideration that if I have to reach to any particular empty room, how many hops did I had to take in order to reach to that empty room. Also, it could be possible that some other gate can also reach to same particular empty room. Then we will try to put the value that contains like the lower value compared to the current value we have as part of the empty room. So let me explain the solution, then it would make sense. Now the question is, let's say that we identify that these two are the gate positions. We know where we want to iterate from, but the question is how we going to iterate. Are we going to use depth first search or breadth first search? So logic is quite straightforward, since in this case we will have to calculate how many hops it take to reach to any particular location. We don't want to do the backtrack and keep on going in just one direction. We actually wants to branch out in each of the directions. So logically it would make more sense to use breadth first search in order to calculate our result. So if we have to use breadth first search, we will actually have to use a queue in order to generate the result. So idea is we are going to initialize a queue. In the queue we are going to mark all the positions that contains the current gate values. Then from this particular gate value we will keep on iterating over until the next element, and all of its neighbors that we are able to reach that are currently empty rooms, we would mark them to the gate as well, and we would try to update the value of those empty rooms by 1 plus. And the moment we do the next iteration we will add one more value. The moment we do the next iteration we will do one more value. So let's say that we start our iteration from this value. So currently this one is a gate. Okay, these are all the walls that we cannot use or we cannot go over. So let's try to start populating our array using this gate value and see that how is the result we get. During the first iteration we are going to go down this path. So we know that for both of them the distance is going to be 1 1, and currently remember the distance is infinite, so we are always trying to put the smaller distance on the place of the gate. Next is from here we cannot go anywhere because this is a wall. We already visited this node, and so there are no other ways to go, but from here we still have two ways to go down. So let's mark the values for both of them. So this is going to be 2, this is going to be 2. Once again from this 2 we have one more way to go, so this is going to be 3, and from 3 we have one more way to go, this is going to be 4. That's it, we exhausted all the possibilities down this path, but over here we still have more paths that we haven't traversed over. So this is going to be 3, then this is going to be 4, this is also going to be 4, then this is going to be 5. So, or sorry, no, this has to be a gate value, so we are not going to do anything. So now we exhausted all the possibilities at this gate. Once again we are going to repeat the same process from this gate and try to fill in the lower value. So if we branch out, this value actually becomes 1 because this value is, and 1 is less than 4, so we are going to put 1 over here. Then this value becomes 2 because 2 is less than the current value we have, so this becomes 2. Then this value becomes 3 because this value is actually smaller than this one, so we can mark this as 3. Now from this 2, if we have to go this way, this becomes 3, but we already have a 2 which is already a smaller value, so it makes no sense for us to go down to this path. From this 3 we cannot go anywhere else, So that's it. Now this state actually contains every single possible like distance of empty room to the gate that we have been able to identify, and all we had to do was to use a breadth first search starting at the gate and keeping track of all the graph related principles. So basically keeping track of all the visited nodes and updating the value from the current position, or every single new BFS we make, we simply have to add value by one, and then we need to branch out in all four directions where the given gate is the given cell value is not a gate and it's not a wall, which means any place that is an empty room, we need to calculate that what is the distance from a gate. And if we do this for all the gates, eventually we would left with what is desired from us that we can return. So if we have to understand the time and space complexity in this case, the time complexity is going to be big O of m multiplied by n, but we will have to do this by the number of gates that are present. And if we see space complexity, well, we will have to use a queue in order to do that, and queue depends on the number of elements, so it is also going to be big O of m multiplied by n. And this is what we need to return. This is a pretty good time and space complexity, and congratulations, you just learned an awesome LeetCode problem. That is a premium problem, and you didn't have to pay for the LeetCode premium. So anyways, now let's quickly see the coding solution. So this is going to be the solution, and I cannot run this in LeetCode because this is a premium problem, but I would still paste the solution in our GitHub repository so you can check it out from there. So we have our infinite marked as a very large number. Then we are creating a static position called direction to iterate over all four directions. Basically this will help us during our breadth first search calls. Now this one is the main method, the walls and gate method, where we are given the rooms as part of the input. We first check for an edge case, that if the given rooms are null, we can return. If that is not the case, we define the values of m and n. Then we also initialize a new queue which we are going to use to do a breadth first search. Then we are going to find all the gates that are currently present inside our given array by using two for loops, and we are checking for the value that is equal to 0. After that, we are simply going to do a BFS for every single gate, where we are checking that for this particular gate position, what are all the four directions that we can explore into. For each of the four directions, we are going to check that number one, we are not going out of bounds, and number two, if the given value of room that we are reaching to or the cell is actually infinite, then we are simply going to update the value of the distance, and in the end we can simply add that value to our queue as well to keep on updating the distance. So basically we are going to be storing like the smallest distance possible from every single gate, and this is what we need to return in the end. So this solution would work as expected. And now let's I won't be able to run it, but you will be able to find the solution at my GitHub repository, so feel free to check it out from there. Thank you. Hello friends, we are still not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do course schedule lead code problem, and this is one of the most versatile problem that has been asked at bunch of different companies, like huge number of companies. We can see the companies like Amazon, Microsoft, Facebook, Google, TikTok, Snapchat, Robinhood, Twilio, Uber, eBay, Tesla. All the companies have asked this question, and this question is very practical, real life application. So that's why a lot of companies like to ask this question. So this is a LeetCode medium problem, and we are given a number of courses, and we are also given an array of prerequisites where any single entity in array is defined like this, where we are given two values, suppose a and b, separated by a comma, which means that we must complete course b first in order for us to complete course a. So suppose we are given an entity in the prerequisites like this 1 and 0, which indicates that this course 1 actually has a prerequisite called course 0. So we can define it like this, that course 1 has a prerequisite on course 0, and in terms of the practical manners, we first complete this course 0 in order for us to complete this course 1. And based on the information given, we need to check that whether we can finish all the courses or not. And if we can finish all the courses, depending on whatever the prerequisites we are given, we need to return true, otherwise we need to return false. Okay, now that we understand the problem statement, let's take a custom example to understand the problem. Suppose we are given the list of prerequisites like this, and we are given the number of courses as 4, which means that we need to complete the 0, 1, 2 and 3. These 4 courses we need to complete, and this is the list of prerequisites we are given. Now we can consider this as actually graph problem. We can consider these as graph nodes, and the prerequisite information we can treat them as graph edges. So over here we can say let's plot it on a graph and let's see that how it would look. So over here 1 has a dependence on 0, so I mentioned this. 0 has a dependence on 3, so let's also mention this. And 2 has a dependence on 0, so 2 has a dependence on 0. Okay, so this is how we can plot this on a graph, and we need to see that whether we can complete all of these forces or 4 courses or not. So the most intuitive solution is to check from the beginning. We check at this course number 0, that can this course number 0 be completed or not. Now in order for us to complete this course number 0, we see that this course 0 actually has a edge pointing towards course number 3, which means that course 3 is a prerequisite for course 0. So we need to complete this course 3 before we can complete course 0. Now we are at this course 3 again. We check the same thing, that whether we can complete the course 3 or not. Now course 3 does not have any prerequisite, which means it can be completed on its own. So we say that okay, course 3 can be completed. Now again we backtrack to 0. At 0 we check that does 0 have any other prerequisites that we need to take care of. No, 0 only has one prerequisite on course 3 which we can complete, which means that we are able to complete course 0 as well. So we can mark this and the square box indicate that we are able to complete that course. So we are good. So we already know that 0 can be completed, 3 can be completed. Now we check for this course number 1. So at course number 1, we check that what are the prerequisites for course number 1. Well, course number 1 has a prerequisite on course number 0. So since we already know that course 0 can be completed, which means we can also conclude that course 1 can also be completed, which we can mention over here. And we can check for this course number 2. So course number 2 also has a prerequisite on course 0, which is already done, which means we are able to complete course number 2 as well. So in this case, for all the 4 courses, we are actually able to complete them, and we can return true in this case, that yes, based on the given number of courses and prerequisites, we are able to complete all the courses. Now we need to check that what could be the scenario if we cannot complete the course. So suppose we are given an additional edge like this in the same example. Suppose we are given this additional edge. Now let's see that how the dynamic would change. Let me clean this up a bit. Okay, now we have this additional edge 3, 2, which means that in order for us to complete this course number 3, we would need to complete course number 2 as well. Now let's see that can we complete. So initially we would check that can we complete this course 0. So in order for us to complete course 0, we would need to complete course 3. Okay. Now in order for us to complete course 3, we would need to complete course 2. Okay. And again, in order for us to complete this course 2, we would have to complete this course 0. So notice that we are constantly stuck inside a loop. It's the same scenario where you need experience to gain a job and you need a job to gain experience. It's somewhat similar kind of example, that we are stuck inside the loop, which means that no matter what happens, we are not able to complete any of these 3 courses without completing the other one, because there is an interdependence between each other. And essentially in this case, we would have to return false, that we cannot complete all the courses. But the thing is, why did we have to return this false? Well, the reason is quite simple. Basically, in terms of graph manner, if we speak, what was the difference from this graph compared to this previous graph? Only this edge. And when we added this edge, what essentially we did was we introduced a loop inside our graph amongst these 3 values, 0, 2 and 3. So we can conclude one thing, that at any given moment, if we've identified that there exists a loop inside our graph, we would be able to immediately return false. If there does not exist a loop and we are able to, from every single element, we are able to complete all these prerequisites, in that scenario, we need to return true. So now we have these two information. Let's see that how can we use them and how can we solve this. So suppose we are given an example like this, and these are all the prerequisites that we are given, and we need to complete the total six number of courses in order for us to conclude that this graph can be scheduled or not. So essentially we are going to apply the same logic. We are going to first of all take these inputs, we are going to convert them in a graph like this. Inside the graph, for every single course, we are going to see that whether we can justify these prerequisites or not, and at any moment, if we identify that there exists a loop, we will immediately terminate and return false. If there does not exist a loop, we would keep going, and eventually we would return true. So that is the idea. And in order for us to achieve that, first of all, what we are going to need is, we are going to need some sort of graph data structure, because initially the only two values we are given is number of courses and the set of prerequisites. So first of all, we would create a data structure like hash map, and inside our hash map, we are going to store two values. We are going to store as a key, we are going to store the number of courses, and as a value we are going to store the number of prerequisites that every single course has. So initially we would have, so this is the number of courses and these are the prerequisites that we have. And we would try to see that can we complete all the courses or not. So first of all, we are at this course 0. So in order for us to complete this course 0, we need to see that what are the prerequisites for course 0. So for course 0, the prerequisite says course 2. Now for this course 2, what is the prerequisite? The prerequisite is actually course 3. Okay, and now for this course 3, the prerequisite is actually course 4. So here, and for this particular course 4, the prerequisite is actually course 5. So here, now we are at this course 5, we check that can we complete this course 5, and yes, we are able to complete the course 5 because there exists an empty list. So which means we can conclude that course 5 can be completed over here because there is an empty list. So again we backtrack, we go back to course 4. At this course 4, we know that course 5 can be completed. Since course 5 can be completed, we can also have an empty list over here because it defines that at any moment, if we are at this course 4, that course 4 can always be completed because its prerequisites are already met. So we can have an empty list over here. Now again we go back. If we go back, we are at this course 3. So in order for us to complete this course 3, we would need to set up an empty list over here because course 4 can be completed. That is done. Now again we come back to this course 2. At this course 2, again we will create an empty list, and now we are at this course 0. So at this course 0, we only have dependence on course number 2, so we can also have an empty list over here, basically defining that course 0 can be completed. Okay, so that is one observation that has been done well. Now, and see that we were only trying to calculate that can we complete this course 4, but we already concluded that we can complete all these courses as well, and we have already established them inside our hash map. So at any moment, we only need to identify the remaining courses and not all of these courses that we have solved already, which means we are efficiently improving our solution. Second, we come at course 1. Now this course 1 actually has 3 dependencies, course 2, course 4 and course 5. So let's take care of each of them one by one. First of all, we will check that from course 1 can we complete course 2. So we check for this course 2 and we check that these prerequisites are already met because there exists an empty list, which means that we can eliminate course 2 from over here from the list of prerequisites because we know it can be completed. Again, we check the same thing for this course 4. Over here, this course 4, we again have the empty list, so we can also eliminate the course 4 over here as well. And again, we can repeat the same process for this course 5, that course 5 can also be completed because there exists an empty list, which means even at this position course 1, we can create an empty list over here. And now if we look at all the courses, the only prerequisites we have are just empty lists. And once we achieve that, basically we can conclude that we have already reached our solution and we can return true in this case. So this solution works perfectly fine. But the thing is, we missed the key point over here. Like, because this was a true scenario, we did not identify any issues. But the thing is, if there was a loop, we were not actually checking that whether we are encountering any loop or not. So let's see that if we want to encounter any loop at any iteration, what would be the additional steps we need to take. So let's modify our example a bit. Suppose we have an additional prerequisite like this 5 3, that in order for us to complete this course 5, we will need to complete course 3. So we will have an edge like this, and let's modify our prerequisites table. Okay, now in this example, we know that there exists a loop between this 3 4 and 5. So we need to take care of it, and in order to take care of it, I'm suggesting that we create an additional hash set at the beginning of checking for any single course. So we create a hash set, and in our hash we just name it as visited or something, and over here we will keep track at any location are we repeating the same element. So let me show you what I mean by that. So initially, suppose that we are at this course 0, and then we start our program. So we want to check that whether we can complete course 0 or not. So first of all, we will check that whether we have already visited this course 0 in this current iteration. So we check in this visited node that have we visited course 0, and because it's a hash set, it's a constant time operation, so we are not adding any additional strain on the time complexity. So we haven't visited this node 0. We would add an entry over here first. Now we will check over here that what are the prerequisites for this course 0. So the prerequisite is course 2. So again we would check our visited node first. So course 2 is not part of it, so we would add an entry over here, and again we would continue over here. So now we need to check this course 3. Again we would add it entry to the visited node. We check over here, we need to check course 4 we haven't visited, so we would add an entry over here. Then we would check the force prerequisite 5 we haven't visited, so which means we would add an entry over here. And now at this 5 we would check the prerequisite for 5. So for the prerequisite for 5 is actually 3, so we are again at this position 3. So first of all, we will check that whether we have visited this 3 or not, and this time we would know that yes, we have already visited this node 3, which means that we are in a loop. So this is what this hash set confirms, and the moment we find out, we can immediately return false over here. We don't even need to check any additional items in this given graph, and we would be able to terminate our case immediately, which means, and in case if this edge was not existent, this entry for this value number 5, we wouldn't have to check anything, and we would have been able to complete all our code, and we would have been able to return true, but which is not the case this time, because there exists an additional prerequisite as specified over here. So this would be our final solution. And now let's calculate the time and space complexity for this one. So for time complexity, we can actually complete this whole thing in big O of v plus e time, because at any moment the maximum traversal we will have to do is from one node to all the single nodes, and throughout all the single edges. So this would be the time complexity. And space complexity, because we are creating an additional data structure like this hash map and also this hash set, but the thing is hash set is going to be smaller, so we are only concerned with this hash map. For general time complexity, it would be space complexity, it would be big O of v plus e as well. Okay, first of all, we will create a hash map, and we are going to store integer and list inside it. We will name it course graph. Okay, now we will have to build our graph. So essentially we are going to iterate over every single prerequisite in the given prerequisites, and first of all we will check that whether this prerequisite is already added in our graph or not. So If it is added already, we only need to append the new prerequisite. And if it does not exist, we will need to create a new one. We'll have to create a new entry in our course graph. So we will create a new list and add the list, and then we will add the entry of the course and the list to our graph. Okay, so after this loop ends, we should have our graph structure ready. So now we will create a hash set that will take care of integer values, and we'll name it visited. And now we will have to run a loop for all the courses that we are given. And now we will have to create a method to check that whether there exists a cycle inside the loop or not. And let's name our method that course schedule, which indicates that whether we can schedule a course or not. In this course schedule method, we are going to provide the current course, the visited node, and the graph that we had created. And if this responds back to false at any given moment, we would know that we cannot create the course schedule, so we will return false immediately. And if this loop ends and we don't return false, which means that everything was successful, and we can return true. Okay, now we will have to create this course schedule method. So let's create a boolean method. Now let's test our terminating cases. So if our set contains the current course, which means that we have detected a cycle, so we can terminate immediately, so we can return false. Also we check that if for the current course, if we already have an entry in the graph where it has an empty array list, we can return true. If that is not the case, we will have to iterate over all the prerequisites for any particular course. So first of all, we will add the current course that we are iterating over in our visited hash set. Then we will iterate over every single prerequisite for that particular course. We would call our recursive function. So and we will provide the current prerequisite we are at. We will provide the visited hash set, and we will provide the graph. And if at any point this returns false, we can return false immediately. However, if this loop executes, we know that for that particular course we are actually able to complete the course, and we can schedule it. So first of all, we will remove it from the visited node, and then now since we know that this particular course can be completed, we would update the entry for that course in our course graph. So we would set the prerequisite to null, which means that in future at any point, if we identified this particular course, we know that we are able to complete it, and we can just move forward quickly. And at the end, we can simply return true in this case. So I guess this would be our course schedule function where the main logic happens. And let's try to run the code. Okay, seems like our code is working. Let's try to submit the code. Okay, our solution works, and it works pretty efficiently. So I would be putting this solution in the comments. You can check it out from there. And this was a really long video. It took me a lot of time to make it. So I hope you like it, and let me know in the comments on what are your thoughts about this problem. See you next time. Hello friends, I'm a cloud solutions architect at Microsoft and my aim is to empower every single person to become better at technical interviews. Keeping with that goal in mind, today we are going to solve a very important LeetCode problem. So let's get started with the problem. So today we are going to do course schedule 2 LeetCode problem, and if we see some of the popular companies who have already asked this question, there are companies like Amazon, Google, Microsoft, TikTok, Apple, Plantier, ByteDance, Roblox, Uber, Facebook, Robinhood, Snapchat, Bloomberg, DoorDash, Lyft, and Goldman Sachs. So this has been a very popular question at many different companies. I'm going to pay my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem and also very well like problem on LeetCode. In this case, we are given two items. First item is number of courses. Now the number of courses, it says that suppose we are given number of courses to be 3, which means that we are given the courses 0, 1 and 2. Suppose we are given the number of courses to be 5. In this case, the courses are 0, 1, 2, 3 and 4. So this is what the number of courses define. Second item we are given, which is more important, is the array of prerequisites. Now, what does an array of prerequisites define? Well, there can be a structure that looks like this, A, B. What this means is that course B is a prerequisite for course A. We all know that we need to complete like the prerequisite course in order to go and do the more advanced level courses. So in this case, if we complete course B, then we are eligible to complete course A. But say for example, for some reason we are not able to complete course B, we are guaranteed that we would never be able to take part in or be eligible to complete course A. Now, after having these two items, number of courses and prerequisites, basically what we need to do is we need to return an ordering of courses such that we are able to finish all the courses. And what does finishing all the courses means? That we are abiding by the list set of or the all the prerequisites that we are given amongst all the courses. And definitely there could be many different answers to that. We can complete the courses in many different ways, so we need to return any of the valid answer. And for some reason, if we are not able to complete all the courses, we need to return an empty array. So let's try to understand this with few examples. So in the first example, we are only dealing with two courses. So the two courses are going to be 0 and 1. Now for these two courses, we are only given one prerequisite, and this prerequisite says that course 0 has to be done in order to be eligible to complete course 1. So if we complete the courses in the ordering of 0 and 1, then this is going to be a legitimate answer, where we complete the course 0 because it has no prerequisites, and since we have already completed course 0, we are eligible to complete course 1, and this is going to be a valid answer, so we can return this as the answer. If we take the second example, this is a little bit more complicated. Now we are dealing with 4 courses, which means courses are 0, 1, 2 and 3. Now in this case, if we see, there are a bunch of different prerequisites, so let's go every single one of them and try to find some answer. So first one, it says that course 0 has to be done before we can do course 1. Okay, that is good. Second one says that course 1 needs to be completed before we are eligible to do course 2. So we have already completed course 1 over here. So let's try to do course 2 after that. Then it says that course 2 has to be done before we are eligible to do course 3. So over here we are already done with course 2. So let's complete course 3 after that. So this is one of the valid orderings. And in this case, if we return 0, 1, 2 and 3 as the answer, this is going to be a perfectly valid answer. And in this manner, we are keeping track of all the prerequisites and we are also completing all the courses. Let's take one final example. So if we see in this final example, this is a little bit different example. So over here, we are given 3 courses. So courses are going to be 0, 1 and 2. Now we are given some prerequisites. So let's try to go through each one of them. So first one is 0 to 1. Okay, we need to complete course 0 in order to complete course 1. That's good. Now second one, it says that we need to complete course 1 in order to complete course 2. So 1 we have completed over here. Let's create it for 2. But now this prerequisites, it's a little bit tricky, and the tricky part is that we need to complete course 2 in order to complete course 0, which is the tricky part, because now if we see, there is no way for us to complete like all 3 courses, because every single time we are going to be bounded by some other course. Because definitely in order to complete course 1, we need to complete course 0. In order to complete course 0, we need to complete course 2. In order to complete course 2, we need to again complete course 1. But we cannot complete course 1 because 0 hasn't been done. So this is going to be keep running in the round and round, and this is a huge problem. So in this case, we are simply going to return an empty array because we cannot find an ordering that satisfy all the properties. So based on my drawings and all the logic I'm trying to show you, it becomes pretty trivial that how we are going to solve this problem. The way we are going to solve this problem is using graph theory. And for the graph, we need two items. We need nodes and we need edges. So as the nodes, we are actually going to use the number of courses, that all the courses are going to represent a node in itself. And for the edges, we are going to take all the values that are present inside the prerequisite table. And based on that, we are actually going to create an edge. And that is going to give us very interesting results. Now, in this case, say for an example, just consider this example. And let's try to draw a graph in this case. So first one, okay, we are given 4 courses. So we are going to draw 4 nodes. So first prerequisite is that we need to complete course 0 in order to complete course 1, which means 0 is actually a prerequisite for course 1. So we can have an edge between 0 and 1, where 0 is a prerequisite and 1 is the node that needs the prerequisite of 0. So notice in this case, I'm only drawing one directional edge. Why? Because for 1, 0 is a prerequisite. So that's why there is an edge between 0 to 1. But the thing is, for 0, there is no edge coming back from 1, because so far we haven't find that there is a prerequisite in this case. So because it is not the case, we are simply going to keep progressing. Now next one is that we need to complete course 2 in order to complete course 1, right? So basically from 1 to 2, there is also going to be an edge, because course 1 is a prerequisite of course 2, and course 1 has to be done before we can proceed to course 2. So that is why there is an edge from 1 to 2. Same way, we must do course 2 before we can proceed to course 3. So we must do course 2 in order to proceed to course 3, and this is also a prerequisite. And this is a graph that is being made based on the number of courses and the array of prerequisites that we are given. Now our aim is to find any legitimate offering. So in order to find any legitimate offering, the logic is going to be quite simple. What we are going to do is we are going to pick any single node and we are going to do a depth first search. Now in the depth first search, we will have to keep track of like 2-3 items. First thing we will have to keep track of is that there are no cycles. If we find cycle, basically we have entered a scenario where we are not able to complete all the prerequisites. Say for example, in this case, if we are given an additional node that looks like this, or sorry, an additional edge that looks like this. So in this case, we have actually detected a cycle, and because we have detected a cycle, there is no way for us to complete all the courses. So definitely in this case, we will have to return an empty array. But lucky for us, in this case, we are not given a prerequisite that looks like this, right? So we found no cycles. Second thing we need to do is we can pick any single node, and from that node, if we start iterating over all of its neighbors in the DFS manner, and then keep a track of all the elements that we have visited, by doing that we won't be able to find any cycles, and also we will try to order them in a manner that we match all the dependencies, and in the end we simply need to return the ordering. So this is going to be a perfect logic to solve this problem, that we are taking consideration of everything. Now let's see that we know the core logic, that how we are going to use it. Let's see how we are going to implement it. So in this case, we have total 7 courses that we need to take care of. And for all of these 7 courses, I also have a prerequisite array. Now, based on these two things, we know that for any single graph problem, we need a way to represent the entire problem in a graph manner. So how we can do it is we have 2 ways. We have adjacency list and adjacency matrix, right? So in this case, I think we are good with going with adjacency list rather than adjacency matrix, because the graph is not going to be too sparse. And so let's try to stick with adjacency list. Now, based on this given array, we would be able to create our adjacency list. Now, how we are going to create our adjacency list? Well, basically for adjacency list, we are going to create a hash map. Now inside this hash map, we will have to take care of 2 values. First one is like the key, and second one is its value. So as a key, we are going to take all the courses that are present, and as the value, we are going to take that which courses, like for that particular node, for whom it is the prerequisite. Again, I'm repeating myself. So as the node, we are going to take all the courses. So basically the nodes are going to be 0, 1, 2, 3, 4, 5, 6, 7 over here. And as its value, we are going to see that for what are all the courses it is a prerequisite for. So let's try to draw our graph and also fill up our prerequisite table. Okay, so based on the given prerequisites, we have been able to draw our graph. Now, if we see on the graph, our graph is only for our explanation. Basically, all we will have to do is we will have to create our prerequisite adjacency list that I mentioned. Now, in the hash map, these are all the nodes or the number of courses as mentioned. And now let's try to keep on mentioning their prerequisites. So first we will see that for what are the courses, 0 is a prerequisite. So from the graph, we can actually take a look at this prerequisite array as well. But the thing is, I feel it would be better if we just do it from the graph. It would be easier to visualize. So in this case, basically course 1 and course 2, these are the two neighbors, or these are the two edges that derive from course 0, which means unless completing course 0, we cannot complete course 2 or course 1, because for both the courses 0 is a prerequisite. Same goes, okay, let's see for course 1. Course 1 is actually a prerequisite for course number 6. Okay, that's cool. For course 2, okay, course 2 is a prerequisite for course number 4. And 6 actually has no prerequisites. Okay, now we have done half of the work. We have created our graph. Now the question is how we are going to traverse the graph, how we are going to make sure that we are finding cycles, and how we are going to keep track of all the answers, that what should be the correct ordering. So these are the three tasks we will have to do. So the traversing part is pretty easy to solve. We are simply going to use a DFS and we will keep on iterating. The question is how we are going to detect cycles, whether they exist or not. In order to do it, basically from any single node, if we are going to do a DFS, we will have to keep track of that at any given position. We are not coming back to that particular node that from where we started. So we will have to find a way to keep track of all the visited nodes. So one of the best way to keep track of visited node is using hash set. So we are going to use couple of hash sets. And there is also another trick where we can give the nodes some numbers and or some colors where we can treat them as such that whether they have been visited or not. But for explanation purposes, let's just keep track of hash set. When we go to the coding, we are going to use it differently. Now we also need to keep track of the ordering. The idea we are going to use over here is that we are actually going to use a stack. Initially the stack is going to be empty, and from whatever the node we started visiting, we will keep on visiting until we reach to a point where it does not have any prerequisites or all the prerequisites has been met. Once we get to that point, we would add that course into our stack. Eventually our stack is going to be full. And remember, the idea of a stack is that in the stack we keep on adding all the values. When we pop off all the values in the reverse manner, then we add it. So basically we are adding the first value inside that contains basically all the prerequisites, and then we will keep on adding values on top of it. So the top value inside our stack is going to be a value that contains no prerequisites, and then we will keep on popping one value at a time, and in the end we should be able to get our answer. So after this long explanation, let's see all of these things in action. Okay, so now we have our structure ready. I have created an adjacency list over here. Now for this adjacency list, first of all, we are going to do DFS. So I'm going to keep track of that what element we are DFSing over. For any single DFS that we are doing, we will also have to keep track of the current visited nodes that we are going through, because during the DFS, we do not want to find any cycles. So if any element appears in the currently visited elements during the same DFS, we would know that we have encountered a cycle, right? Suppose we do not encounter a cycle and we reach to an element, say for example like 6, that does not have any prerequisites, then we can simply conclude that that node is a good node to be added to the stack. So we will simply add it to the stack. Once adding to the stack, we will also add it to the node of visited nodes. What this would do is, this would allow us not to do redundant work or not to do duplicate work. So let's see the whole calculation in action. Okay. So first we are going to start DFSing over the first element. So we are going to start with element number 0. If we start with element number 0, what are the neighbors or what are the values for element number 0? Okay, so first value is value number 1, right? So currently we are visiting, okay, initially we started our visit with element number 0, then first element we are visiting is currently 1. Now we are going DFS, which means we are going in depth. So even for node number 1 we are going in depth. So node number 1 has is a prerequisite for course number 6. So which means if we want to get to course number 6, we will have to go through 1. So now we will go to course number 6. So currently we are visiting course number 6. Now course number 6 does not have any is not prerequisite for any of the courses, which means this is wonderful. So now what we can do is we can conclude course number 6 to be done. So we will take the course number 6 value from here and we can actually add it to our stack. So if we add the value number 6 to our stack, okay, now we have added a value number 6, which means course number 6 we have already put the ordering for that. If we put the ordering for that, which means we have already visited that course. So we are going to add an entry in our visited hash set. Now let's go back. Now if we go back, okay, we still have one more element 1 that we haven't processed, right? So if we check for element 1, does it has any other prerequisites or is it a prerequisite for anything else apart from 6? No. So which means this is done. So for 1 we do not have any more courses where 1 could be a prerequisite, which means 1 can also be added to stack. So we will add entry number 1 to the stack as well, and also at the same time we would define 1 has also been visited. Now we go back to course number 0. So for course number 0, currently we have taken care of this course number 1, but we haven't taken care of this course number 2. So we will keep on iterating. So currently now we would visit course number 2. For course number 2, do we have any ways to go to next course? Yes, we need to go to course 4. We will have to go through course 2. So we can go to course 4. Now for course number 4, is it a prerequisite for anything else? Yes, it is a prerequisite for course number 5. So in order to go to course number 5, we have to go through course number 4. Now for course number 5, okay, course number 5 can go to course number 6, but the thing is 6 has already been visited, so we can ignore this case. If we ignore this case, course number 5 is no longer prerequisite for any other courses, which means now course number 5 is actually ready to be added to our stack and also visited hash set. So let's do that. We will remove course number 5 from here. We will add that 5 has been visited and we will add an entry 5 over here. Awesome. Now we have course number 4. So for course number 4, okay, apart from 5 it did not add anything else, so which means course number 4 is now also eligible to be added to the stack. So we will visit course number 4 and we will visit course number 4 to our stack. Now for course number 2, let's see if there are any more entries. No, there are no more entries. Awesome. So now we will put course number 2 over here as well. So 2 added and also 2 added, 2 removed from the current stack. And now we are back to the course number 0. For course number 0, okay, we already took care of course number 1. Now we also took care of course number 2, which means 0 is now also eligible to be added. So awesome. Let's do that. So we add 0 over here and we add 0 over here. That's great. Now if we go back, this has been jumbled up. So let me clean this up a bit. Now in this case, okay, now we took care of course number 0, right? Now for node number 1, we will check our visited hash set. So in the visited hash set, yes, we have already visited course number 1, so we don't need to do anything. Course number 2 has already been visited. Awesome. Course number 3 hasn't been visited. So now for our current DFS, we will start visiting course number 3. Okay, so for course number 3, it has many different prerequisites. So course number 3, okay, course number 3 is a prerequisite for course number 1. So currently we are visiting course number 3. Let's see, course number 1, okay, 1 has already been visited, so we do not need to visit this one. 4 has also been visited, we do not need to visit this one. 5 has been visited and 6 has been visited, which means all of the courses which could lead us to these courses have been visited, which means course number 3 is no longer prerequisite for any other courses. So it is a good candidate to be added to our stack and our visited hash set. So we can add it to our stack and we can also add it to our visited hash set, right? Awesome. Now if we see our stack is already full, so do we need to worry about adding these more courses or checking for them? No. But if we want, we can do it. It would only be constant time because all of them, they have already been visited, so we don't care. Now since we have our stack ready, let's try to pop out all the values sequentially. If we pop out all the values sequentially, this is going to lead us to our answer. Why? Because, okay, first we have to complete course number 3, then 0, then 2, 4, 5, 1 and 6. If we complete courses in this manner, we would be able to meet our prerequisite. So let's see that whether our answer that we received is this a valid answer or not. Let's compare it with the graph that we created. Okay, so now we have both the values side by side. Let's see if we start iterating. So if we first complete course number 3, then we would be able to finish a lot of different courses. So we won't have any prerequisites for course number, all of them have some other prerequisites, but if we do course number 3, there is no harm, so that is good. If we do course number 0, that is also good, right? Now can we do course number 2? Yes, course number 2 only has prerequisite on 0, which we have already completed, so we can do course number 2. Can we do course number 4? Yes, course number 4 can also be done because it had prerequisites on course number 2 and also course number 3. Both of them have been done. Awesome. Now for course number 5. Okay, 5 can also be done because it had prerequisites on course number 3 and course number 4. Both have been completed. Course number 1. Course number 1 only had prerequisites on course 0 and course number 3. Both have been completed, so we can do that. And also for course number 6, it had actually prerequisites on course number 1, 3 and 5. All 3 of them have been completed before. So this is a legitimate valid ordering that we can use. And this is a great way to solve this problem. See, time and space complexity. In this case, the time complexity is actually going to be big O of v plus e, where v is the number of vertices and e is the number of edges. And if we see space complexity is also going to be big O of v plus e, and this is a great example. And also the way to find this ordering is also topological sort. So congratulations to you, you also learned a new algorithm. So since this video is already too long, the code solution for this problem, I'm just going to explain it and then paste this code in the comments so you can check it out from there. Okay, so first of all, we are actually doing things a little bit differently than what I explained. Basically, we are creating 3 different like white, gray and black values. So this is going to be assigned to every single node. White is going to represent that the node hasn't been visited or it hasn't been touched so far. Gray means that during the current DFS, this has already been visited. And black means the code that is already going down into the stack or that we have created, which means from where we can fetch it and use it for the answer. Now let's go to our main method first. First, we have this find order method where as an input we are given number of courses and we are also given prerequisites. Now first thing we need to do is that based on the prerequisite, we are actually going to create the adjacency list. This is what we are going to create as I explained in the explanation. Now after this adjacency list, we are going to assign every single value to the white color for the first time. Why white color? Because it hasn't been added to any list or it hasn't been visited. And then we are going to go over every single values of this adjacency list and call our DFS function. Now what does this DFS function is going to do? It is going to recursively call all of the values or all of the neighbors of that particular node until we reach to the end. Now let's see what happens inside the DFS function. We receive a node as an input. Now we have a boolean value is possible. That is going to check that whether we have been able to find any cycle or not. And how we are going to be able to find a cycle? By using this gray color. So if a node that is already assigned a gray color and somehow in the DFS we find it to be gray again, which means we came back to the same node which we have already traversed during our current DFS. So there is a cycle present. So this is a good way to detect that. And for that we just created a different method that if the given color is gray, we simply get the DFS method. We simply assign the values is possible to be false. Okay, now in this case, first we assign the value to gray for any particular node that we are visiting. Then we start visiting all of its neighbors. Now for every single neighbor, we are only visiting the node that the color where the color is white. If the color is black, we are going to ignore that. If the color is gray, we are going to assign the value is possible to false, which means that this is not possible to do it and we can simply return an empty array in that case. If not, basically recursively we are going to call our DFS function for every single neighbor, and for every single neighbor we are going to assign the value to gray, and we are going to keep on doing it until we reach to a point where it does not have any more neighbors left. So at that time we are going to put the node and assign it to color black, and also we are going to assign it to a topological order list that we have created. Recursively, if we keep on doing it, basically our topological order list is going to be basically our stack where we would have all the values filled up. And once that is done, from our main method we will check that, okay, if this is possible, if that is true, which means if this is still possible, then we will simply iterate over all the number of courses, and we are going to create a new array called order. For this order, we are going to take all the values in the reverse from the topological order, and we are simply going to return the order list that we just created, and this is the whole solution. So I would be posting this in the comments, so I hope you understood it. And if we try to run the code, this runs perfectly fine. If we try to submit the code runs decently efficiently. And yeah, so let me know in the comments what do you think about this. So the LeetCode problem we are going to understand now is called redundant connections. This is one of the most popular questions in my opinion. Why? Because we are going to be dealing with graphs. On top of it, we are also going to be learning about the trees, a data structure, and we will learn a new data structure called disjointed set union. So this problem contains two of the most popular data structures that we already know, and one very popular method that can come in handy in all sorts of different cases. So let's understand what this problem statement is asking us to solve. First, we are given the difference between a tree and a graph. The only difference between a tree and an undirected graph is that graph is connected and it can have cycles. Meanwhile, tree is completely connected and it can never have any cycles. That is the only difference. Now we are told that we are given a graph that was originally a tree, which means it could be possible that this graph may be not connected or it may contain cycles. Okay, this is the important clue, that originally this was a tree, but then it turned graph and now it is no longer tree, which means there has to be some cycle existing inside this given graph that contains total n nodes, and we are given the number of nodes as to be 1 to n. On top of it, we are also given an edges array that defines that any particular edge between any two array 1 to 2. Now the thing is, we need to return an edge that if we remove it, so that the resulting graph actually becomes a tree of n nodes. That's it. So we need to basically remove an edge that is part of the cycle, that removing that edge would not have any impact on all the nodes of this particular graph or tree from being connected. And if we can remove that, then basically there should not be any cycles inside the existing graph. So let's try to understand this with few examples. Let's say that we are currently given three nodes, 1, 2 and 3, and we are given bunch of different edges between them like this one. So in this case, we can clearly see that this is not a tree. Why? Because there exists a cycle inside this loop, and wherever there is a cycle, it can never be a tree. So this is currently a graph. But imagine in this case, if I just remove this particular edge between these three nodes, then this is a very clear example of a tree. Why? Because we can see that it currently has three nodes. All three nodes are connected with each other, because that is one of the conditions of being a tree, that all the nodes has to be connected. On top of the connected portion, we can also see that there are no cycles, which means that removing 2 to 3 was one of the good decisions. And in this case, we need to return 2 3 edge as part of the answer, that if we remove this edge, then we can completely generate our answer. Now the question comes that why do we only decided to remove edge 2 to 3? In this case, if we had removed an edge, let's say 1 to 3, then also the answer would have been perfectly fine. We would still have a tree that looks like this. But thing is, we are given in the problem that if there are multiple answers that we can remove the edge, then we need to return the answer that occurs in the last input, which means like the last edge in this case made sense to be 2 to 3. So that's why we removed 2 to 3 and not 1 to 3. Okay. So now we already understood that what does the problem statement is asking us to solve. Basically, we are given a graph that contains bunch of different endpoints, and amongst some endpoints there exists some sort of cycle. and we need to first of all detect that which particular cells contain are part of the cycles or which edge is part of the cycle, and then try to see if we are able to remove that edge or not. So if we once again take one more example, in this case once again we can see that removing this edge from 1 to 4 makes no sense. Now why? Because it does not solve our problem. Number one, there is still a cycle persisted, and number two, now we have unconnected components, so this is no longer a tree. This is always going to be a graph. So logically in this case the answer once again has to be the same one, that we need to remove the edge between this 2 and 3, and by doing so we are still going to have a tree like structure where this one node is parent of 3 different nodes, that is 2, 3 and 4, and this is what we need to do. So once again we need to remove this 2 to 3. Now let's understand that what I'm suggesting we use to solve this problem, and for that I'm suggesting to use a very popular data structure that is called disjointed set union. Now first let's understand that what does this disjointed set union data structure is. So this data structure actually only has two properties, but these two properties are very important and very awesome properties. So first let's understand that what are the two properties. Basically disjointed set union allows us to create a groups of set, and that's it. So it can show us that if we have like bunch of different objects or values, it can show us that that particular object belongs to which group, and if we provide two different objects, it can say that whether those two objects are part of the same group or not. So let me explain it to you, then it would make more sense to you. Let's say, so I mentioned that this disjointed set union works with two methods. First method is a find method, where if you provide in some value, then it can say that this value belongs to which group. Okay, on top of it, second one method is a merge method. So for the merge method, basically if you provide two distinct data structure, like two distinct objects that belongs to separate groups, then it merges into one common group. So let's see how it works. Let's say that currently I have these 3 nodes that are part of this one particular group. Okay, and let's say that I have these 2 nodes that are part of this second separate group. Typically in a disjointed union set, all the nodes are typically represented by some node that is currently present already inside that particular group. So let's say we randomly select that this one is the leader or the representative of this entire group. So we will call this as a group 1. Okay, that every single node that is currently present is being represented by this value 1, so we can call this as group 1. Same way over here, the representative is this value number 4, so we can call this as group 4, where every single node is being represented by group 4. Now we know that we can do two methods. We have the find method and we have the merge method. So let's say that if I try to do a find method and if I try to find value number 3, so if I try to find value number 3, all I am going to get in the return is that this value number 3 is part of this group 1. So in the answer, I would only get value as group 1 and in the return. Why? Because all of these nodes are represented by their parent node or by their representative, and representative in this case becomes like the parent of all the nodes that are part of this particular group. Same way, if I try to do a find operation and if I want to find value number, let's say 5, then in this case the answer we are going to get back is going to be group 4, because this value number 5 is part of this group 4. Now let's say that we wanted to do a merge operation. So the moment we do merge operation between group 1 and group 4, then both of these are going to be merged into one single set, one common set. And how it is going to operate? Number one thing, this property is going to remain as it is. Now we have two options, which who is going to be the representative from 1 to 4, either 1 or 4. We can pick whoever we like. So let's say that in this case we decide that representative is going to be 1 of this common jointed group. So how this group is going to look like, that 1 is the representative. It already had values 2 and 3, so it is going to continue to have values 2 and 3 that represents or who has parent value as 1. But same way, now we are also going to add one more node 4 whose parents or representative is now going to become value number 1. And for this value number 5, it is still going to have 4 as one of its parents. But now for this newly created group, if we try to find that any particular character, let's say if we want to find value number 3, then for value number 3 we are going to say that value number 3 is part of group 1. So in the answer we are going to return the value as group 1. Same way for value number 5, if we try to do that, in this case once again we are not, previously we were returning value number 4, but remember now value number 4 is also being represented by value number 1. So once again for value number 5, the same property is going to be inherited to value number 5 as well. And now for value number 5, we are also going to say that this is part of group 5. So this is the whole concept of a disjointed set union. But the thing is, why the hell am I explaining you this concept? What purpose this serves us? Now let me show you that how we can use this method to actually solve our problem and very effectively find or detect that whether there exists a cycle inside any particular graph or not, or cycle does not exist. And remember, whenever you have to find a cycle in an undirected graph, then this is a very popular method in order to do this one. So not only we are learning about the redundant connection LeetCode problem, we are also learning a new method, a new algorithm, a new data structure with our existing tree and graph data structure. And that's why this is a beautiful problem. Okay. So coming back to the solution. Now remember the problem statement that we needed to find that amongst these 3 nodes, let's say that if there exists a cycle, like amongst these 4 nodes, we don't know where the cycle exists. If there exists a cycle, we will need to remove the node that is causing the cycle, or sorry, remove the edge that is causing the cycle. And once we find that, we need to return that as part of the answer. So let's say that currently we are given these 4 nodes, okay? And we are being told that these are the edges we are currently given. So what we can do is, currently we can create 4 separate groups, and these groups are not connected with each other. So if we create 4 separate groups, how it is going to look like? We will have a group 1, we will have a group 2, we will have a group 3, and we will have a group 4. Currently these 4 groups are not connected with each other. So we can actually have a disjointed union set that is currently present, that represents that for every single node, who is the representative or who is the parent of that particular node. So if we want to define that, currently we can have a parent array, let's say, and for every single node we will try to define that who is currently the parent of that particular node. So since this one is being represented by its own, so the parent is going to be 1. Same way the parent for this one is going to be 2. Same way the parent for this one is going to be 3, and so on and so forth. So currently all of these 4 nodes are unique on their own. They don't share any parents so far. Now what we are going to do is we currently have 4 edges that we need to deal with, and let's mark these 4 edges. So the first edge is 1 to 4, same way second edge is 1 to 2, the third edge is 1 to 3, and fourth edge is 2 to 3. Okay, so logically if this is the case, now we currently have parent for each 4 separate sets. We are going to start iterating over the edges. For every single edge, we are going to check that what are the current parent groups we have. And if we identify that they contain separate groups for both the vertices of this edges, then we are going to do a merge operation. Okay, let's start doing that, and then you will understand. So currently we are dealing with edge 1 to 4. Now for this edge to 1 to 4, we will have to check that which are the vertices involved. So number 1 vertices is value number 1, number 2 vertices is value number 4. So for both of these, we will check we will do a find operation that who is the parent of those particular sets. For 1, the parent is already 1. For 4, the parent is currently 4. So both are separate sets. There is no commonality. So if there is no commonality, we will do the merge operation over here. So if we do the merge operation, what will happen is we are essentially establishing a link between this node 1 and node 4. So by doing the merge operation, now we will have to select that who is going to be the representative. So let's say that we are going to choose the smaller value as the representative. So I choose representative to be 1. Now if I choose the representative to be 1, which means now even for this 4 the parent is going to be 1 because 4 is being represented by 1, and for the value number 1 the parent is going to be itself. So we will have to make some adjustments to our parent array. So this value number 1 is going to stay as it is, that it is currently the parent of its own, but for this value number 4 the parent is going to change, and now this is also going to be represented by value number 1. Okay, we completed this operation, and now we have made the updation on the parent block, and we also are done with this 1 to 4 edge. So now let's take care of 1 to 2 edge. Once again repeating the same operation, we have two nodes 1 and 2, and for both of them the 1 has parent as 1 and 2 has parent as 2. We can see over here. But now since both are separate, so we will have to do the merge operation. If we merge these two cells, once again we are establishing a link between this 1 and 2, establishing a link between 1 and 2 now, which means we are also updating the parent of this 2 to be value number 1. Okay, and now the next edge we currently have is once again edge 1 2 3. So once again for 1 2 3 it currently has 1 and 3 as separate nodes. If we take a look at the parents, it is going to be 1 and 3. If we do the merge operation, because they are separate links, so if we do the merge operation, we are going to have our parents array that is going to look like all 4 values are being represented by 1, because we are also establishing this link as well. Now this is our parents array, all 4 values contain 1, but we still have one more link that we haven't tested, and that is this link 2 to 3. So let's do that. For this 2 to 3, if we see, we currently have vertices 2 and 3 as part, but now when we check for the parents, we can see that the parent is going to be common, that is going to be 1 and 1 for both 2 and 3. So this is going to be common. The moment we identified common parents amongst any two vertices, we can clearly say that if we were to create an edge between these two nodes, that edge is already part or is going to be part of the common nodes that are already connected in a common set. So creating this new edge is only going to lead to creation of cycle. And the moment we identify any two nodes that share a common parent, basically we can just return that edge as the answer. And this is the whole solution basically. So you understood how beautiful the solution was. We first of all understood that how a disjointed union set works. Then we understood that what is the difference between tree and a graph. Then we understood that how we can use disjointed union set and its property to find or update the parent values or create new links between any two vertices. And then we find the edge that is causing all sorts of trouble and return that as part of the answer. So this is a beautiful solution and a beautiful approach. So now let's quickly see the coding solution for this one. Okay, now the coding solution for this one is not so complicated. So let's try to understand what is being asked us to solve. First of all, we need to check that for any particular given node, we will have to define that what are all the different parents. So first we are going to initialize a new array called parents, and notice that we are setting the value as edge length plus 1. Now we are starting to iterate parent from 1, not from 0, because initially each node is its own parent, and we are being told that the current nodes we have are 1 to n, not 0 to n. So that's why we are starting from 1, and we are marking all the values as their own parent, which means all the nodes are currently individual sets of their own. Then we are going to iterate through every single edge in order to find the redundant one. The moment we identify a new edge, we are going to break both the values in part of two nodes, node 1 and node 2. For both the nodes, we are going to be finding the parents of those nodes, node 1 and node 2. And for that, we are going to be calling our find method that we have defined. Next, we need to check that if at any given moment we identify that the roots are same for both node 1 and node 2, we need to return that edge as the answer, because that edge is causing all the trouble and creating the cycle. If that is not the case, then we need to update the root of that particular second, like the parent of second root, to become the value of the first root. And this is what we are doing, is the union or the merge function amongst our two values. So let's quickly try to see the helper function we have created, that where we can actually use to find that who is the parent of that particular node. Basically, we are simply checking that if the node is not the node we currently have, if that is not equal to the parent node, we are simply going to keep traversing up in order to find that which is the parent node, and we are going to be updating the value of the parent node. That's it. It's very simple, and we are returning that value. So basically we should be able to calculate everything. Now this is just a return statement that is ideally just returning the value 0. Basically this should never happen, because we are being told that for every single input we do have a graph that contains a cycle and we need to return proper edge. So we should be able to find a scenario like this. Now let's quickly try to run this code and see if our solution is working as expected or not. Seems like our solution is working beautifully. Let's submit this code. And our code beats 100% of all the other solutions, which is awesome. In terms of memory usage, it is exceptionally well. So in both aspects, this is doing wonders, and this is a really good solution. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do number of connected components in an undirected graph lead code problem. This is a graph theory problem, as you can see from the name. And this problem has been asked in one of my favorite companies: Amazon, LinkedIn, Facebook, Pinterest, Microsoft, Google, Bloomberg, Apple, Twitter. So these are all my dream companies. I want to get a job at any one of them, and that's why I'm making these videos. So I would be paying my utmost attention. I hope you enjoy the video. So this is a LeetCode medium problem, but in my opinion this should have been an easy problem. And if we look at the problem statement, we are given n nodes of a graph, and we are given an array of edges, and those edges are undirected, which means if we are given an edge like this, that A to B, which means we can say that we can go from A to B and we can also come from B to A. Now we need to return that based on this given input, how many different kinds of connected component there exist inside the given graph. So over here we are given an example with 5 nodes, 0, 1, 2, 3 and 4. These are the 5 vertices of a graph, and we are given some array of edges. Based on these arrays, we are able to see that there exist this is the graph, and there exist these two different set of connected components. So over here, because there are two connected components, we need to return two. Suppose we could have given some example like this, that 0, 1, 2, 3. So this is one connected component inside the graph. Then there is also one more node that is isolated, and then there is one more node that is something like 5, 6, something like this. So in this case, how many different connected components we can find? So if we see over here, the number of different connected components we can find is 1, 2 and 3. So in this case, we would iterate over this given input, and we would say that, hey, there exist 3 separate connected components. And let's see that what could be the intuition behind the solution for this one. Okay, suppose we are given a custom example like this, and always remember that it is really important to come up with your own custom example in any interviews. So suppose we are given a custom example like this, where the number of nodes we are given is 8, and these are list of edges that we are given. Now based on these edges, we are able to form a graph like this, and we can imagine that there exists a graph like this. Now over here, if we just look at it, we can understand that there exist 3 separate components that are connected with each other inside this given graph, and in this case the answer is going to be 3, and we need to return that. Now the idea is that first of all, based on this given input, we will need to find a way to iterate over this given graph. Now to iterating over this given graph can be a little bit tricky, and the best way to do it in any computer language is to use adjacency list or adjacency matrix. So we can use either one of them. So in this case, we are going to use adjacency list. Usually we use adjacency matrix when the number of edges are far more than the number of nodes, and we don't have any clear indication that that would always be the case in this scenario. So it's better to go with adjacency list. Now once we have our adjacency list, it becomes easier for us to iterate over these given nodes, right? So we have solved a part of problem, but the other part of problem is that we need to find that how many number of connected components there exist. Now in order to do it, basically we need to find a way to keep track of whatever the nodes we have visited so far, and the best way to do is to create a hash set. So suppose we create a hash set and we keep track of all the visited nodes that we have visited so far. Now the approach we are going to use is that initially we are going to start at the 0th position. Now from the 0th position we are going to run a DFS in this case. And then why DFS? Because the DFS has a very particular property that it starts iterating from one element and it will continue to iterate till it can reach all the subsequent elements or all the subsequent neighbors of this initial element. So we are not going to stop up until then. And how we are going to use visited hash set is, let me show it to you. So essentially we will start our function with the 0th position. We are first of all going to check that whether the node we are currently visiting, is it present in our visited hash set or not. So 0 is not present, right? Which means we will have to add 0 over here. So we add 0 over here now. And at the same time we are starting our DFS function from the 0th position. So we are going to have a variable called counter, and initially this counter is going to be initialized at 0. But now since we have started our DFS function, so we are going to initialize our counter as 1. Now from this 0th position we are going to see that okay, it has a neighbor 1. So we will check that whether 1 exists in the visited hash set or not. It does not exist, so we will add 1 over here. So now this 1 has been visited, and then we see that 1 has a neighbor 2. So again we will come back at 2. 2 has not been visited, so we will add the value 2 over here. Now all the nodes in this case have been visited. That 0 has been visited, 1 has been visited, and 2 has been visited, which means we don't have any more nodes to go to. So we will just end our loop over here. And now in our adjacency list, because we have already checked this 0, 1 and 2 nodes, so we won't be doing anything for them because they have already been visited. Now we will come at this node number 3. Now again this node we are at this node number 3, and this has not been visited, and this is a new starting for the DFS function. So every time we do that, we are going to increment our counter function. So now the value of counter is going to be 2. So we will add the count to be 2. And again we are going to repeat the same process. So this 3 has not been visited, so we will add an entry over here called 3. From this 3 it has neighbor 4 and 5. So again 4 and 5 have also not been visited, so we will add an entry over here. And once all of them has been visited, which means that we no longer needs to iterate over these nodes because they have already been visited and their count has been accounted for. And because they were connected, so we only need to increase counter once when we start the DFS function. We do not want to increase the counter for all the nodes that are present. And once that is done, so these all nodes are taken care of. Now we are at node number 6. So again we start the DFS function from the scratch. So we will have to increase our counter. So we are going to increase our counter to value number 3. And now we are going to add the values to hash set. Inside our hash set we are going to add value number 6. So we are done with this one, and now we visit value number 7 as well, and we are done with this one. So now essentially we in our visited set we have visited all the number of nodes that were originally given as part of input. And at the end of this we simply need to return whatever the value of counter function we have found. So in this case the counter we have found is 3, and this would be our answer. So basically this is the simplest approach. It's very easy to understand, very easy to explain in any interview. And I don't know why LeetCode put this as a medium problem. This should have been easy problem, as I mentioned it from the beginning. Now if we calculate the time and space complexity, in terms of time complexity, essentially we are doing a couple of things over here. So first thing we are doing is we are creating an adjacency list. Then after creating this adjacency list, we are iterating over all the values that are present inside the adjacency list in form of graph. So the time complexity in this case is actually going to be big of v plus e, where v represents the number of vertices or nodes and e represents the number of edges, because at any given moment we will have to iterate over all the number of nodes and all the edges that are present. In terms of space complexity, so for the space complexity, essentially it's going to be the same. It's going to be big of v plus e. And why? Because we are storing this adjacency list, which is essentially the combination of vertices and edges. And we are also storing this visited hash set. So but in this visited hash set we are only storing all the vertices. So this is actually big O of v only. So essentially the space complexity is going to be big O of V plus E for adjacency list plus big O of V, but generically we can write it as big O of V plus E. Any interviewer would be satisfied with this answer. So first of all, we are going to create a variable counter and we are going to initialize it to value 0. And now we will initialize an array called visited. And I know that I mentioned that we are going to use a hash set, but we can also use an array as well. And initially we are going to initialize this array with the size n. The reason we are not using hash set is because it was causing some issues with in Java by passing by reference and passing by value. So I'll try to probably work upon that separately. And now we will create an adjacency list, and we are going to store all the nodes and edges inside our adjacency list. We will run two for loops, one to add all the nodes and one to add all the edges. And now we are going to iterate over every single node, and we are going to check that whether that node has been visited or not. If not, we are going to initialize, we are going to call basically our DFS function, and we are going to increase the counter as well. And when this for loop ends, essentially we only need to return whatever the counter whatever the result of counter variable we got. Okay, now let's create our DFS function. So first of all, we are going to mark the current node as 1. So we know that we have already visited this node. And now we are going to run a for loop for all the neighbors of this particular node, and we are going to call the DFS function again recursively. And notice that we are only calling DFS function for all the nodes that we haven't visited. And this should be it. Let's try to run our code. Okay, seems like our solution is working after a bunch of different compilation errors. Let's try to submit this code. We have some solution seems to be working as expected, and I would be posting this in the comments so you can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a very important LeetCode graph problem, graph valid tree. Basically we are checking that whether the given graph is actually a tree or not. And this question has been asked in a bunch of different top tier companies, companies like LinkedIn, Google, Amazon, Bloomberg, Microsoft and Facebook. So these are my dream companies, so I'm paying my utmost attention. I hope you enjoy the video. Okay, so this is the LeetCode medium problem, and we are given n number of nodes. We are also given a list of edges, and we are told that these edges are actually undirected edges. Now we need to see that whether the given graph is actually a valid tree or not. If it is a valid tree, we'll return true. If it is not a valid tree, we'll return false. And we are also given an example to understand this problem. Like in this example, we are given these 5 nodes and we are given some list of edges. Based on this list of edges, they have shown that this could be a pictorial representation. And over here, they are saying that, yeah, this is a valid tree. So that's why they are returning true. Now the question is, in order to understand this, first of all, we will have to understand that what is the relationship between any graph and a tree. What is the difference between a graph and tree, and how can from the given input we can identify that, okay, this is a valid tree or not, right? That every single tree is also a graph, but that is not the case for every single graph, that it will always be a tree. Because if I put it in Venn diagram, essentially graph is actually a superset, and tree is just one of its subset. So this can be a tree, and this is a graph. There are a lot of real life cases to understand that as well. Like the person who got slapped by Will Smith is always going to be a human, but not every single human has been slapped by Will Smith. It is something, that kind of relationship, right? Now the thing is, what are the differences between a graph and a tree? That inside the tree, all the components are connected. or all the nodes are connected. There is no restriction for graph that all the nodes should be connected. And the second difference is inside any tree we will never encounter any loops. So we can just say no loops, while inside the graph there can be loops. Let's try to understand this with some examples. Is this a valid tree? Actually yes, this is a valid tree, because notice over here that from one node, like every single nodes are connected with each other, and we do not find any single loops. But the thing is, say for example in this case, if I had an additional edge something like this, I can clearly see that there exists a loop between these four nodes, and because we have identified a loop, we can clearly say that this is a graph, but this is not a tree. Now let's take another example. Now this is a valid tree, like all the nodes, they satisfy these two properties, that they are connected and there are no loops. The same graph, if I had some components like this, some additional nodes, though they are not connected with all the nodes, they are connected with each other, or there are some isolated nodes, something like this. If this is the case, this will always be true that okay, this is a graph, we can put it in the category of graph, but this will not be a tree, and in this case we will need to return false. Now before we move on towards solution, I just have a simple request. If you see, a lot of people, they watch my content but they are actually not subscribed to my channel. It takes me a lot of time and a lot of effort to make these kind of videos, and I would really appreciate if you can just show your support and subscribe the channel. Like, now this problem actually can be solved in so many different ways, and I'm going to show you few different ways on how we can do things. Now the question is, what we need to find basically we need to find that whatever this given input is this a valid tree or not. In order to find that whether it's a valid tree or not, we need to check two things: whether all the nodes are connected, and if there are any loops or not, right? So what I'm suggesting is that we break this problem in two parts. In the first part, we check that what could be the different ways we can see that whether these nodes they are connected or not. If they are all connected, we are good, and if they are not connected, we can return false immediately, that this is not a valid tree. And once that is done, we will find all the ways on which we can identify that whether there are any loops or not, right? So first let's go with the first approach. Now our aim is to check that whether all the nodes are connected or not. What could be the different things we can do over here? In order to check that, essentially what we will need to do is we'll have to traverse over whatever this given input graph is. Now traversing over this given input graph based on the structure we are currently given in the input is going to be a little bit tricky, based using this number of nodes and edges. So the question is, like, first thing we need to do is we will need to convert this given input in either adjacency list or adjacency matrix. Either of them can be used and it will work perfectly fine, but in this case I will suggest to use adjacency list. We only use adjacency matrix when there are too many edges. We don't have any clear indication in this case that there would be too many edges, and we would try to use an adjacency list, right? So now we are trying to check that whether all the nodes are connected or not, and we have already created our adjacency list. Now what I'm suggesting is that through this adjacency list, we know that we would be able to iterate over this given input, and through this given input, what we do is we create a hash set. Inside the hash set, initially it would be empty. Whenever we are at any point iterating over any single node inside this given hash set, we will check that whether that particular node already exists in the hash set or not. If it does not exist, we will add a new entry inside the hash set. And at the end, once we have traversed all the values inside the given input through this adjacency list, what we are going to do is we are going to check that what is the total size of hash set and what is the total number of n given. If both are same, we can conclude that from any single point we are able to reach to all the other elements, and because we were able to reach to all the other elements, all the elements are connected, and we at least satisfy one condition. So let's see that how it would work. Suppose in our adjacency list, we start traversing through this position number 1, right? So initially we check that whether this value number 1 exists in the hash set or not. It does not exist. So we'll add an entry over here that, okay, value number 1. Now through this value number 1, we can traverse in two directions. We can either traverse to the neighbor on the right or neighbor on the left. So let's say that we go to this node number 0. Again, we add 0. From this 0, we go to node number 2. Again, we come to 2. Now from this 2, we can't go any way forward, right? But the thing is, we still need to go back. We'll need to do backtrack. We'll go back to 1. Again, through 1, we will go back to 3. Now at this 3, this is not added, so we add it over here. From this 3, we will go to 4. So we will add 4 over here. From this 4, again we will do a backtrack, and we would come back at 3, and then we will come to 5, and then we will add 5 over here. Now at the end of this hash set, we are able to iterate over all the elements inside the given input, right? And we check that what would be the size of this hash set. So size of this hash set would be 6. And what is the given n? So n is also 6, which means in this case we are at least able to conclude that this given hash set is actually satisfying our condition, and inside this given graph all the nodes are connected. So we are good. Now suppose in this case, if we had another node, something like this, and this was not connected to any of them, basically this would not have been entered inside our hash set, and our n in this case would have actually been 7 rather than 6. So we can clearly see that if our size of our hash set is going to be lesser than whatever the number of n we have, if that was the case, we could have written false immediately, because we found that there exists some not connected component, and which was not the case in this case. So this is one of the very good approaches to identify that whether the graph is connected or not. Okay, now we have taken care of the first part, and now we need to take care of the second part, that we need to check that whether in the given graph does there exist a cycle or not. So first thing that comes to our mind is that why don't we use the visited hash set that we have already created. And in that visited hash set, what we are going to do is at any point in time, we are going to start exploring from one of the node in the given input graph. From that node, we are not going to stop exploring till we exhaust all the neighbors of this particular graph. And at every single time we are planning to come to next element, we would first check that whether that element exists in the visited hash set or not. If it exists, then we would consider that there exists a loop, and we would break out of it. If it does not exist, we would add that entry over here. So first we will start traversing this value number 0. So it does not exist in visited, so we will add an entry over here. From this 0, we will start exploring its neighbor. So one of its neighbor is this value number 1. And remember that we are going in depth first search, so we will not stop until we exhaust all the possibility in one direction before going to the other neighbor. We could do it breadth first search way as well. It's up to us. Now from this one, again depth first search, we see its neighbor, that there is a neighbor 2. So we add an entry over here because it does not exist. Now remember that this is actually an undirected edge. So what does an undirected edge means? Undirected edge means that from 0 we have an edge to go towards 1, and from 1 we have an edge to go towards 0. Same goes from 1, that we have an edge to go towards 2, and from 2 we have an edge to go towards 1, and same goes from 2, that we can go to 0 and we can come back. Now over here from this position number 2, because we have an edge that goes to 0, we can consider that 0 is also a neighbor of 2. In this case, from this 2, we will try to go to this 0, and the moment we try to go to the 0, we will see that okay, it has already been visited, it is part of this hash set. So we would say that okay, there exists a cycle, and we are pretty happy with ourselves that hey, we have identified a cycle and now we are done with our case. But the thing is, this is actually a wrong approach, and the reason why it is a wrong approach, it is wrong approach because there exists this undirected edge. And let me show you by an example that what could be the problems if we keep using this visited hash set only, and how can we find false positives. So suppose we are given an example like this, that 0 calls 1 and 2, and that's it. This is the input we are given, right? And now we don't have any entry inside our hash map. Now the thing is, all the edges are undirected edges. Now because they are undirected edges, we can represent them in different manner. So let's represent them in slightly different manner. So from 0 we have an edge that goes towards 1, from 1 we have an edge that goes to 0, same goes from 0 to 2 and 2 to 0. Now initially we start traversing from this 0. Now we have our algorithm that initially we are going to add the entry to visited hash set. So 0 does not exist, so we add the entry towards our visited hash set. Now from the 0 we need to check all of its neighbor before we move on to some other node. Now from this 0, first of all, let's say that we go down this path and we check its neighbor 2. Because there exists an edge like this, we are able to check its neighbor, right? So we are at this position number 2. Now at this position number 2, we don't have an entry in the visited hash set, so we enter an entry over here that this is 2. Now from this 2, again we will need to repeat the same process, that we will need to check for all the neighbors or all the edges that this 2 can point to. Now it does not have any edges that go further, but it has an edge that goes back to 0. Now the thing is, in this case, again we will use our same logic. So from this 2 we can still go to 0. So we will check that whether we have visited this element 0 or not, and over here we find that hey, we have already visited this element 0, which means by our logic that we were previously trying to impose, we could have said that okay, we have found a cycle that looks like 0 to 2 and 2 to back to 0, and we in this case say that hey, we have found a cycle and this is not a tree and we will need to return false and blah blah blah. The thing is, this is actually not the case, and why it's not the case is because of this correlation of having an undirected edge that is causing all this problem, which means that we cannot rely only on having a visited hash set. If we do that, then essentially we are not going to be able to find an answer, because in this case we know that from there does not exist an edge, and from this 2 we are coming back to 0 only because there exists an undirected edge from this 2 to 0, and that's why we can consider this 0 to be 2's neighbor. But in reality this 0 is actually parent of this child 1 and 2. So if that's the case, why are we still doing things like this? What could be a better approach we can use to find that what would be the solution to detect these cycles? There are a couple of different ways where you can tackle this problem. One way to tackle this problem is that initially, remember, the only reason we are causing this problem is because there exists an undirected edge, which means that there exist 2 directed edges from any 2 nodes. So what we can do is we can put a condition that from any point, if we travel from this 1 to is 0 or 2, if we are able to travel in one direction, we would get rid of the remaining edge. And let's see that how it would work. So what I'm proposing is that initially we are at this 0th position. So we check in our visited hash set, we don't have any entry. So we add an entry over here that okay, we are at the 0th position. Now from the 0, first let's say we travel to 1, which means that now we have traveled from 0 to 1 in this direction. So our aim is that we get rid of this reverse edge in our adjacency list. So if we get rid of that, now we are at this position number 1. At this position number 1, again, we add an entry over here in our visited hash set. Now from this position number 1, what we have to do is we will have to check that what are all the neighbors that we can travel to, or all the children we can travel to. But this one does not have any neighbor or children, so which means we don't have to worry about anything. So over here we can say that okay, from this one we can't go anywhere, but thing is there still exists some nodes that we haven't traveled to, and we are using either BFS or DFS in any manner to traverse over entire graph, right? So which means that we will have to do a backtrack. So now from this one we do a backtrack. Now again we end up at this 0. But the thing is, in this scenario, remember, we are not ending up at this 0 because from 1 there existed an edge like this where we consider 0 to be 1's neighbor. We are coming back to this 1 because we are using backtracking through any BFS or DFS algorithm. We can implement this recursively or iteratively, doesn't matter. In any scenario we will have to iterate over all the nodes that are present inside the given graph, and since we haven't traveled all the nodes, that's why we are coming back to the 0. So again this would be a new entry in the visited hash set. So again we come back at the 0, and this 0, we check that okay, we have already explored one of the neighbor of the 0, but we still have to explore another neighbor. So again we repeat the same process. From the 0 we explore another neighbor of 0, we come back at 2, and immediately we get rid of this this edge that was coming back to it, and then we add an entry over here that okay, we are at this position number 2. Now from this 2, again we don't have any more neighbors to go to, so now we have explored all the neighbors of 1, so we can mark 1 as being done. We have explored all the neighbors of 2, so we can mark 2 as being done, and now we come back at this 0 and we can mark 0 as being done because we have explored all the neighbors of 0 possible as well. And in any scenario we did not find any single loop because we did not find repeated value inside our visited hash set, so we can determine that there does not exist a cycle, and which means in this case we can return true because there are no cycles. So we can say that there is no loop for this one. And the only reason we are able to come up to this conclusion is because at every single position we were removing the edge where in one direction we have already traveled. So that is one way to take care of this problem, and this solution would work as expected as well, right? Now the thing is, there could be another solution where we can use the little bit different logic, little bit different data structure, and we can do things in better manner. And let's see that what would be that approach. So the second approach is that rather than using this visited hash set, we don't need to do anything with this visited hash set. Let it be used for the purpose of counting that whether all the elements are connected components or not. What I'm proposing is that we created another data structure, a hash map, and in this hash map, what we plan to do is we as a key we have parent, and as a child we as a value we have the value of its children. Now let's see that how can we use this combination to do things a little bit differently. Also over here, let's say that we are given a graph like this, that 0 1 2 3, something like this, right? So 0 is connected to 1, 1 is connected to 2, 2 is connected to 3, and now we have this 3 connected back to this 1 as well, which means that there exists a cycle over here. Now because these are undirected edges, which means that they are bi-directional edges as well. So from this 0 we can go to 1, from this 1 we can go back to 0, and blah 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 whatnot. So initially let's say that we are at the 0th position. From the 0th position we start exploring its neighbor or children or whatever we want to call. So the moment from the 0 we are able to reach to this one, we would add an entry over here in this hash map, and the entry we are going to make is that 0 is actually a parent in this case, and one of the children that we could find for this 0 is actually node number 1. So node number 1 is the children of 0, and just stay with me that why we are using this approach. Now again from this node number 1 we need to explore its neighbors, right? So what are the neighbors of this node number 1? We can explore neighbors based on the number of edges that goes out from this node number 1. So from this node number 1 we actually have 2 edges that goes out. First edge is that from this node number 1 we can go to node number 2. Now we check in this hash map that does node number 1 exist. Node number 1 does not exist as a key, so we add an entry over here. So we say that okay, parent is node number 1, and from this node number 1 we can actually travel to node number 2. So we are good with that. Now again from this node number 1 we still have possibility that we can go back to this node number 0. So again we check in this hash map, okay, that whether there exists an entry for this node number 0 that we are trying to reach. Remember this very importantly. We will check that whether this node number 0 that we are trying to reach from this node number 1, does that exist in the hash map or not. Okay, so 0 exists in this hash map. Again we check that from this 1 we are trying to reach to this 0, is this one of the children of this node 0 or not. In this case, yes, 1 is the children of node number 0. If that is the case, we can identify that this connection from 1 to 0 is actually not a cycle, it's just a trivial loop, and that is being caused because there exists an unidirectional edge on both the sides. So that's why we will ignore this case, we will ignore this connection. We are not removing the edge. Again, remember, we are not removing the edge, we are just ignoring this case because in the hash map we are able to find that okay, this 0 to 1 connection is actually just a trivial cycle, and we move on with our life. So from this 1, again, since we have reached to this 2, right, and 2 is not existing, and 2 is one of the children of 1. Now again we are at this position number 2. Now again from this position number 2, what are the different ways we can travel? We can either go back to 1 or we can go to 3. Let's say that we go to 3 first. So we check that whether 3 exists inside the hash map. 3 does not exist, which means we can create an entry that where 2 is a parent and 3 is a child. We are good with this so far. Now again from this 2, when we try to check that from 2 we are trying to go back to 1, is that a cycle? So first we check that whether this 1 exists in the hash map or not. So 1 exists in the hash map over here, and 2 is one of its children. So because 2 is one of its children, we are going to ignore this case, and we are going to ignore, and because we are ignoring this particular error, we are just going to move on with our lives. Now we are at this position number 3. From this 3 we will check that okay, what are the different places we can travel back to. So from this 3 we see that okay, one edge that goes to 1, one edge that goes to 2. First of all, let's explore this edge from 3 to 2. So over here we will check that we are trying to reach to this node number 2. So 2 already exists and 3 is one of its children, which means we are going to ignore this edge, so we don't have to worry about anything. Now again from this 3 we check for this value number 1. So okay, from this 3 we try to see that whether we are able to reach to node number 1. Node number 1 has already been visited inside the hash map, and that's why we are able to determine that there exists a loop inside over here, from where we are actually going back to one of the places that was actually not that is already been visited inside our hash map. And this hash map acts as both. It acts as a visited hash set that we were planning to use, and also it acts as a way for us to determining that whether we are detecting the correct cycles or we are detecting the trivial cycles between the unidirectional edges. And this would be a way on how we can check the cycles, which means that the combination of this, using this hash map to identify that whether cycle exists or not, and using this visited node and iterating over using BFS or DFS inside our graph, original graph, using these two data structures, we can actually get rid of both of our cases where we need to check that whether the graph is connected, and we need to check that whether the graph contains any cycles or not. And because we are able to do both of these things, at the end, if we are able to reach to end node, we will return true. If we are not able to reach to end node, we can return false. And this solution actually works perfectly fine. There are no issues with this solution. It is a very elegant solution. If you tell it in any interview, they are going to be very impressed with the depth and breadth of your thinking capabilities. What are the space and time complexity over here, and can we do something better? So let's first try to determine that. So space complexity, in this case, we know that we will have to use the hash map, and we will have to use the visited array as well. Inside the hash map, we are going to iterate over all the nodes plus all the edges, which means that over here the space complexity would be big O of v plus e, because we are iterating over all the vertices and all the edges. The time complexity in this case would also be big O of v plus e, because we will have to iterate over every single node and every single edge multiple times in order to come to this solution. But the thing is, we are not doing loop inside loop work, so which means we are not doing repetitive work at any given moment. Okay, after such a long explanation, let's see that can there be a better approach. And yes, there is actually a very elegant, very beautiful solution, where actually we don't even have to go through all of these mess to detect that whether cycles exist or not. In order to do that, actually we need a higher knowledge of graph theory. What do I mean by that? Okay, at any given moment, suppose we are given a graph like this, that 0, 1, 2, 3, 4. Suppose we are given a graph like this, right? Now, if we want to identify that whether this is a tree or not, like in this case, we can clearly see that, yeah, this is a tree. There is a very legitimate scenario. There are no cycles. All the nodes are connected and blah, 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 whatnot. Everything is good with this, right? Can you notice an important property over here? The important property that I'm talking about is, if you count that what are the number of nodes and what are the number of edges, does there exist a correlation? Yes, actually there exists a correlation, and the correlation is that suppose we are given the number of nodes equal to n, and if we are given the edges that are n minus 1, and we determine that all nodes are connected, if we determine that all nodes are connected, because remember in our solution when we are trying to finding that whether the nodes are connected or not is much simpler. We simply need to use a hash set. We need to iterate over whatever the given input we have, and basically we can determine that okay whether the nodes are connected or not. But checking for the cycle is slightly more complicated, actually not slightly, much more complicated, because either we have two options and both options require us modifying a lot of things or managing a bunch of different data structures. Either we can choose to remove the edges like this, or we can choose to create a hash set like this. In both the cases we are actually doing a lot of work. So what if we actually don't need to encounter that whether we need to find the cycles or not? If we only encounter that whether the given nodes are connected or not, if that is true, and at any given moment we identify that okay all the nodes are connected, and then we identify this property that whether the number of nodes that are given and number of edges that are given, if there is the difference between them is only 1, if that is the case, then the given graph will always be a tree. Let's see in this scenario. In this scenario, we can identify that okay, from this 0 all the nodes are connected, that this 1 2 3 and this 4 we are able to connect to all of them, right? What is the number of nodes? So number of nodes in this scenario is actually 5. This 1 2 3 4 5. Now let's see that what are the number of edges. So if we calculate the number of edges, the number of edges is okay, this is one edge, this is second edge, this third edge, and this is fourth edge. There are only 4 edges that are possible. If we have any more edges, then for sure there would be a loop. Because remember, where would you add an edge in this scenario? You can add an edge over here. Okay, that creates a loop. Let's say that you don't add an edge over here. Suppose you add an edge over here. Again, it creates a loop. Well, you don't even add an edge over here. You add an edge like this. So again, this creates a loop like this. Eventually, as long as the difference between the number of nodes and number of edges is actually not exactly 1, and if the number of nodes are one number higher than whatever the number of total edges are given, if that is the case, and we determine that all the nodes are connected, then we can clearly say that okay, everything is good with our life and we don't have to worry about anything. Why we need to check that whether all the nodes are connected or not? The only reason we need to check if all the nodes are connected or not is, suppose we are given a scenario like this, that we are given these three nodes. Suppose we are given these 4 nodes, right? And in these 4 nodes, so remember our equation is that number of nodes and edges. So if nodes are 4 and if edges are 3, so we can say that okay, everything is good with our life. In this case, the number of node is 0 1 2 3. Okay, so total 4 nodes, we are good. Number of edges 1 2 3. So this is also good. The thing is, over here you can see that there exists a cycle over here between these 3 edges. And why there exists a cycle? Because this particular node is not connected. So always at any case we will have to check that whether all the nodes are connected or not. And once we identify that all the nodes are connected, we are good, and then we can just wrap up our solution. So using this solution, actually everything becomes so smooth that if we calculate the time and space complexity, the time complexity in this case is actually big O of n, because we only need to iterate over the given number of nodes, and where n defines the number of nodes. If we calculate the space complexity is also big O of n, because we only need to maintain a hash set to take care of all the number of connected edges. So once we find out that what are the number of connected, if all the elements are connected, we can immediately identify that whether this given graph is a tree or not. So let's move on towards coding now. First of all, we are going to check that whether the given number of edges, if its length is 1 less than the number of nodes or not. If that is not the case, we can return false immediately. So, and if that doesn't happen, we will have to make an adjacency list. So we will create an adjacency list, so it becomes easier for us to iterate over the given input array. So for all the given n, we are going to treat them as vertices, and all the values that are provided in the edges, we are going to treat them as edges basically. Notice over here that for every single edge we are actually adding 2 entries inside our adjacency list, and that is because the given edges are actually undirected. So that's why we will have to add an edge for both the nodes. So if there is an edge between 0 to 1, so we will have to create 2 edges, and those 2 edges would be 0 to 1, and from node 1 to 0. So that is what we are doing by this second for loop. Okay, now we will start iterating over the given graph inside the adjacency list. And I want to learn that how to iterate over the graph using stacks. So I'm going to do it using stacks, and I will be doing iterative depth first search. So first I'll initialize a stack of integer values and just name it as stack. And we will also have to create a hash set of integers called visited. Inside our stack we will add the first entry. So we will add the node 0. And inside our hash map visited, we'll mark the first node as visited. We will pop the first node that is inside our stack, and then we will start iterating over its neighbors. And we'll see that if that neighbor has already been visited, then we will simply ignore that case. If that is not the case, we will start iterating, we'll start adding those neighbors to our stack as well. And we will also add that neighbor to our visited hash map as well. It would be neighbor, not node. Okay, and after this loop ends, we only need to check that what is the size of our hash set. So if, or else we will return false. And let's try to run the code. Okay, seems like our solution is working. Let's try to submit this code. Okay, our solution works pretty efficiently. Hello friends, I'm a cloud solutions architect at Microsoft, and my aim is to empower every single person to be better at technical interviews. Keeping with that goal in mind, today we are going to do a very interesting LeetCode problem called word ladder that has a real life application, because this is a game by itself as well. And if we see some of the popular companies who have already asked this question, there are companies like Amazon, Bloomberg, LinkedIn, Microsoft, Google, Uber, Apple, Facebook, Lyft, ByteDance, and Goldman Sachs. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also very well-liked problem, which is a rare combination to be seen. Now in this problem, we are given two words, a begin word and an end word, and we are also given the list of words called dictionary or word list. Now our aim is to reach or go from the begin word to the end word by a transformation sequence. The question is, how does this transformation sequence works? Well, the transformation sequence works is that suppose we are currently at word 1, we can only jump to word 2 if the difference between the characters is only 1. So say for an example, if we are given a word like cat and we are given the second word like cot, we can go from cat to cot because there is only difference of a single character A. The C and T are common across both the words. So this is a valid transformation sequence. The idea is that from the begin word, we need to keep on doing the transformation sequence amongst many different words, and our aim is to reach to the end word somehow. And if we are able to do it, we need to see that what is the minimum number of ways we can do it, and these words, they has to be present inside the word list that we are given. So we cannot just create words out of fly. This is the purpose of this word list set that we are given, bunch of different words. And if somehow we are not able to reach to this end character using the transformation sequence, we need to return 0. And if we can, we need to return the minimum number of hops needed to reach to there. So let's try to understand this with a couple of examples. If we see this first example here, the begin word that we are given is called hit and the end word is cog. And these are the different words that we are given. So one of the ways we can solve this problem is by creating a word sequence that looks like this. In this case, we are starting from the first word and we are reaching to the end word. And these are all the different hops that we are making using the transformation sequence. So this is a valid example. But if we see in this case, we are actually taking 6 different hops to reach to the end word. Can we do something better? And the answer is yes. There exists a better solution for this problem. So let me quickly show you the better one. Again, even for this example, we are able to reach from this beginning word to the end word. But in this case, we are doing the whole journey by only 5 different hops. So in this case, we need to return 5 as the answer because we are only taking 5 steps to reach from the first word to the end word. And this is going to be our word ladder. If we take a look at the second example, in the second example, the word we are given is hit and again end word is cog. So that is true. But the thing is, in this case, we need to return 0. Why we need to return 0? Well, because this cog is actually not at all present inside this word list that we are given. So since the end word is not present, we cannot reach the end word. So basically we need to return 0. So I hope this explanation makes sense and you are able to understand the problem statement. Now let's see that what is going to be the approach we will take. Okay, so before we come up with the optimal solution, first let's see that what kind of pattern we can see in this problem. Basically, we are given a beginning word and an end word, and we are told that there are some series of words that we need to go to in order to reach to this end word, and we need to return the minimum sequence possible, right? The thing is, in this problem, we are not only guaranteed to given all the words that would be used between this beginning and end word, and it could be possible that we are given some different words that are not being used, or they can be used, but the thing is that leads to like a longer answer, and we do not need to like go through all of them, and we only need to find the shortest path. Now if you see this kind of structure, what does this reminds you of? Well, you are absolutely correct. This is actually a very similar structure to a graph, where you can see the words that are given, they can be treated as different nodes, and the relationship between these nodes can be treated as edges. So we have our vertices and edges, and we have a way to define edges. Now how does a vertices connects to an edge? A vertices connects to an edge through the mechanism that the number of characters of word 1 and word 5 in this case, they only have one differing character, and that's it. That is the only way we can define a relationship between them. Once we have a structure like this ready, now let's see what is our aim. Our aim is to find a path from the beginning word to the end word, and if we want to find the path, what we can do is we can simply iterate over the given input and see that what are the different paths we can take, and try to find the most optimized path or the shortest path that leads us to the correct answer. So in this case, we can actually find 2 different paths that leads us to the answer. First one is the one that I indicated in blue, and second one is the one that I indicate in this purple color. Now in both the cases, this path is actually the shortest path that leads us to the answer, and we need to in the end we need to return the distance between the words amongst these paths. So in this case, the answer is going to be 5. But you get the idea that basically we can, if we are able to generate this graph structure, then all we need to do is we need to do the breadth first search traversal. And the question is, why breadth first search? Because we are trying to find the shortest path, and if we do depth first search, it could be possible that in practice it might take us longer. So breadth first search would be a better candidate in this case. So if we are able to create a graph structure, and if we do the breadth first search, we can actually find the shortest path. Okay, so now we are going to use the same example that we have been given as the input. Now, first of all, we need to find that the beginning word that we are given is the word hit, right? And say for example, we devise some mechanism to easily traverse through these words to make sure that whether these words exist or not, right? Now the question is, from the hit, we are treating this hit as one of the nodes, right? Now we need to find that what are all the different edges this hit is able to connect to. The idea we can do is that we can see all the possible words that this hit can have with just one differing character. The logic is we can start with the first character and keep all the characters from A to Z and then keep the remaining two constant. So what we will do is we will try to check for the words such as AIT, then BIT, all the way up to ZIT, right? These are all the different words we can make. Then same way we can keep the H and T common and then do A, B, C all the way up to Z, and we can keep on repeating the same process. So basically at every single word, what are the different possible words we can have? Well, say for example, if the length of this is equal to M, then basically we can have M multiplied by 26 differing characters and or differing word possibilities. Now amongst these 26 word possibilities, all we need to do is we only need to find the words that exist inside this word list. And since this is a dictionary, basically we can access pretty fast and check that whether any word exists or not. We can do it in constant time. So this is not going to be an extra overhead. So by using this logic, we are actually able to generate all the graph pairs for our given input. So first value is going to be hit, and now let me just quickly draw the graph structure. Okay, so we can actually make a structure that looks like this, and this is a pretty decent representation of the input that we are given. Now this is going to be our start node, and this is going to be our end node, or the beginning word and the ending word. Now basically we need to iterate over the given graph, and we are also going to keep track of all the nodes that we have visited so far. That is to not end up inside any like unexpected loop or infinite loop. Now all we need to do is from starting point, we already mentioned that we are going to run a BFS, and we are also going to have a variable called min that is going to keep track of what is the minimum path we have found so far. So if we just see the input, one of the path we can take is that we start from hit, and then we can go down this path, and eventually we would be able to reach to the end word. So in this case, if we see, and definitely we are going to keep track of all the visited nodes and everything is going to be taken care of. If we see this path, basically it is going to take us 6 words, and currently this is the minimum value we have because we haven't identified any other path, right? So 6 is the correct answer. Now let's see that if there is any second option that we are missing. So yes, there is another option that we are missing, and the option is that if we start from this hit, we can go down this path, and through this path the number of words we encounter is actually 5. So because we are encountering 5 words, basically we need to update the minimum number of answer we can get. Let's see if there is any another path that we can take that we are missing. And yes, there is also still one more path that we haven't taken, and the path that looks like this. And in this path also we are encountering 5 words. So again the answer is going to remain 5, and we have explored all the possibilities. So in this case we can simply return 5 as the answer because that is what we need to create. And you see, once we have this graph kind of a structure ready, things becomes much easier to comprehend, and we can simply return the answer pretty fast, pretty efficiently. So this is the whole logic behind this problem. Now in this problem, currently we are only going in just one single direction, but in practice there can be like a bi-directional BFS where we start iterating from here and we also start iterating from here, and we can do like BFS from this direction, BFS from this direction to reach somewhere in the middle and to find the answer. And we can do things slightly faster in that cases, but I don't think anyone is going to expect you to do this in any of your interview, so don't even bother. If we see time complexity, in this case the time complexity is actually going to be big O of m So m is the number of length of any character, and I mentioned that length is going to remain constant amongst all the word list characters, so we don't have to worry about that. So number of m square. Now why m square? M square is taken in order for us to generate this graph like structure. So it takes big of m square time, and for every single character there can be one possibility that we need to iterate, because we know the starting and ending point. So basically it's going to be m square times n in terms of the number of time complexity, where n is the total number of words given. And if we see space complexity, well, basically we are anyway storing this graph like structure, and that is going to give us like big of m square space, so we also need to take care of that. So in my opinion, this was a tough problem, but once you know the logic, you can solve it easily. And this goes to show you that if you know the logic about different data structures, things becomes much easy, because this word ladder game is actually a real life game that people use and people play. So yeah, this is not just a random out of the blue question. Now let's move on to the coding. So since this word ladder problem was already becoming such a big video, so that's why I'm just going to explain you the code rather than typing all of it, and I will go through the explanation. So first of all, we are going to initialize a variable to note down the word length, because that is pretty important. And we are also going to initialize our hash map that contains the information of all the combinations inside the dictionary that could be possible. Now what we are going to do is, for every single word that is present inside this given word list, we are basically going to iterate over all of its characters, and we will try to see that for all the differing characters, what are all the transformations possible. And whenever if a transformation is possible, we will basically add it to our all combination dictionary. Because this is a hash map, inside the key we are going to store the value that is being present and inside the word list, and as its subsequent value we are going to have a list of all the possible combinations that any particular word can have. So this is going to give us our dictionary, and this is going to take basically m square time to do it, or l square time to do it. Now in order to iterate over the breadth first search, we are going to have our queue where we will keep on adding, or we will begin with the first word, and we will not rest until we have iterated over all the neighbors of this first word, and we will keep on repeating the same process iteratively. So we are not doing recursion. We can do recursion, but we are doing it iteratively. And also as mentioned that because we do not want to get inside a position where we end up in any infinite loop, we are basically going to initialize a hash map, and now we are going to basically put the first word or the begin word that we are given as the input, and then we will start iterating over our given queue in the BFS fashion. So first of all, we are going to create a pair, or so first of all we are going to remove the node in that is existent inside the priority queue, and then we will try to get its word value. Then we will see that what level it is, and basically we will iterate over all of the different possible words that can be present, and we will keep on repeating the same process for all the adjacent words. And every time we go to the new level, we are basically going to increase the size of the level. So this is going to return us that how many different paths that we have taken so far. And somehow if we get out of the loop, then basically we need to return 0. So this is the whole logic behind the whole problem. And this condition refers to if we have reached to the end word, and this condition refers to in the scenario where we have not reached to the end word, we are somewhere in the middle. So basically we are going to add a new entry inside our queue, and we are going to increase the current level we are at. So I think this solution makes sense. I would be posting this code in the comments, so you would be able to check out the code. Don't worry about it. Let me try to run this code, and our solution works as expected. Let's submit this code, and our code runs decently efficiently in terms of space complexity and time complexity. Both are really good, and this is the BFS solution from the LeetCode. So once again, we are going to do a very awesome LeetCode problem. This one is a reconstruct itinerary. We can see that this one is a LeetCode hard problem. Also, constructing an itinerary is actually a very popular real life use case that we see in like aviation industry all the time. So this is an important problem. Let's pay our utmost attention. Now we are given a list of airline tickets where any particular position we are given like a tuple value inside the array that defines that where what is the departure and arrival for locations based on that particular unit. Now we need to reconstruct the itinerary in in like a particular order and return that reconstructed itinerary. Now let's see that what are the constraints around reconstructing the itinerary. Number one thing is all the tickets belong to a man who departs from JFK, which means JFK is the starting position for our entire itinerary. Then next thing is that if there are multiple valid itineraries that we are able to construct, then we should return the itinerary that has the smallest lexicographical order. So what does lexicographical or lexical order means? It means that we need to sort them in like A to Z manner, basically, which means if we, let's say if we have two tickets, first one is from JFK to LGA and second one is another ticket from JFK to LGB, then we must return LGA first before returning LGB, because remember that we are sorting lexicographically. So this one has character A and this one has character B. So A comes before B, which means this has a smaller lexical order. So we need to put this in priority. Now we are also told that we may assume that all the tickets are valid and we must use all the ticket once and only once. So let's try to understand this problem and try to see that what could be the potential solutions. Number one thing is this is the type of input we are given. Now we can see that there are a bunch of different tickets we are given. In this case, we are given a ticket that is from Munich to London Heathrow. We are given a ticket from JFK to Munich, then San Francisco to San Jose, and London Heathrow to San Francisco. So these are the 5 tickets we are currently given. I have just plotted all the 5 airports over here. And now let's see that what is the solutions we can make. So let's just take a simple approach and let me just keep on marking all of these nodes or like all the flight connections. So we know that we have a connection between Munich and London Heathrow. So let me mark this one. And then we have a connection from JFK to Munich. So let me also mark this one. Then we have a San Francisco to San Jose. So marking this one. And then we have London Heathrow to San Francisco. So let's mark this one. So this is a valid order. We can see that every single ticket we currently have, that are 4 tickets we have, we used all of these 4 tickets over here. After using all of these 4 tickets, we need to reconstruct itinerary starting from JFK. So we can see that if we start our journey from JFK, the direction is going to be JFK to Munich, then Munich to London Heathrow, Heathrow to San Francisco, and San Francisco to San Jose. This is the reconstructed itinerary that we need to return in this order. Let's take one more slightly complicated scenario. So we have like bunch of different tickets in this case, and we only have 3 airports to deal with. So first ticket is JFK to San Francisco. So let's just mark this one. So JFK to San Francisco, this is one option. Second option is JFK to Atlanta. So let's mark this one. Then San Francisco to Atlanta. Okay. Then Atlanta to JFK. Okay. And then Atlanta to San Francisco. Okay. So currently these are all the different options we have. Now let's see that what is the optimal option we need to choose. We know that we need to start our journey from JFK. Now notice at JFK we have 2 different tickets going outwards. First ticket is going to the San Francisco and second ticket is going to the Atlanta. So question is, which ticket should we choose? Now here comes the lexicographical ordering that we need to pick from, and we can see that Atlanta is lexicographically smaller than San Francisco. So we are going to pick ATL first. So in our path, this is going to be the first path we are going to take. All the markings that I'm marking with red is like the correct marking. Okay. So we took care of one ticket. Then from Atlanta, once again, we have 2 options. We can either go to JFK or we can either go to San Francisco. So once again, it makes sense to pick the smaller amount, and that is once again going back to JFK. So let us go back to the JFK. Now at JFK we only have one option, that is go to San Francisco. So we go to San Francisco, and then from San Francisco now we only have one option, that is to go to Atlanta. So we go to Atlanta, and now from Atlanta we still have one more edge that is remaining, and that is to go back to the San Francisco. So we will once again go back to the San Francisco. So this is the sequence we are going to follow, where first we are going to go from JFK to Atlanta, then this is the second, this is the third, this is the fourth, and this is the fifth flight we are going to take. So this is what we need to return. Now I know understanding this question took way longer than expected, but don't worry, the solution is not that complicated. So let's just try to understand a simple logical scenario just for this particular input that we are given. What is the one thing that we did to solve this problem? Well, it is quite obvious what we did to solve this problem. We first of all mark that from every single airport, what are all the different possibilities we can take, and then we started iterating over our journey from JFK. On top of it, not only marking all the different possible journeys, we also mark that what under what order should we start picking and start moving in any particular direction. So what I'm suggesting in this case is that we are only given the tickets, we are only given these values from any particular two nodes. What I'm suggesting is that we actually treat this as a graph problem, and which is pretty obvious. Why are we treating it as a graph problem? Through this one, we are going to be marking every single airports we currently have as the nodes, and all the tickets that we currently have as the edges. Okay, we already got our nodes and edges. On top of it, what we need to do is we need to iterate over the given graph. Now iteration of the graph is quite simple. We know that we have two methods. We have a breadth first search method and we have depth first search method. Now in this case, going in one particular direction makes more sense, because notice that over here we are going in like a depth first search fashion. Even in this example we saw that we were doing bunch of different back and forth in order to complete all of our transaction, and that was also being done in depth first search fashion. So in this case we are also going to be using DFS to iterate over all the nodes. Next thing is we need a starting pointer to iterate over. We already have a starting pointer, and that is starting from the JFK. So we know that we first of all need to treat it as a graph. We will need to do a DFS. We will need to start iterating over from JFK. Next thing is when we are constructing a graph, we will have to set up ordering in which sequence are we going to go to any particular airport, and for that we will have to follow the lexicographical ordering. So for that, what I'm suggesting is that we actually use an adjacency list kind of a scenario, where we store the adjacency list for our graph, and we do it in lexicographical ordering. So what I'm suggesting is that we initialize a hash map. As part of the hash map, we need two items, key and value. As part of the key, we mark the nodes or the airport. As part of its values, we mark that from that airport how many different tickets that we can traverse over. So or how many different airports or destinations we have. Okay. Then once we have these two values, then we need to populate these arrays. So let's start populating this value for this given input. Okay. So currently let's go one by one in these throughout all of these tickets. So first one is we are starting from JFK. So one node is JFK. Okay. Now from the JFK, we need to have a ticket. The destination is San Francisco. So let me mark this as SF. Then we have one more ticket from JFK, and the destination is Atlanta. Now we know that JFK is already present. The thing is we are trying to insert Atlanta over here. So one logical thing is that rather than just doing anything, let me just create a linked list over here where I'm storing Atlanta as well, that from JFK I have one more ticket that goes to Atlanta. Okay. Same way, we have a San Francisco and the destination is Atlanta. So let me also do that. And we have Atlanta and JFK. So Atlanta and JFK. Okay. And last one is Atlanta to San Francisco. So we are going to have one more destination, San Francisco from Atlanta. Now we have our key or our graph, our adjacency list being created, okay, inside our hash map. But the thing is, we need to sort this in lexicographical manner. So what we are going to do an intermediate step where we are simply going to update this given graph that we have created so far. And for this one, we are simply going to sort all the values or all the inputs we have in the destination in lexicographical manner. We know that this can be done in n log n time, so we are going to spend that extra time in order to complete that. So let me just start marking this one. So first entry is JFK. Okay, for JFK we currently have two values. First one is San Francisco and second one is Atlanta, but this is not sorted correctly, so we are going to sort it. First one is going to be Atlanta and second one is going to be San Francisco, as this is going to be the sequence of linked list. For San Francisco we only have Atlanta, so let's just mark this one. And the last one, even for the Atlanta, we have JFK and San Francisco, that is already sorted in correct order, so let's just mark this one. So JFK and we have Atlanta. Okay, sorry, San Francisco. Okay, so let's just mark this one as well. And now we have everything we are looking for. Now all we need to do is just do the DFS operation from our adjacency list on the graph, and every time we update, we iterate over one destination, we are going to remove that from the list. So next time when we are at the same airport, we simply pick the next lexicographical entry in sequence. So let's try to run the solution. So we start our journey from JFK. So we are initially at this JFK location. We saw that the first ticket we need to find, or first flight, is Atlanta. So let's just traverse to Atlanta, marked as A. Now we need to go to the Atlanta because we are currently presented in Atlanta. Also at the same time we are going to remove Atlanta from here, and we are going to go to the Atlanta. Now Atlanta, the very first flight is JFK. So once again we are going to come back to JFK. So after coming back, we are going to remove JFK from here. So now at the JFK, the next flight in sequence is San Francisco. So let's just make another journey to San Francisco. And now we are going to remove San Francisco from here. Now at San Francisco, next flight is Atlanta. So let's just mark a journey to Atlanta, and we are going to remove Atlanta from here. And now from the Atlanta, let's just mark one journey to the San Francisco. So we are going to mark a journey to the San Francisco, and we are going to remove San Francisco over here. Now the moment we come to any particular position, let's say we came to San Francisco, now there are no more entries or no more destinations for us to visit, which means we can conclude that we have iterated over every single possible tickets that we currently have present, and we can simply say that we iterated over all the entries, and this is the path that we created. We can just keep track of the path in like a backtracking function, and because we are making recursive calls to use the DFS and solve this problem quite easily, quite beautifully, quite simply, and this is an awesome LeetCode problem. If we understand the time complexity in this case, that is going to be big O of vertices multiplied by edges plus big O of n log n in order to do the sorting, but this is already greater than n log n, so we don't need to factor that in. And if we talk about the space complexity, it is going to be big O of once again vertices multiplied by edges, because we are creating a new hash map that is going to be of length v. So actually this is only going to be big O of size v, but in the value section we are going to have all the edges that we currently have, so it's going to be v plus e. Okay, so this is still a good time and space complexity. Now let's quickly see the coding solution for this one. Okay, so the very first thing we are going to do is to create a map to store the list of destination for every single departure airport. So we are going to create a new hash map where as a key we are going to store the string that is going to store the name of the airport, and as part of its value we are going to be storing a linked list or list of strings. Now we are going to iterate over every single tickets that we currently have and keep on marking all the values inside our graph hash map that we have just created. After having a representation, now we are going to be sorting all the values that we have in the destination of the graph. So we are going to run a for loop and just do a sort operation. After sorting it out, we simply need to start our journey from the JFK terminal. So we are going to have a linked list that is going to be creating an itinerary that we need to return as part of the answer, and we are going to have a DFS operation that is going to start from the JFK airport, where we are going to pass in the graph that we have just created that contains all the sorted destinations, and the itinerary linked list where we are going to be storing all the values in sequence. Now let's see our DFS method. So first thing we are doing is that we are adding the current airport we are at the destination. After that we are checking that while the given destination is not null, and the list of destination is not empty, then we are going to remove that destination to avoid revisiting the same path. So we are simply going to removing that inside our array, and we are also going to be calling the next value that we need to iterate over and calling our dfs function once again. So that's it. This is the whole solution, where instead of passing in JFK, we are passing in the next airport that we have to iterate over. And we are also adding the airport to our itinerary as well, just so that we know that what airport we are beginning at, and we are generating the itinerary in the reverse order. So now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our code runs beautifully compared to like almost 75% of all the other solutions, like 71%. It can still be improved in terms of space complexity. So let me know in the comments if you want to see that. But anyways, you can still see or find the solution on our GitHub repository. So feel free to check it out from there. Thank you. So the LeetCode problem we are going to solve now is called minimum cost to connect all points. This is a very popular question in my opinion. Why? Because we are going to be dealing with something very important that is called Prim's algorithm to solve this problem. And this Prim's algorithm actually has a lot of different practical applications that you can use it in all sorts of different questions and different techniques. So let's understand the problem statement. We are given an array points that represents an integer coordinates of few points on a 2D plane, which means x and y type of graph. And we are told that any particular point value is defined as xi and yi, so the coordinates of that location. Now we are told that the cost of connecting 2 points x and y is the Manhattan distance. So let's say that if you typically has like 3 values, and if you are trying to, let's say, connect any two like this one, in this case the cost of this one is going to be the Pythagoras if we try to choose the diagonal. But the thing is, Manhattan distance is that instead of picking out the value of the straight diagonal between these 2 points, you first go to a common point and then go to right. So in this case you are actually doing the delta of x, and you are also doing the delta of y, so absolute values of x1 and x2 amongst these 2 points, and the sum of this is going to be the total distance you are going to cover. So this is called Manhattan distance, and this is what we are going to follow. So it's slightly better for us so that we don't have to spend so much time on calculating the Pythagoras or root values. Now we need to return the minimum cost to make all the points connected. Now let's try to understand this with an example. In this case, suppose these are the different points we are given. Now we need to make sure that number one, we connect all of these points in some fashion, and after connecting these points, we also need to make sure that the distance we are traveling by connecting them is the minimum distance we can. Now let's try to understand first of all that how does a Manhattan distance is going to work. So let's say you want to find out that what is going to be the distance between these 2 points, then logic is going to be quite straightforward. You are first going to do the difference between x pointers, so this y pointers, and you are going to add it to the difference between x pointers. So in this case the distance between these two nodes is going to be 4. Though it's not a diagonal, I'm just writing it diagonally so it becomes easier for us to understand. Now the thing is, the solution of this problem is something where we will have to deal with minimum spanning tree. Now minimum spanning tree is a very important concept in the graph theory, where you are given bunch of different points on any particular plane, and you are trying to connect all of these points in some fashion such that there are no cycles being formed, and you are trying to span the tree in like only the places where it is absolutely needed, nothing more than that. But the question is, the first thing that should come to your mind is that, hey, in this case we are only given points, we are not given the edges, which means these are simply just the nodes we are given. We know in order to solve any particular graph problem we need two items. We need a nodes, and we also need edges. But the thing is, good thing for us is we already know how to calculate edge between any 2 points. And the thing is, in this case there is possibility that from every single point you are able to connect to every other point in order to treat it like an edge. The thing is, if I try to draw the whole solution by that matter, it's going to look very bad, because imagine how many number of different edges you can form amongst all of these points, and then it is only going to look so much more messy and complex if you have to understand all the different flows and data entries and data points and whatnot. So what we will try to do is we will understand that what is the most simplest logic we can use to solve this problem, and we will also understand that how we are going to be using the Prim's algorithm and the solution of basically Prim's algorithm plus the graph theory concept to solve this problem. So let's start working on the solution of the problem. I hope you must have understood that what the problem is asking us to solve. So now let's very quickly and very simply think one by one that what are all the different possibilities we have across all of these 5 different points. Well, number one possibility is that if we are at this point, we don't know that what are all the points that are currently present inside the remaining graph, which means we don't know that if we have to generate a minimum spanning tree that crosses or that goes through every single nodes that are currently present, which node should this node 0 be connected to. So we don't know this question, number one thing, that what is the minimum cost to reach to any particular point from this node 0. And remember, we need to make sure that we don't form any cycles, because we simply need to connect all the points, and if there are cycles, basically our cost of connecting all the points would increase. So the shortest way to connect all the points is through like some sort of a straight line or a tree kind of structure where there are no cycles. So now at this 0, the number one thing we will have to do, if we have to find the shortest distance or the closest point, we will first have to calculate every single distance we can from all the remaining points to this 0th node, and the distance between these points would be treated as the edges, because we are basically connecting 2 different points, and amongst those edges we will have to find the edge with the smallest value. So these are actually weighted edges. And the other thing is, the connection in this case is going to be bidirectional. Why? Because whatever the distance from this 0 to this node is, same distance is going to be from this node to 0 as well. So we don't need to do any directed distance calculation in this matter. All we are concerned about is unidirectional transfer, and to understand that what is the minimum place to reach that place. Now comes another problem. Let's say that from the 0, it makes logical sense that this is going to be the smallest distance that we can calculate, and we also know that the distance amongst this one is going to be 2. So sorry, 2 plus 2, so total, let's say that this distance is 4, that we already know that this is going to be the smallest distance. But once again, when we come back to this place, now we still have 3 more nodes that we will have to iterate over. We are not going to iterate over node number 0. We are going to treat that this 0 has already been visited, but once again we will have to repeat the same operation. And from this position, we know that the shortest distance we should be able to find is going to be this value. So if we calculate this, I think this distance is going to be 3. Okay. And same way, from this 3, the shortest distance that we calculate for any particular node is going to be this one, and this distance is also going to be 4. But the thing is, now we still have one more node remaining, and we already found the results for these 4 different nodes. So question is, how do we know that which node is actually going to call to this particular node? So for that, we will actually have to find a way that while we are calculating the distance from 0th node to all the other nodes, and same way from this first node to all the other nodes, we will still have to keep track of all the nodes that are still remaining. Because the thing is, it could be possible that there are some nodes that are not down the path of the shortest nodes, but the thing is, we need to connect all the points, so we will still have to find a node that is still closest to this node that it makes sense to make that connection. Now I know what I just said might sound confusing, but the thing is, try to understand this from an example point of view, that if you are if we only traversed, or if we only use the greedy approach where we are just iterating in the minimum fashion, then we are always going to be stuck with one node that is not following this beautiful path. And the thing is, if we try to find the path to that node, that remaining node from here, this might be much longer compared to this distance. So in order to do that, what logical solution I'm suggesting is that we first start at the 0th position. From the 0th position, we make the calculation that how much time it is going to take to travel to this first node, second node, third node, fourth node, all of these nodes. Same way, then we find that amongst these four nodes, which one has the smallest value to reach to there, so smallest edge, and we realize that the smallest edge is 1 in this case. Then from this 1, we know that we already calculated the distance for 0. 1 is a self node in its own, which means now from 1 we will have to keep track that how much time it takes to reach to node number 4, 2 and 3, and keep all of these results stored somewhere as well, and then try to pick the smallest value that we can. Once again, from the smallest value, repeat the same operation for the remaining elements. So even from this smallest value, we will calculate these two distances. Once again, pick the smallest one, and then from the smallest one, see that what is the remaining value, and for all the remaining values, so for this remaining node, see that currently we should have three results. One result is between node 1 and this one node number 4, second result is node 2 and node number 4, and third result is node 3 and node number 4, and amongst these three, whichever is the smallest one, pick that one, and that would be our solution. So now let's just try to walk through the whole solution that we just talked about and see that what are all the different concepts we will have to use to complete the solution in a manner that we are proposing. Now, first of all, what we need to do is we will need to make sure that there are no cycles. In order to make sure that, we will have to keep track that all the nodes that we have currently visited. So we can use some data structure like a hash set or an array or a boolean array of size n to keep track of all the values that we have visited so far. So let's say we will use hash set for now for our understanding purposes, but at the same time we are also going to be using array during the implementation. Okay, so let's say that we currently have our hash set that we are going to be storing to make sure that there are no cycles. Next thing is we will have to make sure that for every single node we calculate the distance to all the remaining nodes, find their distance, and we need to sort those distances. So in order to do that, one of the beautiful data structure we have is actually a heap, and we can have a min heap where from every single node that we start iterating over, for all the remaining values we will try to calculate the distance and put them in the min heap, so that it would be stored in like from in a ascending order. So smallest value would be at the beginning that we should be able to find. And how we are going to be storing the value inside the heap would be in this fashion, where the first value is going to be the distance and second value would be the point. So we would say that in order to reach to that particular point, what is the smallest distance that we will have to cover? That's it. That's all we need, because we are only concerned about the cost to reach to that point. So now let's see that first node is 0. In order to reach to 0, and let's say that we decide to start from 0. It's not necessary that we have to start from 0, but let's say that we decide to start from 0. So in order to reach to 0, what is the minimum cost it takes? So minimum cost it takes is still going to be 0. So we are going to be adding the value 0, 0 over here. Next thing is from 0, now we have 4 different options to choose from, that in order to reach to all of these values. So first value is in order to reach to, let's say this one is node number 1, node number 2, node number 3 and node number 4. So in order to reach to node number 1, the smallest distance it's going to take is going to be value number 4, and we will mark it as by 4, 1. Same way, if we have to reach to this value number 3, let's say that the distance is going to be 5 plus 2, 7. So we can mark the values as 7 and 3. Same way, if we have to reach to this value number 2, then the distance is going to be 13. So we can mark 13 and 2. And next thing is same way, if we have to reach to value number 4, then the distance is going to be 7. So we can still mark 7 and 4. And notice that we are going to be sorting these values because this is a min heap, so it would automatically be sorted. So the value would be something like this one. So 7 and 4, and then I think it was 13 and 2. So these are the currently 4 values that, or 5 values where we have so far. We will pop, and now we have started our iteration. So we will pop the very first element, which means we pop this value 0, 0, and we know that the cost to reach to value number 0 is 0. So we will also need to have a variable to store all the cost. So let's say that we have a variable that where we are storing all the cost. In the cost, we first add 0 because that is the cost to reach to value number 0. Let's say we kick out value number 0. The thing is, because we already visited 0, we are also going to be marking 0 inside our hash set. So let's say that this is our hash set and we already visited node number 0. So from now on, any subsequent entries that come in with value number 0, we are simply going to ignore that because we have already visited that inside our hash set. Okay. And let's keep on doing the iteration. Now the next entry inside our heap is node number 1. From node number 1, it takes 4 cost to reach to node number 1. So let's mark the cost to 0 plus 4. We are also going to be marking that 1 has already been visited so far, and we have this channel being established. Okay. Now from once again, from 1 we will have to repeat the same operation, because remember, from every single node what we are trying to do is we are going out in the breadth first search manner, not depth first search manner. So we went to one of the neighbors of 4, and then we are going to be visiting one of the neighbors of 1. Same way we are going to be visiting one of the neighbors of 3, and same way we are going to be visiting one of the neighbors of 4. So this is a BFS traversal, not a DFS traversal. And now let's just mark 1, and okay. So now once again we are going to leave all, we are going to be popping these 2 entries, but these 3 entries like 7.3, 7.4 and 13.2 is still going to be present inside our heap. Now from this 1 we have once again 3 options. First option is this one, the cost of this is 9. Second option is this one, the cost of this one is 3. And the third option is from 1 to 4, so the cost is going to be 2 and 5, so 7. So once again we are going to be having one entry, that is 3 and 3, which is, in order to reach to node number 3 we are going to be using distance 3. Next entry is in order to reach to node number 4, the distance is going to be 7. So next entry would be 7.4, so we can also put one more entry over here, 7.4. Okay. And we are going to be having one more entry, that is 9.2. In order to reach to 2, the distance is going to be 9. So we will have one more entry, 9.2 over here, and then the 13.2 would be like succeeded to the back end, and this is going to be the current values inside our min heap. Now once again we are going to be popping out the very first element, that is the smallest element, that is node number 3. And in order to reach to node number 3, we will have to add cost as plus 3. So we will mark plus 3 cost over here. We will mark 3 as being visited because we already visited this one, and we will get rid of this entry. So now you can see that now the moment, let's say that suppose I'm just giving you for an example, suppose we say that this is the next closest node and we will try to extract this one. The moment we see that in order to reach to node number 3 it takes 7 cost, the thing is we already visited 3 inside because it's present inside the hash set, so we can simply ignore this case. And same way we are going to be ignoring all the cases that are going to be like different from the nodes that we have not visited so far. Same way from 3 to 4 we have this type of distance, and that distance to 4 is going to be 4 once again. So we can mark 4 because that is the smallest entry, and from 3 we will have to calculate one more distance, that is 2 up to this 2, and that distance is going to be 10.2. So we can mark one entry over here, that is going to be 10.2. But so once again we are going to be adding cost 4 because we visited node 4. It takes 4 unit of time to reach to node number 4, and we have visited all of these entries. Now the thing is we visited all of these. Now from 4 we will once again calculate the distance to 2. So let's say that this distance is going to be 15, so 15 to 2. So currently these are all the entries we have inside our heap, and let's see that what we need to do. So we already visited 0, 1, 3 and 4. We haven't visited node number 2. So we start popping values out. So we first pop this value 7, 4 because we have visited 4, so we can just ignore this one. Same way we can just ignore the 7, 4, and then we have this node 9, 2. So we pop 9, 2 out. 2 we haven't processed, so we are going to be marking the node 2 visited over here and add this cost 9 over here as well. And now you can see that the size of our hash set is exactly same as the size of all the number of points that we are given, which means we have visited all the nodes and we can stop our conclusion. So in order to do this one, the moment we the size of our hash set becomes the number of nodes present, we can stop our calculation, and whatever the cost we found so far, we can return that as the answer. So in this case, the answer is going to be 20, and this is the whole solution. So I hope it makes sense to you that how did we calculated this. We dealt with a lot of concepts, that how not to detect cycles. Then we also make sure that we had a hash set to understand that what are the nodes visited so far. We had a heap to find the smallest entry from any particular point, and we were doing all of this while calculating the cost of the minimum spanning tree. So this is a beautiful solution. If we understand the time and space complexity, time complexity is going to be big O of, first of all, let's imagine we will have to do n square work for any single node. Why? Because at this position we will have to calculate distance between all of these 4 points. Same way at this particular location we will have to calculate the distance between all of these 4 points. So we will have to do big O of n square work to calculate all the distance, and then we will have to find the shortest distance, and shortest distance we are finding by using a heap. So it takes n log n time in order to find the solution from the heap. So overall the time complexity is going to be big O of n square log n. If we see space complexity, because we are storing all the entries inside our heap, it is also going to be big O of n square. So overall this is an expensive time and space complexity, but given the scope of problem, we cannot do anything better than this one. So now let's quickly see the coding solution. So the very first thing we are going to do is to define the total length of given all the points that we currently have. This we are going to be using to check against that whether we have collected all the points or not. Then we are going to be initializing our priority queue, and this is going to be our min heap. Then we are also initializing a new Boolean array to store that all the values that we have currently visited so far. So we are marking it as in MST, whether it is present in the minimum spanning tree or not. Then we are defining a new class called point. So let's understand this one. So we have a new class called point, and it only contains two values. First one is a distance and second one is an index. And we can see that we are going to be using this instance of this class to store values inside our min heap, where we are storing that in order to reach to any particular index, what is the distance that it takes, and then heap would sort it out for us. And the very first element we are adding inside the heap is that we are adding the very first value, value located at index position number 0 inside the points, and we are saying that it takes 0 cost to reach to those points, and this is how our priority queue works. We are also having a variable to store the minimum cost that we have been able to find so far, and we have a value called points connected, so which we can use it to compare it against the total given length of points to define that whether we should complete our iteration or not. Then we are running our loop until our points connected reaches to the total number of n that is currently present. Then we are fetching the very first value that we currently have out of the priority queue. So we are doing a poll operation and then checking that whether this point that we found out, this current point, have we already visited that current point. So we can check that using the Boolean array that we have created. Then we are checking that if we have not visited, then we are going to be marking it as visited, and we are also going to be updating the minimum cost to reach to all the nodes by the distance that it takes to reach to that particular node, and we are also updating the value of points connected so far. So now we already calculated and visited that particular point, but the thing is we will have to still calculate the distance to all the remaining points from that point. So we are going to be running another for loop that is going to span across every single n that is currently present. First we are checking that any particular index that we are checking, have we already visited or not. If we have already visited that, then we can ignore. If we have not visited, we will calculate the distance by using the math.absolute points, and then we will add a new entry inside our priority queue by adding that ith location and the distance to reach to that ith location, and it would sort it automatically. In the end, we simply need to return the min cost that has occurred so far to reach or connect all the points, and this is the whole solution. So let's try to run our code. Okay, seems like our solution is working as expected. Let's submit this code. and our code runs beautifully compared to a lot of other solutions. It's almost 80% faster in terms of time complexity and also 80% faster in terms of space complexity. So which is pretty great. Once again, the solution is present inside our GitHub repository. So feel free to go ahead and check it out from there. Thank you. So the LeetCode problem we are going to solve now is called network delay time. This is a pretty popular LeetCode problem. So let's understand the statement. Basically, we are given a network of n nodes marked from 1 to n. So in total, we are given three items. First one is times, that defines that in order to reach from one particular node to next node, how much time it takes. So if we take a look at this example, let's say 2, 1, 1, then we can say that in order for us to reach from node number 2 to node number 1, it is going to take 1 unit of time. So this is how bunch of different times we are given. Then we are given told k as a starting point, and that says that we will have to start iterating over our journey from k is equal to 2. So in this case from second node, and this n defines the total number of nodes that we currently have. Now the problem is asking us to solve is that we need to return the minimum time it takes for us to travel all the n nodes to receive the signal. And if it is not possible for all the n nodes to receive the signal, then we need to return -1. So let's try to understand this with an example. Say for an example, in this case, we are given an input like this. So we can see that in total, we are dealing with 4 different nodes, and we are given 3 different edges. So first edge is from node 2 to node number 1, it takes 1 time. Same way from node 2 to node number 3, it takes 1 time. And same way from node number 3 to node number 4, it takes 1 time in order for us to reach. Now we are given k is equal to 2, which means starting from k, we will have to make sure that are we able to send a signal that reach every single node, and what time it takes for to reach all the nodes in the minimum. So during the very first minute, we will have a signal that can go to node number 1 and node number 3. So we can say that these two nodes would have been visited after 1 minute. And then from node number 3, we still have to visit node number 4. So we can say that in order to reach node number 4, it is going to take 1 more minute, which means it took 1 minute to reach over node number 3 and then 1 more minute to reach to node number 4. So in total, it took us 2 minutes to reach to node number 4 and 1 minute to reach to node number 1 and 3. So in the minimum time 2, we can reach or a signal can reach every single node starting from node number 2. So this is what the problem statement is asking us to return. Let's say in this case, instead of 2, if we are being told that our k starting value is at 3. So in this case, now we are starting our iteration from value number 3. So once again, we will have to check that how many nodes can we reach. So we know that in the k3 only points to one node. So during the first minute, we would visit node number 4. But the thing is, we don't have any way for the signal to visit to node number 2 and node number 1. So in this case, we will have to return -1. So this is the whole problem statement. Now let's say that this is the input we are currently given, and we are trying to deal with that how we can actually find the network delay time starting from any particular node. The thing is, we don't know that what node we are going to be starting our code with, but all we have is the information about the total number of nodes that are currently present and the distance it takes in order to reach from one particular node to other particular node. The logic is quite straightforward. We treat this one as a classical graph problem where starting from any particular node, we will try to see that if there exists a shortest distance that can cover all the nodes that are currently present. If we are able to reach to all the nodes, then we will have to check that which is the farthest node and how much time it took us to reach to that particular level. Let's try to understand this with this example, that we were starting our node at node number 2, and it took us 2 minutes to reach to node number 1. Then the amount of time it takes to reach to this node number 3 and node number 1 is obsolete, because we are only concerned about the minimum time it takes to reach to every single node, and that should be our key focus. So few assumptions we can make is that number 1, we can use this as a graph problem. This one is going to be the Dijkstra's problem, that in order to reach us to the shortest minimum span, and I don't know the spelling of Dijkstra, so sorry about that, and no worry. Now coming back to the question, basically we need to, number one thing is have a graph like structure. So what I'm suggesting is we create some sort of an adjacency list or adjacency matrix kind of a structure. So let's say that we do create an adjacency matrix or hash map that contains all the information related to nodes and what are all the different distances that we can travel from those nodes. Now we all know that what are the different edges it takes us for from any particular node that we can iterate over. So because we are given the information in this fashion, like x, y and t, where x and y are the nodes and t is the amount of time it takes to reach there. So we can just simply take this x, put it in the node section. So this would be the key for us to search inside our hash map, and this y and t defines that in order to, let's say that in order for from x we can have an information like this one, that y and 1. So we can say that the node is x. If we have to reach to y, it takes us 1 time. So let's try to build a graph like that for all the nodes that are currently present in this case. But the thing is, we are also going to do one thing smarter, and that is that instead of just pointing out the nearest neighbor any particular node can visit, we will also try to sort these values based on the shortest value first and the longest value later. Why are we doing that? Because we have two objectives. Number one objective is to reach to all the nodes, and second objective is to do it in the minimum time. So we will have to find the quickest route possible. Next objective is that we will have to iterate over all the nodes that are currently present. So we are going to fulfill all of these goals by making some adjustments in the way we do our calculation. So for that, first let me just set up the graph structure that I'm suggesting, and then we will start tackling over the other problems. Now in this case, we are only dealing with 4 nodes. So starting with node number 2, we have two options. If we have to reach to node number 3, it takes us 2 times. So it makes sense that this is the shortest distance. So we can mark the values as, in order to reach to node number 3, it takes 2 times, and in order to reach to node number 1, it takes 3 times. So we are going to mark things like this. Same way, starting at node number 3, once again we have two options. In order to reach to node number 4, it takes us 3 times, and same way in order to reach to node number 1, it takes us 6 times. Same way, from node number 1 we only have one option, and that is in order to reach to node number 1, it takes 5 times, and from node number 1 we don't have any option. So at the node number 1 we basically just don't have any edges that are going out, so we will not mark anything. Now we knew that these are the 4 edges that we will have to traverse over. Next thing is that we also need to keep track that what are the nodes that we have visited so far, and also the other thing is we need to know that is the node visited if that is the shortest distance that we found so far. Now in order to tackle both of this problem, what I'm suggesting is we create a new array that is of size n. So we will have values like this one, like 0, 1, 2, 3 and 4. But the thing is, in this case we are only dealing with nodes starting from 1 to n, so not from 0 to n. So the thing is, for the very first value inside the array, we are just going to ignore this one. Okay, so let's say that we ignore this, and initially we will set this array up to a very large value. So let's say that we are populating the entire array with the maximum value possible, and then the only time we will update this array is, number one, if we find out a path to reach to that particular node by some smaller value, and number two, if we cannot find that, in the end it would be able to show us that there are some nodes we are not able to reach, so we can just return -1 in those cases. So let's try to start iterating over our solution now. It would make much more sense. Let's say that in this case our given k is equal to 2. We are starting our iteration from node number 2. So what is the minimum time it would take us to reach to all the nodes? Now from at node number 2, we can see that the very first possibility is that if we have to reach to node number 3, then we can do it in 2 times. Currently node number 3 has not been visited. So we found a shorter way to visit node number 3. So we will mark it by 2. And then same way we are going to ignore or pop this case out from our given list. Basically we are dealing with a priority queue or a hash map like a structure. So inside the hash map we will add the value number 3, but we will pop out this value from the priority queue. Now from this node number 3, once again we are going to repeat the same process. And by the way, currently inside the priority queue we only have these two values present. So first value was 3 2 and second value was 1 3. Now we add one more value, that is the value 4 3. So now notice that we popped one value out, and we have two more values that we will have to deal with. Okay, and we would keep on iterating in terms of priority queue, and we would always try to find the shortest distance that we will try to kick out. In this case both values are 3, so let's say that we decide to update node number 1 first. So node number, in order to reach to node number 1, we can do it in 3 times. So let's mark this one. Now once again, at node number 1 we don't have anything, so we cannot add anything to our priority queue. Then we are located at our node number 4. So sorry, node number 3. So at node number 3 we added one value, that is 4 3, and we also have to add one more value, that is 1 and 6. So for the 4 3, currently 4 has not been visited, so we would mark value number. In this case we would not mark value number 3. Why? Because in order to reach to node number 3 it took us 2 times, so we will have to do the sum with 2. So in order to reach to node number 4, it is actually going to take us 5 times, so we are going to mark 4 and 5. And same way, if we have to follow this path and reach to node number 1, then it would have taken us 8 times, so we are going to mark this as 1 and 8 inside our priority queue. And this is the important step where we are updating the total number it takes in order to reach to that particular node based on the previous value we had for in order to reach to that node. So in this case, once again, the node for 4 has not been visited, so we will update it by value number 5. But notice that this 1 8 does not need to be updated, because we already know that we can reach to 1 in 3 times. Then why would we choose a path that reaches 1 in 8 times? So we will ignore this one. And then now we are at value number 4. So from 4 we have one more path then we can go in order to reach to node number 1, and this takes 5 times. So if we choose that, then it becomes 5 plus 5, so 10. But the thing is, we still don't need to update because we already have value number 3. Now the thing is, because we are starting from k is equal to 2, which means from k is equal to 2, in order to reach to k is equal to 2, it is only going to take 0 time. So we should have updated this at the beginning. So I forgot to update, but let me just do it right now, that in order to reach to k is equal to 2, we can do it in 0 times. And now we can see that we are done with our entire iteration. Our priority queue has to be empty because we took care of all the nodes, and we are left with this array. Now in this array, all we need to do is we need to iterate over all the nodes. Ignore the first node because we are only concerned with between 1 to n nodes. Check that if we found at any particular moment any value that was the original max value that we started with. If that is the case, then we can simply return -1, saying that there were few nodes that we were not able to reach. If we don't find any value with -1, we are going to find that what is the maximum value we have in this current array, and currently the maximum value is 5. So we can say that 5 is the minimum number of time it takes for a signal to reach to every single node starting from k nodes, and this is what we can return. So this is a beautiful solution. It has a lot of practical application like aviation industry, network routing industry. All the things use methods like this in order to compute that what is the shortest distance to travel from one point of the plane to the other point of the plane, which is pretty awesome and pretty nice. Now let's try to understand the time complexity. Now it makes sense that we will have to do big O of n multiplied by v work for every single node, and at every single node we will have to check that what is the shortest distance. For that we will have to add those entries inside our priority queue. So it is going to be multiplied by logarithm of n, and this is a pretty decent solution where n is the total number of nodes and v is the total number of vertices. And sorry, not vertices, but this should have been edges, so n multiplied by e. If we look at the space complexity, well, we are using quite number of additional data structures. We are using a graph like data structure to store all the values. We are using a priority queue. We are using bunch of different pointers and stuff like that. So overall, the biggest one is the graph like structure, that is big O of once again vertices multiplied by edges. So this is going to be the space complexity that we would be dealing with. So now let's quickly see the coding solution for this one. So the very first thing we are going to do is that we are going to create a graph-like representation using an adjacency list. And for that we are using a hash map to store the nodes as integers and its subsequent edges as the linked list type of structure. We are simply iterating over every single edges we are marking the very first node that we currently have as part of a key, and then the second value and the third value is being represented as the edge and the time it takes to reach to that particular level. Then we are initializing a new priority queue where this is going to be a min heap, and we are going to be checking that what is the minimum amount of time it takes to reach to any particular node. Then we are going to be adding the very first value as saying that in order to reach to node k, it takes 0 amount of time, and this would be the starting point for our min heap or priority queue. Next thing is that we will have to initialize the distances of an array with the starting value as maximum value. So we create a new array starting with n+1 nodes, plus we fill out all the values that we currently have with the maximum value possible, and the value at the kth position. In order to reach to kth distance, we mark it as 0 because it takes 0 amount of time to reach to node number k. Now then our priority queue iteration starts, that while the priority queue is not empty, number one thing we are going to do is pop out the very first element that is present inside the priority queue, mark the current node with the very first value inside the priority queue and the current distance in order to reach to that node as the second node of the tuple. Then we are checking that if the current distance is greater than the current distances that we have already found, then which means we can simply ignore that case and we don't need to do anything with that particular node. But if we don't have calculated or we found some value that is smaller, then we are going to check that what are all the neighbors for that particular node, and we are going to be marking all of those neighbors in our graph like data structure and adding those to the priority queue. On top of it, we are going to be updating the distance that we need to calculate by adding the current distance plus the new distance that we found in order to reach to that particular neighbor. So this way we are continuously updating all the values we can inside our array. Lastly, all we need to check is that inside the new maximum distance array that we have created, that we need to check that in the given array, what is the maximum value we currently have. Notice we are skipping the very first element inside the node because we are starting from n is equal to 1 index, not 0th index. And then we can simply check that if we found that the maximum distance to be the maximum value possible, then we need to return -1. If that is not the case, then we simply return whatever the maximum distance we found inside the array. So let's try to run this code. Hopefully it should be working. Seems like our solution is working as expected. Let's submit this code. And our code beats almost 70% of all the other solutions, which is pretty great and pretty awesome. So once again, you can find the coding solution for this problem in our GitHub repository. Link is in the description. Take care. First of all, many congratulations to you if you made this far into the video. I know it hasn't been easy, especially if you have already completed part 1 and then doing part 2. That is nearly 24 hours of just DSA problems, and that is in itself mind-boggling. So first of all, kudos to you. Now in our NeetCode 150 journey, we have been able to reach up until question number 95. So for the remaining questions, there is subsequent part, and because YouTube does not allow me to post a video longer than 12 hours, so that's why there is a third part to this. But hope you find enjoyable and useful up until this point. Just comment the word spoon, so I would know that somebody watched this portion and then commented the word spoon. Okay.